Ladies and gentlemen, may I please have your undivided attention for an important announcement about this course's content. I'm very excited to announce that we have hit a major turning point in this course. From this point on forward, we will be discussing data structures.
Data structures. Well, as you may have heard, we're talking about data structures, which it really is a big turning point in this course. We've spent a lot of time talking about many different topics, different types of algorithms, approaches for problem solving, big O notation, recursion, sorting, searching, a lot of stuff. But now, from here on out, everything we cover will be a new type of data structure or related to a new data structure that we learn. So in this video and this section, there's a couple things we have to get out of the way before we dive into the many data structures we're going to cover. This will be quick, but I want to talk about why you should care, what the data structures are, why there's so many of them, how do they differ, what's the point of learning these, and then also we're going to learn about ES 2015, the class syntax to create classes in JavaScript, which is how we'll be defining our own data structures from here on out. So if you already know about that, you can skip it, but it's like 10 minutes of content across 3 videos if you do want to check it out and see how it works. Okay, so I mentioned we're covering a ton of structures. Binary search trees, queues, singly linked lists, undirected, unweighted graphs. We're talking about binary heaps, priority queues, I didn't put that on here, directed graphs, hash tables, doubly linked lists, stacks, and there's actually some more that I didn't put on here. What the heck is going on? Why are there so many? Why am I teaching them? And what do they all do? So we're not going to get into what each one does individually here, but just know we will implement each one of these as their own class. So we'll define it from scratch, sort of like if we were defining our own array or our own object, although it's a little higher level than that. The structures we're going to build are a little bit more complex. So let's start with what all of these have in common. What do they do? What makes something a data structure? We've kind of touched on this early on. We talked about arrays and objects. Those are data structures, as well as all of these things. These are data structures. And there's dozens of very well-known ones, and hundreds of, maybe thousands of very nuanced niche variants of data structures. All of them, what they have in common is that they are collections of values. They contain the relationships among those values and the functionality or operations that can be applied to the data. So think of an array. An array holds many values. It also contains the relationships between those values, the order in the case of an array. And arrays come with all sorts of built-in methods and functionality, ways of interacting with them, adding to them, removing, push, pop, that sort of thing, but also sorting, reversing, whatever other functionality there is. So we'll define our own structures that fit this exact same mold. When we define a singly linked list, that's the first one we cover, it will not only hold data, but it also puts them in a particular way where there's a relationship between each piece of data. It's not just randomly deciding how to store it. There is a particular pattern, a relationship. So it holds a collection of data, and we'll be writing a bunch of methods. We'll add our own push, our own pop, our own reverse. What else? There's probably 7 different methods we add to a singly linked list, and they all help us interact with the singly linked list. Same thing when we talk about graphs and trees and heaps and everything else we do from here on out. We'll be defining a class called whatever our new data structure of the day is. And then on top of that, we add a bunch of functionality. So why are there so many? That's a good question. It comes down to the fact that different data structures excel at different things. So some of them are very specialized, but some of them are pretty general, commonly used things like an array or an object in JavaScript, which is why those come for free, right? We don't have to implement those on our own. But if we're trying to work with a red and black tree or an undirected graph, something like that, you usually don't get that for free in a programming language. You have to go and implement it. But that doesn't mean they're not useful. It just means that they are very useful in special cases. And you have to be able to know when to use one of those. You have to know about them in order to write one, if that makes sense. So they all do different things. And as we go through this course, you'll see when certain ones make sense. And we talk about usages and examples and real-world use cases, as well as interview problems. So you might see a data structure like this. This is a visual representation of an array. Here's another one we'll look at, a linked list. This is a singly linked list. We'll also talk about doubly linked lists. Here we have a hash table. These are just visual representations, but you can see these are all different relationships between the pieces of data, but they all are storing numbers, just totally different ways of storing the same type of data. This here is a binary heap. It's also a tree. This is a binary search tree, slightly different rules. This is a graph. This case, an unweighted, undirected graph. This is an unweighted, directed graph. Similar, but different. So the point is, all of these do the same thing at the end of the day. They store data, but their behavior, the relationships between the data, and their functionality, the methods we get to act upon them, are very different. So the next question is, why should I care? Or why should you care? Well, there's a lot of time devoted to data structures in this course, and there's a couple reasons. First of all, the more time you spend as a developer, the more likely you'll need to use one of these more advanced data structures. Usually there's a time in every developer's life when using an array for every single possible problem just doesn't cut it. You might need something more efficient. You might need something to express a different relationship. You might be working with more complicated data that isn't linear, and you need another way of storing it. There's many situations where this can come up. Or you might be working with an API or a library that gives you, like a database, for example, that returns a graph representation, and you need to understand what the heck a graph is in order for that to make sense. Also, another reason worth knowing is that you've already worked with many data structures, probably unknowingly. So if you have ever worked with the DOM in JavaScript, you've manipulated and interacted with a tree. That's just one example, but as we go through the different structures, I'll constantly point out existing use cases, things that you're probably familiar with each data structure. And then finally, a really important one, of course, especially in this context, interviews. So these data structures are the fodder of many an interview. It's worth knowing alone just for that, but I don't want to make that the focus of all these data structures. These exist for a reason. They're taught for a reason, and it's not just to ace random hard interview questions, though it can definitely help with that, and a lot of people like to ask data structure questions. Can you reverse a singly linked list? Can you implement a priority queue? Can you balance a binary tree? All that stuff is worth knowing, but at the same time, these data structures are useful in the real world. If you never interview, they're still worth knowing. So we'll come back to why as we visit each individual structure. An important note, a lot of people ask this, what is the best one? Which one should I know? The answer is there is no one best one. They all do different things, right? They each have specific talents, if you will. Some of them are more general, just commonly used like an array, but some of them are very specific. But they all excel in different environments. Otherwise, why bother having them at all? Why bother learning them? I wouldn't be teaching them if there was one data structure to rule them all, one you could master and then call it a day. So they all excel in different situations. For example, maybe you're working with map or location data. You're writing a GPS application like, Google Maps, which should be a huge undertaking. But let's simplify it even further and say you're trying to write code that will route you to the nearest gas station or something like that, that has the cheapest deals, whatever. You might want to use a graph. A graph would make sense for this. And we talk about graphing data. We talk about finding the shortest path between points on a graph, representing GPS data and location data using a graph. So that's one situation. It would be very difficult to represent a map using a single array. What if you need an ordered list, like an array, but you need fast inserts and removals at the beginning and the end? So if you watched early on, we talked about arrays. They do not do well when you insert at the beginning or remove from the beginning. Everything has to be re-indexed. So maybe you have a huge data set and you have to have it ordered. It's like 1 million data points and you are always inserting and removing from both ends. Then you might not want to use an array. That's where a linked list could come in handy. So knowing about a linked list would help you in that situation. Are you web scraping nested HTML? Are you writing some sort of app that is scraping data from, airlines websites or hotel websites and you're interacting with that HTML, or maybe you're using a library to help you? Well, it's almost guaranteed to give you the data in a tree. Do I have another example? Need to write a scheduler. So this might be a bit more nuanced than HTML, but if you're writing an app that has tasks that are scheduled and you need to find what's the highest priority task to handle at any given point, you might use a binary heap. So we'll talk about priority queues and binary heaps in that section. Okay, so enough of those examples, but hopefully that makes it clear. These all excel in different situations. There is no one data structure to rule them all. Definitely go through all of them. But along with that, a quick message. There's a ton of content here From here on out, this data structure stuff gets dense. And I highly recommend you don't just go one section at a time and sit through the night, or even do it all in a day or two. It's a lot. I beg you, please. It will burn you out. This is content that in my classes, we do over 2 weeks of an intensive boot camp where it's 10 hours a day, sometimes 8 hours, but usually 10 hours a day. We do 2 weeks, so that's 10 full days to cover this data structures content. And those are people who have been, in this classroom for 12 weeks or 10 weeks at that point. So they're relatively skilled developers, and they are expecting a tough time for the last 2 weeks. So I beg you, don't try and fly through this in a night or two, or even a single week. It's a lot. For example, watch the singly linked list section. Take a break. Take like an hour, 2 hours, 3 hours, an entire day, come back after the weekend, whatever it is, and then do doubly linked lists. Don't do them one right after the other. It's up to you, of course, but that's my recommendation. There's a lot there. Okay, and one last little note. Please pay attention to the prerequisites listed for each section. So a lot of these data structures build upon one another, or in some of the later sections, like when we talk about graphs, we talk about a particular algorithm called Dijkstra's shortest path algorithm. And in the algorithm itself, we actually use another data structure from earlier in the course called a binary heap. So if you skip the binary heap section and go right to the graph section, you will be missing some important information. So I made it at the beginning of every single section is a text lecture that explains what you need to know for each section. So you don't have to go through them in a linear order, but they are in an order that makes sense. And if you do want to learn them all, just start at the beginning at singly linked lists and go all the way up through graphs. Okay, I'm done with all these little announcements and pep talks and whatever else this has been. So welcome to the new section, or the new sort of portion of the course devoted to data structures. There's a lot of important content here, some very useful stuff, but there's a lot of stuff in general. So again, take your time. The first thing we're going to do before we actually implement our first data structure, the singly linked list, we need to just discuss ES 2015 class syntax. We're defining a new class for every data structure we learn. So if you already know how to do that, skip the next 3 videos after this one. But if you don't, highly recommend you start there, because we use this syntax, the class keyword, in every single video from here on out. Okay, I'm done, I promise. Welcome to data structures. Let's get going. Hey, welcome back. So as I've already mentioned, this section marks a significant turning point in the course. We're now going to focus our attention on a bunch of data structures. So classic data structures like singly linked lists, doubly linked lists, stacks, queues. We're also going to implement more complicated ones like trees and binary search trees, graphs. But along the way, not only are we going to learn about these data structures and talk about why they matter and how they're useful, we're also going to implement them. JavaScript doesn't come with any of these pre-built. And so the point is that we're going to go through and write our own. But in order to do that, we need to take advantage of the ES 2015 class syntax in JavaScript. So depending on how familiar you are with JavaScript and with object-oriented programming, you may know that JavaScript doesn't really support OOP, or object-oriented programming. However, with ES 2015, a new class keyword was introduced. We're going to take advantage of that throughout this course because it makes it really easy and simple for us to define our data structures. So if you're already familiar with it, if you feel good about using the class keyword, writing constructors, instantiating new instances using your class in JavaScript, then you could skip this section. But if you need some review over it, or if you've never learned it before, I think that this will help you out. Also, if you've never worked with any sort of object-oriented language before, or you've never defined any sort of patterns, whether it's in JavaScript or in Python or Ruby or any other language, then this is going to be kind of a lot to take in right away. But I recommend that you watch this video, you try some of the examples, and then you start out with a singly linked list, which is up next, and see how that goes. But take it slow if you've never written a class before. So first, our objectives. We're going to start by talking about what a class is. We're going to understand how JavaScript implements the idea of classes, which I bolded because it's not quite true object-oriented programming. We'll define terms like abstraction, encapsulation, and polymorphism, and then we'll use ES 2015 classes to implement data structures. Okay, so first up, what the heck is a class? So in general, a class is like a blueprint for creating objects with predefined properties and methods. So we'll learn how to make a singly linked list or a doubly linked list. We define a pattern for a doubly linked list, but then we can actually instantiate many objects, many individual linked lists using that blueprint, using our class. It's sort of like arrays in JavaScript, although it's not quite the same. We have a pattern for an array, and arrays come with a bunch of methods and things that they can do, but we have to first instantiate a new array, and then we can get access to all of those. So there's an array, it's not technically a class, but you can think of it as sort of a blueprint, and then we can instantiate objects based off of that blueprint. So as I kind of hinted at, JavaScript doesn't really have classes. If you go to the documentation on MDN, Mozilla Developer Network, you can see up top on the, this is their classes main page. JavaScript classes introduced in ES 2015 are primarily syntactical sugar over JavaScript's existing prototype-based inheritance. The class syntax does not introduce a new object-oriented inheritance model to JavaScript. So what this is saying is basically JavaScript has never really been truly object-oriented. It takes advantage of something called prototype-based inheritance or prototypal. And all that happened with ES 2015 is that this class syntax was introduced, but it's not changing how things work behind the scenes. It's just an easier way to work and to define class-like structures. So if you are not familiar with either of those, with object-oriented programming or prototype-based inheritance, then that probably made zero sense. But all that we'll say is that it does help to know that technically this is not true object-oriented programming, but that's not going to hinder us in any way. We just have to, it's good to know that. Let's just leave it at that. So next, why do we need to learn this? Well, as I've already mentioned, we're going to implement tons of data structures as classes. So anytime we build, we're going to learn how to build a tree or a graph or a singly linked list. We're going to define a class, define a pattern in JavaScript that we can then instantiate individual lists from. For example, here's a little spoiler. Here's two classes we defined for our singly linked list. So you can see we have the class keyword, constructor. We'll go into all this detail, but here is the class for the singly linked list. It's kind of long. There's a lot of methods we add in there. This is a blueprint though. This doesn't actually represent any data. There's no instance of a list. We still have to instantiate one. Here's another really short class called a node, and the singly linked list class utilizes the node class inside of it. So that's all I'll say about it for now, but this is just a single example of many that we're going to see and implement on our own. So I think that I'll leave off here. Just know that classes are what we're going to use throughout the rest of the course. Coming up next, a bunch of data structures. In the next video, though, we're going to introduce the syntax for classes. So if you know it, you can skip it, get some review. But if you don't know it, I highly recommend that you just sit through the next couple videos. I know it's not on data structures just yet, but it's really important because we're going to use this. Okay, I'll shut up. All right, welcome back. Now we're going to actually take a look at how you declare a class in ES 2015. Here's a really simple example. So we have a class called student. Conventionally, classes should start with a capital letter. That should be camel-cased. So we've got student here. So this is a pattern for a student. And every student is just going to have a first name and a last name. That's it. Obviously, this is something we don't need a class to do. Yeah, I mean, you don't really need a class to do any of the things that we're going to do in this course. It's just a nice way of organizing your code. We could use just a plain old object, just key value pairs. But instead, we're going to create this blueprint so that our code is easier to work with, easier to understand, and just nicer, better organized. So we define our class, student, and then we have our curly braces, but then we have to have this thing called a constructor. So it has to be named constructor, and it's a special method that will be used to instantiate new student instances. So we pass in, when we create a new student, we're going to provide a first name and a last name, and then all that we do in here is set this dot first name equal to whatever the first name was, and this dot last name equal to whatever the last name was that was passed in. So this is just a way of saying that whatever is passed in when a new student is created, assign those two properties to the individual object, the individual student. So then next, to actually create a new instance, we've defined the pattern here, the blueprint, but this doesn't make any students. We have to use the new keyword. So this is how we instantiate objects from a class. So we say new student, and then we pass in first name and last name. So we have two, cold steel and blue steel, and each of those is going to basically create a new student object based off of this pattern, where first name will be set to Colt, last name will be steel in the first one, and in the second one, first name will be blue and last name will be steel. So if we just copy this over quickly here, And let's expand on this, and let's add in first name, last name, and let's also add in year or grade level or whatever you want to call it. But the idea is that it's just going to be, how far in school this student is. So let's say that our school goes from 0 to 4. It's a high school in the US at least. There's 4 years of high school. So I'm going to set this.year equal to year. Now this name can be anything I want, just like this can. So if I call this instead grade, that's fine. This.grade will be set to whatever is passed in when a new student is instantiated. Okay, so just on its own, if I run this, nothing happens. But now I'm able to instantiate, well, I shouldn't say nothing happens. No students are created. We've just defined a pattern. We're basically saying, all right, here's this thing that now we have this blueprint. We can actually go and make new students. We've made like a mold, like at a factory. You make a mold for a part that's not actually making the part. You just are ready to make the parts now. I don't know if that's very helpful. So if I did something like this, new student, and then I pass in some data. So let's have a new student named, not email, Emil, I don't know, Katz, and he's in year 3, sure. You can see what I get back is just a JavaScript object that has a first name set to Emil, grade is 3, and last name is Katz. So notice year is nowhere to be found, the actual name year, because we just called it grade instead. This is just a placeholder, just like any argument in a function. Okay, now if I save that to a variable, let's call it, let's just call it person. Now I'm terrible at this. Let's go with Emil, like this. I can now access, for example, first name. So nothing revolutionary at this point. This is just a nice way of organizing our code. But I just want to make that really clear that when we define a class, it doesn't do anything on its own. We have to actually instantiate using the new keyword instances of that class. So we will eventually have a class called, let's say, tree, for example, or singly linked lists. Defining the class is just the pattern, but then we're still going to have to say new tree or new singly linked list and then do something with that, call a method on it. So now if I run this, we have 2 students. By the way, if you're just skipping to this, I use Command Enter to run my snippets. You can also click here or wherever you're doing this, but I realized that might have looked like magic. I hit Command Enter. So now we have a first student and we have second student. And notice that grade is undefined in all of them. And also, if I wanted to, I could now define a grade or update a grade to be, let's see, for second student, grade is 4. Now if we look at second student, grade is set to 4. So you might be wondering what the this keyword is referring to here. So often, the keyword this is a source of confusion pretty much always in JavaScript for many students, and it changes, its meaning changes depending on its context. But in this situation, when we're inside of a constructor or another instance method, we'll talk about instance methods in the next video, but when we're inside of a constructor, let's just say that for now, this refers to the individual instance of the class, so the individual student. So this refers to this student or this student, depending on which one we're talking about. So when we instantiate a new student, let's say let Kitty equal new student, and her name is Kitty Cat, and she's in grade 1, like that. When I do this, what it's saying is that on this new instance of student, this specific instance, its first name should be equal to whatever is passed in, Kitty. Its last name should be equal to whatever last name is passed in, which is Cat. And this dot grade, its individual grade should be set to whatever the value of year is. I hit enter, and now we have our Kitty defined. Okay, so that's the basics of the class syntax, the idea of the constructor. I guess I never went over the fact that we're never explicitly calling constructor, right? We're not saying student.constructor or something. There's some magic behind the scenes, some syntactic sugar that we use the new keyword, but the constructor method is going to be executed. Our data will basically be patched on through, and our constructor will run when we instantiate a new student or whatever our class is. Okay, so next we're going to talk about defining methods on our classes. Okay, welcome back. In this video, we're going to talk about instance methods as well as static methods or class methods. So to start, instance methods are something we're going to use all the time in the course, much more frequently than the second type of methods we'll see. Instance methods are methods that basically, I don't want to say they live on a particular instance, but they provide functionality that pertains to a single instance of, in our case, a student. Or when we talk about a singly linked list, we will define many instance methods on those particular instances. Think of, for example, when we're working with an array. If I make a new array, so let's just call this array, data equals, and I'm going to do this syntax and pass in some numbers. Here we go. So we now have our array called data. If I do something like data.push, this is a method that acts on the individual instance of the array, which is data. So an array is a pattern, and we can define individual array objects based off that pattern. And so this is one instance, and push is a single method. I was going to do something like sort, and then I realized that I made a sorted array. So we'll do push and push 20, how about 99? And there we go. Now we look at data and it's changed. So we work with instance methods all the time, or the rough idea of instance methods in JavaScript. So we're going to do the same thing now on our student. We're going to create a method or two methods that correspond to individual instances. So not things that work on the class level, but things that are relevant to individual instances. So for example, here's one called full name. Again, not very useful, but it returns a string. Your full name is, and then inside that string, we're adding in this dot first name and this dot last name. And again, this refers to the individual instance. So whoever is calling this, whether it's first student or second student, will get a different output, assuming that they have different first and last names. So if we go back, I'm going to add this method in right here. And now if I execute my code, I have first student and second student. If I try first student, oh, there's no grade for either of those. That's okay. But let's do first student dot, and now we call full name. And I need to, if I just leave it at this, it returns to me. It's basically saying, yes, I know there is a method called that, but if I want to execute it, there we go. Your full name is Cold Steel. If I do second student dot full name, I get your full name is Blue Steel. So these are silly examples of what we're doing here. When we get to a linked list, though, we will define a reverse instance method or a push instance method, things that will actually work on individual instances. For example, in the next section, here's our singly linked list class. We have our constructor, but then we have a push instance method, a shift, an unshift, a get, insert, what else? Reverse, remove. Those are all, and pop. Those are all individual instance methods that work on a single linked list. On a singly linked list. It's confusing. So we have to instantiate a linked list in order to use those. Just like if we're trying to pop from an array, we have to have an individual array to pop from. We don't just pop from nothing. We need an instance. So let's extend this class. Let's add in a different method that actually updates the value of one of these properties. So let's say in our school, students can only be late 3 times. So let's create a new property. What do we want to call this? Absences is too hard to spell. Let's just call it, at least in the US, we call them tardies. I don't know how universal that word is, but we're going to call it tardies, and it's going to be set to 0 whenever we create a new student. By default, they've never been late. But now we're going to have a method called mark late. And all that it does is it adds 1 to tardies. So we need to access this dot tardies, which is referencing the individual student, the instance, his or her tardies. And I'm just going to add 1 plus equal 1 like that. So that updates it. And then let's return a string, or we could just return the number of tardies, but let's return a string that says, let's do full name, this dot steal, this dot last name, this dot first name, this dot last name has been late. And then in here, let's add in the number of times, and we're not going to pluralize correctly or anything. We'll just say this dot tardies like that. So Blue Steel has been late 3 times. Okay, so if we save this now and we instantiate a new student, we're not using grade, so I guess I could pass 1 in here. So I'm in first grade or first year, and Blue is in second year. Now I'm going to run this code, and if we look at students now, so let's look at first student. Now, if I access mark late, I have a method available to me, and if I execute it, don't need to pass anything in. Cold Steel has been late 1 times. And if I look at firstStudent.tardies now, I should have earlier looked at it. It was 0. There we go, tardies 0. Let me make this a bit larger. I've now marked it, and I can do the same thing one more time. And how about 2 more times? So now I have been late 3 times. We don't have any logic in there. I mean, we could add in a little conditional to check. If it's greater than 3, then we expel you. Why don't we do that really quickly? So we'll add 1 to tardies, and then we'll just add a conditional. If this dot tardies is greater than or equal to 3, return you are expelled. So if I rerun my code, instantiate, or let's go back to first student and do mark late the first time, the second time, and now the third time, you are expelled. And every other time you're expelled. Okay, that's good enough for us. The last thing we'll talk about with an instance method is defining one that takes some sort of argument. Let's also add in an array here called scores. It will start as empty because there are no tests at the beginning when we create a student. But then we're going to create a method. And our first one, this will be super easy. We'll just call it add score. And it will take in a new score. And then we'll just do this dot, and what do we call it? This dot scores dot push score. So this will just add the score on to the end. Now, yes, you could access this directly, but we'll talk about that in a second. So this dot scores dot push, and then let's return this dot scores. So if I rerun my code, and I now look at, let's do second student this time. Second student dot scores, it's empty. And I could just do manually just push on from here. There's nothing stopping me from doing that, but it's more conventional to define a method that will do this to prevent, there's nothing stopping anybody from manually changing any of these properties. But the conventional way of writing a class is that you assume that a developer or somebody will use a method that you put there. So we're going to use this instead as our interface to the data, rather than we would ask someone not to directly change our data. Instead, go through some sort of method. So we have add score. So I'll do second student dot add score. And then in here, what do we want to add? Let's say the score is Blue is pretty good. She's a 92. And let's do one more, this time an 87. And now if we look at second student dot scores, you can see, well, we were returning it already, but we have 2 scores in there. So the last thing that I want to do is create something called calculate average, a method. And it doesn't need to take any arguments in, and it should return the average of the scores in the individual student's scores array. So we'll have this dot scores, and we're going to need to sum them all up, and then we'll need to divide them by the length of the array. So to calculate the sum of all the elements first, we could use reduce like this, and I'm going to make a separate variable here. So let's call this sum. And then we're going to return sum divided by this dot scores dot length. So this logic is just here to reduce. It's going to take each item, it's going to add it together and create a total. So each number in this dot scores array, save that to the sum variable, and then we return sum divided by this dot scores dot length. Let's test it out. So first student dot scores, or no, wait, we wanted to use add score. So 98, and then I did poorly and I got a 76. And then I did, let's just leave it at those 2. It'll be easier to tell if it's working actually. So now if we do calculate average, there we go, 87. Now if I add a different score in, see, I do really well, I get 100. Now our average goes up, and we could round it and all of that. Okay, so all that I want to show here is the basics of defining a class with instance methods. So we can define a simple instance method that just returns a string using some properties. We can define one a little more complex that manipulates one of the existing properties on our instance, or we can do something like calculate average, which is going to have a little more math in it. But the idea is that all of these operate on individual instances. So next, we'll take a brief look at creating a class method, which we won't do very often, but I should put it in here just because if we're talking about classes in ES 2015 at this point, I need to cover it. Okay, see you then. Welcome back. In this video, we're going to talk about class methods. So we talked about creating a class or defining the pattern, writing a constructor method. We talked about the new keyword. We talked about instance methods. Now we're talking about a second type of method you can add to a ES 2015 class called a class method, where we use the static keyword in front of the method definition. So what this allows us to do is define methods or functionality that is pertinent to classes, but not necessarily to individual instances of a class. So this is actually not that common, and most of what we do in this course is going to be around instance methods for our data structures. But if we go to the docs on MDN again, I like this explanation. The static keyword defines a static method for a class. Static methods are called without instantiating their class and cannot be called through a class instance. They're often used to create utility functions for an application. So the example that I added here, which is not a complete method, by the way, I didn't write the actual functionality, but the idea is that we could have a method called enroll students, and this is a class method. You could pass in multiple students in an array, for example, like we have down here, and this would go and maybe send emails to each of their associated email addresses or something like that. The idea is that this has to do, it's more of like a utility function. I like that explanation. It's not related to a single individual student where we are using data from that instance like we were here. We're using the name, the first name, and the last name of each individual student. And so we would call this first student dot full name. But this enroll students, which again is not fully defined, what it does is not related to a particular instance. It's just part of the class in general. It's some overall functionality, some utility function that we want. And the way we call that is student with a capital S. So back here in our code, if I try and add a class method down here, we'll call one enroll students, which is fine, but we're not going to actually enroll any students. We're just going to return a string, enrolling students. Oh boy. Okay. So just the most basic possible class method here. And what I want to show is that if we instantiate these first student, I can't call first student dot, what do we call it, enroll students. Oh, I use a capital E, which I did not mean to do, but either way, it's not going to work. I need to do student dot enroll students, and I need parens, and now we can execute that method. So this is functionality that is not relevant to an individual instance, but we still want it as part of the student class. It has to do with students in some way, or it's a helper method, a utility method. And with students, it's kind of hard to show an actual example that makes sense. So I actually have a second example here. This is one that I took from the documentation on MDN. So we have a class called point. So imagine a point on a Cartesian plane, an XY coordinate, basically. And if we're working in this coordinate system, each point has an X value and a Y. So we can initialize new ones down here, 5, 5, 10, 10. But then there's some utility method that we want, like distance, calculating the distance between 2 points, which it's been a while, probably for me, definitely for some of you, probably since you've had to use this, or maybe you never learned it. There's a distance formula where this is the math you need to do to figure out the point between two, or the distance between 2 points, which has to do with forming a right triangle and the hypotenuse of that triangle. Anyway, let's not go into it. But this is the math for it. So you could make this into a class method. It doesn't make sense to have the distance method be on an individual instance. So for example, I'm going to run this. So I have P1 and P2. If I wanted to find the distance between P1 and P2, rather than putting, how would I do that? P1 dot distance, and then I pass in P2. I mean, that could work. You could implement it that way. But this is more a utility function, so we make it a class method. So instead, I'm going to call point, capital P point, dot distance, and then I pass in P1 and P2. And this is the distance between the two. Does that make sense? Why you would maybe organize it this way? Of course, all of object-oriented programming, all of everything we're doing with this class syntax, it's just about making things organized better or easier to understand and more logical. So that's pretty much it to class methods. All that you do is put the static keyword in front of them, and that makes it a class method, which means that you no longer call it on an individual method or on an individual instance. You call it on the class itself, like point. Or earlier in our example, we had student, capital S, dot enroll students. Okay. Versus instance methods you call on an individual instance, like second student or p1 dot, well, we don't have any instance methods in this example, but if we did, we would call them on p1 or p2 and so on. So as I mentioned earlier, this is how we'll be using classes ourselves. We'll mainly be defining a class, some data structure, class binary search tree, class doubly linked list. Inside of it, we'll have our constructor, all the default values or the initial properties we need our singly linked list or our binary search tree to have. And then we'll have a bunch of instance methods, as I showed in the last video. Some of these data structures we'll look at might have 10 different methods that we define, and it's going to be pretty rare that we're going to use any static methods, but I felt that this would be incomplete if I didn't at least explain their existence. If I only mentioned instance methods, it would be disingenuous. That's not the right word. It would be incomplete of me, so I needed to show that they exist. But most of what we're going to do is going to follow this pattern. Class data structure, whatever it's called, our constructor, and then a bunch of instance methods that make it all work. And lastly, remember that the keyword this behaves a bit different than normal. If there is a normal, it always behaves differently. But the way that it behaves inside of ES 2015 classes is that inside of any instance method or the constructor, the keyword this refers to the object created from that individual class, the actual instance. And we've already mentioned that, but I just put a slide in here just to make that extra clear. So to recap everything here, classes are blueprints that when created make objects known as instances. Classes are created or instantiated with the new keyword. The constructor function is a special function that gets run when the class is instantiated. When you run new student, the student constructor is run. Instance methods can be added to classes similar to methods and objects, and class methods can be added with a static keyword. All right, now that we get all of that out of the way, now we can look forward to actually diving into our first data structure. We're going to start off with singly linked lists. So that's up next. We'll be defining our first class. See you then. Hello, welcome back. So this is the first of many sections on data structures. The first one we're going to talk about is called the singly linked list. We also have a doubly linked list. We'll see that later. We're starting here. So a quick preface, a warning, a note. If you're unfamiliar with the ES 2015 class keyword, JavaScript's approximation or syntactic sugar to sort of look like traditional object-oriented programming. If you've never seen that before, or you want to refresh your memory on it, take a look at the previous section. I think a lot of students may have jumped to this section. If you did, I would check that out if you're not familiar with how it works. It's a quick little section. And the reason is that we're going to use that class keyword in pretty much every data structure we make, or every data structure we create. We'll define our own JavaScript class. We're going to make a singly linked list class in this section and do the same thing for graphs and every other structure we see. Okay, so quickly, our objectives. We want to explain what the heck a singly linked list is. We're also going to compare it to the list structure we already know, the built-in array. We use it all the time. So that stores a list of data. What's the difference? And then the bulk of this section will be devoted to actually defining our linked list class and adding in a bunch of methods, a lot of functionality to push things into it, or to pop things, or to search and traverse, or to delete things, to all sorts of things. So that's what we're going to do in this section. Okay, so let's start with a definition. What is a linked list? So it's a data structure. It stores whatever sort of data you want, strings, numbers, it doesn't matter. And it's ordered. It's a list of data, just like an array, but there's a really big distinction. In an array, each item is mapped, it's indexed with a number. So I can get the 5th item, the 6th item, and anytime we add something in, it gets an index that is mapped to its position. A linked list, on the other hand, just consists of a bunch of elements with no indices who are just pointing to the next element. It's sort of like a bunch of train cars connected, where one car connects to the next one, and that one connects to the next one, but there is no index that we use to access things. We can't say, give me the 5th thing. We have to start at the first one, and then move to the second one, move to the third one, move to the 4th, and then move to the 5th. So just some terminology here. I'm going to show you a diagram in just a second. But we say that each element is a node. So a linked list consists of a bunch of nodes. A node stores a piece of data, like a string or a number, but it also references the next node. Or if it's at the very end, there is no next node, it references null. And then 3 properties we keep track of. The head is the beginning of the linked list. The tail is the end. So we don't keep track of every single item in the middle. We just keep track of the head. And from the head, we can figure out the next one. And from there, we can figure out the next one all the way until the end. And then also we keep track of the length to make things easier. So here's sort of a diagram of what a linked list looks like. Notice there is no index. So we don't say this is the 0th, the 1st, the 2nd, the 3rd. If we want to access something from this list, we start at the beginning. If we want the second to last item, we have to start here and ask for the next item, which gives us 6. And we have to ask for the next item, which finally gives us the second to last item. So a linked list is just a bunch of nodes pointing to other nodes. So one node points to the next one, points to the next one, sort of like a chain of elephants. Back before they banned elephants at the circus in the US, they would grab each other's tails with their noses and walk in a line. I kind of like to think of it as a skyscraper that has no elevators. So in an array, there's elevators. You could say, take me to the 5th floor, and it takes you right there. If you're in a linked list, there's only stairs, and each floor is connected to the next one by a set of stairs. So to get to the 5th floor, we have to start at the first one, take the stairs to the second, then go up to the 3rd, then to the 4th, and then we get to the 5th. I don't know if that's a great analogy or not. By the way, the terminology singly linked list comes from the fact that each node is only connected one directionally to the next node. A doubly linked list, which we'll get to, so don't worry about it right now, also has a connection pointing back to the previous node. And we'll talk about the pros and cons of that later on. So here's a visualization on Visualgo. I never know how to say this. It's a great website though, and it's going to be very useful here. So this is a linked list where each node just contains a number. Remember, it could be whatever we want. We could have, strings. We could have we could have an array in each one. It doesn't matter. And they all just point to the next item, except for the last one. There's nothing after it. And let's say that we're going to, insert something. Actually, let's start with searching for something. So if we want to search for, let's say 43 in this linked list, we have to start at the beginning and check the next, then the next, then the next, then the next, and then we find 43. Okay? If we wanted to insert something into here, if we want to insert something in the middle, that's this one. Let's say at position 4, we want to insert the number 90. We have to start at the beginning, then move down to the next, keep going until we get to the correct spot, and then we insert it in. Now, the actual process of inserting we'll come back to. We're going to write our own insert functions. It's pretty easy, though, especially if we're inserting, to the beginning or the end. All we have to do, let's say, to insert it at the very beginning is just make this the new head and have it point to the old head. And all of a sudden, we're in business. Unlike an array where we would have to, we don't do this, but in an array, every single item would have to be re-indexed to get a new position number. Okay, so we're going to come back to this and spend a lot of time sort of walking through this as we build our own methods. But let's wrap up with a comparison with arrays. So linked lists don't have indices or indexes, I think it's indices. They have no number that corresponds to each item. Instead, we just have the head pointer, which is just a variable that says this is the beginning of the list. And we have a tail. You actually don't have to have a tail. It just makes it easier if you're trying to add to the end. But we have to have that head. That's the beginning. And then we can just move to the next, and to the next, and to the next, until we find what we're looking for, or we insert something. Unlike an array, there's no positional, there's no indices. So each node is connected with a next pointer. What this means, random access is not allowed. So random access means I can't just ask for the 10th item and get it immediately. We have to traverse from the beginning all the way to the 10th item. Just like the analogy I explained with the skyscraper, if you have an array, you get an elevator straight to the 10th floor. If you have a linked list, you walk all the way up to the 10th floor. However, one of the things that linked lists are good at is insertion and deletion. So because arrays are indexed, if we insert something at the beginning or in the middle, we've already talked about this, it has this cascade ripple effect. Everything has to be re-indexed. In a linked list, that's not the case. And we'll get into this further. We'll talk about big O of certain operations throughout this section. But just know that. That's one of the reasons, or really the main reason you would want to use a linked list, is if you really care about insertion and deletion. Especially if you're working with really, really long pieces of data, or not pieces of data, with a long data set, lots of information, and you don't need random access, you just need to store it in a list, well, you might want to use a linked list. But we'll come back to this. Remember, a lot of this right now is just going to be very sort of theoretical and conceptual. Don't get too caught up on, why would I use this if we already have an array? Because at the end of the day, you could use an array for all of this. But there are advantages to linked lists, and we'll expand on that. Anyway, in the next video, we're going to define our linked list class and add our first method in. So that's coming up next. Hey, welcome back. So let's start writing our code. Remember that a linked list is just a collection of nodes. So let's start by defining a class for each node. And a node is very simple. It just stores a piece of data. We'll call it val or value, and then it stores a reference to next node, which we'll call next. So let's define our class. I'll call it node. We need to add our constructor, and it will just take in a val, whatever the piece of information is. And we'll just set this dot val equals val, and then we'll initialize this dot next to be null, because at the beginning, there's nothing that comes after it. All right, so this is actually all we need for our node. It's very simple. And we could sort of approximate a linked list right now. What we're going to do is define our own singly linked list class that will utilize node. But for now, I could just do something like this. Var first equals new node. And let's say our first node is hi. Then I could do first.next equals new node. Let's not do capitalize. Hi there. And then do the same thing again. Dot next. Does that make sense? So we're starting with the first thing, and then we're just accessing the dot next and setting it to be a whole other new node. And then we're taking that value and giving it a new dot next, a whole other new node. So I'll do hi there, how are you? Overcommitted to the number of words here. All right, we'll leave it at this. How are you? I think I need two. Yeah, I need two dot nexts. I don't have any of my shortcuts in this. All right, there we go. So this is a very bad way of representing a linked list, because if I want to add something in, I need to keep writing dot next, dot next, dot next, dot next. What we'll be defining later on is we'll have a linked list class, and I should be able to say list.push you, for example, and that will add on to the end. It will keep track of where to add that. Anyway, this is what we have for now. So if I actually run this, if we look at first, all right, that's what we have. The value is hi, and there's a reference to the next node. If I click on it, we can see next is this node that says there. And if we click on that, I can see that the next is on that is a value that says how, and we could keep going. So let's actually define our linked list class to make this a little bit cleaner so we don't have to do all of this. So down here, I'm going to define class singly linked list, and we'll add our constructor, and it's not going to actually take anything. Our interface is going to be something like this. We'll define a new linked list. So new linked list, technically it should be singly linked list. So quickly update that. Save that to a variable. Let's say it's, I don't know, list equals. So our interface will be something like this. We create a new singly linked list, and then we can say list.push something. List.push hello. List.push goodbye. And this will add on to the end of the list. And we don't have to do dot next, dot next, dot next, dot next. It will just keep track of it and do it for us. So this is where we're going. Still very simple, but much better than having to do it this way. So our constructor, we don't initialize a linked list with any data, so it's just empty, or it's not empty, but it doesn't take any arguments. And in here, we're going to define a couple of things. Remember that a linked list has a pointer to the head of the list, a pointer to the tail, those are just variables, and then a length. And so at the beginning, this dot length should be 0. Also, head and tail will be null. So this dot head equals null. This dot tail equals null. So we've now defined the basics. So we have our two constructors. Those are actually done. We're not going to change those. What we are going to work on is adding a bunch of methods into singly linked list. So what we're going to do in this video is add a push method. So push should take a piece of data. Let's call it val. So I should be able to do this, list.push hello, and it should assign a new node, it should create a new node like we did over here, and assign it to the head of the list, and also the tail because there's nothing in here. And then if we push something in again, it should now assign goodbye to be the tail of the list, and have the head, hello, point to the tail of goodbye. So if we were to visualize how push would work, right now we have an empty linked list, and if I try to insert, so push means inserting at the end, so we're going to go with this option after the tail. So if I insert 80 at the beginning, it's super easy because we just set the head and the tail to be 80. But now if I insert something else at the end, let's go with 100. Oh, I guess that's too high. Let's go with 81. All that we do now is take the head and have the next property point to 81. And then we set the tail to be 81. All right, one more. Let's do 85. We're going real high here. So I'm going to insert this at the end. All we have to do is take the current tail and point it to 85, and then update that to be the tail. So pushing to the end of a list is super easy. If we have 1,000 or 1,000,000 items in here, we don't traverse the whole thing. As long as we're keeping track of the last item in the list, all we have to do is say, hey, take that last item, point it over to this new last item. And now the tail we update the tail to be the very end, 85. So here's some pseudocode. If you would like to try and implement this on your own, in the next video, I'll go through a solution. So we're going to implement a push method. I already defined the skeleton here. All it needs to do is accept a value. I already gave that to you. Create a new node using that value that we passed in. So if we pass in 50, you should make a new node where the value of that node is 50. Now, there's a special edge case. If there is no head, meaning if the list is empty, set the head and the tail to be that newly created node. That's the first thing we saw over here, where we had an empty list. When we added in 80, the head and tail both pointed to 80. Otherwise, if there is a head, set the next property on the tail to be the new node, and then update the tail property to be the newly created node. Once again, if we added one more thing in here, this is our current tail. If we add in 90, all that we do is take the current tail, point it to the new node with 90, and then set the tail to be 90. And then finally, increment the length by 1. We are keeping track of the length. So add 1 because we're pushing something in. All right, so those are the basic steps. Give it a shot if you'd like. In the next video, I'll have a solution. If you do get stuck, don't be hard on yourself. If you've never seen linked lists before, I recommend attempting as much as you can, get through the section, and then if you have time or the energy, at some point, go through all the exercises and try them from scratch and see if you can replicate it. Nobody's expecting you to get everything right the very first time through. Okay, the next video will be a solution to push. All right, so let's write up the solution to push. If you don't care about it, if you already got it, you want to just check your work, just look at the file included with this video. Okay, so I've made a new snippet just so we can keep track of the first one. I'm going to do this for every single function or method we add. Anyway, here's push. We already have a skeleton, so this first bit is done. It should accept a value. Now what we need to do is create a new node using the value we pass in. So that's easy enough. We have our node class. We just need to make a variable. Let's call it new node equals new space node, pass in the value. So for example, when we make a new list, I'll just give it the name list, it's empty. Then we do list.push hello. It's going to take that string hello and make a new node. It's not added to the list yet, it just exists. Next, we need to check if there's a head property on the list. If there is, set the head and tail to be the newly created node. That's the edge case when it's empty. Whoops. So to check that, we could just do if this.head, or let's actually do if not this.head. So if there is no head, meaning it's an empty list like it is right here, what do we want to do? We want to make this.head equal to new node, and then we'll set this.tail to be the same thing. We could just do this.tail equals this.head, if that makes sense. So they're both pointing to new node. The head and the tail are the same thing. So right now, push will work one time, only the first time. And if we look at list, I just ran the code, we can see that, okay, well, first of all, the length is incorrect. It needs to be updated. It says 0 still. But otherwise, the head and the tail are pointing to the right thing. But if I push something else in, like goodbye, nothing will happen, because if I do list.push 10 or 1, nothing happens because it's all guarded by this if statement, which this is not true anymore. So nothing happens except we make a new node and it just never gets added. So on to the next part, which is otherwise set the next property on the tail to be the new node and set the tail property on the list to be the newly created node. So this only runs if it's empty. Otherwise, what we want to do is take the tail. So take the current tail, this.tail, take the next property and set that equal to the new node. So if I have hello as the tail and I push goodbye, we're going to take goodbye as the new node, take the current tail hello, set the dot next to be goodbye. And then we just have to update this dot tail to point to that new node. Like that. That's our new tail. Okay? So we took the current tail, we added on to the end of it, and then we moved the tail marker over. And then the last two things we need to do is we need to increment the length by 1. And the last thing, return the linked list. I didn't actually click that far in the last video. I apologize. We do need to return it. So let's go back and do that now. We're just going to increment the length. So this dot length plus, let's just do plus plus, and then return. How do we return the whole list? Just return this. And that should be all we need to do. So if I'm going to get rid of this for now and just I'm going to rerun my code. Okay, if we look at list right now, it's empty. I'll do list.push. Let's push in hi. Okay, so now the head and the tail are both pointing to hi. Cool. Now if we do list.push hi you, I don't know, this makes no sense. If we look at the head, it should still be hi. And if we look at the tail, it's you. And our length is 2. So that's all working. Let's just do one more. List.push hi you. Let's push in the number 99. And we look at list. The head is hi. The tail is 99. So if I did list.head.next, that gives me you. .next again, that gives me 99. And then there is no next. Cool. So push is done. This is the basics of pushing onto a list. We have the one edge case if it's empty. Otherwise, we just take the current tail. It's nice and easy. It doesn't matter if there's a million items in here. It's really fast. We just take the tail and add on to the end and then move the tail one spot over. Okay, so that's push. In the next video, we're going to get into pop. And pop is a little trickier, and you'll see why. Hey, welcome back. Our next method to implement is pop. So just like on an array, a pop, when we call pop, it removes from the end of the linked list. It takes the last item on there, the tail, and returns it to us. Now that seems simple because we're keeping track of the last item, the tail. So we should just be able to return it. The problem is, to remove it, we have to assign a new tail. And that involves going all the way through the list from the beginning because we don't have a backwards pointer. We can't just take the tail and say, give me the one before this. That's not how a singly linked list is set up. If we look at Visual Algo again, if we try and pop off of this, we just say, take the last item off. Well, we have the tail. We know it's 90. I could give you the last item very easily. But to then update the tail here, otherwise, we're not actually popping it off. We're just getting the last item. To move the tail here, we have to start at the beginning, go to the next, and go to the second to last item and make that the new tail. So if we insert, let's walk through this. Or no, we're not inserting. Let's remove. We want to remove from the tail. So that would be popping. We go to the second to last item. All right, so we found it. Let me slow this down a little bit and rerun this. If you want, you can look at that code on the right, but I'm going to walk through. Let's go step by step. Okay, so we start at the beginning. We go to the next thing. That's not the end. And we have two variables because we need to keep track of the second to last item. And how do we know what the second to last item is? Well, if we have the first variable and it hits the end, so they're sort of like offset by one node. So we have this one variable called pre or previous node or second to last, it doesn't matter, or new tail. And that's going to keep track of what we're actually going to set the tail to be. And we're just trying to find the second to last item. Okay, so we have now found the second to last item. So we remove 85, and all that means is taking this item dot next, setting it to null. That severs the link. And then we take this and save it to a variable so we can return it. And then we set this to be the new tail. Does that make sense? Hopefully. It's a little more complicated. And I'll walk through the pseudocode, but the first thing that we have to be able to do is traverse our list. So to traverse it, it's not that bad. All that we do is start at the beginning using the head, and then we can loop and keep going while there is a dot next. So this isn't the solution, but if I wanted to make a method called traverse, all that we would need to do, let's say I just wanted to print out every item in the list. So we're going to start with a variable, let's just call it current, if I can spell, equals this dot head. So we start at the beginning. And we can do a while loop, a for loop. You could use the length and do a for loop. I'm going to do a while loop and just say while there is a current, just like that, we're going to say print, nope, not print, console.log, current.val, and then we need to update current equals the next off of current. I keep saying, does that make sense? Probably not. it's confusing. So we start at the head. If we have hello, goodbye, and let's do exclamation point at the end, like this. If we start at the head, we're going to set current to be this node, hello, and we're going to console.log hello. Then we're going to change current to be current.next, which means it's now goodbye. So the loop starts over. This is still true. So we console.log goodbye. Now current is current.next, which is exclamation point. It starts over, still true. We print exclamation point. Then we set current to be current.next. There is no next. It's null. So this loop now is done. And if we tried running this, I do list.traverse. Oh, I have 3 hours. Hopefully you saw that before me. Try this one more time. Rerun it, and we do list.traverse again. All right, so we get hello, goodbye, exclamation point. Nothing's returned, so we get undefined. So that's one way of traversing a list, and we're going to need to do something like this in order to figure out the new tail. Now there's a slight distinction, which is we don't want to get all the way to the end of the list. We need to get to the second to last item, and we don't need to print anything out. So I'm going to actually comment this out. We're not using this in our code. I just wanted to show you one way of traversing. Okay, so if you want to try this on your own, first thing you need to do is define, I didn't add this time, define a function called pop, and it doesn't take in any variable or any data, right? It just pops the last thing every time. If there's nothing in the list, nice and easy, return undefined. So you could check if there's no head, or you could check if the length is 0, whatever metric you use, return undefined if it's empty. Otherwise, loop through the entire list until you reach the tail. But it's not that simple because what we're actually doing is trying to get the thing right before the tail. So loop through until you get the tail, but also have a variable that keeps track of whatever the last item was, like we saw in Visual Algo, where well, this is a bad example. If I go back, can I go back here? Here we go. So we have two variables, and we're getting to the end with this one called temp, and then pre is always it's lagging one item, one node behind. That's going to give us the second to last item once temp hits the end. All right, so we just set the next property of the second to last node to be null, and then update the tail to be that second to last node. And then we subtract 1 from the length and return the node that was removed. So that is important. You need to store it in a variable so you can return it. Okay, so that's pop. This one actually, push is pretty straightforward. I think pop is one of the trickier ones. Some of the other things we'll see later on are actually easier. It's just that push and pop go together, so I felt bad about splitting them up. Anyway, give it a shot. Don't feel bad if you get stuck. So, second attempt at this video, I recorded the whole thing, or I thought I did, but the mic was muted. So, giving it a second chance. We're going to write pop. The very first thing we need to do is define the method pop, takes no arguments, and then let's start with the edge case. If there are no nodes in the list, return undefined. Okay, so let's define pop and check if there are no nodes. We have a couple ways of doing this. Let me clear down here. We could check if the length is 0, or I'm going to check if there is no head. So if no this dot head, if not this dot head or this dot tail, just return undefined. We can do it on one line. Nice and easy. So the next piece is loop through the list until you reach the tail, except really we're trying to find the tail and the second to last thing that comes right before the tail. So when we loop, we're going to have two variables. One that's going to be called, I don't know, current. It doesn't really matter. Just the thing that is going to hit the end. And then two, which we'll call previous, or I like to call it new tail because it's what is going to become the tail, right? If our list looks like this, hello, goodbye, exclamation point, we're going to start at the beginning. They're both going to point here, current and new tail, NT. Right? And we're going to loop through, and I'm going to move current up here and check. Is this the end of the list? Nope, it's not. So we move new tail up. Then I'm going to move current up again and check, all right, is this the end of the list? And it is. So I don't move new tail. And this tells me that this is my new tail. So I'm going to pop this off by severing this arrow. And then I'm going to make this the tail. So that's kind of our workflow here. Let's reset them back to the starting gate. I think I deleted a bracket over here. Okay, so to do that loop, let me comment that out. It's not valid JavaScript, is it? What I'm going to do is start by making those two variables. So var current And I'm going to start that at the top, this dot head. And then I'm going to make my other variable called new tail, and I'll set it to be current. They're the same thing at the beginning. They both start at the very beginning. Now we loop over. So from the last video, I showed you one way of doing this. I'm going to do while current dot next. That means while there is something, so if current is goodbye, is there a next? Yes. But when current is exclamation point, there is no next, and that's when we're going to stop. And there's a couple ways of writing this code. So if you didn't do current.next and you made it work, if it works, it's totally valid. Okay, and all that we're going to do is set new tail to equal current, and then move current forward 1. So new tail is always lagging behind. New tail is set to whatever current was, and then we move current 1 forward. And we keep going until there is nowhere for current to move forward to. So at the end of this, if I just did a console.log current.val, and then console.log newtail.val, you'll see if I do list.pop, we end up with current is the exclamation point node, and goodbye, new tail is the previous one, goodbye. It's the one right before it. Okay, so that gets us what we want. At the end of this list, current and new tail are the correct values. So now all we need to do is move the tail. This dot tail is now pointing to new tail. So at the end of our little simulation, current is referencing this right here, and new tail references goodbye. So all we do is say, all right, this thing right here is the tail. That's what this does. Then if we reference this, we need to set the new tail's next node to be null. So we'll just do this dot tail dot next equals null. So there's nothing that comes after it. That severs the connection with exclamation point. So it's not enough just to say this is our new tail, because if it keeps pointing at something, then that doesn't mean it's the end of the list. So we need to sever the arrow, which is what we've done now. So we have current. So we know at the very end of this, we want to return current. Okay? And the other thing we need to do is decrement length, this dot length minus minus. And this will get us 99.99% of the way there. This meets all the requirements. And if we test this out, get rid of this for now. Let's push on this dot. Okay, that should work. Let's give it a test. I'm going to refresh my code, execute it, list.pop. Right now it has 3 things in there. It returns to me exclamation point. And if we look at the list, it's now 2 items long, and the tail is goodbye. All right, let's pop one more time. It returns to me goodbye. That's correct. And if we look at list, it is now 1 item long. Okay, so it seems like it's working. Let's try pushing something on. Push 99. It's a bunch of 9s on. We look at list, it's 2 items long. The head is hello. The tail is 9999. If we do list.pop, it gives me that number back. Okay, so that's all good. But if we do list.pop one more time, it does pop off the value of hello and give me what I expect. But if we look at list, it still has a head and a tail, but the length has gone down. So there's a special case when there's 1 item left in the list. And I didn't specify this in the instruction, so I would expect nobody to catch this unless you actually went through and tested this. If there's 1 item, there's a problem, because we're never setting the head and the tail to be null. It should be empty. If there's only 1 item left and we remove it, well, we've done that, but because the way our code works, new tail and current are set to be the exact same thing. So I'm going to show a refactored version of all of this at the end of the section, but one really simple workaround that is, it's kind of clunky, but if we just check if the length of the list is now 0, so down here, if we subtract 1 from the length and we just check, all right, is the list empty now? So if this dot length equals 0, or we could also check if the head is equal to the tail. Let me do 3 equals. If that's the case, we're now just going to say this dot head equals null, this dot tail equals null. That means that there was 1 item, we popped it off, and we subtracted 1 from the length. So now there is 0 items in there, so we just reset head and tail to be null. Let's verify that it works. So we have our list. If we do list.pop, first thing gone, second thing gone. Right now it is 1 item long. So if we pop this time, it gives us the correct value. And if we look at list, it now has a length of 0. The head is null, the tail is null. And if we try and pop again, we should get undefined, and the list should still be 0 items. Oftentimes I've seen this where, it keeps going into negative numbers. That's not correct. We want length to be 0. All right, so that's my solution to pop. If you came up with something better, more elegant, please share it. I'm going to show you a nice refactor later on that will slim this down significantly to 1 line by calling another function, another method we're going to define. So it can't be 1 line on its own right now. But once we define this auxiliary function, it will be shorter. Anyway, that's pop. Hey, welcome back. Next, we move on to something nice and easy compared to pop, shift. So shift removes a node from the beginning of the linked list. So whatever is at the start, we remove it. All that really means is taking the head and deleting it, and then moving the head over to whatever the second item was. So if we visualize it, if we go to remove from the beginning, from the head, all that it really means, let me slow that down again, one more time. Remove from the head, actually I'll pause it. So we take whatever the current head is, we need to save it to a variable because we want to return it. And then we take its .next and make that the new head. And then we sever that connection like that. And we return the old head. So it's really easy. There could be a million items on the list. To insert at the beginning, it takes constant time always, compared to an array where we have to reassign every index. If there's a million items, it's a lot of indices to change over and over and over to cascade and ripple down. On a linked list, it's super simple. So here's some pseudocode. If there's no nodes, return undefined. Otherwise, store the current head property in a variable, then update the head property to be the current head's next node. So move it over 1. And then finally, decrement the length by 1 and return the value of the node that was removed, of the old head. Okay? So go ahead and give this a shot if you'd like. Nice and easy compared to pop. In the next video, I'll have a solution. Okay, so let's type this out. First, we need to define shift, and it doesn't take any arguments. And then let's start with this first one-liner. If there's no nodes, if it's empty, return undefined. Okay, so down here, we'll just do shift, and we'll check. Again, there's a lot of ways of doing this. If this .length is 0, if there's no head, it doesn't really matter. Return undefined. Okay. Next, store the current head property in a variable. So I'm going to make a variable, I'll call it current head equals this .head. This is pointing to, in our case, hello at the beginning. Then we're going to move the head over to be the current head's next node. So we're going to say this .head equals the current head's .next. So we've saved this to a variable called current head, and we say, this is the old head. Well, now the new head is right here. We take current head.next and make that the new head. All right, almost there. Then we need to decrement the length by 1. So this .length minus minus. And then finally, return current head, which is technically no longer current head. So you could have also called this old head, removed head, doesn't matter. This is what we took off. And if we test it out, run our code. If I do list.shift, we get hello, which shows the beginning. And if we look at the list now, it's 2 items long. And what's the head? The head is now goodbye. Let's do it one more time. We got goodbye off. Now the head, if we look at the list again, is equal to this. Head and tail are the same thing. I will note though, if we do list.shift one more time, it does give us the right value. And if we look at list, the head is null, the tail isn't null. And that's not really going to be a problem because as soon as we reassign something to the head, as soon as we push something back in, the tail will be reassigned. However, if we wanted to fix that, if we wanted it to be null, we could just add an extra conditional check and just check, right here. If this dot, basically just copy this code. Set tail to be null. Just like that. So if we refresh our code, run it again, list.shift, .shift again. All right, now the list has 1 item in it, which is the exclamation point. If we shift one more time and we look at the list, it now is null, null, length is 0. If we try it again, we get undefined. The list is unchanged, the length is still 0. Let's just make sure we can still push something in. Let's push 100 in. We look at the list. Head and tail are both 100. Push one more thing in. 1000. Anyway, it's working. All looks good. List.pop gives us 1000. List.shift gives us 100. And list is now empty. Perfect. All right, so that's shift. All right, welcome back. In this video, we're working on adding unshift to our singly linked list. So unshift is a way to add a node to the list. However, unlike push, it adds to the beginning of the list. And fortunately, it's pretty easy because of the way the singly linked list works. We already have the head. All we have to do is say, here is a new head, and point it to the old head. So if we walked through it over here, let's do an insert at the beginning. We're going to insert the number 13. Nope, there we go, 13. Okay, I'm going to pause it. So all we do is we have the old head, and we now point the new head at the old head, and then move the head to be the new head. It's kind of confusing when I keep saying old head, new head, but we just take this old pointer, the value there, we take the new node, point it at that, and then set this to be the head. And that's it. So if we were to walk through the pseudocode, define the function, accepts a value that you're going to add to the beginning, you're shifting or you're unshifting. So we create a new node, just like we did with push. We need to check if there is no head, then we set the head and tail to be the new node. Otherwise, set the newly created node's next property to be the current head, and then move the head to be that newly created node. And then increment the length of the list by 1, and finally return the linked list. Okay? So try and do this on your own if you'd like. In the next video, as I've been doing this whole section, I'll have a solution. All right, that's coming up next. All right, so let's get to work writing unshift. So I'm going to go over to my snippet, and I'm just going to define unshift, which takes a value that we're adding in. And the first thing we need to do is make a new node. So I'll just do var new node equals new node and pass in that value. Okay, once we've done that, we now need to check our edge case, which is if there's no head property. So we'll just do if there's not a head. In that case, we set both the head and the tail to be that new node. So we'll do this.head equals new node, this.tail equals new node, or this.head. Just like that, they're now both set to the new node if there was nothing in the list to start. After that, otherwise, we're going to set the newly created node's next property to be the current head property on the list. So if this is what our linked list looks like right now, hello is the head. If we added something to the beginning, let's just say it was a star for some reason, and this is still the head, all that we do is we take this new node and we point it at the head. So that's just a matter of saying new node dot next equals this dot head. So that gives us this connection, but this is still the head. So then we need to update the head. So we just say this dot head equals new node. And then that effectively moves our head over here. And that's all we have to do. So no matter how long our list is, again, I've been saying this a couple times, if it's 1,000,000 items long, it's just one little thing we have to do. Unlike an array, even though us as humans don't have to do anything, behind the scenes, if we add something to the beginning of an array and it's 1,000,000 items long, the entire thing has to be re-indexed. Every single item gets a new index, and that's not good. So I think all we have left to do is to increment the length of the list and then return the list. So we'll do this.length plus plus, return the whole list, return this. Let's test it out. So I'm going to get rid of that. We've created our list here. I will execute the code. So we have our list. It's 3 items long. Let's do an unshift of, I don't know, I'm just going to write first. Oh, looks like I have a typo in here. This dot head, if not this dot head. Hopefully you saw that before me. Let's rerun this code one more time. Okay, list has 3 items, dot unshift first. Looks like it's working. Well, actually, we can't tell from this. It added something in, and indeed, the head is first, and it's pointing to hello, which is pointing to goodbye, which is pointing to exclamation point, which points to nothing. Now there is one issue with our code that only becomes clear when we have an empty list. So I'm going to do pop a couple, I guess that's a dumb way to make an empty list, but that's one way to do it. Just pop everything out of there, or you could just start from an empty list, but I didn't think of that. So we have our empty list now. If I unshift it, list.unshift, let's say add me. It looks like it works. The head and the tail are both set correctly, but the next property on the head and the next property on the tail are actually self-referential. We can keep clicking next and it's always pointing to add me. So this is wrong. Now, as soon as we unshift something else, list.unshift 100, and we look at list, now the head is 100 and it's pointing to add me, but add me is still pointing to add me over and over and over, and our tail is still set up like that. But if I push something at the very end and we look at it now, it should be fixed. If we look at our head, the next is add me and its next is end. Okay, so it's not the end of the world, but it's not good. We don't want that. And it's happening because of this logic right here. It's a very small change that we need to make. Right now we have our if statement to check if the list is empty, if there's no head. And then we have this other code that always runs. In reality, it should be, and it's actually in the pseudocode, it says if there's no head, do this, if it's empty. Otherwise, meaning else. And we don't have that else right now. Because what's happening there is without the else, we are setting the head and the tail to be the new node if it's an empty list. If we go back, let's just do L equals new singly linked list. L is empty right now. If I do L.unshift hello, it sets the head and tail to be hello. And then without this else here, it takes hello.next and sets it to the head, which is hello. So we're saying hello.next is hello. And then it sets the head to be hello, which is not what we want. It's already set to that. So we add the else in so that this code only runs when there's at least one thing in here in the list. This code only runs if it's empty. And then this code needs to run in either scenario. So let's try running it again. This is a very stupid way of doing this. Okay, list.unshift add me. If we look at list now, it still works, but there is no next set on add me. It's set up correctly. All right, a tiny change, but important. That is unshift. Next up, we're going to take a look at some other methods that have to do with retrieving values based off of a position or an index called get and set. And these are a little bit trickier. All right, welcome back. So next we're going to add or implement get. So get is a method that takes a number, an index or a position, and it returns the item in that position. So if we give it the number 0, it should give us the first item, the head. But if we give it the number 4, it should give us the 5th item, so starting at 0. But that's not really the important part. The important part is it takes in a number and you traverse the list that many times and then you return the item at that index. So it has to be visual go. It's the only way I could pronounce that. It doesn't have a built-in get method that it illustrates, but if we just looked at this list, we can sort of mouse through it. So if we did list.get and then we pass in the number 3. Basically, we start at the beginning. This is number 0, the head, and then we just do .next. And we keep doing .next until we've done it 3 times. So 0 to 1, 1 to 2, 2 to 3. And so we'd return this value, which is 6. So there are no indices that correspond to each individual item. It's not like we can just access and get the 700th item immediately. We have to start at the 0, the very beginning, the head, and count how many times we do .next. We have to loop until we hit that item. So whenever we say index in this video, it is not like an array that has a built-in index that corresponds to every element. We are manually counting. So it's not that efficient compared to an array. If we need to access something based off of its position all the time, then you might want to use an array. It depends. And again, we'll come back to considerations like that later on. So here's a pseudocode. Function should accept an index, so a number that we pass in. If the index is, so these are the edge cases, if it's negative or greater than or equal to the length, then we're not going to do that. We can't find something at index -2. So we return null, or we could do undefined, but just return something that signifies it was not found. Then we're going to loop through the list until you reach the index and return the node at that specific index. So I recommend having a counter variable, and you just loop through, continue like we've done with a while loop or a for loop, doing .next, 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 and each time through, just add one to the counter. And then once you get to that however many, the index, the 5th item, the 10th item, all you do is return that value. So give it a shot. In the next video, I'll implement it. Surprise, surprise. Okay, let's get going with get. So we're going to define it down here, and it takes an index. And the first thing we need to do is check if the index is valid. So if it's not valid, meaning it's negative or greater than or equal to the length of the list, return null. So if index is less than 0 or index is greater than or equal to this dot length, return and null undefined. It doesn't really matter to me. We'll do null. So we have that out of the way. Otherwise, what we need to do, let's say somebody passes in the index of 3. I added in a couple items in here. So we now have 5. So index of 3, that means 0, 1, 2, 3. We want the heart back is what we should get. So to do that, we need to start here and basically count with a counter starting at 0 and continue to traverse one at a time while adding 1 to our counter. So we go 0 to 1, and then we would add 1 again when we traverse to this to give us 2, and then add 1 to our counter, which is 3, at which point we would stop because our counter was equal to the index 3. So I'll make a variable called counter, started at 0, or count, it doesn't matter. Then I'll make a variable called current to start at the head. This is what will keep track of our current position as we traverse. And then current is what we will return. So I'm going to start with a while loop. While, and we'll just do while counter is not equal to index. So at the beginning, if we called get 3, counter start to 0, they're not equal. So what do? We just add 1 to counter, and we change current to now equal current.next, and then add 1 to counter. Okay, so we go through this, and this is actually all we need to traverse it. There's only one thing we're missing at the very end, which is return current. So if we step through this, we're going to have at the very beginning current equals this, and then I'll just visualize it. Here's our counter. All right, so very first time through, current is equal to the head, counter is 0. And our index that we're looking for is 3. So the loop runs, we change current to now be this, and we add 1 to counter, so it's 1. Okay, we keep going through because counter is not equal to 3. So we move current down to the exclamation point node, and that means that we add 1 to counter, which is now 2. Still, this is true, so we run it again. So we move current down one more time, and we add 1 to counter, at which point counter is now equal to the index if we're looking for 3. Then all we do is return current, which is this node. All right, let's test it out. So we have our list, which has 5 things. Let's do list.getIndex0, which should give me hello, the first thing. Let's try -1. Shouldn't work. Let's try 100. Doesn't work. How about 3? So that gives me the heart. And if I did 4, that should give me the smiley face. If we do 5, there should be nothing there. But if we push something on, let's do a $sign. If I do list.get5 now, it works. But 6 won't work. Okay, so that's the solution, or a solution, to get. Next, we're going to work with its counterpart, which is set. All right, next up, we're working with set. So set is a method that will accept 2 things, a position or an index, and a value to update the item at that index to. So we would pass in, for example, this Visual Go doesn't actually have the capability to illustrate this, but if I were to say this list dot set 1 as the index, comma, hello world. What that is saying is take whatever is at index 1, so 0, 1, take this node and update or change its value, set it to hello world. So to make it work, you need to define a function that accepts 2 things, a value and an index. Or I actually like to put the index first, so I should have written an index and a value, but it doesn't matter as long as you are consistent. And we can actually use our get method that we just defined in the last video to help us out. So we're going to use our get function to find that node, or if it's not there, our get function will handle it. For example, if you tried to update the -10th item, but it should return to us the found node, and then we just update its value. So if the node is not found, return false. If the node is found, update its value, and then return true. So it's a nice and short one. It's like 4 or 5 lines, I think. So in the next video, we'll have a solution. Ready, set, go. All right, we are all set to implement set. Yeah, all right. So I'm going to hop over here, and I'm going to add my method set, which takes 2 things, the index, and then a new value to set it to. And all we need to do is call our get method with that index. So this.get with the index that was provided, set it equal to a variable. So we'll call it found node. And we're just going to check if that returned something valid or not. I don't know what I'm doing that for. It was already indented properly. Just fidgeting. So get will take care of it. And it's either going to return to us null or the actual node. So if it's found, we can just do if found node. All that we need to do is update found node.val equals the value that was passed in here. And then return true. Otherwise, return false. And we don't need to do the, return else. We don't need to do else return false because it's only one or the other, either or. Okay? And that's actually it. So it's nice and easy because we have this get method already defined. But let's test it out. So we've got all of this here. Let's run the code. And I'll do list.get. What's the item at index 2? All right, it's an exclamation point. Let's now set it, list.set at index 2 to be triple exclamation point. And if we look at the list and we look at list.get index 2 now, it's triple exclamation points. However, if I try and do list.set something at index, 6, doesn't exist, so it's false. And if we look at our list and we do, let's just look at the tail. The last thing is still the smiley face. What else could we do here? Let's do list.set -1 and set that to be LOL. It's not going to work because our get method is rejecting it. Returns null, so we return false. And that's all there is to set. Nice and easy, hopefully. Welcome back. Next up is insert. So insert is sort of like set in that it takes 2 pieces of data. It takes an index and a value. However, instead of updating an existing node, insert is going to insert a new node at whatever position we specify. So for example, I could call on this list, insert at position 2, the number 17, in which case we would go 0, 1, 2. So we would put the number 17, a new node right here, and we'd connect this node to it and then connect it to 77. So let's actually do that. So this allows me to insert at the beginning, unshift it, or push to the end after the tail. Here I can insert at a specific index. So index of 2, I said 17, and I'll pause it. Okay, so what we want to do, if we pass an index of 2, we want to find the item at index of 1, and we're going to connect that to our new node. So if we're inserting 17, okay, here we found index of 2. So we know we need to insert between these 2 things. And so we take our new node, which is 17, that's the value, and we're going to have it point at 77. So we hook it up one way, and then we need to change this so that the prior node is pointing at the one we just inserted, like that. Okay, so this can be a little more complicated than some of the other methods, but we also can make use of methods we've already built. So let's talk about how. So you're going to define a function. It takes 2 things in, the index and the value. And if the index is less than 0 or greater than the length, return false because we can't insert something there. Notice that it's greater than the length, not greater than or equal to, because if the index is the same as the length, that means just insert it at the end, in which case your code can just rely or call upon your existing push method. So if we're trying to insert something at the end, just use push, don't rewrite it. Same thing if it's trying to be inserted, or if someone is trying to insert something at index of 0, use your unshift method. Don't rewrite that logic. So the first little bit of the method can be a couple of conditional statements. So if none of these are true, it means that the index is somewhere in the middle of our list. Let's say index of 3. What we want to do is basically find the item at index of 2. And we have a really easy way of doing that now. We have that get method we built. So we can just call get, but pass in the index minus 1. So instead of get of the index, we want the item before. So remember, if I was trying to insert 17 at index of 2, 0, 1, 2, we could call get on index of 1, which would give us this node right here. Then all that we need to do, once we have the previous node, the one right before where we're trying to insert, we take that previous node and we set its next to be the newly created node, which I didn't specify you need to create a new node, but you do. So we create the new node, we find the one right before it using get, and we connect that sort of pathway from the previous one to the new node. Then we have to connect the new node to the old next node, right? So if we find this here, this is our old one. We need to connect this to this and this to this. Now the order they go in, it doesn't matter which one you do. You just might need to use a temporary placeholder variable. Okay, so then the final thing is to increment the length because we've inserted something, and then return true. So one quick note, ideally, your method will return only true or false. So if the insert was successful, it returns true. If it was unsuccessful, it returns false. The problem is that if we're going to rely on our push method and our unshift method, for example, those don't return true or false. So if you want to get fancy, you could coerce the return value of push and of unshift to be a Boolean, true or false. But don't worry about that, honestly. I'll show you a really quick way of doing that in the solution. But it's just a note that to make this a little nicer, it should always return true or false. Okay, insert is probably one of the trickier ones, so give yourself a break if you can't get it. I'll see you in the next video. Okay, so let's get defining insert. So it takes an index and a value. And the first thing we want to check is if it's a ridiculous value, if it's negative or if it's greater than the length. So we'll just do if index is less than 0. 0 is okay, but if it's less than 0, that's not okay. Or if index is greater than this dot length. And it's okay if it's equal to the length. That just means insert at the very end. So even in this scenario, the greatest index is 3, right? 0, 1, 2, 3. If we wanted to insert at 4, that's okay, even though there is no current index 4. So if that's the case, let's return false. Okay, so that's if there's a problem. Next, we have if the index is equal to the length. So if index equals this dot length. What do we do in that case? Well, we'll just do this dot push, the value. Okay, and I'm just going to return that, and we'll come back to this because push on its own, if we pass in a value, we go all the way back up, where are you? It doesn't return true or false, it returns the whole list. So if we wanted to make everything true or false in this method, we have a little work to do, but let's leave it for now because we have another scenario, which is if the index is 0. So if index is equal to 0, what do we want to do? We're going to call this dot unshift with the val. That inserts at the beginning. And we'll also return that, but unshift doesn't return true or false, it returns the entire list, so we need to address that later. But functionally, this should work. So if it's invalid, return false. If the index is equal to the length, call push with the value, push it to the end. If the index is equal to 0, call unshift, add it to the beginning. Okay, so now we have the rest of the logic. This means that the index is somewhere in the middle of our list. Let's say index of 2, which would give us this, 0, 1, 2, right here. Okay, so we need to find the item right before it. So we can just use our this.get index minus 1 and save that to a variable. I'll call it previous, right? So that is going to use get, which we defined up here, and it's going to give us the item right before it. So if we're trying to insert here, it will give us this node. So once we have the previous, the other thing we need to do sooner rather than later is make our new node. So we'll call it new node equals new node and pass in that value. Okay, so now we just need to connect previous to our new node and new node to whatever came after previous. So if this is previous, we're going to put our new node right here and connect previous to new node to this. Now the thing is, if we just went right ahead and did previous.next equals new node, there's a problem, which is we are erasing the connection to this node, because all that we had connecting this node to this one was .next on this, right? .next is equal to this. So if I change previous.next to be our new node, like this, and I try and set new node, this is gone because it used to be right here. So I need to use a placeholder variable. So I'll just make one called, I don't know, temp, var temp equals the current previous.next. So I'm just saving whatever was in there. All right, so we've now set previous.next to be the new node. So we've connected one part of it. Then we just need to set new node.next to equal temp, which is just holding what used to come after it. So if this is where we're inserting it right here, this is previous, okay? And so we're saving this to a temporary variable right here. And we're just inserting the new node here. And we're saying previous.next is new node.next is temp. And that's just placeholding it. So now we'd have 205 or whatever the number is we're trying to insert. 225, I think is what I said. Anyway. So all we have left to do now is add one to the length. So this dot length plus plus, and we need to return true because that means it worked. Okay, so if we run this code right now, if we look at our list, right now it's 4 items long. If we want to insert at index 0, we could do list.insert 0, and let's insert just the string first. If we look at our list, the first thing is now first, and that points to 100, which was the old head. All right, so if we do list.get, what's the last index we have in there? I think it's 4 right now. List.get 4 is the last thing. If we did 5, there's nothing there. So if we do an insert at index 5, the string last, this should add something to the very end, which will trigger our push right here. Notice that what we get back, well, it works, but what we're getting back is the whole list. And I mentioned it would be nice to get true or false, because if we do list.insert at index 1, I don't know, insert 37 at index of 1, it gives us true. If I do list.insert -1 or -2 something, it gives me false. If I insert at index 100, it gives me false. So it would be nice if it was consistent and always gave me true if the insert worked. So there's a simple way to change that. If you didn't want to expand these into separate, like you could do this, right? If index equals this dot length, do brackets here, multi-line, and then move this inside and say this dot push val, and you could just do, return true, for example. And we could do the same thing down here, or we can do the sort of sneaky thing, which is to put double bangs to doubly negate whatever comes back from push or from unshift. So what that means, it's a Boolean operator, not. So if we just had a string like hi, if we do not hi, no, not like that, it's going to give us it's going to coerce it to a Boolean value, give us the opposite of it. So if we do bang bang, it gives us true, if it's truthy. If we do bang bang of 2, it's true, but bang bang of 0 is false. So this is just a way of converting this to a Boolean. This dot push is going to return the entire list. Unshift returns the entire list. So if we coerce it to a Boolean, it should just return true. So let's test it out. I just reran the code. If we now do a list.insert at index of 0 first, it gives us true. If we do at the end of the list, what is our last index right now? List.get, I think is it 4? Okay, so if we did 5, it would be the last thing. So if we do list.insert at 5, last, it gives us true. Versus list.insert at 100, it's not going to work. It gives us false. Okay, so that's insert. Personally, I would sort of put this on its a little new section just to separate these edge cases out. I think that's all I wanted to cover here. So that's insert. It's a little more complicated. Next, we're going to talk about remove, which is sort of like a sister to insert. That's coming up next. Hey, welcome back. So we're talking about a method called remove. We're almost done with singly linked lists, I promise. Remove takes in an index, and it removes the value at that index, and it patches up the list around it. So if you were to remove from the beginning, it just takes the last item. Oh my gosh, it takes the first item. If you remove from the very end, it takes the last item. But if you remove from the middle, it's a little more complicated. So if we take an example, if we remove the index of 1 from here, what we have to do is first find that item. This is the one that's going to be deleted, index of 1, 0, 1. And we take it out, but to do that, all it really means is taking the previous one and setting its next to the deleted one's next. So set this dot next to this. So here's the pseudocode. Define a function, it should accept an index. If the index is negative or it's greater than the length, return undefined or something, null, whatever you want. If the index is the same as the length minus 1. So technically this should be greater than or equal to the length because you can't remove, if there's 5 items, the length is going to be 5, but the greatest index is 4, so we can't remove from 5. We can only remove from 4. So if the index is the same as the length minus 1, we want to pop. Just use our pop method we've already written. Same thing with the beginning. If the index is equal to 0, use our shift method. Otherwise, use our get method, sort of what we did in the last video, where we used get, but we passed in index minus 1 to get the previous node. And then we just set the next property on the previous node to be the next of the next node. And then we subtract 1 from the length and return the value of the removed node. So give it a shot. In the next video, surprise, surprise, we'll have a solution. All right, so let's write a solution for remove. I'm going to hop over to my snippet, and we'll define remove, which takes an index. And the very first thing it needs to do is check if that index is valid. So if the index is negative, if it's less than 0, or if the index is greater than or equal to the length. What do? We return null or undefined. It doesn't really matter. Just something bad. I guess you could return false too. If the index is 0, we're going to return this dot shift. That means remove the first thing. And if the index is the length minus 1, if it's the last item, then we return this dot pop. Okay, so those are the 3 edge cases. Then we have the rest of the logic. So this means if we get to this point and we haven't returned yet, it's somewhere in the middle of the list that we're trying to remove. So we need to find the previous node. So let's make a variable called previous node equals this dot get index minus 1. So retrieve the value, or retrieve the node 1 before what we're trying to remove. Then what I'm going to do is make a variable called removed, and it's going to store previous node dot next. So this is what we're going to return at the very end. We can actually just do that now. Return removed, but it's not removed yet. So now all we need to do is set previous node dot next equals removed dot next. So if we're trying to remove this right here, we find the previous node 201, and we make a variable called removed, and we set it equal to this dot next. So this is going to be in our removed variable. Then we take the previous node dot next and set it to removed dot next. So we take this and set its next to this, at which point this is out of the picture. We have it in a variable, so we can return it at the end. But we also need to, before that, subtract 1 from the length. So this dot length minus minus. And that should do it for us. Let's try executing it. Let's do list dot remove the first item. So that gives us 100, and the list now starts at 201. Let's remove from the end. Actually, let's do from the middle first. Let's do index of 2. So that should be, if we remove this, index of 2, 0, oh, that's going to be the last thing, isn't it? Okay, let's do index of 1. So that should give us 250. And it does. And if we look at the list now, it has 2 items in it, 201 and 350. Let's do list.remove the last item, index of 1. Cool, so that called pop. And if we look at the list now, it has one item left. Let's do list.remove the 0th item. And we look at the list, it's empty now. Try and remove something that isn't in there. That's not going to work. How about a positive number? Cool. So that is remove. Hey, welcome back. So next up, our final method on our singly linked list is called reverse. And this is a really classic computer science interview question. I'm not sure why, to be honest, because in my experience, it's just not a very it's not a very commonly done thing where you have a linked list and you need to reverse it. But it is a pretty common challenge. It's in a lot of textbooks, a lot of interview prep books. So you take a linked list and you reverse it in place. So you don't make a copy. That's a little easier. You don't make a duplicate and return that. You do it in place. So you traverse, and as you go, you reverse things. Traverse and reverse. So here's what it looks like. I couldn't find a little animation to use or a way of visualizing it, so I made my own sort of ugly attempt. So if this is our linked list, singly linked list, we have our head and our tail and a bunch of next pointers. If we want to reverse it, basically what we're going to do is start at the beginning. We can only move one direction. We can't start at the end. So we start here, and we're going to make this the tail. And then we build the list backwards from there. So we do .next, which gives us this node 27. And we're going to set 27.next to be 13. But we also need to keep track of what 27.next used to be, which is 32. So we don't just overwrite it. We need to make a second variable to store the old next, which is 32. So let's say we're on 27. We're going to store 32 on the side. Just remember, 32 is in a different variable. Then we take 27 and we set its .next to be 13. There we go. Now we're on 32. So we take the .next of 32, which is 71, and we save 71, put that on the side. Then we take 32 and set its .next to be 27. And now we go back to 71. There's nothing after 71. There's no .next. So we just take it and set its .next to be 32. And then this becomes the head. So as far as the logic, the pseudocode is a little bit tricky to walk through. I tried to word this in a way that was a little easier to understand, but I think your best bet is going to be to just try this, loop through things. Don't try and follow my instructions exactly, because there are other ways of doing this, and I don't want you to get too hung up on it. But with that said, here is my pseudocode. So start off. We're reversing in place, so you write the method reverse, no arguments, swap the head and the tail. Then create a variable, you can call it next. Again, the variable names don't really matter, but create a variable called next, another one called previous, and then a variable called node or current or something, and initialize it to start at the head. So we would start all the way back here. This would be our node variable or current. And then from there, got to fast forward, we're going to loop through the list. And we're going to set the next variable to be the next property on whatever our current node is. So that's what I talked about. We're going to store the current next, so that once we change the .next to the item that came before it, we haven't lost that connection forever. So then we're going to set the next property on the node to whatever the previous was. And then we set previous to be the value of the node variable, set the node variable to be the value of the next variable. Like I said, try not to get too lost and hung up on the actual variable names. And I debated, I wasn't sure if this was helpful because it is just so ugly and confusing to read all this text and next and previous and node and variable. So to walk through that one more time, if you want some extra practice or review, you swap the head and the tail. And from there, we take the .next to the tail, 27, and we're going to store the current .next of 27. We're going to store a variable called next to keep track of 32, so that when we take 27.next and we set it to the previous thing, 13, we still have a reference to 32. So in this scenario, 13 would be previous, 27 is our current node, which I called the node variable, and 32 is next. So you make this connection, and then we now set 27 to be previous, and 32 to be current, and 71 to be next. So we set 32, connect to 27, and then we move our previous variable to be 32, and our node current variable becomes 71, and we connect them, and there is no .next. Okay, I hope I didn't lose anyone with this one. I know it can be tricky. Give it a shot. I'll have a solution coming up. All right, so let's implement reverse on our singly linked list. The first thing I want to show you, just to make this a little easier, I added a method called print. This was not something you were expected to do, or I didn't even mention it until now, but it's just going to make it easier for us to see that our reverse worked, because it's kind of annoying when all that we have is the head or the tail to have to, iterate over it or check if we did it correctly, because for all we know, we might have swapped the head and the tail, but the inside might be totally wrong. So I made a method called print, and it's very, very simple. All that it does is it returns, or it actually doesn't return anything. It prints, it console.logs all the values in our linked list in order in an array. So why an array? It defeats the point of using a linked list to turn it into an array, but it's just the easiest way to print it in one line. I could have done a string, I guess, and concatenated everything, but this is just a super short thing. This is not about being efficient. It's just purely to help us see what's happening. So with my current list, here's the values in there. If I do list.print, it just gives me this array, and I can see the order that they're in. So when we do list.reverse and then print again, we want to see the opposite order so that we know it worked. Anyway, let's get started on reverse. So I'll add our reverse method in here. And the first thing that I'll do, remember we have 3 variables that we're going to try and keep track of. The current node, the next variable, the thing that's ahead of it, and the previous variable, the thing that's behind it that we're going to connect to. So I have to start somewhere. I'm going to make my node variable and start it at the head, this dot head. Then I'm going to swap the head and the tail. So this dot head now becomes this dot tail. This dot tail equals node. I can't just say this dot tail equals this dot head because this dot head is now changed. So I made it, this is just a shortcut. It's serving as a temporary variable, but we're also going to use this node variable in our loop. So what we need to do now is start our loop. And instead of a while loop, because I've been doing that in all of my solutions, I'm going to do a for loop just to show you that you can, because we're keeping track of the length. So I'll do for var I equals 0, I is less than this dot length, I plus plus. So now we have the bulk of our logic, where we're going to go through, and we've established that this is node to start. This is our very beginning. Now we're going to make a variable called next and set it equal to this node.next. And then we're also going to use a previous variable. However, at the beginning, previous is going to be null because there's nothing in front of it. So we'll start it at null, but we'll update it as we go. So let's do that now. I'm going to make a variable called previous, and that will be null. I need the variable keyword var, and I'll also do next, and we can set that to null, or we could just leave it like this. The reason we want previous definitely to be null is that we need to make sure that the end of our list, the tail, dot next is null. We don't want it to be undefined or something else. We want null because that's how currently the tail is set up. If there is no dot next, it's set to null. All right, so now what we do is we go through the list and we save the next variable. So we already have next. Next is going to be equal to whatever we're currently looking at, dot next. So that's what we showed here. If this is what we're currently looking at, we're going to take dot next and save it in our next variable so that we can move on to it in a little bit. Then what we're going to do is take whatever the previous value is and set this node dot next to be that previous value. So it starts at null. So the very first time, it's not very exciting. We're going to say node dot next equals previous. So equals null the very first time through, but that will change. Now all we do is we shift things over. We say, okay, so this was our current node. Well, now our current node is going to be whatever the next node was, and our previous node is going to be whatever the node used to be, what current used to be. So that's simple. At the end, we're just going to say previous now equals the current node, and the current node now equals the next node. We just move one thing over. And then that's actually it. Let's return this at the end. We'll verify that this works, of course. I know it can be conceptually confusing, so we'll try and step through it one at a time. But let's just make sure it works first. I'm going to run the code. And we look at our list, .print right now. Looks good. Let's do .reverse and print it again. And let's just make sure 100, 201, 250, 350, 999. It's totally reversed. Okay, so what actually happened here, if we look at the initial state, I'll put this in comments. If you understand this, I'm not going to teach anything new here, but if you want to walk through, I'm going to do that right now. So we started with this, and we have 3 variables that we're keeping track of. We have one that we're calling node. We have one that we're calling, here, I'm going to do it just like this. We have node, previous, and next. Previous starts at null, and next doesn't really start at anything. It doesn't matter because we assign it right at the beginning. So the very first time through, node is equal to this dot head right here. So now we're going to set next equal to node.next, which is 201. So this becomes next right here. Then we say node.next is actually previous, which is null. So in our new list that we're building, we have 100, and we're having it .next, we're having it point to null. So there's nothing there. Then we shift previous to now be 100. So this is previous. And then we set node to be what next was. So this is now node. And then we start the process over. Okay? So then we go next equals node.next. Well, here's node. So node.next gives us 250. Node.next is now reset to be previous. So that means 201.next is going to be 100. Which is the current value of previous. So that's the same as us drawing this arrow right here. We're connecting 201.next to be the rest of the list. Then we update previous to be the node. So this becomes previous. Then we set node to be next. So 250 becomes our node, and we start over. Again, you can drop out of this video at any point, but if you'd like to stay in for the long haul, we go through again. Next equals node.next. So this becomes next, 350 does. Node.next equals previous. So now we're connecting 250.next is 201. So that's us drawing this arrow. We're building it backwards, one thing at a time. Now previous equals this node. I'm just going to get rid of next for a second and just shift these over. Previous equals node, node equals next. We go through again. Next equals node.next, so that's 999. Node.next equals previous, so 350.next is 250. 350 now points at 250. Previous equals node, so we shift all these over just like this. Perfect. Now we take next, which is going to be node.next, so it's next is over here, it's null. There is no .next. Node.next equals previous, so this node.next is now equal to 350. So that's our final connection, 999 points to that. Then this doesn't really matter because we're done, but previous equals node. So we shift these all over just like this. But we're now done and our loop has finished executing. It doesn't keep going because we used a for loop based off of the length. This loop runs 5 times, 1, 2, 3, 4, 5. If our list is 5 items long, and looks like we're done. What am I saying? We are done. It works. We can just double check one more time. Let's do list.print. And then we do list.reverse. List.print again. Opposite order. Let's look at the head. It should be set up correctly. And let's look at the tail. It should have null as its next. Okay, that was a tough one, I know. Or it's a tough one for me to explain at least. Hopefully you were able to understand what I was saying. Okay, welcome back to the last video on linked lists, or on singly linked lists, excuse me. Next, we're talking about doubly linked lists, but we're done with singly linked lists, and I'm getting real tired of saying that word right now. So let's wrap up by talking about the big O notation of the common operations, things like insertion, deletion or removal, searching and accessing data, and also compare it to an array. And then we'll do a quick recap and move on to doubly linked lists, and at the end of that section, we'll do the same thing, where we'll compare not only doubly linked lists to arrays, but also to singly linked lists, and we'll see their unique strengths and weaknesses. All right, so let's start with insertion. In a singly linked list, inserting things is really easy, right? We either push it onto the very end. All that we had to do was take the current end, the tail, make a new node and just set the tail.next to be that new node and then update the tail. Same thing at the beginning. If we want to add something at the very beginning, we just make a new node and we set its .next to be the current head and then move the head. So it takes constant time. It doesn't matter if our list is 1,000,000 items long or 10 items long. It takes the same amount of work, same amount of time to add in a new item. Now that's not the case with arrays. Remember that if an array is 1,000 or 1,000,000 items long, let's go with 1,000,000, and I add something to the very beginning, to the index 0, I have to shift every single index over and rewrite it all the way down to 1,000 or 1,000,001. Or if I add to the very end of an array, then yes, it takes constant time. But on average, if we were going to take the average, it's O of n, where n is the length of the array. So singly linked lists win that battle as far as inserting data, much faster, constant time versus an array where the average is O of n. Then we get to removal, taking things out of the linked list. And this depends on where we are removing from. If we're removing from the very beginning, super easy. That's O of 1, constant time. All that we do is, we've already seen, we take the current head and we just set its .next to be the next head. And then we take the old head and set its .next to be null. We chop that tie. But if we're removing from the very end, it becomes difficult in a singly linked list if we're popping, because we need to find the item right before the last item, right before the tail. And that involves iterating the entire list. So in our best case for removing from the beginning, it's O of 1. For the worst case of removing from the end, if there's 1,000,000 items, we're going to have to go, well, we're not going to have to go to the 1,000,000th. We're going to have to go to one before the 1,000,000th in order to remove that last item. Next up, searching. So searching through a linked list, if we're looking for a value, let's say that we're looking to see if the list contains 99. Worst case, that's O of n, where n is the length of the list, because it could be the very last thing or the second to last thing, and we would need to start at the very beginning and check every single node. So as the list grows, so does the amount of operations it takes to search for something. And the same is true of accessing, getting a certain node out. If we ask for the 10th node or the 100th or the 1,000,000th node, as that number grows, as the list grows, so does the number of operations there. When we compare that to an array has random access, meaning that it's constant time to access items once they're indexed. So the indexing takes time, and insertions can take time, and so can removals. But other than that, if you're asking for the 10th or the 50th or the 0th item in an array, it takes the same amount of time because of the way that arrays are structured. So arrays win that battle. So really, to wrap it up, singly linked lists excel at insertion and deletion compared to arrays. So if that's something that you're really concerned about and you don't need random access, you just need to have some data represented in a list with an order, but you don't need to just access the 50th item or the 1,000,000th item. You just need to access it in order. Then a linked list might be what you want if you're concerned about insertion and removal times and you don't care so much about random access. Okay. All right, so that's big O. Let's just recap a couple things. So linked lists, singly linked lists are an excellent, this is just what I said, excellent alternative to arrays when insertion and deletion at the beginning are frequently required. Remember that inserting at the end of an array is not a big deal. We don't have to reindex anything. Arrays contain a built-in index, whereas linked lists do not. Linked lists are just nodes that are connected to one another with a .next, with a reference or a pointer. There is no number, there's no index or position. We can't access things easily using an index. And the last point that I'll make, if you're wondering why would you use this, well, remember, this is a course on data structures, and a lot of it is oriented sort of towards teaching theoretical things, but that doesn't mean that linked lists never have uses or applications. We'll discuss more as we go. We're going to learn about some more specialized data structures that are built on top of linked lists, like stacks and queues, which are coming up. And so we have to understand how linked lists work in order to implement a stack and a queue. Congratulations if you made it to this point. I know this is a lot of content. It's a little different than some of my other courses that are focused on building something cool or fun, or it's supposed to be fun at least. This could be a bit dry. So I highly recommend you take some time, take a break, do whatever you need to do, get ice cream or go yell in a pillow. And I'll see you in the next section. Doubly linked lists. Hey, welcome back. So we're moving on to our second data structure, another linked list. This time it's a doubly linked list instead of singly linked list. And basically, spoiler alert, all that we do is add a pointer to the previous node and the next node. So each node points in two directions. That seems like a very tiny change, and it is to the actual structure, but it has some large ramifications for the code that we write, the methods. But first, let's talk about our objectives. We're going to construct a doubly linked list. We'll compare and contrast doubly and singly linked lists, and we'll also implement basic operations like we did in the last section: push, pop, shift, unshift, insert, get, set, all those things. But first, let's start by just describing how it works. So as I've already mentioned, it's almost identical to a singly linked list. We have a bunch of nodes. There's no indexing, so it's still a linked list. It's not like an array. We don't have random access using numbers or an index. We have a head and we have a tail, but every node in the list points to the next node ahead of it, but also the previous node behind it. So that's where the doubly linked part comes from. Instead of just pointing to the next, it looks more like this. So we have a head pointing to the next item, and then it also has a previous pointer, but there's nothing because it's the beginning. So then our second item points to the next item, but also to the previous item. And all the way down to our tail, the last item, it has no next, but it has a previous. So as I already mentioned, it's a tiny change structurally to each node, just one pointer pointing to the previous node in each node, but it has a large impact on some of the code we write and the efficiency of certain operations. For example, when we're talking about popping off the last item of a linked list, a singly linked list like we have here, there's just one way, the arrows are pointing one direction. There we go. If we want to pop this last item off, and I go to remove from the tail, we have to iterate the entire list, and we have to find the second to last item. Remember, if you watched the video on pop in the last section, we had to find the second to last item and make that the new tail. We can't just go to the tail, like if we want to remove 16, we can't just go to 16 and remove it. We have to go to the item before it and make that the new tail. So we can't work backwards. When we're talking about a doubly linked list, however, if I want to remove the last item, I can just go to the tail and work backwards with .previous. I can move this direction. Instead of having to go from the beginning until the end, or the second to last item, I can just work backwards. Or another thing that is much, much easier, imagine that you wanted to print out a linked list in reverse, or you wanted to iterate it in reverse. If you had a singly linked list and you tried to go backwards, it is a huge pain. It's horribly inefficient. You basically start at the beginning, go all the way to the end, and you can't work backwards. So you could start over and go to the second to last thing, or, you could make an array and just add things to that array one at a time as you go through, and then reverse that array. But there's no easy way to just start at the beginning and go, or start at the end and go to the beginning. With the doubly linked list, you can start here, and we can just do .previous. It's just as easy as going from the beginning, .next. And as we go through the section, I'll definitely spend time comparing the two singly and doubly linked lists and how they perform on certain operations. And you'll see that some of the code we write is a little bit more complicated because at the bare minimum, we have to now account for two pointers. We have to update a next and a previous every time we add something in or remove something or delete some, remove and delete, that's the exact same thing. So we have some more work to do, but it's not that much harder. The real drawback is that it takes up more memory. So it's kind of always a trade-off in programming. More flexibility using a doubly linked list, but it also means more memory that's used up because now we're storing a previous and a next instead of just a next. Okay, so this will be something we come back to, but I'm going to leave this off for now at this. A singly linked list and a doubly linked list, they are very, very similar in a lot of ways. They're linked lists, there's no indices, there is an order to them, and they just consist of a bunch of nodes connected by pointers. A singly linked list is one directional, just .next, or, theoretically, just .previous. But a doubly linked list has both directions. It points to the next item and the item behind it, the previous item. In the next video, we'll implement our own doubly linked list, and we'll get working on push and pop and some of the other methods. All right, in this quick video, I just want to set up our two classes. We're going to have node, just like before, and we're going to have doubly linked list. And the basics of both are very, very similar to what we had before. The only difference is that a node now has a value, it has a next, and it has a previous. Our doubly linked list class is just going to have a head a tail, and a length, just like before. So this is unchanged. Now the logic, the code we add to this will change a lot, all the different methods we add compared to singly linked list. That's why we have a whole section on it. But the actual constructor is going to look the same. So let's start class node. So we'll do class node here, add our constructor. Each node has a value. So we set this dot val equals val. And then we have this dot next, and we'll set that to null at the beginning. And this dot previous equals null. So this is the only difference in the node class. Otherwise, it's identical. And then our doubly linked list class, we'll just do class doubly linked list has a constructor. Just leave it empty. And we just need to set this dot head equals null, this dot tail equals null, and this dot length starts at 0. And that's it. That's our skeleton. So I'll get rid of this now. We don't need that. This is what we'll be using and adding on to. Our node class is done. We don't touch that anymore. We add everything to this class. So we'll be adding, push, just like before, or pop, or whatever else we do. If we wanted to just test it out, though, just to make sure it works, let's run this code. Let's just work with the node class. Let's do, first equals new node, give it a value. Let's just give it the value of 12. All right, so we have first, and I can do first.next equals new node. This time it's going to be 13. And so far, we're just working with this as a singly linked list because I set first.next to be that new node. Now, the crazy thing is I also need to take 13, which is the next item, and I need to link it backwards. So I want to say first.next, which should give me 13. Yep, that node. First.next.previous. It's very bizarre, right? We're saying first thing dot next. Its reference to the previous thing should be the first thing. And now if we look at first, it connects to this next node, but that next node has a reference to the previous node. And actually we could just keep clicking this and going back and forth between the two. Anyway, that's the skeleton for our doubly linked list class. In the next video, we're going to start adding methods. First up is going to be push, so we can get some data in there. All right, welcome back. So our first challenge is to write a push method. So our doubly linked list class doesn't do anything right now. Let's add a method called push that takes a node, or takes a value, and adds a new node to the end of the doubly linked list. So if we visualize that here, if I wanted to push something in at the end, I'll do create, and, not create, insert. After tail is how we specify at the end. Let's do 80. All that we have to do is find the tail, and we make a new node, 80. We connect the dot next of the tail to our new tail, and then we also need to go the other direction. We need to take the new tail and connect it backwards to the old tail. And then finally, we make this the tail. We move that over. So if we wanted to write the pseudocode, the steps that we need to follow, the first thing is to create the new node that you're going to add in. So create a new node with the value passed in. We need to check if the head is null, or you could also just check if the length is 0. Basically check if the list is empty. If it is, the head and the tail are both the newly created node, and you don't actually have to do anything else if that's the case, because there's no previous or next to connect. We just make the head and the tail the same. Otherwise, if there is something in there already, we take the current tail and we set the next property on it to be the new node that we just made. But then we also need to take the previous property of the new node and set it to be the old tail. So we need to point the arrow backwards. If this is making the forward arrow, the dot next, we need to do the dot previous from the new node back to the old tail. And then we just need to update the tail property to be the new node that is now at the end, just like we did here, where we inserted, if we step back here, we make the new node, we connect the old tail to the new node, then we connect the new node to the old tail, and then we just say, all right, this thing is the tail. That's the last step. And then lastly, increment the length, and then return the entire list. All right, so in the next video, we'll have a solution. Welcome back. Let's get writing our solution to push. Okay, so the very first thing we'll do after actually writing the method is create the new node with the value passed in. So let's start there. So on our doubly linked list class, I'm going to add push, which accepts a value because I want to be able to say list.push 50 or .push hello or whatever. So let's make that new node. New node equals new node with that value that's passed in. So we have that new node. Next, we want to check if the list has anything in it. So if the head is empty, empty head, I have the empty head right now. If the head property is null, or if the list is empty, meaning that the length is 0, we could do this however we want. Let's actually, just to show that it doesn't matter, I'm going to do something that I didn't specify. I'm going to say if this.length equals 0, which is another way of just checking if the list is empty. We could also do if this.head is null, or if this.tail is null. It doesn't really matter. Okay, so I'm going to do this. If that's the case, what did we need to do? We need to make the head and tail be the newly created node. This.head equals new node. This.tail equals new node. Otherwise, set the next property on the tail to be the new node. Okay, so let's do else. So this means that there's something in there already. So let's say that the list already has the number 99, and what we need to do is add in 100 at the end. So if this is the current tail, I'm going to say this.tail, which would give me 99, .next equals the new node. So that gives me the arrow going this way. But then I need to also set this, the new tail, or it's not the tail yet, but it will be, .previous to be the old tail. So to do that, all I need to do is say new node .previous equals this.tail. So that's giving me, I'm going to basically say 100.previous, let's see if I can do this arrow backwards, there we go, is the old tail, this.tail, it's still the current tail actually. And then finally, we need to update the tail to be the newly created node. So I just say this.tail is now new node, which is now moving, if this was the tail before, this, if I can tab over, is now the tail. Finally, we need to add one to the length. Okay, so that's going to be this.length plus plus, or plus equals 1, and then return the entire list. Return this. Let's test it out. I just executed my code. Let's make a new list. So I'll just call it list equals new doubly linked list. And then I'll say list dot push. Let's push in a number like 99. Let's look at the list. Expand this. It should have head be 99 and tail is 99 and length is 1. All right, list.push one more time. Let's do 100. This time we should have head is 99 and tail is 100. This has a next. The head is pointing to 100. That's good. And the tail, 100, should be pointing back to 99 in the previous. Perfect. Last check. Let's do list.push last item. And if we look at our list, length is 3. That's all correct. Everything looks good. Our tail has last item. It points previous to this node, and this node with 100 has both a next and a previous. All right, so that worked. It's pretty similar to what we did with a singly linked list. The main difference is that we have to do a double connection. We have to do a little more work. Connect the .next and the .previous. Next up is pop, which is a little bit different, much simpler, in a doubly linked list. All right, next up, we'll implement pop on a doubly linked list. So pop should work the same way as before on a singly linked list or any array or list for that matter. It should just remove the last item and return it. The difference on a doubly linked list, I'm actually looking at a singly linked list here, which was more complicated. It's annoying, honestly, to pop something from the end because it's not a matter of just finding the tail and removing it. Well, that actually is the problem, because to actually remove the tail, we have to find the item before the tail and set the .next property to null in order to chop that, to sever the bond. But we can't work backwards, so we have to go at the beginning, and I'll fast forward through this. Actually, it's going to be very short. There we go. Just keep going. We have to go all the way until we find the second to last item. Here we go, and sever that tie. A doubly linked list is much easier. We just start at the tail, and we can just access .previous. So if I want to remove the last item, we just start there and work backwards. So the pseudocode looks like this. If there is no tail, so we need to first check, if we're trying to pop off something that's empty, if there's no head or no tail, or if the length is 0, just pick one, return undefined. So if it's an invalid pop, if there's nothing to pop off, return undefined. Otherwise, take the current tail, store it in a variable so that we can return it later. So we're going to chop off the connections, the lifeline between the second to last item and the tail, but we need to first store the tail so we can return it. There is a special case. If the length is 1, set the head and the tail both to be null because the list is now empty. Update the tail to be the previous node. So this means we had the old tail at the end. We want to now say the tail is actually the old tail dot previous. Then we want to now take the new tail that we just updated. We moved it back one item. We want to take its dot next and make it null. So that's what was happening here. If I step back. All right, so we find the tail. We move the tail to this item. Now we want to say this dot next is null. So that should sever the bond. And actually, to be extra precise, we want to take the thing that we're returning and set its dot previous to be null as well, just to clean up any extra ends, any extra references. Then we subtract 1 from the length because we pop something off, and then we return the value that we removed. And that's it. So the slides don't make this very clear, but actually they don't say it at all. It's not even that it's not clear. When you sever this bond, you need to remove both connections. So it's not enough just to say this dot next is null to get rid of one direction. We should also remove the other reference. Technically, it may not be a problem because if we're moving this to be the tail and we set the dot next to be null, it's not an issue unless somebody somehow starts from this node and they go dot previous, and then that gives them the entire list. So we do want to chop that off so that it's on its own. It's just the node that we're returning. We're not returning any linkages to the list. Okay, so give that a shot, and in the next video, I'll have an implementation. Okay, so let's implement pop. So I'm going to head over and just write the skeleton. So we've got pop, no arguments. And the first thing we want to do is check if there's anything in the list, or rather, we want to check if it's empty. So instead of, last time I did if this dot length is 0, this time I'll do if there's no head. If we have a headless list, return undefined. So that's just like the singly linked list pop. Next, what I'm going to do is store the current tail in a variable. So I'll call this popped node. This is the thing that we're popping off. It's going to be this dot tail. Then we have our special case that we talked about. If the length is 1, make the head and tail null. So if this dot length equals 1, what do we want to do? We want to set this dot head equals null, this dot tail to be null. Perfect. Otherwise, we need to update the tail, and what that entails, what that means, if this is our current list, let's say we just have 1, 2, 3, and 7, and we're popping 7 off. Well, there's 2 connections there. We have this connection, and you'll have to pardon this hideous diagram. Oh my gosh, this is terrible. There we go. We have this connection. Okay, so if this is currently the tail, that's what the letter T means. We have this in a variable. We're going to say this is the new tail. So that's easy to move that reference there. All that we have to write is this dot tail equals pops node dot previous, right? That's just going to say take this thing dot previous. That's the new tail. All right. Next, we're going to set the new tail's next to be null. So that's going to be severing this bond here. So that's just this dot tail dot next equals null. Now there's one thing that we have to do, remember, is so we remove this linkage, we updated the tail, we need to remove this linkage too. And that just means, so actually I'm not going to do that right away just to show you, so I'll come back to that. This is a better way of teaching it, I hope. So we need to lastly decrement the length and return the value. So this dot length minus minus or minus equals 1 and return the value, so popped node. Okay, so let's run the code. Here's our list. Well, we don't have one yet. Let's do new doubly linked list. list.push1, list.push2. Okay, so if I do list.pop right now, it gives me back the node, and you'll see that its next is null, but its previous is still there. It's still pointing to the old tail, or to the new tail, excuse me. This used to be the tail, and it has that linkage still. So the list itself doesn't. It's not connected. If we look at the list, the tail has no next and no previous because it's only one item long. So there is no connection to this old node going one way, going .next. But if we have the old node, if I saved it to a variable, so let me actually do a couple more pushes. Let's just add on, 50 and 100. If I look at the list, it's 3 items long, and the last item right now is 100. If I do var old tail equals list.pop, and I look at the old tail, I can do .previous, and then .previous again, and I can walk through the entire list. So I didn't just return, I did just return the node, but the node has lingering connections. So we want to sever those ties, remove that entirely. And to do that, it's not that bad. We're just going to take popped node dot previous equals null. So to summarize the steps, we create a new node. We set the new tail to be the one right before the new node. That's much easier than the singly linked list. We don't have to loop through or navigate the entire list. We don't traverse it. We just start at the end and do .previous. Then we just set this .tail.next. So this is the new tail. .next is now nothing. It's empty. So we chop that one line, and then we take the old tail .previous and set it to be null as well. So we chop the second connection. Then we subtract 1 from length and return the popped node. So let's just verify it works. So let's verify it works. List equals new linked list, doubly linked list, that is. List.push. Let's just make sure if I do a pop right now, by the way, it shouldn't work. Oops, looks like we have one small issue, which is this shouldn't be giving me an error, and it's because it can't read previous of null, so it's getting to this line, and it shouldn't be because it's empty. This is why. We want to check this .head, not head, because there's nothing called head. So if we do if not head, that's always going to be true, or false. Now, this is a situation, let's rerun it, just double check. If I do list equals new doubly linked list, list.pop, okay, it doesn't let us pop anymore. Now if we push 1, and then 2, and then 3, if I do a list.pop, it gives me 3, and the next is null and the previous is null. It's totally isolated. And if we look at the list and we look at the tail has a previous, but it has no next. And we're all good. Let's just make sure if I do pop again, we look at the list, it's 1 item long, list.pop. One more time, it gives us the last item. And if we look at the list, it's now empty. Everything's working. Okay, so that is pop. Again, it's easier if you compare it to the code from the singly linked list. We don't have to navigate the entire thing. We don't have to have a loop. We just start at the end and work backwards. The only annoying thing, as with everything we do in a linked list, we have 2 linkages to account for. But otherwise, it's much faster and much easier. Welcome back. Next up, we'll add shift to our doubly linked list. So shift, hopefully you know by now, removes a node from the beginning. No shame if you don't. I always mix them up. Shift and unshift and push. Well, push and pop are easy. Shift and unshift, I always manage to think that unshift is shift and shift is unshift. I should know that by now. But shift removes the node from the beginning of a list. And if we go back to our singly linked list example, to remove from the beginning, it's pretty easy. We just take the current head, we find its .next, and make that the new head. And then we take this .next and make it null. We set it to null. And then we return that old head. And we're done. With the doubly linked list, it's pretty much the same, except we have an extra linkage. If we remove from the beginning, let me pause this. All that we do is find the current head, and then we find the .next, and we make that the new head. Then we have to set this .previous to null, and this old head .next to null. So 2 connections that we have to sever, and we return the old head. So they're very similar. The doubly linked list, we just have to also update the dot previous, but there's no real benefit that we get from a doubly linked list in this example. It's just as easy or difficult or annoying or whatever it is in a singly linked list. It's the same in a doubly linked list, except for previous. Okay, so here's the pseudocode. You're going to start by just checking if the length is 0, or if there is no head, return undefined. Just our edge case that we've been returning to. Otherwise, store the current head property in a variable. I'll call mine old head just so that we have something to return at the end. We need to store it. We can't just remove it. We have another special case. If the length is 1 and you remove the last item, we need to set the head to be null and the tail to be null. Otherwise, update the head to be the next of the old head. So that's what we did at the very beginning here. So we have, this is the old head. We're going to move it, the head reference, to be old head.next, which is just moving a little reference, a pointer like that. So do that, and then set the head's previous property to null, meaning the new head's previous property to null, and then set the old head's next to null. So that's severing these bonds right here. And then finally, decrement the length and return the old head. So give that a shot. Like I said, it's basically the same as doing it on a singly linked list, except we have to pay attention to previous. So there's no real benefit of a doubly linked list in this scenario. Okay, next up, I'll have a solution. All right, so let's get working on shift. Okay, so the very first thing we'll do, aside from defining it, is add in that edge case. Again, we can check if the list is empty by checking if the head is null or if it doesn't exist, or by checking if the length is 0. So I'll do length this time. We did this.head last time. I'll do if this.length equals 0, return undefined. All right, now the next thing we need to do is store the current head in a variable. So I'll call it old head, or shifted node, or whatever you want to call it, is right now the current head, this.head. But that's about to change. First, we have this edge case. If the length is 1 and we remove the last item, we need to make sure the head and the tail are null. So if this.length is equal to 1, we're going to set this.head equal to null. I could have just copied this from above. This.tail equals null. Okay, so that's that edge case. Now we need to update the head to be the next of the old head. So going back to this diagram, I guess I'll put it in comments because it's getting an error. If we have 99 and 100, 2 items in our list, and we have 2 connections, the .next and the .previous, what we want to do, we also have a reference to the head. First, this is the current head, and I've stored it in a variable. I'm moving the head to be 100. So I'm just going to say this.head equals old head.next. So 99.next, meaning this is the new head. Now we just need to sever these bonds. So it doesn't matter which one we do first. I can say this.head, meaning the new head, .previous equals null. So that's going to remove that connection. And then I can say old head.next equals null. This is the old head.next is null. Old head.next is null. And now that removes this entirely. They're not connected at all. This is called the head now, and this is old head. So I can return old head. We have one more thing, which is to decrement the length. So this.length minus minus, and then return old head. And that should be it. So I just added in some code here, so I don't have to type push over and over, and you don't have to watch me do that. So we have our list that has 3 items, Harry, Ron, and Hermione in there. And let's do a list.shift. So it looks like that worked. We got Harry back, where next is null and previous is null. It's totally isolated. And if we look at the list now, the head is Ron. It has no previous. That's correct. It's at the beginning. And the tail is Hermione. Let's do a list.shift again. Okay, we got Ron on its own, and we look at the list. It's 1 item now, Hermione. No next, no previous. It's just head and tail are Hermione. One more shift. Aha. So we have a problem here, which is that in this scenario where length is 1, we're setting head and tail to be null. We don't want to do any of this other stuff. So I'm going to add an else here on these 3 lines. and close it up there. And this is the same thing we did up here for pop. We checked if there's 1, set the head and tail to be null. Otherwise, do this. So we set the head and tail to be null because there's nothing else to do, and then we subtract 1 from length and return the old head. Let's just make sure it works. Rerun the code. So I'll do list.shift 1 time, 2 times, 3 times, 4 times. And now list is empty, but we don't get an error if I keep trying to shift like we were doing, or we were getting before. Okay, so shift is pretty much the same or very similar to writing shift for a singly linked list. We just have to pay attention to previous and next rather than only next. Next up, we're working on, surprise, surprise, unshift. All right, next up is unshift. So unshift will add a node to the beginning of our doubly linked list. So it's about the same as what we did with a singly linked list. We just have that extra connection. So if we come over here and we do insert at the beginning, we'll add the number 85. All that we do is find the current head. We make a new node. We point the new node at the current head. Then we point the old head, or the current head, at the new node, and then we make this the head. That's the final step, and we're done. So it's pretty short. All that we have to look out for is if the list is empty, and in that case, we make the head and the tail the same thing. All right, so here's the pseudocode. Create a new node with the value that's passed in. If the length is 0, if it's empty, set the head and the tail to be that new node. Otherwise, we'll set the previous property on the head to be the new node. Then we set the next property on the new node to be the current head. And then finally, we move the head label. We make the head the new node. We shift it over, or unshift it over. And then we increment the length and then return the list. All right, so just to reiterate that, we take the current head. Well, first we make the new node, then we take the current head, and we have the new node point.next at the current head. Then we have the current head.previous set to the new node. There's that other arrow. And then finally, we say this isn't the head anymore, this is the head. And we're done. We just have to look out for the edge case. When it's empty, the head and the tail are the same thing. All right, so let's implement unshift. The first thing we'll do is create a new node with the value passed in. Okay, so we have unshift, which takes a value, and we'll just make new node equals new node with that value. All right, then what we're going to do is check if the list is empty, if the length is 0. Or that's just one way of doing it. If this dot length equals 0, we could also do if not this dot head. If that's the case, we're going to set this dot head equals new node and this dot tail equals new node. Okay. Next up, I have 4 equals. There we go. Otherwise, set the previous property on the head of the list to be the new node. So we'll do else the previous property on the head. So this dot head dot previous equals new node. Then we need to go the other direction. Set the next property on the new node to be the current head. So new node dot next equals this dot head, the current head. Not for long though, because we're now going to update the head to be the new node. This dot head equals new node. And then finally, increment the length and return the list. So that's going to be this dot length plus return this. So we return the entire list. Let's make sure it works. So I'm going to execute the code. And what do we have here? List with 3 things in it. Let's do list.unshift. I think this is Harry Potter themed. Let's do, I don't know, Hagrid. Okay, if we look at list, the head now is Hagrid. Perfect. And it should be pointing to Harry, which it is, and there's no previous. Perfect. Let's just pop them all off, or unshift. Let's do pop a couple times. Okay. Now we just have, what do we have? Is it empty? Yeah, it's empty now. Let's do list.unshift and make sure it works. When it's empty, and it looks like it does. Yep, head and tail are both set properly. Okay. Hey, welcome back. Next, we'll implement get on a doubly linked list. So get takes an index, a number, and it returns the node at that index, at that position. And we could implement it the same way that we did with our singly linked list, but there's actually a nice optimization. It's a pretty significant change that we can make. that we can only do with a doubly linked list. But just to recap or recall how we did it with a singly linked list, let's say we're looking for .get and we pass in 5, or let's say 6. So we're looking for the item at index of 6. We started at the head. That's our only option. And then we had a counter variable. We set it equal to 0. This is index 0. And then we just did, in a loop, .next, we add 1 to counter. It's now 1. .next, counter is 2. .next, counter is 3, 4, 5. .next, counter is now 6. So we return this node, 95. And that works. And if we wanted to do, I don't know, index of 8, for example, we still have to start at the beginning and just go all the way down. Now, if we have 1,000 items in the list and we're looking for the second to last item in a singly linked list, we have to go through all the items before it. In a doubly linked list, we could do the same thing. We could start at the beginning and work down to the tail or to the element, but we could also start at the end and do .previous. So you could just do working from the end if you wanted to, or you could only work from the beginning. But the optimal solution is to work from one or the other depending on the index that is provided. So if I did, let's make a new list that's a little larger. I think 10 is the largest I can do. If this is the list, we know that there's 10 items in here. The highest index is 9. If somebody is looking for the index of 7, if someone did this list .get 7, we could just start at the beginning and just add until we get to index of 7. But 7 is closer to the end of the list. So we could, and we should, start at the end and work backwards. So we know this is index of 9. It's the highest index is 1 less than the length. So we can start at 9 and work back to 8, back to 7. So that's what we're going to do. We're going to write code that checks, is the index that's provided closer to 0 or closer to the last index, the length minus 1. And that would make a very significant difference if we're talking about, I don't know, 1 million items in a list and we're looking for the 900,000th item, for example. No need to start at the very beginning. So here's the pseudocode. The first thing we need to do is just check if it's a valid index. So if it's negative or greater or equal to the length, return null. Remember, it can't be equal to the length. If there's 10 items, there's nothing at index 10. The highest is 9. Otherwise, we're now going to check if the index is less than or equal to half the length of the list. If that's the case, we're going to start from the beginning and move to the right, .next, until we find the correct node. Otherwise, that means that the index is greater than the half of the length of the list, meaning that it's closer to the right side or closer to the tail. So we'll start here, and instead of adding 1 each time we do a .next, we will subtract 1 from a counter every time we do a .previous. So our counter is going to start as the last index. Our position will be, in this case, 9, because there's 10 items. 10 minus 1 gives us 9. Or if we had 5 items in the list, we would start at index 4 and subtract 1 each time we did .previous. So hopefully this makes sense, this idea. All you have to do, take the length, divide by 2, and compare the index to that result. And it's up to you. If we're looking for the exact middle of the list, the middle index, if you would rather group that in with the head or with the tail. Doesn't matter. Okay, so give that a shot. One more time, here's the pseudocode. Oh, return the node once it's found. I didn't specify that. And that's pretty much it. So try it out. In the next video, I'll have a solution. All right, let's implement get. So first things first, let's define get. It accepts an index. And we're going to check for our edge case or the error. If index is negative, that's not good. We can't find that. Or index is greater than or equal to this .length. So we can't have it be out of bounds on either side. And again, we can't have it equal to the length because the highest index, just like an array, is always 1 less than the length. If that's the case, return, null. Undefined, false, it doesn't really matter to me. Just return something bad, something negative. Okay, otherwise, what we need to do now is let's just start by implementing the left part. So we start at the head, just like we did with singly linked list, and just do .next. We're going to have to do that at some point. So let's just start there. So I'll make a variable called count and start it at 0. And then I'm going to make another variable called current and set that to be the head. Okay? And then I'm just going to do while count is not equal to index. So we're going to start with count at 0, and we're going to add 1. Well, we're going to do current equals current.next to traverse the list. Hopefully this sort of approach is review at this point. And then we'll add one to count, count plus plus. So we start at, let's say we're looking for index of 2. Count starts at 0. Current is head, or this dot head. Then we check, is count equal to index? It's not. So current now is equal to the head dot next, and we add one to count. And we keep going until we hit whatever's at index 2, Hermione. And then once we found that item, we just need to return current at the end. So this is the unoptimized version. But let's just make sure it works. See if I have any errors in this. Make this a little bit larger. Let's push on a couple other things. Let's just push on last, and then I'll do actually last. Okay, so if we look at list, it has 5 things. I shouldn't be able to do get of -1 or of 10 or even 5. But if I did get of, let's say 3, index of 3, it gives me last. If I do index of 4, it gives me actually last. Index of 0, Harry. 1 is Ron, and 2 is Hermione. 1 second, I have to yell at my cat. Hey, stop it. Come on, girls. They're destroying my furniture. Okay, so that's great. That works. We're going to use a lot of this logic, but now we also want to do the same thing. We want to start at the end and work towards the middle. And we're going to do it based off of where the index is in that list, how high or low that index is. So we'll go back to the pseudocode now and check if the index is less than or equal to half the length of the list. So we're going to do this approach right here. If index, so I'm going to write this out, if index is less than or equal to, and the equals part doesn't, you could do it on the other one, whichever way you'd prefer to do it, it doesn't matter. But I'm going to say if the index is less than or equal to this dot length, divide by 2. If that's the case, we're going to do all of this. And we'll refactor this in a bit. There's going to be a little duplication. Otherwise, that means we're going to start at the end of the list. So we're going to start with a count variable equal to this dot length minus 1. For example, if our list looks like this, our length is 10, our last item is index of 9. So we're going to start with count at 9 and subtract 1 each time. So we're actually going to write the same sort of loop. We're just going to do, I need to do current as well. Var current equals this dot tail. We're starting at the end. While count is not equal to index, what are we going to do? We're going to say current equals current dot previous. We're going to step backwards, and then we're going to do count minus minus. Subtract 1 from count. And then at the end, return current. Hey, stop it. Okay, I'm back. So let's add a little test in here, or let's just do a console.log to say working from beginning. I hate typing the word beginning. Let's say working from start. And then in the else, we'll do working from end. And let's see which one runs. And then we'll reduce some of the duplication. Okay, so we have list that has 3 things in it. Let's push in 300, 400, 500, and 600. Okay, so length is 7. If I do a list.get of 0, it says working from start. If I do a list.get of, let's say, 5, it does working from end. And if I do, 6? That's our last thing in there, right? There's no index of 7, right? So it looks like it's working. It says that it's working from end. We could, you could create a variable to count how many times the loop actually runs if you wanted to really test it out, but we can just trust that this works. We've added a little bit of logic to check if we're closer to the beginning of the list or the end, and that changes where we're working from. Now, a tiny change. First of all, we can return current afterwards, so we don't need to duplicate that. So let's move that outside of the conditional and just put it afterwards. It happens for either one, however you say that. We also have, let's see, we can get rid of those console.logs now. We have count and current are both being declared. This is fine. I would probably do this personally, do var count and current, and then just update them. But it doesn't really matter, honestly. We still have to have these lines that are duplicated here. But overall, I'm happy with how this looks, how it's working. If you have a better refactor, there are other ways of doing this, or of rewriting this where we don't have so much. This logic is very, very similar except for the actual operation that we're doing inside of there, but this loop is the same, right? We're setting current, we're setting count. There are ways, slightly more complicated, of slimming this down, but this is fine. Absolutely, it works. Let's just verify it one more time that it works. So we've got our list. Let's do list.get -1. Shouldn't work. Let's do list.get 0. It works. 1, 2, nope, I didn't type a number. And then 3 shouldn't work. Looks good. It's working. I think that's all that there is. All right, next up we have set on our doubly linked list. So set takes an index like get, but it also takes in a piece of data or a value to update the node at that index with. So we can say set the item at index 3 to now be hallelujah. So if you implemented get from the last video, set is really, really easy because we don't have to do any of the logic to actually find the node. That's what get does. We can call get, and all we have to do is actually update the node. So the pseudocode is pretty short. Create a variable, which is the result of the get method at the index that was passed to the function. So we don't actually even have to check if the index is valid or invalid because we did that in get. Get is already checking if the index is negative or greater than or equal to the length. So we just use .get, pass in the index, and whatever comes back, if it returns a valid node, set the value of that node to be the value that was passed in to set and return true. Otherwise, just return false. So you can do this one in just a couple lines. I think it's 4 or 5 lines. It's just the same as what we did. I think it's identical, actually, to what we did with a singly linked list. So if you want to practice, rewrite it, but it's super short. All right, solution coming up. Welcome back. Let's write set. So I'm going to go below get and add our set, which takes an index and a new value. And the first thing we do is just call get with that index. So we'll do this.get and pass in that index and save it to a variable. Let's call it found node or no, call it whatever you want. I'm going to go with found node. And then we're just going to check if found node, or we could do it the other way and say if not found node. So if there was a found node, we could also be more specific and check if it's not null. It's probably better. So if found node is not equal to null, we're going to take found node dot val equals the new val that comes in, and then we return true. Otherwise, return false. And we don't need to do an else. We can just return false. Check our pseudocode. Was there anything else? I think that was it. And let's test it out. All right, so we have our list, and it has 3 items, Harry, Ron, and Hermione. Let's just test it out first, doing this dot set on -1 or -100 or 10, apparently, because I didn't type an extra 0. And just make sure it doesn't work. Okay, it's false. Our list is unchanged. Same thing if we tried to do it with index of 10. Same thing, unchanged. Now, let's try and set, let's say, the first item, instead of Harry, let's have it be all caps, Harry. We get true, and if we look at the list, it's still 3 items, but the first node is Harry, and everything looks good. Otherwise, it's still pointing to Ron, which is still pointing to Hermione, which is pointing to nothing. Let's try and update Hermione, so that's index of 2, and we'll do all caps again. And if we look at list, or look at the tail, it's all caps. Cool. So that's working. That's all that there is to set. Nice and easy. If we write get, that is. Without get, it's a pain, but we have get, so it's nice and short. All right, welcome back. Next, we're going to implement insert on a doubly linked list. So this works in a very similar way to how it does in a singly linked list. You pass in an index, a position, and a value, and it creates a new node with that value and adds it at that position to the linked list. The main difference is that we can optimize it rather than starting at the beginning and always going .next, .next, .next. We can also start at the end and go .previous, and it's up to our code to decide which is more appropriate depending on what the index is. But we don't really have to worry about that because we already wrote a get method, so we can use that get method to retrieve the appropriate place to insert it. And that get method already has the logic to check, length divided by 2. Is the index less than? If so, start from the head and move towards the middle. Or is the index greater than half of the length? If that's the case, start from the tail and move towards the middle. Anyway, what we want to do, let's say I'm inserting at index of 4, the number 77. Oh, I can't do that because our list is 10 things. Okay, let's make a new list that is 9 items. Do this one more time. Insert index of 6, sure, 65. All right, so we traverse the list until we find the item right before what we're going to insert. So we found it. And now the annoying part about the doubly linked list is that we have a lot of connections to make. So we need to remove this connection, both connections there, and instead we need to have 66 point at 65, 65 points back at 66. Then we have 12 point at 65 previous, and 65 next point at 12. So if we step through that, you can see all these lines that we're drawing, and we're done. So there are 4 different little patches that we have to make. So here's the pseudocode. First, we're going to check if it's a valid index, just like before. If the index is too small, or if it's negative, or it's greater than or equal to the length, return false. If the index is 0, use unshift. We already wrote that. If the index is the same as the length, meaning, so if we have 8 items, the length is 8. If the insert is at 8, that's actually valid, remember, because even though it's currently not a valid index, it's okay for us to insert at the end, which would make it a valid index. So if that's the case, call push. Otherwise, use our get method to access the item right before where we're trying to insert, so index -1. And then you need to do all the patching, the next and previous properties on the correct nodes to link everything together, increment the length by 1, and return true. So try it out. In the next video, we'll have a solution. All right, so let's write our insert solution for a doubly linked list. So I'll define insert, which takes an index and a value. And the first thing we'll do is check if the index is negative. So if it's less than 0, or if the index is greater than the length. Then we'll return false, or whatever value you want to return to indicate that it doesn't work. Then we had our special case. If index is exactly 0, what do we want to do? We're going to return this dot, not push, this dot unshift, add to the beginning. And if index is exactly equal to this dot length, that means we're adding to the very end. We're going to do a return this dot push val. Okay. And let's just test that part out for now, just make sure we didn't mess anything up. So we have our list. If I do list.insert index of 0 first, let's look at the list. Is our new head correct? It looks like it's correct, and it's pointing to, yep. Let's try the same thing. Our length is 4. So if I try and do list.insert at 4, and let's say I do last is what I try and insert. It looks like it worked. If we look at our tail, it's set to last. Okay. And also, if we tried to do something invalid, like 40, it shouldn't work. We should get false, and we do. Okay, so otherwise, the rest of our logic was use the get method to access the index -1. So we can do, what should we call this? Let's do found node again, equals this dot get, and we're going to do index -1. Because if I'm trying to insert right here, I need to first find the item before it. So that's what we're doing right now. So we're finding the one before. We also need to make the new node. So we can call it new node or inserted node equals new node and pass in the value, just like that. Now all we have to do is patch everything correctly. And to make it a little easier, I'm going to make another variable. So this is called found node. I think I might actually relabel this to previous node. And then I'm going to have, let's call it before. I like that more. And then I'm going to have after node equals before node dot next. So I just have 2 references now. So if our list looks like, I don't know, A, B, C, D, E, F, and if we're trying to insert at index of 3, 0, 1, 2, 3, what we did is we found before node is right here. And then I set after node to before node dot next, which is right here. So I now have a reference to here and a reference to here. And it's just going to make it a little cleaner or easier to understand what's happening. So we want to set the before node.next to be our new node. So before node.next equals new node. Then we want to set new node.previous. So we just inserted something right here. Let's say we're inserting hello. We did this connection. Now we need to go from hello back to before node. So new node.previous equals before node. Now we need to go connect this to the after node. So we'll do new node.next equals after node. After node.previous equals new node. It's kind of a pain. But I prefer to make a separate variable to do this. You don't have to. You could just write before node.next instead of after node. It's just, I don't like chaining that together and having, .next, .previous. And other than that, what else do we need to do? This .length goes up by 1 and we'll return true at the end. Let's test it out. See if it works. So we have our list. Right now it has 3 things. If I try and insert list.insert at index of 1, we're going with Harry Potter. Let's do Tonks, underrated character, and let's look at the list. So it's now 4 things, that's correct. The head should still be Harry, but the head now points to Tonks. And Tonks has a next reference and a previous. If we look at the previous, it's set to Harry, so that's correct. And if we look at the next, it's set to Ron. And if we look at Ron, and we look at its previous, it's set to Tonks. So everything is connected correctly, which is probably the most annoying part of verifying or making sure something works in a doubly linked list, is making sure that you have all the connections, because you need to make sure you have the next and the previous for every single thing that you're changing. A couple small changes. First of all, if we might want everything to return true or false. Right now, everything does unless we are unshifting or pushing these 2 scenarios. This was the same thing in our singly linked list example. Just to refresh your memory, if I do list dot insert anywhere, like in the middle, it returns true. But if I do it at the beginning, it returns the node, or at the end for that matter. What's our last? Yeah, it returns true. What is the last index? 6 now? There we go. It's giving me the node. So if I want to coerce it to a Boolean, we can do the same thing we did, the double bang, 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 which is now going to turn it into a Boolean. Another thing I'll do, I'll add a little a return here just to separate out these little edge cases in our conditionals. I'll also add in, it's opinion, I guess, but I kind of like separating out our variable declarations. And then I'm actually going to put these on the same line because they're paired together. We're adding the before node.next equal to new node and new node.previous equals before node. So I like to group those together to show that we're sort of doing, one set, a pair of connections at a time. Same thing here. Definitely not necessary to do that at all, but I like that change. And now just double check everything still works. Insert at the beginning. That works. Insert in the middle. That works. And insert at the end. Now, was that the end? What is our last thing? No, that was not the end. If I insert at 6, it should work. Now the length is 7, so if I insert at 8, it shouldn't work. Okay, so that's insert. All right, next we have remove for a doubly linked list. So remove just takes in an index or position, and we're going to remove the item at that position. Just like before, we can take advantage of get. Here, let me restart this here. We can take advantage of get, which we already built in the functionality to check if something is closer to the head or to the tail. So we don't have to write the logic to work from the end or from the beginning. We can take advantage of get. But we still want that logic to be running, because if we have a million items in here and we're trying to remove the second to last item or the fifth to last item, it makes no sense to start at the beginning and go next, all the way almost a million items down, when we could start at the end and just go previous, or however many times. So that's what we're going to do here. But of course, we're not going to have to write most of that logic. All that we really have to do is first check if the index is invalid. If it's less than 0 or greater than or equal to the length return undefined, or some falsy value. If the index is 0, shift. Just take advantage of shift, remove from the beginning. If the index is the same as the length minus 1, or if it's equal to the length minus 1, I don't know why I said if is the same as, just use pop. Otherwise, use the get method to retrieve the item to be removed. So that retrieves the item, then you have to update the next and previous properties to remove it correctly. We have to patch the hole. And then what I like to do is set the next and previous on the found node itself, on the thing that you're removing. Just wipe those out so that when you return it, it's just the value, and next and previous on the returned item are null. And then subtract 1 from the length and return the removed node. So for example, if we remove something from the middle, let's say index of 4, we find it first using get. Okay, we found it. So we have to patch the thing before it and the thing after it. 2 connections, and then we remove the connections from here, from the deleted item, and then we return the deleted item. Okay, so give this one a shot. Remove, take advantage of the get method that we already wrote, and yeah, solution coming up. All right, let's implement remove on our doubly linked list. We're almost there. So we need to specify the index that we're removing at, and we first check if that index is invalid. I'm actually just going to copy this from insert. So if index is less than 0, or if it's greater than, except this time, or equal to the length, because unlike insert, where we could insert right at the very, very end, if there's 8 items, we can insert at index 8. If we're removing, the length is 8 items, there's nothing at index 8. So we need to check if it's greater than or equal to. Return false or undefined. Otherwise, our next thing is to check if it's at the very beginning. So if we're trying to remove from the very, very beginning, let's just do a return this dot shift, which should remove the thing at the very beginning. If we're trying to remove at the end, which we could check if the index is equal to the length minus 1, we're going to return this dot pop. And let's just make sure that that works. Run our code. Let's do this list dot remove 0. And that gives me the first node. If we look at the list, it's only 2 things. So I could do a remove at index of 1, which now is the last index, and we get Hermione. And we look at the list, it's only 1 thing. So if I try and do a list.remove of 1, it's invalid. If I do 0, it works, and our list is empty now. Looks good. Now the rest of our logic, we're going to use the get method to retrieve the item to be removed. So let's do that now. We'll make a variable called removed node equals this.get and just pass in the index. So that gives us the thing that we're removing. Now we just need to remove it by setting the next and previous properties to the correct things. So I'm going to set the node before it. So here, let's go do A, B, C, D, E, F again. If we're trying to remove this node, this is removed node, we need to set this node's .next to be this node's .next. So we leapfrog over it, which now sets B's .next to be D. So that's removed node .previous gives us B. .next, the .next of B should be equal to removed node .next. Now I don't really like doing this .previous .next, so we could also do what we did earlier and make a before node and an after node. But I'm going to start with this. So that's 1 connection from B to D. Now we need to go from D to B. So removed node .next .previous equals removed node .previous. So removed node .next D.previous is now going to point to removed node .previous, which is B. I know, it's kind of crazy. Otherwise, all that we have left is to set next and previous to null on the found node. So that's just cleaning up some loose ends. So removed node .next equals null. Removed node .previous equals null. Then we subtract 1 from the length. And then we just return removed node. Let's see if it works. I'm going to test it out. So we have our list. Let's do list.remove index of 1, which is Ron. So our list should now have Harry connected to Hermione. So the head is Harry, and its next is Hermione. And if we look at Hermione, its previous is Harry, and there is no next because it's the tail. If we try to do list.remove an invalid index, -1, we get undefined, or 100 or 10, undefined. Let's do a couple pushes. Okay, I pushed in a couple values, LOL, bye, and ha ha ha. So if we look at our list now, it's 5 items. If I try and remove from the very end, if I do list.remove 5, it doesn't work. But if I do list.remove 4, it works. And notice that what we get back has no next and no null. That's correct. We don't want it to have the lingering references. So we get list dot, let's look at the tail now, which is bye, and next is correct. It should be null. It's the end. And previous is pointing to some other node, which is what? Saying bye. Okay, this all looks good. Let's just remove from the beginning. Let's just remove a couple times. How many things are left? Okay, we should be done now, right? It's totally empty. Everything looked good. You could clean this up a bit, and it's up to you if you think this is cleaner, but you could do var before node equals removed node dot previous. Oops. Var after node equals removed node dot next, and then we could do the same thing that we had before. So we just set before node dot next equals after node, and then say after node dot previous equals before node, if you don't like this syntax here. And if we refresh it, I run the code again, it should still work just fine. We have our list, nope, list with a T. If we do list.remove at index of 1, and we look at the list, it should be correctly patched still. So we have Harry, which is pointing next to Hermione, and Hermione is pointing previous to Harry. So up to you which you prefer. This is a little more verbose, but then you have this nice, clean, easy to understand syntax here, what you're actually doing, versus before it's a little longer, and you have this removed node. Everything is in reference to removed node. Honestly, I don't know which one I prefer. For insert, when we had to change more properties, I like doing this. For removed, either one. I think I'll leave both in here and just leave it commented out. Okay, so that's remove. All right, welcome back. Last video on doubly linked lists. What I'd like to do here is just run down and recap the big O notation for the common operations: insertion, removal, searching, and access. Same thing that we did for singly linked lists. And in a lot of cases, it's very similar, but there's a couple of exceptions. So insertion is constant time, which is the same. It's what it was for a singly linked list. That's really where linked lists excel. Inserting data is very, very easy. It doesn't matter where, it's very easy. It doesn't matter how long the list is, unlike an array. Removal for a doubly linked list is always constant, which is not the case for a singly linked list. Remember that if we are removing from the end of a singly linked list, we have to iterate over the entire thing until we get to the second to last item to make that the new tail. On a doubly linked list, it's constant time. It doesn't matter if you're at the millionth item. You don't have to traverse the entire list to get to the 999th node. You just do dot previous. So removal is faster, or it can be at least. Searching is still O of n, but I have a note down here because the way we implemented searching is optimized, where we either start on the left side from the head and move towards the middle, or we start on the right side from the tail and move towards the middle, depending on what the index is, if it's closer to the end or to the beginning. But even though that is O of n divided by 2, that still simplifies to O of n. Overall, as n grows, it's still insignificant if we're dividing it by 2 when we talk about things like n squared or constant time. The differences are so large that dividing by 2 doesn't matter, so we simplify it to O of n. But keep in mind, it is faster still, and it's worth knowing that because we use that divide and conquer approach where we either start at the beginning or the end and move towards the middle. All right, so that's the big O. Really what it comes down to is that doubly linked lists are basically the same, except there's an extra pointer pointing to the previous node, so we have 2 connections. And that does make certain things much easier. For example, if we didn't talk about this really in this Big O video, but if you need to start at the end and work backwards, often if you need to access your data in a reverse manner, let's say that you're representing your browser history. This is actually often done with a doubly linked list because every page that you're on has a next or a previous, actually. Both are set. So, if I hit back, which I won't do, who knows what I was looking at before this, but if I hit back, there's a web page. And if I was on that web page, I could hit forward or back. That is a doubly linked list. And a doubly linked list allows us to easily move backwards using .previous or forwards using .next. A singly linked list would not work. Also, doubly linked lists are better for finding things because it can be done in half the time. However, that extra pointer comes at a cost because it does take up more memory. So if that's something you're worried about or you want to keep in mind, even if you don't care, it's just something you should know. If you need to talk about doubly linked lists, if it comes up in an interview, that's really the key distinction. So doubly linked lists can be much better in certain ways, and they're certainly easier to navigate, but it comes at a cost of more memory. All right, so I said this at the last video of the last section, the most recent recap for singly linked lists. This is very heavy stuff. There's a lot here. It's a lot to digest. It's also not the most captivating content potentially for a lot of people. In my experience teaching this in person, some students loved the problem-solving aspects. They didn't care that it wasn't really building any sort of final product. We're not making a game or an app or a website. Some people loved that or didn't care. Other people, though, had a really hard time staying motivated. So I said this in the last video, in the last section, do whatever makes you happy. If you're going to come back to the next section, I wouldn't just add these all together and try and do some power session, cram all of this into a night or two. I would spread this out. It's a lot. Go pet a dog or a cat or a llama or get a foot rub if you can do that. Make some coffee. Do whatever you need to do. All right, that is doubly linked lists. We're done with singly linked lists and double, which means we are done with linked lists. Hopefully by now you feel pretty comfortable with, at the very least, explaining what they are and how they compare to each other and also to arrays. Hey, welcome back. This section covers two new data structures that are linked together. They're often taught as one chapter in a book or one day in a course. They're very simple, and this will be a lot less code than something like a linked list. So those two structures are stacks and queues. We're going to start with stacks for the first couple videos, but like I said, this will be much faster, much easier than some of the linked list logic we had before. So first, a couple of objectives. What is a stack? We want to talk about a definition. We want to talk about use cases, both in the real world, they're used all over the place, but also in this course, we will come back and use stacks later on. And then we'll implement operations on a stack. We're actually going to talk about two different ways to implement a stack. But first, what is a stack? Okay, so both stacks and queues, which we'll talk about in just a bit, they are both data collections. They're a data structure. They're an abstract data structure. And really the only rule is it's a collection of data and it needs to abide by a LIFO principle, last in, first out. So a queue follows a different principle, which is first in, first out, but we're talking about stacks. So the last element added to a stack is going to be the first one to be removed. Think of a collection of books on your desk, or if you have a messy countertop and you haven't done the dishes because your roommate is a terrible person, if you have a bunch of plates stacked up, the most recently added plate is on top, and when you remove a plate, you're going to remove from the top. You're going to remove the one that was just added, unless you're crazy and you want to remove the very bottom plate and, cause a crazy mess. So a stack, again, is just a collection of data, and the first thing that you added in is the last thing to be removed. The last thing to be added in is the first thing to be removed. There's more than one way to implement a stack, but you could use a linked list, and we'll get to that. But what we have here is our first element added in, our last element added in, and we would remove from the last side of things, from the left. When we remove something, it would come from here, and then here, and then here, and then finally 7 would be removed as our last thing to be removed. It was the first thing to be added. So we've seen this before. If you remember in the recursion section, we talked about the call stack. So if you're not familiar with the call stack, I recommend you go check that section out. We talk a lot about it. The name says stack in it. And if I head over to some code and I run this code, here's factorial, it's recursive. It doesn't matter if you remember how it works or not. When I execute this with a breakpoint, if you watch the call stack, here's this is the first thing, but here's our first function call that we wrote, added into the call stack, and it will be the last one to be removed. So things are added on top of it. As you can see, we're almost there. I think, is this our last one? Yes. So we now have this stack where this was the first thing added in, this is the last thing added in. This is going to be removed first. Imagine a stack of books here. We take from the top until we get to the bottom. And so then we remove from the top, although it's deceiving because it does look like we're removing from down here, but the list is just shrinking. So if you look in this context, we're looking at return value of 2, x is 2, this one, x is 3, x is 4. So when we remove, there we go, we removed 1. Now we're down to x is 3, x is 4. So it looks sort of like we're removing from the bottom the way the animation works here, but we are indeed removing from the top of the stack. And now we have one more. We remove this, then we get back to this original anonymous, and now we're done. Okay, so if you don't remember how the call stack works, definitely check out that recursion section, but this is an example of a stack. The last thing added in is the first thing removed. So a couple other uses. We talked about how stacks are used to manage function invocations. That's in many, many programming languages, really commonly used. Undo and redo functionality, like in Photoshop. When you're typing, well, I guess not typing, but when you're editing a photo, removing wrinkles on your mom's face because she makes you do that because she knows you know how to Photoshop things. Well, if you make a mistake, you hit Command Z, it's going to undo the latest action, which is at the top of the stack. It doesn't just go, 100 actions back. You have to step through it constantly. So every time you do a new action, you remove something or you clone something, it gets added to the top of the stack. And then when you undo it, you're removing from the top of that stack. Another example has to do with history objects in your browser. Many front-end frameworks like React will use a stack to model the history, the pages you've viewed, the routes that you've visited, if that makes sense. And one final example, in this course, we'll actually use stacks in some of our own algorithms. So when we get to things like trees and graphs later on, some of the algorithms that we'll be writing, we actually use a stack and also queues, which we'll talk about later. But in this case, we'll use a stack to store sort of the history of things that we want to come back to. We're going to use them as an intermediate in our algorithm. So here's an example. Again, don't worry about the code itself, but we make a stack, and you can see here I'm calling on my stack. I'm calling on my stack inside of this algorithm, and we're using it as a place to help us to store data along the way. As we go through this algorithm, we're collecting things and then removing them from the stack. Anyway, don't worry about the code itself. Just know that this is not a one and done thing where I'm just going to introduce a concept and say, yeah, these are cool and they're used. We're actually going to use them later on. So in the next video, I want to show you that we can implement a stack without actually writing any new code ourselves. We don't have to create our own data structure. There's more than one way to implement a stack. It's an abstract concept, and we're going to start by just doing one with an array, using a built-in JavaScript array to build a stack. So that's coming up next, and then we'll do a more official linked list implementation where we write some code. All right, welcome back. So if you watched the last video, we talked about how a stack is a LIFO, however you pronounce it, last in, first out data structure. And there's more than one way to create something like that. In fact, a stack is just a concept. It's basically a set of rules that says, okay, we need to be able to store data in such a way that the first thing added in is the last thing removed. The last thing added in is the first thing removed. And it doesn't really define how you do that. It's just a concept. So there's more than one way of doing it. And the easiest way is to use an array. So some data structures, some programming languages come with their own stack data type. But we can still use a built-in array or list data type to create our own stack. So all that we have to do is store data in here in a way that the first thing is the last thing removed and the last thing in is the first thing removed. So if I hop over to my console, if I make a new array, I'm just going to call it stack, and it starts out empty. Let's say that I'm storing web pages that I've visited, and I'm creating a history of where I've been. Okay, so to add something into this stack, how do we add to an array? Well, there's a couple options, but let's just use push. So I'll push, I start at google.com. Okay, so we push Google in. And then let's say from Google, I go to, I don't know, Instagram. And then one more site that I go to is YouTube. My stack now has 3 things in it. So in order for this to be a stack, I need to have a way to remove from it where the most recently added thing is what I get first. So when I remove from here, I want to start by getting YouTube. And then next time I should get Instagram and then Google. So how would I do that? Well, there's a method to do it. Stack.pop. Well, array.pop. So pop is going to remove from the end. So using push and pop in tandem on an array creates a stack, as long as that's how we're adding and removing. If somebody goes and adds something to the middle of the array or to the beginning or removes from the beginning, then it's not quite functioning as a stack anymore. But if we just push and pop, like if we're trying to use a stack in our code, which that's actually something we'll do later on, is use an array as a stack just because it's simpler. And if I pop, I get YouTube and then Instagram. If I push something else in there, like let's say I go to Amazon, now when I remove using pop, I'll get Amazon first. It was the last thing added in, so it's the first thing I get out. And then one more time, I get Google. So that's one way of using an array to create a stack structure. But we could do it another way using built-in array methods. Can you think of how that would work? We're working with the end of the array right now. We're adding to the end and removing from the end. There's another way. Well, there's at least one way. If I make some space here, I think I still have an empty, caps lock. I have this empty array. Well, if I add to the beginning of the array, I could do that. So how do we add to the beginning? Well, you can use unshift, the confusingly titled method. And let's say this time we're modeling, my Photoshop history. So I start with create new file. And then the next thing that I did, what did I do afterwards? I resized file. And then I removed, cloned out wrinkle or something like that in Photoshop. Okay, so our stack has 3 things in there. In order for this to work, the last thing in needs to come out first. So I can't pop anymore because pop will remove from here, meaning it will take from the end, which this is the first thing added in. We don't want the first thing in to be the first thing out. We want the opposite. We want the last thing in to be the first thing out. So I use unshift to add and shift to remove, which will remove from the beginning. Cloned out wrinkle, resized file, create new file. So both of these approaches are valid stacks. They work. It's all that matters is that we have a way of adding data in and removing data such that it satisfies this last in, first out principle. The first thing in is the last thing out. The last thing in is the first thing out. But there's a distinction between these two. Pushing and popping was the first thing we did, meaning we're adding to the end and removing from the end. And then we also talked about shift and unshift, adding and removing from the beginning. So based off of what we've talked about with arrays earlier on, which is better? What's more efficient? What's the problem with one of these? Well, if we think about how arrays work, remember that adding to the beginning, removing from the beginning is not good. As far as big O notation, time complexity, what we have to do is if we have an array with 3 things in here, each item has an index. And if I add something to the very beginning, we have to re-index all the other items because this is no longer going to be index 0. This will no longer be index 1. Everything gets shifted down. Okay, so if we have this stack with these 3 items in here, if I unshift again, and this time I add something else in, like, I'm just doing dumb abbreviations, all of these indices have to be shifted down, and that's very inefficient. I mean, for 4 items, it's not really a problem at all, but just it's worth considering if we have a lot of data. It's not a great way of doing it. Instead, if we use push, we're adding to the end. We just have to create a new spot, a new index, and add, index of 4. But we don't have to re-index every other item in there. It is worth mentioning that if you actually care about the efficiency, then you probably don't want to use an array for a stack. If you're going to have a ton of data in there, all you need is this last in, first out capability. We'll use our second implementation coming up where we use a linked list. There's no reason to have these indices. We're not accessing information based off of an index. We're simply accessing information based off of when it was inserted. The order needs to be preserved, and a linked list will do that for us. So to recap, we can use an array to create a stack. We can use push and pop in tandem so that the first thing added in is the last thing out. The last thing added in is the first thing out. I know I'm a broken record on that. Or we could use shift and unshift. Unshift to add to the beginning, shift to remove from the beginning of the array. So it doesn't matter what direction we're doing it in, if we're adding down here or adding over here, as long as we're removing from that same direction, if that makes sense. But in general, if you are going to use an array, push and pop are the better options because it doesn't require re-indexing the entire array every time you add or remove something. You just have to create a new index at the end or remove that index. Okay, so next up, I'll show you an implementation of a stack using a linked list. Welcome back. So as I mentioned a couple videos ago, there's more than one way of implementing a stack. It's just a general idea of a data structure where we can add data in and remove data using a last in, first out principle. LIFO, LIFO, the last thing that's added in is the first thing we get back. And I showed you how to do that using an array, and that works. We didn't have to write any new code. We didn't even define a class. We just used an array and used the built-in methods we get for free. Nothing wrong with that. It's a little heavy-handed. We don't need, indices, for example, which we get for free. We don't need all the other, dozen plus methods that an array comes with. We don't need any of that. All we really need are the methods to add and remove in a last in, first out fashion. So what I'm going to show you in this video is how to build our own stack class that doesn't use an array at all. In fact, it's built kind of following the principles of a singly linked list. So if you didn't watch the section on singly linked lists, you should go back and check that out. You could also do it with a doubly linked list, but I'm not going to do both because it's a lot of time and it's very similar. And if you see how it works with a singly linked list, you'll get it with a doubly one. All right, so one note. When we use and learn other algorithms later on, some of them use a stack and queues, which we'll see in a second, to help them out, to store data, sort of to keep track of what's been processed and what has yet to be processed. And we could use an array implementation. We could use our own class. To keep it short, I will be using an array implementation. That doesn't mean it's better, though. It's just easier and quicker. But this is the stacks and queues section, so I'm going to show you how to make sort of the best possible stack from scratch. And it should work or look like this. I should be able to initialize a new stack. And there's only two methods we care about, stack.push and stack.pop. So I could push something like first and a couple more second. Notice it's returning to me the size or the length of it. And then let's do one last one. And then when I pop, it should, of course, follow last in, first out. So it gives me fourth, and then third, then second, then first, and then null. So that's it. We need a class defined called stack, and it needs a way of storing data. So we'll have a node class as well. It looks like this, just like we did with the linked list. Instead of head and tail and length, I went with first, last, and size. Head and tail is usually reserved for a linked list, even though this is a subset or a special case of a linked list. I like to use first and last, but it's the same idea, head and tail. They're just pointers, they're variables. And then we have the node class that has a value for each node, and then a pointer to the next node in the stack. So at this point, you might be thinking, well, we already built a singly linked list. It had a bunch of other methods, but it had push and pop. So why not just use push and pop as they are? And that could work, except for one small problem, which is that in a stack, push and pop are supposed to be constant time. And if you remember, if you didn't watch the singly linked list section, this probably won't make sense, but pop in particular was not constant time. Because to pop something off the end of the list, the way that it works, we have to iterate over the entire list and stop one node before the end, one node before the tail. That's what this code is doing here. So this is not constant time because we have to loop over the entire list. So instead, it's much better to use shift and unshift, except they're supposed to be called push and pop. So I'm going to show you, I'll actually write the code, but hint, hint, you could basically just rename shift and unshift to push and pop and call it a day. but I'm going to define my own stack class right now. I do have pseudocode if you want to do this on your own, but I didn't want to drag it out into multiple videos. So basically, push is going to work a little differently than push that we wrote earlier on, because we're going to be adding to the beginning of the list and removing from the beginning of the list, instead of adding to the end and removing from the end. Same idea, it's just that when we add and remove from the beginning, it's faster, it's constant time in a singly linked list. If we use a doubly linked list, then it wouldn't really matter. It would be constant time to pop as well from the end. Anyway, so we'll define a function called push, and it should accept a value, create a new node with that value. If there are no nodes in the stack, set the first and last property to be that new node. If there is at least one node, create a variable that stores the current first, and then reset the first to be the new node. And then all we need to do is connect everything together. So set the next property on the node to be the previously created variable, and then increment the size by 1. So I'm going to come over here and define first I'll do my node class. So node is really simple. It's copied from before. We have our constructor. I'll fast forward. It looks like this. Value, we pass in, we set this value equal to whatever was passed in. This dot next starts as null. Then we start with our class called stack, which also is really basic at the beginning, doesn't take anything. And instead of head and tail, I'm going to set first to null, last to null, and then also I'm going to go with size instead of length, just to differentiate it. And it starts at 0. Okay, so now to push in, it needs to accept a val. And then we create a new node with that value. So let's just do var new node equals new node with whatever was passed in. Then we check if there are no nodes in the stack, set the first and last property to be that new node. So we'll just check we could check if the size is 0, or just if there is no first. If there's nothing at the beginning, we set this dot first to be the node, the new node, and then do the same thing for this dot last. All right, so that's that. Next, if there is at least one node, create a variable that stores the current first property on the stack, and we can go from there. So we need to have an else, and I'm just going to make a variable called temp equals this dot first, the current first, because we're adding this to the beginning. Then we're just going to say this dot first is now equal to new node, and then this dot first dot next equals temp, the old beginning. And then the very last thing we need to do is increment the size of the stack by 1. And I didn't actually add this in the pseudocode, but I explained this earlier that it's best to return the size. So I'm going to do that in one line, just return plus this dot size. And if I run my code, I should be able to do var stack equals new stack and do a push. Let's just push some random numbers in. Looks like, well, we can't actually tell if it's working, but at this point, the order in that stack, the first very beginning should be 2301, and then that should point to 230, and then that should point to 23. So now we just need to implement pop, which will remove from the beginning, which again, we're doing it backwards, sort of counter to what we did with a singly linked list, because we want constant time for adding and removing, for pushing and popping. So now to implement pop, we're going to define a function called pop, and we're going to check if there are no nodes in the stack. If it's empty, return null. Otherwise, we're going to take whatever the first property is on the stack and store that in a variable to return at the very end. Whoops. If there's only one node, set the first and last property to be null. Meaning if the first is now equal to the last, set the last and first to be null. If there's more than one node, set the first property to be the next property on the current first, decrease the size by 1, return the value of the removed node. So you could pause it if you want to implement this on your own, but again, these two are very similar to shift and unshift on our singly linked list. We're just using first and last and size instead of head and tail, and we're naming them push and pop. Okay, so pop. First, we're going to check, what was that? If the list is empty. So I'm going to do if not this dot first. If that's the case, return null. That means there's nothing to return. We're done. Or there's nothing in the stack to pop. Otherwise, I'm going to take, I'll call it temp, set that equal to first. This is what we'll return at the very end. And I'll actually do that now. Return temp.val, or value. So we're returning the value at the end. But along the way, we need to patch things together. So we want to check if there's only one node, meaning if this dot first equals this dot last, what do we want to do? This dot last equals null. And that's just an edge case. When there's only one thing left in there, we need to make sure we're also updating last, because on this next step, we're going to update first. This dot first equals this dot first dot next. So we needed to do this beforehand. If it's the last thing in this list or in this stack, we need to make sure that last is null, so that when we do this dot first equals this dot first dot next, we're setting first to be null as well. But in the case of this example where we have 3 things in our stack, we're not going to change last to be null. Instead, we're just updating first. And then the only other thing, we need to decrement size. So this dot size minus minus, just like that. And we should be good to go. Let's test it out. So let's make a new stack. Var stack equals, no, that's not supposed to happen. I thought it was going to autocomplete for me. Stack.push. Let's do first like this, second and third. Sorry, my cat is making a lot of noise over there. What are you doing? And then we'll do stack.pop. We should get third, and then second, and then first, and now nothing. And we have successfully implemented a stack. So hopefully you did watch the singly linked list section. Otherwise, this would be a complete whirlwind, and that's not my intent. You're not supposed to see this unless you went through that first section, because there's a lot of stuff here that I'm not explaining. Anyway, so just to reiterate why we did it this way, rather than using push and pop that we already wrote for a singly linked list, just to reiterate, remember, if we're adding to the end and removing from the end, it's not constant time to remove from the end, because we had to iterate the entire list to get to the second to last item to set that to be the new tail. And a stack is supposed to be constant time, so we're adding and removing from the beginning of our list, but we're calling it push and pop because it is a stack. All right, so the last thing we'll do is quickly talk about the big O of stacks. And all that really matters are these first two, insertion and removal. So the way that we wrote our stack class was to make sure that pushing and popping were both constant time. That's kind of the one thing you have to care about in a stack. Searching, accessing individual items using like an index or position, that is not important at all. And if it is, you probably want to use an array or some other data structure that's going to give you faster access. So a stack is really prioritizing insertion and removal. And the way that we implemented ours, if you wanted to search for something, you'd have to start at the beginning and just traverse the entire stack, .next, 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 which would give us O of n. Insertion and removal, though, because we're adding to the beginning and removing from the beginning, we don't have to iterate over the list or the stack. We don't have to, look for anything. We just jump right to the start, and that means constant time. And lastly, to recap, stacks are a last in, first out, LIFO data structure, where the last value in is always the first one out. They're used to handle function invocations like the call stack. We've seen that. They're also used for operations like undo and redo, for routing, your page history, where you've been in your browser, and a whole bunch more. And they're not a built-in data structure in JavaScript. In some languages they are, but JavaScript is not one of those. But they're pretty quick or easy to implement. And like I said in this video, or in the last video, you'll see me use an array to implement a stack because it's shorter. We don't have to use all of this code here. It's not that bad. But when we're doing these more complicated algorithms later on where we need to use a stack, I've already recorded them, so I definitely will be using an array. But this is the preferred way of creating a stack. If you are using it for tons and tons of data, there's no reason to use an array to store 10,000 items. If you're only accessing using push and pop or shift and unshift, there's no reason to do that. Just to use a custom class like this. So that's stacks. Next up, queues. All right, so we're moving on from stacks to talk about a similar sister data structure called the queue. These two are often taught together They're often grouped into one section just like they are in this very course, stacks and queues. So before we get into the details, quickly define our objectives. Define what a queue is, understand use cases and examples of where they're used, and then implement our own queue data structure, just like we did with stacks. So what is a queue? Well, it's very similar to a stack in the sense that it's a data structure that you add data in and you remove data out, and those are really the only two operations, adding and removing. However, the order is different. Instead of last in, first out for a stack, LIFO, this is a FIFO data structure, first in, first out. So the name queue, just like with stacks, where I said think of a stack of paper or books on your desk, with a queue, think of a line, a queue. What a lot of people around the world would say, in the US, we'd say we're waiting in line, but lots of places say forming a queue. So a queue, like at Disneyland, or you're waiting for, I don't know, getting on an airplane or something, the first person in line is the first person out. The first piece of data in a queue is the first thing out. And these have uses all over the place. Waiting in line, humans, we do that all the time. It's a miserable experience for most people. But in programming in our computers, that are also really commonly used. If you've ever played a video game where you're waiting to join a game, like it's an online game, there's usually some queue structure keeping track of who's been waiting the longest, who's going to get added into the game first. Also, background tasks on your computer. Anytime you're uploading or downloading something, if you click you download one file and it takes a while, and you go to download another file, if they're the exact same size, the first thing that was added in is going to be processed first. Or if you're uploading something, usually the first thing that you start to upload is going to finish first. However, that's a little tricky because there's different file sizes and some things will upload or download much faster. So a better example is a print queue. So if you go and print 10 different things, a printer can only handle one thing at a time. So unlike uploading or downloading where things could be happening concurrently, when we're talking about printing, you print one page at a time, one project. So there's a queue. If, like at a public library, 20 people try and print their essays the last night before they're due, whoever's hit print first is going to be processed first. If we used a stack instead of a queue, that would be disastrous. If we did last in, first out, that would reward people who waited until the very, very end. So they're used all over the place. It's a FIFO, first in, first out data structure. And just like before, we can implement them with an array, or we could implement our own queue class. And we're going to do both. And just like before as well, I'm going to mention that in later algorithms that we learn, we'll be using queues. We'll also be using stacks. And we could use the classes that I'm going to show. We already showed the stack class, but to keep it short and simple, I'll be using an array. But that doesn't mean that it's better to use an array. It might be simpler or shorter. Definitely doesn't require as much work on our end. But it's definitely worthwhile knowing how to implement your own queue class because it's lighter weight. We don't have to worry about all the extra garbage we get when we use an array. So next, I am going to show you how to model a queue, or I shouldn't say model. It is a queue, to create a queue using an array, and then also how to create our own queue class. So in summation, just like with a stack, there's more than one way to implement a queue. It's not, rigid. There are as many different implementations. The only rules governing it is that the first thing added in is the first thing removed. So we need an interface to add something in, usually called enqueue, ENQ, and then a way to remove something usually called dequeue, DEQ. And that's really it. So in the next few videos, I'll show you two different ways of meeting those requirements. All right, welcome back. Let's quickly talk about building a queue with an array. So this is the easy way. So all we would really need to do is create a variable. I'll just call mine Q, like the letter, instead of QUEUE. I think that's how you spell it. So it's an empty array. And there's at least two ways of doing this, really. We can add to the beginning or add to the end. So let's just pick one. Let's say that we're going to start by adding to the end of the array. So we could use push, right? So let's push first and a couple more. Let's do second and surprise, we'll do third. All right. So the array looks like this. So for this to work or operate as a true queue, we need a way to remove first, second, and third. So we want to remove from the beginning. So pop is not what we want. If we were doing a stack, then that would work. Instead, we need to remove from the beginning with shift. And we get first, second, and then third. So that's one way of creating a queue. And it's super easy, right? Of course, one thing that's not great when we do this is if we had 10,000 items in there, they each have an index, and removing from the beginning means that every single item is re-indexed. So adding to the end of the array doesn't require re-indexing anything. It just means indexing the new item at the very end. But removing from the beginning shifts everything over. So what if we did this instead? If we look at queue, it's empty. So let's do unshift. Let's add to the beginning. So we'll do first again, and second, and third. Very exciting. So if we look at queue, it now looks like this. And then to remove, following the rules of a queue, first in, first out, we would need to pop from the end. So we get first, second, and third. So those two pairs, we could do unshift combined with pop, or we could do push combined with shift. Both are going to give us that desired queue functionality, first in, first out. However, in the second case, if we think about how it's working, as we grow this to 10,000 items, if we're adding to the beginning, every time we insert, that means re-indexing the entire queue, which also is not good because that means shifting everything over, giving a new index to, if we have 10,000 items, that means reassigning every single item. Popping from the end works well. So unlike when we talked about stacks, you could use push and pop to make a stack, and you would never need to re-index the entire thing, the entire array. Unlike that, when we do a queue, there's no way around it using an array. So it definitely makes sense to create your own queue class if you're really concerned about performance. Like I said, I will be using an array to illustrate or to create a queue for us in some of the more complicated algorithms later on to keep my code short, but it's not ideal. In the next video, I'll show you how to use a linked list based queue to define our own queue class, which will perform better than this. But this technically is a queue. We have a way of adding and removing in a first in, first out functionality. Anyway, you can do it with an array. Next, we'll do it from scratch. All right, welcome back. So in this video, we'll define our own queue data structure from scratch instead of using an array. And just like we did with the stack data structure, it's going to be based off of a linked list. So hopefully you made it through the singly linked list section. I'm going to go through this pretty quickly. So if you didn't watch that, if you didn't kind of understand that code, some of this might be confusing. So I recommend you do that first. So we'll have a queue class, a first and a last, and a size property, just like with our stack, and then a node class for each element in the queue that will have a value and a next pointer. So quickly, to refresh your memory on a linked list, what we could do, just like with an array, we have two sort of pairs of options. We can add to the end and remove from the beginning, or we could add to the beginning and remove from the end, right? So we could, for example, if let's do an insert at the very end, insert 80, there we go, and we keep inserting, let's insert again, 54. The first thing that should be removed is the first thing that was inserted in a queue. So that would be over here. So then we would remove from the beginning, just like this. So that's one option. The other option is to switch it and add to the beginning. So we'd insert at the beginning like 99 right there, and then remove from the end, which theoretically would be the first thing added in. Although in this case, because it isn't, because we were doing it backwards. But if we kept inserting, the list would grow, or the stack grows this way. So this should be the first thing added in. And if I remove from there, from the tail, oh no, look at how slow this is. So this is the exact same thing we encountered in the stack video, where in a singly linked list, removing from the very end using pop is slow, because we have to iterate over the entire list. Let's do it one more time. Remove from the end. Not good. So what we're going to do instead of this is to add to the end and remove from the beginning. So it looks more like this. So our methods are going, instead of push and pop, which is what they are for a stack, the terminology is enqueue and dequeue. So if this is our queue, when we add, I just clicked dequeue. accidentally. So you could see it was removed from the beginning. But when we enqueue something, it's added to the end. So it's pushed on. If we're going with a singly linked list, we would call this push. We're adding to the end. And when we dequeue, we're removing from the beginning, which we would call shift. But because it's a queue, we're going with enqueue and dequeue. So this is our idea. It's a singly linked list, or it looks like one, but it has these two methods. So we add to the end to the tail, and we remove from the head. So let's do that now. Here's the classes that we'll go with. I'm going to start by defining those two classes, and then we'll add the two methods. So I made a new snippet, and I'll fast forward through my definition of the node class. All right, so we have node, takes a value in, we set the value to be that value, and then this.next is null by default. Now I'll quickly define the basic skeleton of the queue class. And it just has a constructor, it takes nothing. And we have a first, which is null, we have a last, which is null, and then a size. And now we just have to add our two simple methods. So we'll have enqueue, which accepts a value. So I'll just call it val. And then we have dequeue, which doesn't. I hate having to type that. I hope oh my gosh, U-E-U-E. There we go. And this should return the first thing that was added in. So this should add something in, and then this will return and remove the first thing that was added in. I'm not very good about, I'm not explaining it in a good way. Anyway, so this will add to the very end of our linked list. This will remove from the beginning. So let's start by enqueuing. So if we look at the pseudocode, our function accepts a value. We've done that. Create a new node using the value passed in. And then if there are no nodes in the queue, set this node to be the first and last property. So that's not all of it, but let's just start by creating the new node. So var new node equals new node with that val that was passed in. Cool. And then we're going to check if there's nothing in the queue. So we could check if size is 0 or if there is no this dot first. In that case, we set this dot first equals new node, this dot last equals new node. So this is our edge case if it's an empty queue. So we set the first and last to be that new node. Otherwise, set the next property on the current last to be the new node, and then move the last pointer to be that new node at the end. So basically add it to the end. So that looks like this, else, and this is identical other than first and last and size. You could replace that with push on our singly linked list. We're adding to the end. We just used head and tail and length. So it's the same logic. So otherwise, this dot last, so the very end, dot next, is now equal to new node. And then we just say this dot last equals that new node. So we've moved over that pointer. So we're now looking at the end. And then finally, we're going to increment the size of the queue by 1 and return that. So I'll do return plus plus this dot size. Okay. And then we'll move on to dequeue. And dequeue should remove from the beginning in order to give us the to give us the first thing added in. We're adding to the end, removing from the beginning. So dequeue looks like this. We define the function, it takes no arguments. If there is no first property, just return null. Store the first property in a variable. This is identical to what we did in the stack section, or the stack part of this section. So it's very, very similar. And let's just get going on it, honestly. So dequeue, we're going to start by checking if it's empty. So if there is no this dot first, return null. That means that there's nothing in our queue. Otherwise, we'll make a variable called temp to store the current this dot first. This is what we'll return at the very end. And then we'll just do our exact same logic. So if this dot first is equal to this dot last, we're going to set this dot last equal to null. Otherwise, actually not even otherwise, but just this dot first. So that's our edge case. If there's only one thing left in there, we set the last item to be null. Then we're going to take this dot first at the beginning and update it to be the next item. So whatever used to be there, for example, if this is the current this.first, we're now going to say this.first.next is now this.first. And then the only other thing we need to do is decrease the size by 1 and return the value of the node. So that's going to be this.size minus minus, and then return temp.value. And that should be it. And if we look at this deque and compare it to our stack, which it was called pop, but it's the same idea, the code is identical. Did I even use the same variable name, temp? Yeah, it should be exactly the same. And that's correct. That's how it should be. The way that we're implementing our queue, we are removing from the beginning. Same thing we did with our stack. It's just that in our stack, we are also adding to the beginning. In our queue, we're adding to the end. And we called it deque instead of pop, enqueue instead of push. Anyway, so let's test this baby out. Let's run our code. I don't know why let's run the code and let's make a queue. I'll just call it new queue like that. And then we'll do an enqueue first. Whoop. What's going on here? It looks like, I have a problem. This.first, or this.size needs to be set to 0. So we'll do var queue equals new queue, and then do queue.enqueue first. That looks like it's working. Second and third. And then we'll do a queue.deque, which should give me the first thing added in, which is first, and then second, then third, and now it should always give me null. And first and last are set to null, size is back to 0. So I can now enqueue something else like hello, and then I can deque hello again, and everything should be happy. And that is our queue. So this queue can grow super large. There's no indexing. There's no problems that we'll encounter. It's constant time for every operation, which is really just adding in and removing. And it is first in, first out. FIFO, FIFO. I don't know what the official pronunciation is. And that is in comparison to a stack, which is LIFO or LIFO, last in, first out. So they're very similar, but also extremely different in how they actually behave. They're similar in the fact that there's two operations, adding and removing. You put something in, you get something out. It's just that the orders are totally different. Okay, so in the next video, I'll wrap everything up, stacks and queues, talk about big O notation, and just summarize it all. Hopefully this makes sense. If you saw the singly linked list section, this is extremely similar. We just put a different wrapper on it, called things a little bit different names, but otherwise it's the same functionality, just slimmed down. All right, so that's it for queues. Really quick, the big O notation should be constant time insertion and removal. That's the only thing that matters. Searching and accessing, it's not something that you really do with a queue. Otherwise, you may not want to use a queue data structure if you need to prioritize searching. Generally, all you care about is adding things in with enqueue, removing things with deque. You want that to be super fast. So with our implementation, it is constant time. Note that when we used an array, it was not constant time because in both iterations or both solutions that we used or that we came up with using the built-in array methods, there was a cascade of re-indexing. So that does not lead to constant time. That's O of n, linear time. That's not what we want. We want constant time. And this is the same for stacks. Stacks and queues, two structures, add things in, remove them, different orders in how they actually work, but both adding and removing should be constant time, O of 1. So to recap on queues, they are first in, first out. Just like at an airport, first person in is the first person out, unless you're selected for additional screening, in which case you might be the last one out. But usually, first person in line gets out first. Contrast that with a stack. First thing in is the last thing out. So queues are used often. Anytime you need to keep track of an order and maintain that order, so that the first thing in, like a print queue, that's a classic example, the first thing that someone tries to print is the first thing actually printed. And then anything else that piles up is kept in the order that it was added in, and then we remove or we print the things that have been waiting the longest. Okay? So useful for processing tasks and also are foundational for other more complex algorithms and data structures that we'll see later on. As I mentioned, we will be using stacks and queues later in the course to help us implement more complicated data structures and algorithms. So they are not just a novelty to show you, they will be resurfacing. And like I said, insertion and removal needs to be. So I said it can be done in constant time. In a good stack, in a good queue, it has to be. Otherwise, it's just a waste. Why even use a stack or a queue? Anyway, that's it for stacks and queues. Very similar in a lot of ways. Adding and removing things, constant time, very different in the order. First in, first out for a queue, last in, first out for a stack. Okay, see ya in the next section. Hey, welcome back. So we have a brand new section here on a brand new, exciting, hopefully exciting, data structure, trees. So trees, aside from being everyone's favorite perennial plant, are also a classic data structure. They're taught in computer science classes around the world. They're also very commonly used all around the world. So they are a bit of a step up from linked lists, a little more complicated, but also maybe a little more interesting. So quickly, let's run through our objectives. We want to define what a tree is, compare and contrast trees with linked lists and arrays and things like that. Explain the differences between, there's different types of trees that we're going to talk about. Just plain old trees, then binary trees, and then finally binary search trees. And binary search trees is what this section is really focused on. But we're going to talk about these three categories. And then most of what we'll be doing is implementing a bunch of operations on binary search trees. So we'll define our own BST, binary search tree. I'm just going to say BST from here on out. Our own BST class and add a bunch of methods like we did with a singly linked list or a doubly linked list. But first, we have to talk about what a tree is. So trees are data structures that consist of nodes, just like a linked list did, but they are in a parent-child relationship, hopefully consensual. We basically end up with branches. So from one node, we can have it connect to one other node, or 2 or 3 or 10 or 0 nodes. But we end up with these branching structures, hence the name tree. Think of an actual tree. We follow a branch and it splits at some point, and then that branch can split and they can keep splitting, and we end up with all these different little branches off of this main original branch. Now often when we see diagrams, they look more like this, where they're top down rather than a tree which grows from the ground up. It doesn't matter, right? It's the same exact structure, it's just flipped. But usually we'll see them represented like this. So here is an example of a tree. Each one of these circles represents a node, just like it did on our linked list. But notice this is very different than a linked list in that each node can point to more than one, or can have more than one reference to another node. So this is our topmost node. We'll go over the terminology, but this is called the root, and it points to 9 as another node. It also references 12 and 8 and 99 and 10. And each of those nodes potentially references one or more other nodes, or actually 0 in this case. This is a dead end. Nothing comes after. 12 has 1, 2, 3 children. 99 has 2 children. 10 has 2 children, and so on. So this is an example of a tree, but they're not always like this. We might have a tree that looks like this. We have a single topmost node, and it branches off into 2 nodes. And then each of those only branches off into 1 node. So it doesn't have to be this nasty, complicated mess. It can be simple. This is also another example of a tree. And, it doesn't have to be numbers. We can, just like a linked list, we can store data in there. We can store strings, or, if you wanted to, you could store anything, arrays, or I don't know. What would you want to put there? Most of the time it's numbers and strings, but it could be anything. So when we talk about lists are linear. It's one thing, and then the next, then the next, then the next, then the next. Everything is in a line, in a row. Trees are non-linear. They can branch. We can have more than one pathway through a tree. With a linked list, there's one path. In a doubly linked list, you could work backwards or forwards, but still there's one line through our data structure. In trees, there's many different paths we could take. Just like the journey of life, right? You end up here, if this is a decision you have to make, you could make one choice and go this way. And if you do make that choice, you'll never know what was over here. And then you make another choice, right? This is one path here. This is another path. This is another path. With a linked list, there's only one pathway through. So you can think of a singly linked list as a very special case of a tree. So this could be a tree. It's not a great use for a tree, but if we had this 2 pointing to 12, which points to its child 11, you could represent that as a linked list, 2 to 12 to 11. but you probably wouldn't do that. You would probably just use a linked list if this is what your data looked like. But I just wanted to show that this is a special case. But as soon as we added a second branch here or here, it's not a linked list as soon as it becomes nonlinear. Now, when we're talking about trees, there are some rules. So this is not a tree. So what we have here are nodes that are referencing other nodes that are not below them, if that makes sense. They're not children. So a node can only point to a child. It's a parent-child relationship. We can't have a child pointing to a parent. We can't have a node pointing to a sibling. We can't have what's going on here. This is actually what's known as a graph. We'll talk about these later. A tree, every node is moving away from the root node, if that makes sense. All these arrows have to point down if we were trying to represent it. So this is also not a tree. It looks like it could be because all the nodes are pointing away from the root, but there is no one root. We have two beginnings of this tree. So that's not a tree. We need to have one entry point. So as I mentioned, there is some terminology. The root is the top node in a tree. So if we go back to this tree, this is the root. A child is a node directly connected to another node when moving away from the root. A parent, it's the converse notion of a child. I think those two make sense. Siblings are nodes that have the same parent. A leaf is a node with no children on this tree. This is a leaf. It has no children. It's also a child of this node. This is the parent of this node. This is the root. And lastly, there's terminology for the connection, which we call an edge. It's the actual arrow between one node and another, or at least in my diagrams, it's an arrow. Okay, so we have root. This is an edge. This is a child relative to this parent, but it's a parent relative to this child. This is also a leaf. It has no children, and I think that's all the terminology, right? Edge, yeah, I covered it all. Okay, so that's basic terminology. It's just helpful for us to discuss when we're implementing code. I'll say something like, all right, we need to, add the edge from this parent to this child. Or I might say, let's check if a node is the root or if it's a leaf and so on. Okay, so we'll leave off here. Next, I'm going to talk about some real applications of trees, and we'll also introduce binary trees and binary search trees in the next video. All right, welcome back. Next, what I'd like to do is quickly run through some real-world use cases for trees. These aren't just theoretical things. This isn't just about, interview prep. Trees are used all the time. Even if you're not fully conscious of it, you've interacted with trees, both as a JavaScript developer most likely, but then also just as a user of the internet. So the most common example is HTML and the DOM, the document object model. So when we think about HTML, it lends itself to a tree-like structure, right? We have elements, and inside of elements, we can have nested elements that are children. And we can keep having children nested and nested and nested further down. And it's a parent-child relationship between those HTML elements, which are just text. But then once it gets to the browser, after a request, we get the response. The browser then reads through it all, parses it, and it creates the DOM, the document object model. And in Chrome, we get this nice debugger. We can click through, sort of an interactive way of viewing the different nodes. But behind the scenes, there is a corresponding JavaScript object for each one of these nodes. So there's a body. We can access it just by typing document.body. And it prints text for us here, but it's actually an object. And if we do dot, we can see it has a bunch of properties, a bunch of methods we can call. And we can do things like look at its children. And it gives us a list of children. So let's take the first thing in there. That gives us a node, and we can do dot children on that. And is it just one thing in there? Yeah, it looks like there's just one child div inside of that first child. Anyway, if you're not familiar with the DOM, I wouldn't worry about it. Just know that it's a tree structure, very, very commonly used one. So another application has to do with network routing. Definitely not my expertise. I'm not even going to try and explain how it works, but if you go to the routing page in Wikipedia, we get all sorts of diagrams of trees over here. So these are different delivery schemes for how basically a message is transmitted to a node or to multiple nodes. And you can see that we've got some tree structures going on here. And that's pretty much all I'll say about that because I know nothing about network routing. But behind the scenes, there are some trees being used. There's a bunch of classic computer science logic that goes into finding the shortest path. Anyways, next up, we'll talk about abstract syntax trees. So these are a way of describing the syntax of a programming language using a tree structure. So without going into too much detail, it really doesn't matter. Honestly, all that matters is that you see that this is a tree structure. Whatever language this is for, it's from Wikipedia if you do want to read more about it. We have, let's say, a while loop. Inside of a while block, we have a condition as part of the while. And then we also have the body inside of that while. And in that condition, we can have a comparison between a variable and a constant. And this is a very succinct, shortened version. It's missing a lot of logic. But the point is to show you that this is a way of, basically, if you were writing code to take in other code and run that code, or to parse that code, or to make sure it's valid syntax, you could use an abstract syntax tree to help you out. Next, trees are used in artificial intelligence all the time. There are tons of applications for trees in artificial intelligence and machine learning. Probably the simplest example is something called a minimax tree. So let's say we're building a tic-tac-toe game. We want to build an AI that is very good, that isn't just picking random moves. We could basically break down the logic of the game into a tree. And we basically would say, here's a given state of the board, and these are all the possible moves that the human player could make. They are O, the computer is X. And what we see here is, okay, if the human player plays an O here, the best possible move to make is to put an X right here. And in that way, X would win. If an O goes here, the best possible move is to put an X in the middle. And then it depends what O does next. There's multiple options. Basically, this tree structure just describes a bunch of different possible options for what could happen. And after a given move by the opponent, the best possible next move. So that's a really superficial, we didn't even scratch the surface of how you actually implement this and what the mini-max part is of the logic. But all that I want to show you is that this is basically called a decision tree. You have different decisions that you make, branching points, and you follow one, and then that splits, and you follow the next decision, and you keep going. And these have applications in very complicated classification algorithms, for example, not just tic-tac-toe AI. And then finally, probably the simplest example is the way that your folders are modeled in an operating system. If you see something like this on a Mac or a PC, your computer is represented as a tree structure. There's all these directories. It's hierarchical. There's a root. There is a topmost folder. On a Mac, I actually don't know what it is anymore. On your account, it's the root directory, but there's multiple accounts you can have on a computer. Anyways, it doesn't matter. But let's just say we're looking at a given folder. This folder inside, this is maybe our root. We have two other folders inside, and then they have files. And technically, this has like two types of nodes, you could say. There's files and folders, but the structure itself is tree-like. We have all these branches, and those children have children of their own, and so on. So that's just a quick introduction to some of the real-world use cases for trees. I assure you, though, this is not, purely theoretical thing. It's not just an exercise. This is stuff that comes up all the time in programming. One example I totally forgot to mention is JSON. So if you've ever worked with JSON, JavaScript object notation, you're getting, an AJAX call, you're sending in a request, and you're getting some data from an API. When you parse that response from a string into JavaScript, or if you're using Python or whatever language you're using, there's code that is traversing a tree or creating a tree-like structure. As we can see here, I'm using a Chrome extension just to view some child nodes, and they each have children, and this is a tree structure. You could represent this easily. Well, I shouldn't say easily. It suits itself to being represented by a tree. It's a lot of work, but it still is a tree structure where we have parents and child nodes, but there's, at the end of the day, a single root. All right, I'll leave it off there. There's a lot of different uses for trees. Welcome back. So much like the real world, where we have tons and tons of varieties, types of trees, we've got different categories of trees, we've got families. I'm not a botanist. I do like trees, though, but there are many, many types, and we can enjoy them all out in the world. Anyway, in the world of computer science, the data structure of the tree, there are many varieties as well. So actually on Wikipedia, there's an article that contains a list. I don't know if it's complete, but this, from here on out, I'm going to scroll through. These are all varieties of trees, all different types. So they all follow the same rule defined by, they fit the pattern of a tree, but they all add in some special properties, some rules, basically something that makes them a bit different. And often, some of them will be much faster at searching or insertion of a particular thing, or they excel at storing data in a particular format, or data that is, contains a lot of duplicates, or data that's all unique. they all, I mean, I haven't heard of the majority is not even a good way of putting it. I haven't heard of like 95% of these. There's some very niche trees here. And you can see also there are different categories of trees, like heaps. Oh dear, I don't know if you can hear that. My cats, hang on. Hey, come on girls, what are you doing? Sorry about that. Where was I? There are many types of trees in different categories, different groupings, like heaps, which we'll learn about later. What we're going to talk about in this video, mainly, are binary trees. So one group. Sort of like, you could think of in geometry, there's this thing called a polygon, just any shape. Well, I guess not any shape. Any sided shape, where there's n number of sides. And within that, we have quadrilaterals. That's one family, just like this is a family. And then we have triangles, another family. And within that, we could have, within quadrilaterals, there's rectangles and trapezoids. And that's about as far as my geometry goes at this point. So the trees that we're going to focus on are trees in general. We've already kind of laid that out. But more specifically, binary trees. And even more specifically, binary search trees. So binary search trees are a special type of a binary tree, which is a special type of a tree. And they excel, as you can imagine from the title, at searching. So we store sorted data in a particular way, we'll get there in just a moment, in a binary search tree, which makes it easier to retrieve. Let's just recap. This is just a generic tree. Each node could have any number of child nodes. We've got, this one has 4 children, 1, 2, 3, 4. This one has 0 children. This one has 3. This one has 2. This one has 1. There's no real rules about how many. A binary tree, on the other hand, has a special condition. Each node can have at most 2 children. That's the binary part. So it could have 0 children, can have 1 child, and it can have 2 children. So our root node usually would have 2, and then each node could have 2, or it could have 1, or it could have 0. But it can't have 3, for example. This is not a binary tree. This is a valid tree in general, if we're just talking about a generic tree, but it is not a binary tree. And there are also, I've heard of ternary trees where there's 3, at most each node can have 3 children. I'm sure there are terms for, quadrinary, I don't know, 5, 6, 7, 8, but they're just not as commonly talked about because binary trees have some special properties that make them easier to navigate. And we'll talk about that when we talk about binary search trees, which is actually right now. So binary search trees are a special case of a binary tree, which is its type of a tree. So they are trees. They, at most, have 2 children per node, 0, 1, or 2 children. And on top of that, binary search trees are sorted in a particular way. They are kept in an order. So BSTs, which is what I'll probably say most of the time because binary search tree gets a little bit annoying to say. BSTs are used to store data that can be compared, that is sortable. So often, classically, we're talking about numbers, and that's what we'll be working with. It could be strings. It could be any other piece of data that has some way of, there's a way for you to order it and compare things. Which one is greater? Which one is less? So this is how they work. This is the special magic property. If we take any node on the tree, let's try the root, all numbers or every item that is less than this node is located to the left of it. Every item or number in our case that is greater than is located to the right. And you could repeat that on each child node. So if we look at 6, to the left are the numbers smaller than 6. To the right are the numbers greater than 6, like 8. Or 15 over here, we only have one node, but 20 is greater than 15, so it's located to the right of it. So to review that, a binary search tree is a type of a binary tree. Every parent node has at most 2 children, but on top of that, every node to the left of a parent node is always less than the parent, and every node to the right of a parent node is always greater than the parent. So here's a slightly larger example. We take any node, like the root, all nodes to the left, all of these should be less than 41, and everything to the right is greater than 41. And then we could try that again over here at 20. Everything to the left needs to be less than 20, and it is. Everything to the right is greater than 20. Same thing down to 11, blah, blah, blah. Over here, it's the same exact property. So that's what makes a binary search tree rather than just a binary tree. So that the data is kept in a particular order. Every node, every child to the right is greater than a parent node, and every piece of data to the left is less than the parent node. So quick pop quiz here. Is this a valid binary search tree? with these pieces of data, these numbers? Take a look, pause it if you need a little extra time. The answer is no. So what's the problem here? Well, if we look on this node 8, to the left, 3 is indeed smaller than 8, but 6 is larger than 8. So that is not good. That's invalid. How about this one? Is this valid? Well, hopefully you can tell right off the bat. The answer is nope. And it doesn't matter what the actual numbers are because this root node has 3 children. So it's not a binary tree anymore. So out of the question. Unforgivable. Next, here's a slightly larger one. Is this a valid binary search tree? Take a moment, think about it. And the answer is nope, once again. And the problem area is right here. So we have 3, and to the right, we have 6. So 6 is larger than 3, that's okay. But to the left, we have 4. 4 is greater than 3, and everything to the left has to be smaller than 3. So invalid. So 3 invalid trees for different reasons. The last thing I'd like to do before we actually dive into coding one up in the next video is explain why these are used. And really the way that we order them, where everything to the right is greater than the parent and everything to the left is less than the parent, makes it very easy, it makes it fast to look things up. Also, it makes it easy to insert things, to find a place for a node. So that search part of the binary search tree becomes very quick compared to looking for a node in an unsorted tree. So let me show you how it works. Imagine we have this tree and we're looking for the number 72. All that we have to start is the root. So we don't actually see, like our code doesn't know what's lying ahead. It just sees the root. All that we have to do is check, all right, is 72 greater than 41? Yes. So we only care about this half of the tree. Basically, every comparison we do should roughly chop in half the number of values we look at. If you remember how binary search worked in a list, it's the same idea, where we have this data sorted, where everything to the right is greater, everything to the left is smaller or less than, and we make a comparison. Ideally, we chop the tree in half. Now, it depends on how the tree is distributed. We could have way more values over here and very few small values, but in general, on average, we cut the number of comparisons or the number of nodes in half. So we check. 72 is greater than 41, so we only care about this side. So then we go to 65. Is 72 less than or greater than? It's greater than 65, so we go over here. Now we get to 91. Is 72 less than or greater than 91? It's less than, and we found it. Now, if you compare that to if this was an unsorted tree and 72 was indeed in the tree, it could be anywhere in this tree, and we might have to look at every single node and traverse the entire tree. And we'll talk about how you would do that. But, you could pick any order. Do you go all the way here first, and then here, and then here, and then down here? Do you go to the right first? There's a million ways. Well, there's not a million, but there's many ways of traversing a tree. But with a binary search tree, when we're looking for a value, there's a very specific procedure we follow. We compare, and we go to the right or the left. We compare again, and we cut it in half. Keep going until you find the value, or you don't find it. But because the way a binary search tree works, that value is not in there if you don't find it. Okay, so to recap here, there's many types of trees. There are binary trees, where each parent or each node can have at most 2 children. There are many types of binary trees, one of which is the binary search tree. A binary search tree works for sorted data or sortable data, where there's an order. You can compare things. And it's the same rule as a binary tree. Every parent node has at most 2 children. But on top of that, every node to the left of a parent is always less than the parent. Every node to the right is always greater than the parent. And that makes it so that we can search, we can find things much faster. Welcome back. In this video, I just want to get us set up with our basic skeleton, our 2 classes. So we'll have a binary search tree class and then a node class, just like we did with a linked list. We had the linked list class and then a node. So a binary search tree itself really only has one important property, which is the root. And then each node has a value, but instead of having a .next or a .previous, we have a left and a right. So I'll quickly code this up. I'll fast forward through some of it. So our constructor takes a single value in, and we just set this .value equals value, and then this .right. I like to do the left first. I don't know why. And this .right. It doesn't matter at all. Okay, so that's our single node. Now we'll just make our binary search tree. You could just do BST if you prefer. And inside of that, we'll have our constructor. It doesn't take anything. You could have it take an initial value and like create the node if you wanted to, but we won't do that. And we'll just do this dot root equals null. Now with this, we could construct our own basic BST. I could say, var tree equals binary search tree. Oops, I need to say new binary search tree. And then we could do tree.root equals new node, let's say with the value of 10. And then we could manually say tree.root.right equals new node, so it needs to be greater than 10, let's say 15. Tree.root.left equals new node of, what's something less than 10? How about 7? And we could keep going. I'll just do one more level. Let's do tree.root.left.right. So this needs to be less than 15 because it's to the left of it, but it also needs to be greater than 7. So let's say, it needs to be less than 10 and greater than 7. So let's go with 8, actually 9. I like odd numbers. And this sets up a simple binary search tree, although it's a huge pain to insert things like this. So just like we did with a singly and doubly linked list, what we're going to add is a method called insert, and it will figure out where something goes based off of comparisons. Oh, this needs to be new node 9. Not sure what I was doing there. Let's run it and just make sure it works. If we look at our tree, okay, we've got tree.root. I mean, there's not much for us to really check at this point, but we have some nodes that are connected. Each node has a value, a left and a right. Okay, in the next video, I'll explain how insert should work, and then we'll get coding. Welcome back. So now let's add a way of inserting into our tree. So we have a value. I should be able to call insert, pass in the value, and the tree will add it to the correct place. It will make the new node and then put it in the correct spot depending on what that number is. So for example, if we were trying to insert 13, where would that go on this list? Well, we would start and we would check, how does 13 compare to 10? Well, it's greater than 10, so it goes over here somewhere. How does it compare to 15? Well, it's less than, so is there a node to the left? If not, that's where 13 goes. If there is a node, then we go to that one and we check, how does it compare to 13? Do we go to the left or the right? But there is no node, so that means this is 13's new home. Or on a slightly larger scale, if we did an insert of, 68, I'll pause it. First we check, is there a root? If there's no root, then that becomes our root. But there is, so we compare 68 to 41. And it is greater than 41, so we check, well, is there a right? Is there a node over here? And there is. So we compare 65 now to 68. Well, 68 is still greater. So we're going to go to the right again. And now we compare 91 and 68. Well, 68 is less than 91. So we go to the left and we do it again. We compare it to 72. Well, 68 is less than 72. Is there a left? No, there is not. So that means this is where 68 goes. That is its new home. So those are the steps that we follow. And if you want, here's the pseudocode. You can do this iteratively or recursively. I think it's easiest to do it personally iteratively, but either one will work. The rough outline, you don't have to follow this order exactly, verbatim. You don't have to create a new node on line 1. But at some point, you create a new node. And then you start at the root. You check if there is a root. If there's not, well, that's super easy. You're lucky. The root now becomes that new node. That just means we have an empty tree the very first time we insert something. But if there is a root, you check if the value of the new node is greater than or less than the value of the root. And depending on that, if it is greater, we check to see if there is a node to the right. If there is, move to that node and repeat the steps. So have some sort of loop, right? A while loop. I would just do like while true. Have something continue to go, if you're doing it iteratively at least. And inside of that, you're just going to check if it's greater, then move on to the next dot right, and then check if you're greater or less than that. And eventually, you will find a place to insert it. So the process, just one more time. Check if there's a root. If not, easy. It's an empty tree. Just add it to be the root. If there is a root, compare your new value to see if it's greater than or less than. And if it's greater than, you need to check if there is a node. If there's nothing there, then that is the new home. Same thing if it's less than. You need to check, is there a dot left? If it's not, or if there is no dot left, then that's your new home. Otherwise, you just move on to that dot right and you repeat the steps, or you move on to the dot left and repeat the steps. Just like we saw here. If we try to insert 13, we check, is there a root? Yes. Okay, so 13 is greater than 10. That means we need to check, is there a dot right? Yes. So now this is where we start again, the same process. Is 13 greater than or less than 15? It's less than. So is there a dot left? No. So that is where 13 goes. And then we would return at that point. So I didn't add this in the pseudocode, but I think it's best to return the entire tree at the end of the method. It's not a deal breaker, but that's what I like to do. Instead of just returning nothing or returning the node, and return the entire tree at the very end. All right, so give it a shot. In the next video, I'll have a solution. All right, welcome back. Let's go ahead and write the code for insert. So I have a snippet over here with the same classes I showed you 2 videos ago. We have our node class, value left and right, and then we have our binary search tree, BST class, which just has an empty root to start. Now, I've recorded this video once before, and I was using this sort of basic binary tree structure because it's really hard, honestly, to visualize how this all should look. Like a linked list is easy. You know, you insert something, it should go afterwards, and you end up with this linear list. With a tree, it can be hard to keep track of where things should go. So I recorded the entire video, and then I realized that I had messed up this entire tree. It just doesn't actually make sense, the values that I used. It's not a valid binary tree. So we have 10. On the left side, every value should be less than 10. So that's true. On the right side, every value should be greater than 10. But if we look at 5, to the left, we have values that are less than. To the right, 4 is not greater than. So I should have something like 7 there. Same thing over here. I don't know what I was thinking. 13, to the left of that, 14 does not work. So let's go with 11, for example. And now we have a valid tree. Okay, so let's start by defining insert, which takes a value. And we'll just make that new node to start. So var new node equals new node and pass in the value. And then let's go with the easy win, which is to check, is there a root already? Or is there not a root? Like if we just did tree.insert 10, that becomes the root. There's nothing in there. So we'll just check if this dot root is null. Then we're going to set this dot root to equal the new node, and then return this just so that we get out of this. None of the other code will run because we're returning. I run the code, we look at our tree, we've got 10. Now if I tried to insert something after this, like 3, nothing happens because, well, technically we make a new node, but then we never attach it or insert it. And nothing's returned because this code doesn't run. Okay, so now the bulk of the logic happens in the else portion. So remember the process, if our tree is only 10 right now, this doesn't exist. What we do, we check, is there a root? Well, if there's not a root, then we do this. Otherwise, which is what we have here, the otherwise condition, we need to check, is our value less than or greater than this value right here? And if it's less than, what are we going to do? We're going to check, is there a left? And if there's not, then we put the value right there. Otherwise, same thing on the right side. Now that's the case if there's only one node in there. But if our tree looks like this, let's say we're inserting the number 1. We would check, is there a root? Yes, there is. All right. Is 1 less than 10 or greater than? It's less than. So then we check. We know it goes on the left side. We check, is there a node on the left? If it looks like this, we would put 1 right here. But if it looks like this, well, there is a node here. So then we compare again. Is 1 less than 5? That's true. So we're going to insert it on the left somewhere. Do we insert it right here? Nope. There's already a value there. So then we move down and repeat. So the process involves looping, just like with a linked list. And I'm going to make a variable called current. And current will start as the root. Just like in our linked list examples, current started as this.head, the beginning of the linked list. And we're going to update current as we go. And I'm just going to add in a while true. We're going to continue over and over and over. So unlike with the linked list where we had a length that we could, you could add a length, but it wouldn't help you here. Length isn't even really the right measurement. You could add like a number of nodes or something, but that still doesn't really help you. So I'm just going to loop while true, and I'm going to break out of this loop using a return statement if we insert the node. So while true, basically our process is going to be, check if the value is less than or greater than. So let's do that now. We'll just do if value is less than, and then current.value. If that's the case, that means it's going to go on the left somewhere over here, but we first need to check, is there current.left? So another conditional. If current.left is equal to null, if there is nothing on the left, then we found our spot. Eventually, like if we end up here, this is current. If there's no left and the value is less than this value, then we insert it to the left. Okay, so we'll just say current.left equals new node, and then return. We're done. We don't want this loop to keep going. Now this code will actually work only if we insert like 10 and then 5. It's not going to work if we insert something after that, because if we insert 10, that's all that we have. Then we check if value is less than current.value. Well, if this is current, yes, 5 is less than 10. There is no left, so we've set 5 right here. And if we just verified that, if I run this code and I look at the tree, then we look at the root, and then we look to its left, we have 5. Okay, but it wouldn't work if we tried to insert 2 or 13 or any other value to the right or to the left. So all that we need to do, if it is less than 10 or whatever the root is, but there is already a value here, then we need to move current to now be 5. And then we do the same thing. And if there's already a value to the left or to the right, then we update current to whichever one it should be, and then we check again. So really here, all that we need, nice and short, is just current equals current.left. So we're moving to current.left because the value is less than the current value. So if this is what our tree looks like, and we're trying to insert the number 3, we'd start here. 3 is less than 10, so we know we need to look to the left, but there already is a left. So this part does not run. So we update current to now be 5 and do the same thing. This time there is no left, so we insert right here. Okay, so this is just handling the left side, and we could verify that it worked by inserting like the number 2, for example. If we run this, our tree should have a root of 10. The left of 10 should be 5, and the left of that should be 2. But we have no right set up on any of them. So we just need to basically do the same thing for the right side. So I'll do else if value is greater than current.value. If that's the case, we're going to check if current.right is null. If it is, then we found our spot. Current.right equals new node. Return this. Otherwise, keep looking, or update current so that we traverse further. Current equals current.right. And we should be good to go here. See if I have any typos or any issues. Let's now also insert some other values. So 10, 5, 2. Let's do tree.insert 13. Let's do 11 and 16. And also 7. Okay, let's run this. Here we go. We've got our tree. And what should we explore first? Let's go down the right side this time. So here's our root of 10. And to the right, we should have 13, which we do. To the left, we have 11. And to the right, we have 16. That all looks good. Let's check the left. So on the left, we should have 5. To the left of that, we have 2. To the left of that, we have 7. Let's just verify it still works. Let's say we insert, what about 3? Where should that go? Well, definitely on the left side. And we find 2. It goes to the right of 2. So if we look at tree, and we look at the root, then we look at the left, which is 5. The left is 2. And then the right of that is now 3. So we basically inserted it. This diagram is getting ugly, but we inserted it right there. Okay, so it looks like it's working. Let's see, how does it handle, or does it handle, duplicates? So if I tried to insert 10, for example, what happens? Well, I had to restart my browser, or at least this window, because we hit an infinite loop. And I was trying to illustrate that, but I didn't actually think it through. There was nothing to show you looping infinitely. All that you saw or would have seen is just my computer get hung up. and me being unable to type. So we got an infinite loop because if I tried to insert 10 or any of these numbers that are already in there, we have this while true, but we're only checking if the value is less than or greater than. Now, how we actually handle duplicates is really up to the special case of what we're doing, the specifics. Some people are just going to ignore them. Some trees just ignore them outright. That's what we'll do. We could just add a check in here to see if the value is equal to current.value, then we will just return false or undefined or something. The other option, though, that you might see is if you need to know, like if we're inserting certain things over and over and you want to keep track of that, you could add a frequency or a count to the node and you could increment that. So next to each node, we could have a count like this. And maybe we have 4 16s are in there for some reason and 2 10s. So if you needed that, you could do that. But I'm just going to add an if at the very beginning. If value is equal to current.value, then let's return undefined or something. Undefined. Okay, let's try running this again. We look at our tree. Everything looks good. 10, 5, 2. Okay. Let's try inserting 10 again. We get undefined, and if we look at the tree, it still works. Not that, hopefully nothing should be changed. Everything still works. If we tried to insert something other than 10 that's already in there, like 7, it takes a little bit because it does have to traverse the tree until it finds the right spot and it realizes, oh, this is already in there. Okay, we're done. Lastly, some people get a little up in arms about this. You can simplify some of this logic. There's a couple of else's that are unnecessary. For example, here, if value is less than current.value, we check if there's currently a left and we return. And before I had an else here, but because there's only 2 options and we're returning here, we don't necessarily have to have the else. It's just a stylistic thing. So I have both solutions. This one is a little longer, but it's more explicit about things. So there's else's, same thing here. This else as well, we don't have to have. We're checking if the root is null, return. If it is, we're done. Else, well, we don't have to have the else. We could just start. So that's what I did here. But just tiny changes, really. So if you prefer the solution, you could use this one. It's really the same logic, just slightly less explicit, but also less verbose. All right, welcome back. Next, let's add a method called find or search or whatever you want, contains node. Basically, the idea is that you have a binary tree and you can search to see if a value is in that tree. So you could search to see if 50 is in a tree or 100 is in a tree. And the process is very similar to inserting, in a binary search tree at least, because we have those rules, the greater than to the right, less than to the left. So we can cut about half the tree away each comparison that we make. So for example, when we go to insert a number, like let's say we're inserting 7 into this list. Let's do that quickly. Insert the number 7. All right, we compare it. It's less than. It was very fast. We checked once we got to 11. Was there a left? Nope. Well, that's where 7 goes. Now, if we're doing the same thing, but searching for 7, I'll go slower this time. We do the exact same steps. We check, all right, is this 7? No. So it's less than. Okay. So we need to look on the left. Is this 7? 20 is not 7. So 7 is less than again. So we look on the left. Is this 7? Nope. It's 11, but we know that 7 is less than 11, so we look to the left. And what do you know? We found 7. So we return true or return the node. We're just going to do true or false to see if we found it, if it contains that value. And if we were inserting something that isn't in there, if we're searching for something that's not in there, like let's say we're searching for 75. Go. All right, we start here. Is this equal to 75, the root? Nope. 75 is greater, so it's going to be over here if it's in here on the right side. So we get to the next node. All right, is 75 equal to 65? Nope. It's greater than, so it's going to be over here on the right. Okay, so we look. Now we have 91. Well, 75 is less than 91, so we need to look to the left. Then we get to 72, and now 75 is greater than 72, so we know it needs to be on the right, but there is no right. So that means it's not in here. If we find the point where we basically hit the end of the tree on one branch, and there is no .next, or not .next, there's no right when we're looking for a right, or there's no left when we're looking for a left, that tells us the value is not in there, assuming our tree is set up correctly. I mean, if for some reason 75 was over here incorrectly, of course, we're not going to find it because we're not checking every single node. That's the point of the binary search tree. We know the order that things are stored in. We know how it's structured, so we can take advantage of that and do a much faster search. Okay, so in this case, we would return false or return null, and this is what they're showing. So the basic steps: start at the root, check if there's a root. If not, we're done because there's nothing in there. If there is a root, check the value of the new node, see if it's equal to what we're looking for. If you found it, then we're done. If not, check to see if the value is greater than or less than. If it's greater, look to see if there's something to the right. If there is, move to that node and repeat the same steps. If there's not, that means that we're done. Same thing on the left. So I'll walk through it one more time. If you feel good to go, try and implement it on your own. It's very similar to what we did in the last video with insert. It's just actually a little simpler. Let's say that we're searching for 40. We're going to start here, 41. All right, 40 is less than 41. So we look to the left. We get to 20. Well, 40 is greater than 20. We check, is there something to the right? Yes. So then we start the loop over. Is 40 equal to 29? No. So we check, it's greater than. So is there a dot right? Yes. So we move down here and start the loop over. Is 40 equal to 32? Nope. So then we check, is there something to the right because 40 is greater than 32? No, there's not. That means we didn't find it. We return false. So those are the basic steps. Go ahead. You don't have to follow this pseudocode to the T. It doesn't contain every bit of information. For example, we want to have probably a while loop. And I would make a variable called found and a variable called current or start or some sort of variable to keep track of where you are, and then a variable that you'll set to true or false that will stop the loop. So when you find it, the loop should stop, or if you hit the end, then you should return. Okay, give it a shot. Alrighty, let's implement find on our BST class. So the first thing we'll do is just add the method find, which accepts a value. And we have a couple of optimizations we can make at the end, but I'm just going to start by following this. We're going to check if there's a root. So that's simple. If this dot root is null, then we're just going to return, what do we want to return? Undefined, false. Let's just say we want this to be true or false. So we're going to say that it either returns true or false. So if there's nothing in there, then we can't find the value, so return false. That's nice and easy. If we run it, we make a new tree. I'll call it T, new binary search tree. If we do t.find1, we should get false. All right, so that's out of the way. Now what I'm going to do is make a variable called start. And I'm going to have start equal the root. You could also call it current. I kind of actually prefer current. So I'm not going to call it start. I'll go with current. And then let's make another variable. And this one is going to be called found. And it starts as false. So found just keeps track of if we've found the item yet. Then we need to get to the bulk of our logic, which involves basically looping. So I'll do a while loop. And we want to loop while not found. So while we haven't found the thing, but also while there is a current. So I'll explain why in just a moment. But we want to keep going because if let's say we never find it, right? It's not in there. Found is always going to be false. So we also need to make sure this loop doesn't go forever. So current is going to be our value that as soon as there is no current, whenever there is, we've hit the end of the tree, we can't update current, it's null, then our loop will stop. So basically this is while there is something to loop over and we haven't found it, what do? Let's start by just checking if the value is less than current dot value. If it is less than, then we're going to say current is now equal to current dot left. We know that it needs to be on the left side. So for example, if this is a tree we have and we're looking for 2, well, if we did a tree.find 2, we're going to set current to equal this node, and then found is going to be false. So we check. 2 is less than current.value. That's true. So now current is this. And so we start again. So let's do the same thing with an else if value is greater than current.value. If that's the case, current equals current.write. Now we're missing the most important part, which is the else. If we found it, we're going to set found equals true. So this is if it's less than, this is if it's greater than. The only other option is that it's equal to. So we'll set found to true, and then the loop should be done because this is now false. Not found, not true is false. So we're done here. Then after this while loop, we'd need to return the node. Well, I was pretty unclear about this, honestly, in the instructions. I regret that. If you should return the node itself or return true or false to see if it contains it. Let's return the node. So that's going to be current. I apologize if you implemented one solution and I did the opposite here, but the logic is the same either way. We could return true right here if we found it. We can return current. Okay, so I'm going to return current at the end. And then we also want to check if it's never found, we should return something. Because right now, oops, did not mean to do that. If we run this code, we've got our tree. What values does it have? It has all of these. So if I look for, tree.find 5, for example. Okay, it was in there. Tree.find 10, that's in there. Tree.find this time 2, that's also in there. Okay, but what about 100? That's not in there. So we're getting null. Instead of null, I think it would be better to return false. So to do that, we could add just an if statement here. If it's not found, return false. Or actually, I think undefined might be better. It doesn't really matter, but just some value here to indicate it's not in there. And if we wanted to, so just to be fair, if we wanted to do the true or false version, so it doesn't actually return the node, it just returns true or false. So maybe I'll call it like contains value. It's a little simpler because if we find it, we can return true. Then we don't need this here. We can just return false. Okay, so if we find it, if it's equal, we return true. And then the only way we get here is if it's not in there. So we return false. So if I run this one, we do tree.contains 1, that's false. But 10 is in there, so is 2 and 16, I think. But 18 is not in there. Okay, so sort of out of left field, but I decided to do two implementations. One, true or false, only return values called contains. The other one is called find, and it actually returns the value, the node itself, if it's in there. Okay. All right, welcome back. So we're still talking about binary search trees, but we're not going to implement any new methods. What we're going to do right now is review the two methods we've already added, and in particular, focus on their performance, their time complexity. So as a binary search tree grows, whether it's, let's say it starts at 10 nodes and it goes up to 1,000,000 nodes, how much more time on average, but we'll also talk about best and worst cases, how much more time does it take to insert a value or to search? I've actually given it away already. This is best and average case, O of log n. And I'm going to explain why that is in just a moment. But if you don't remember what log is, what logarithms are, if you didn't watch if you don't remember from math class, totally understandable. It's not that useful in everyday life. But if you didn't watch the video in the beginning of this course, in the big O section, you might want to go check that out. It explains in some more detail, basically, what this means. And just as a refresher, this actually means log base 2 of n, which is really, it's so lazy the way that big O works. We just simplify. We get rid of the base 2 and we just say log n. Okay, so let's talk about how we arrived here. The first thing to get out of the way is that log n is good. That is a solid time complexity. That's it. If we look at the chart, which we will in a moment, you'll see that it grows pretty slowly. All right, so here we have two trees. Two binary search trees. I just want to reiterate what I'm talking about in this video is only for binary search trees. They have to be sorted because they give us this nice shortcut. So here's this first tree. It's 7 nodes, something like that. As we look for a value, let's say that we're searching or inserting. It doesn't matter because we're basically doing the same thing. We're finding the correct spot for it. So let's say I'm trying to insert 59 into this top tree. Well, we're going to have to start here. And we're going to have to make a comparison, go here, another comparison, go here, another comparison, and then insert the value. Now, if we double the size of the tree, so this has double the nodes as the one above, it only has one more level down, one more step. Its height grows by 1. So in this tree, even though it has double the nodes as the one from above, we only have to look one more time. We have to only take one more step. So if I was trying to insert 61 this time, I just have to go 1 step, 2 steps, 3 steps, 4 steps. This one that has half the nodes was 3 steps. So this relationship here, because the way we keep it sorted, and again, that only works in a search tree, a binary search tree, as the tree doubles, as the number of nodes doubles, we only increase the number of steps by 1. So that relationship is log base 2. So here's the actual chart from Wikipedia of log 2 of x. If you look at it, just the positive side. As we double a value from 1 to 2, we only take 1 step up. As we double it again to 4, 2 steps up. As we double it again to 8, 3 steps up. If we go back to this big O complexity chart where we just see all of the different notations charted next to one another, you can see that log n is really solid. It grows very, very slowly compared to something like, I don't know, n squared, quadratic time. I mean, that's not good. Or n log n, or even linear time. The only thing that's better on this chart, at least, is constant time. So log n is good. It takes a while, it takes a long time for it to start to grow. And this is the same for insertion and for searching. Just to reiterate that, they're the same idea because the way that the tree is set up, we follow the same steps. We compare, do we go right or left? Compare, do we go right or left? And whether we find the value or we insert, it's the same sort of number of steps. Okay, so now let's talk about why I said not guaranteed. So O of log n is the time complexity for the average case of a tree, but also for the best case. There's no faster possible way. But when we talk about worst case, it's not guaranteed. And that's because there are some binary search tree configurations that are very slow, at least compared to the ones we've been looking at. For example, this very sad, floppy, mopey binary search tree. This tree, which really just looks like a linked list or something, it's entirely one-sided, but it's still a valid binary search tree because if we take a value, every node to the right is greater than its parent. And we keep going, it's valid the entire way. So if we're talking about inserting into this tree, if we have a tree like this, let's say it's, how many items is this? 8 or something? If we had it grow to 1,000,000 items, and it was still a one-sided tree, which is not a good use for a binary search tree, but if that's what you had, and it kept growing and growing and growing, then the number of steps it's going to take to insert or to search is going to grow as the number of nodes grow. So that would be O of n if you had a completely one-sided tree like this. Now there's a really easy solution to this, which is just don't store a binary tree or binary search tree like this. If you needed this as a tree and you wanted it to be sortable, you could rewrite this binary search tree where you pick a different root. Pick, 34 as the root, and then restructure the entire tree and have these values to the right, these values to the left. That would make your searching and insertion much faster already. So I just want to point out, though, this is a valid BST. So this is why I said not guaranteed to be O of log n. But on average, insertion and searching in a binary search tree are O of log n for time complexity. And that is pretty good, pretty good. All right, moving on. Hey, welcome back. We have a brand new section here. We're still working with trees, but we're doing something a little different. So tree traversal is what we're going to focus on. And this is the idea of basically given any tree, whether it's a binary search tree or just a plain binary tree that's unsorted, or a ternary tree or some other tree that has any number of nodes. There's no special order, just any tree, all right? Generic tree. How do we visit every node one time? So this is a classic computer science problem. There are many, many ways of doing it. Contrast it with a linked list. To traverse this tree, to visit every node one time, it's very easy, right? There's one linear pathway from here to there. There is no order that you have to decide. There's no decision. It's just go from here to here. So this is unsorted. Imagine, we're searching for a value. We want to know if 43 is in this list. Well, we start here and we go here, here, here. Okay, we found it. Or if we're looking for 99, we would traverse every node. We hit the end, 99 is not in here. Now, when we talk about a tree, it's very different. So this is not a binary search tree. It is a binary tree. Each node has at most 2 children, but it's not ordered in any way. These values on the right are not less than, or they're not necessarily less or greater than, 10. And the values on the left are not necessarily less than. So no order. We can't use our little shortcuts. If we wanted to find a node, if I wanted to know if 29 was in this tree, we would need to visit every single node in order to figure out that it's not there. So do we start here? Well, it's probably a good place. Do we go left and then sort of work our way horizontally and go horizontal again and keep going down? Do we go all the way down to the end and then come up and then go down and then go back up, go all the way down to the right, and then, keep going down any further branches? It's really difficult to know. There's so many ways of doing it. It's not like a linked list where there's one linear approach. So that's why we have a section on this. Like, we wouldn't do it for a linked list because there's only one way. But with trees, there are many, many ways. And we're going to focus on 4 very commonly known approaches. They have names, these orders. One thing I'll say, this section will take advantage of recursion more than any of the other sections so far. So if you skip the recursion section, I highly recommend you go back and watch that, because this will be a little bit mind-blowing, might be putting it nicely. It also might just be really confusing and not fun. So I would really make sure you understand recursion. You don't have to be an expert, but just know the basics so that when I talk about it, it makes sense, hopefully, if I did a good job in the recursion section. There are 2 main approaches to traversing a tree, something called breadth first and another called depth first. So these refer to the general directions. So when we talk about breadth first search, if this is our tree, imagine just starting at the beginning and then basically working across the tree first. So 10, 6, 15, then continue across. Breadth refers to the breadth of the tree. That's the worst sentence ever. Then there's also depth first search. And there's actually 3 main orders for DFS, depth first search, that we're going to talk about. So the idea of depth first is that you're just going down, like your primary direction is going to the end of the tree vertically and then coming back up, versus breadth first is going across. So one version is something called in order, and that would mean basically starting down here and then, well, we're going to spend more time. I don't want to just explain how every single one works. I just want to show you there are different ways. So this is in order. There's also a depth first search called pre-order, where we work from 10 down 6, down to 3, to 8, and then we go down the other side and go down 15 to 20. Then there's also post order that looks like this. So we go down to the bottom and we work our way back up like that. So these are all different approaches, different ways of searching, or at the very least, not even searching, just visiting every single node. If I just asked you to print out an entire tree, there's not one easy way or one given solution, right? These values that we're seeing here are the order that we're visiting them. So this would be the order they would be printed out in. And it depends on what you're trying to do. And I'll have a video where I address that. There are certain situations where you might want to use one versus the other. But for now, let's just leave it at the fact that there are many ways of visiting every single node in a tree. In fact, there are so many ways that we have a whole section on it. And this is really independent of binary search trees. It's really just trees in general. But we will be working with our BST class just so that we don't have to duplicate code and, create a new tree class. All right, welcome back. So in the last video, I mentioned there are 2 main strategies for traversing a tree. Breadth first search, BFS, and depth first search, DFS. And these just refer to sort of the general order that we visit things. Are we going to prioritize visiting all nodes on the same level before we move down? Or do we want to, work in a more vertical way, which is what depth first is. So BFS, what we're starting with, breadth first search, just means we want to visit every node on the same level, every sibling node, before we look at a child. So for us, the order with this tree would look like 10, 6, 15, 3, 8, 20, and then we would keep going if there were more, from left to right in our case. But that part's not as important, the left to right. What's more important is just that we're working horizontally. Now, I'm sure you're wondering, why would you use this versus another one? Why are there all these different orders? Why are we learning this? I will talk about in a separate standalone video, once we've gone over the different approaches, why you would use one versus the other. because it's a little hard to talk about it before you have the context of the other algorithms and how they work. So for now, I'm just going to punt on that and say I'm going to teach them. If you have questions about why, let's just wait. I guess, technically it's a video, so you kind of have to wait, but just hang in there. The one thing I would mention is keep in mind, this is a small binary tree, but we might be working with a tree that is super, super deep and narrow, or something that's really wide. It doesn't have to be a binary tree. We could be talking about each node has 100 children. And so these different approaches, these different strategies actually have an impact, depending on what the tree looks like, how the data is distributed. Anyway, that's enough about the general approach to BFS. Let's get into specifics. How do we implement this? To do that, we're going to take advantage of a queue. So I don't recommend creating your own queue class and going through all of that. Just use a list or an array to model a queue, which if you didn't watch the section or you don't remember, it's a first in, first out structure. So if we used a simple array or a list, you could just use push to add things in and then shift to remove from the beginning so that whatever was added in first is always the first thing out. So here's our basic approach. We're going to have two variables. We're going to have the queue to help us keep track of things, and then we're going to build up a list of data to return at the end. So our end goal, if this was our tree and we're doing a BFS on this, breadth first search, we want to return this at the end. And our queue at the end will be empty. So the queue is just to help us out. So our main idea, we take the root and we add it to the queue. Then we loop as long as there's anything in the queue, and we dequeue a node from the queue, which if you're using an array, just means shifting from the beginning of that array. Take that node and we add it to our return value, the list that we're going to return at the end. And then we check if there's a left on that node and we add it to the queue if there is. Then we check if there's a right and we add it to the queue if there is. And then we return at the very end after the loop, return the variable that stores all of our values. So if that sounds confusing, it is if we don't look at it visually. So let's walk through this briefly. So I have two, this is not really in a programming language, but I have a queue that I'm keeping track of, and then this visited thing, this structure that at the very end, I'll return this list or this array of data, and our queue will be empty. So we start with the root. We add 10 to our queue. This is like our list of, okay, things we need to do. It's our to-do list. And then we start our loop, which just says while there is something in the queue. So our queue has something. We're going to take it out. We're going to add it to our visited list. And then we're going to check if there's a left. Is there a left? Yes. So we add that to the queue. Then we check, is there a right? Yes. 15. So we add that to the queue. Then the loop starts over and we remove the first thing from the queue, first thing in, first thing out. So we take 6 and now we add it to our list that we visited. We have visited 6. Now we check, is there a left? Yes. So we're going to add it in. So that gives us 3. Is there a right? Yes. So we add in 8. And then we're done. We start over. We're not done. We're done with 6. And now we take 15 out. So hopefully you can see already this pattern, right? We're going this level, finished. Then this level, this level. And we're creating this queue to help us remember the things that need to come next, but we're not visiting them next. We're waiting to visit them until we finish a horizontal level, the breadth first search. So we take 15 out and we add it to our list that we visited. And we check if there's a left. Is there? No. Is there a right? Yes. So we add 20 in. And then we start over. We take 3 out. And we keep going. So there's no left, no right, so we don't add anything to the queue. Same thing with 8. We take 8 out. There's no left and no right. So we add that in. Then we get to 20. And now the queue is empty, which is how we know we're done. And we return this value at the end. This is our breadth first search. 10, 6, 15, 3, 8, and 20. This is how we traversed it. This is the order we visited things. So we take advantage of a queue to just store, it's like a to-do list. Like, don't forget this, come back. But we take things from the beginning and we add to the end. So the first thing in is the first thing out. Hopefully that explanation makes sense. This pseudocode is pretty clear, I think. So try and follow this and give it your best shot. In the next video, I'll have a solution. All right, welcome back. Let's implement our breadth first search. So I'm going to go over, and the very first thing is I'm going to define a method. We could call it BFS or breadth first search. It really doesn't matter. I'm going to do BFS just because it's really annoying to type. And it doesn't need to take any arguments. We're just trying to visit every single node. Okay. And right off the bat, we need two things. First, we need our data, which is what we'll return at the end. So I'll just make an empty array. We have a couple other variables, so I'll just declare them all together. We have our queue, which will also be an empty array. And we can just start with that. And the first thing that we'll do is place the root node in the queue. Okay, so that's easy enough. Queue.push this.root. So that puts, if this is the tree we're working with, that puts 10 in there. And then we're just going to loop as long as there's anything in the queue. We're going to take the dequeue from the queue. So let's just start with that loop while there's anything in the queue. So if we just did while queue in JavaScript, if we have an empty array and we negate it, this tells us that we get false, which means that an empty array is truthy. So that's not what we want. It's not like an empty string, or some languages, an empty array is falsy because it's empty. Not the case. So what we're going to do instead is while queue.length. So 0 is falsy, as we can see there. Or doubly, we could get back to false. Anyway, if that didn't make any sense, I'm sorry if I did a bad job explaining that, but we can't just say while queue. We need to say while queue.length. So while there is something in the queue, we're going to remove something from the beginning of that queue. So I'm going to do queue.shift, and let's put this in a variable. But rather than inside this loop continuing to make a new variable over and over and over and redeclare it, let's actually go up here and make another variable just called node. And let's start it as, why don't we actually do this? This.root, like this. Okay, this is just me being sort of ridiculous, but I like all of this to line up. Okay, let's just do that. It really doesn't matter. You could just do 3 different vars. Anyway, we have node start as this.root. Then we can just do push node. It doesn't really matter. But now I don't have to do this var node equals and just have this var keyword in a loop. It's not a good idea. So I'm just going to now assign node to be queue.shift. Now, of course, I could have just started node as nothing. Could have just made it undefined or null. But this works fine for me. So we take from the beginning of the queue. So if we're pushing at the end, we're going to shift from the beginning in order to get that first in, first out. Then we need to take that node and add it to the list that we're going to return. Then we check if there's a left. We add that to the queue. We enqueue it. If there's a right, we add that to the queue as well. So we did node equals queue.shift. Now we're going to do data.push node. So that's adding into our list that we're going to return. So if this is our queue, empty, and this is our data, empty, the very first thing that happened is that we pushed, sorry about that siren if you could hear that, queue.push 10, given this tree. Then while queue.length, node equals, take this out and add it into our data. Now we're going to check if there's a left. If node.left, then we'll do a queue.push node.left. And we'll do the same thing if there's a right. And so we add that in to that queue. And that's actually it for our loop. Then at the end, we just need to return this data variable where we're building up everything we've visited. So just to reiterate that, if we take 10 from the beginning, which was in our queue, we add it to data, then we're going to check, is there a left for 10? Well, given our structure, yes, it's 6. So we add 6 in. Then we do node.right. Is there a node.right? Yes, it's 15. So queue.push 15. And then the loop starts over. There's still a length to the queue. So now node is equal to 6. So we take 6 out and we push it on to data, which is what we've visited, and we return at the end. And then we check if there's a left. There is. So we add that in, which is 3. And we do the same thing with the right. We add that in, which is 8. And we keep going. And I did this in the last video, so I won't step through every single moment. But let's just see if it works. If it does work, we expect to get this. So I'll copy this over. This is what we want. Let's try running it. So down here, I have the code to actually build the tree. And now I'm going to do a tree.bfs. Oh, yeah, that's annoying. Maybe I should just push the value in to make this easier to see what's happening. So let's do push node.value. It really doesn't matter, but just to make this easier to see. Okay, so we got 10, 6, 15, 3, 8, 20. And we're supposed to get 10, 6, 15, 3, 8, 20. That's our breadth first. All the way across, all the way across, all the way across. So horizontal before we go vertical. Breadth before depth. So that's BFS. It's relatively straightforward if you take advantage of a queue. Remember, first in, first out, just a list of things that we need to visit. We're keeping track of it, and it grows, and it doesn't really matter. Yes, this is hard-coded for left and right, but if this was a ternary tree, we could add, first, second, and third child, or we could do it dynamically and have a loop and loop over all the children. So it doesn't have to be a binary tree. It's the same basic principle. You use a queue. All right, so that's BFS. Hey, welcome back. We're pushing on with tree traversal. Now we start depth first search. So there are 3 different orders within depth first search that we're going to talk about, but all of them are DFS algorithms, meaning that they pursue all nodes, they visit or traverse nodes vertically down to the end of the tree before visiting sibling nodes. So that's maybe not the most technical explanation, but it means that we're going to traverse down until we hit the end of the tree at some point. And then from there, there's a couple of options as far as the order that we do things, but we're working down first, depth first, rather than horizontally, breadth first. So we can break down tree traversal into 3 main steps. So for any node, we need to, at some point, visit the actual node itself. Like if we're building a list or printing it out, we need to add it to the list or we need to print it out, whatever we're doing. So we have to actually do the visit. Then we also need to explore the entire left side and the entire right side. At least when we're talking about a binary tree, if we have, a ternary tree, then we need to do the first, the second, and the third children. But let's just stick with binary trees for now. So we have to, at some point, explore the node and then traverse the left and traverse the right. And those 3 things, just by changing the order that we do them in our code, literally copying a line, pasting it above another line, or moving it below another line, will change the output that we get. So with our DFS algorithms, our end goal, just like with the breadth first search, is to just build an array or a list, or if you prefer, just print them out. But basically, we want to visit them in this order. And pre-order, which is what we're starting with, basically means you're going to visit the node first. Then we look at the entire left side, we traverse the left, then we traverse the right. And that's true for any node. So we start off at 10, we visit it, meaning we add it to our list, or we print it out. Then we explore the left side. So that means starting off at 6. And so we visit 6, meaning we add it to our list or print it out. Then we traverse the entire left side, then the entire right side. So that means 3 and then 8. There's nothing to traverse after them, so they get visited. Now we go back to 10 because remember, we visited 10, then we looked at the left side. Now we have to look at the right side of 10. 10 was still waiting to have its right side visited. And so we get 15 and then 20. So we have those 3 operations. We visit the node, we look at the left, and we look at the right. Just by changing the order that we do those in, we'll have a large, very drastic impact on the output order, the actual traversal order. And so we're going to talk about pre-order in this video. Then there's also post-order and in-order. They are all depth-first search algorithms, but they're different orders, and we just have to shift 1 or 2 lines of code. So here are the basic steps that I recommend. You can do this iteratively. It's definitely shorter and easier to do it recursively. So again, if you haven't done the recursion section or you don't know recursion, I definitely recommend you review that section. Okay, so we're going to create a variable just like we did before to store the values that we visited. So at the end, we'll just return that, call it data or visited or whatever. Then we're going to create a variable called current and just store the root of the tree in there. So that's where we start off. Now the slightly tricky part, we're going to write a second helper function. So we're going to have our pre-order function takes no arguments and our second function, which takes a node and it accepts a node as an argument. And all that it does is we push the value of the node to the variable that stores our values that we return at the end. So we visit the node by adding it to the array or to the list. Then we check if it has a left. If it has a node.left property, we're going to recursively call the helper function again, and then do the same thing on the right. If it has a right property, call the function on the right. So basically, we have this helper function where for a given node, we start with the root, we push that node to the list that we're looking at, to our end result, our data. So we visit the root, and then we recursively do the same thing for the left and the same thing for the right. So we'll walk through how this works in the solution. We'll look at a call stack. It can be a little bit crazy to try and visualize. But if you can just write a helper function that accepts a node, it takes the value of that node, pushes it to our array that we return at the end. Then we check if there's a left. We call the same helper function. I would just call it traverse. We call traverse on the left side of the node. And then we also, the next line below, if there is a right property, call traverse on the right side. Then we're going to invoke that helper function with the current variable, which is started at the root. Where is that? Right here. And then at the very end, return the array of values, or the list of values that we've visited. So I know it seems intimidating. If you're not comfortable with recursion, I totally get that. This is this is pretty much word for word, well, not word for word, line for line, what you need to do. You can do the solution in just a couple of lines, maybe 8 lines, 7 lines. And once you get this one, it's very, very similar to the other two, the two other depth first search orders. So try it out. Don't get discouraged if you can't do it, because in the next video, I'm going to have a pretty thorough solution where we actually walk through step by step how it works. All right, so let's try implementing this depth first search pre-order. So we're going to go over here. I'm going to define the function. I'll just call it DFS pre-order like this. And then inside of here, I'm going to start by making our variable data that will return at the very end. So I could actually go down to the very end and return data. This is just the order that we're visiting the nodes. Then we'll make our variable called current and set it to be the root. Just like that. Now for the trickier part. Write a helper function, we'll call it traverse, that accepts a node. So I'm just going to do that actually nested inside of here. Function traverse accepts a node. And the first thing that we do is push the value of the node to our variable data. So we'll do data.push node. Then we check if there's a left property. If there is, we call the helper function with the left property, and we do the same for the right. So we could just do if node.left. What are we going to do? We're going to call traverse node.left. So this is traverse, we're recursively calling it. And we do the same thing if node.right, traverse node.right. And that's actually it for our solution. Except, well, that's a lie. We have to actually invoke traverse, which is what I talked about down here. Invoke the helper function with the current variable. So that's traverse and current, which is the root. And actually, we honestly don't even need this current variable. You could just do traverse this dot root. But what setting a current variable allows you to do, a user could specify a node to start from. They may not want to traverse from the root if you have a massive tree. I'll just do this though, this dot root. Okay, so if we actually run this right now with this tree, 10, 6, 15, 3, 8, 20. Let me just save this, execute it. Let's see if it works. Oh, you know what? I'm realizing it's easier again to push the value instead of the entire node. So let's try rerunning it one more time. Tree.dfs pre-order. Here's what we end up with. 10, 6, 3, 8, 15, 20. And that is the correct depth first search pre-order. So now let's get to the harder part, which is explaining how the heck that works. So I'm going to come down here and do a tree.dfs pre-order and add a breakpoint there. Now let's step through what happens when I execute this code. Okay, so I'm going to go to the call stack and step through this. Very first thing, we make our array called data. We call traverse on the root. Okay, now if we look at the call stack, we now have a traverse call, and we're pushing 10 into our array that we're returning called data. So 10 is in there. Then we check if there's a left, and there is. So we call traverse on the left, and that left node is 6. So we end up with another call added to the stack, this time on 6. And so we now push 6 into our array. So our data array has 10 and then 6. And we check, is there a left on 6? Yes, there is. So then we traverse node.left, which is 3. And so we end up with another call added on top. Now we're working with 3. Data.push node.value. So we add 3 into our list. So we have 10, 6, now 3 is in that data. And we check, is there node.left? No, there is not. So we don't traverse node.left. Is there a node.right? Nope, there's not. So we don't traverse that either, which means we're done with this call with 3. So you'll watch it actually pop off here. There we go. And now we go back to where we were on 6. Because 6, we stopped at this line, right? We're waiting for this traverse to finish. Now we get to the right. Is there a right side? Yes, there is. So that is 8. So now we traverse 8. So we add one more call right there to traverse. Data.push node.value, which is 8. So now we have 10, 6, 3, 8. Then we check, is there a left? There's not. Is there a right? There's not. So we're done. I'll click a few times and it gets popped off. There we go. Now we're back to 6 at the end because this finished. We traversed the right side of 6. We did the left, then the right. There's nothing there. So we're done with 6. Now we're back to 10. So we did the entire left side of 10. Now we're going to do the right side. So the way that this works is that we visit a node and then we traverse the entire left side and then traverse the entire right side. That's sort of the high level overview. But the way recursively it works, it can be a little tricky to step through. So now we're on 10. We finished pushing in for 10. That was very easy. We've traversed the entire left. Now we have to traverse the right. So is there a right? Yes, 15. So we traverse 15. So we get a call added to our call stack. For 15, we push 15 into our list. So now the list is 10, 6, 3, 8, 15. And we check, is there a left? There's not a left for 15. So we go to the next line. Is there a right? And there is, which is 20. So we traverse 20. And traversing 20 really just involves, you can see the call being added over here, data.push 20. So we add 20 in, and we've now visited every node. We don't actually know that until node.left. So this is going to be false. There's no left, there's no right. So 20 gets popped off the call stack. And then the call for 15 gets popped off. And then the call for 10, the original one, is popped off. And we finished all traverses. So this is the line that caused all that trouble. And this is what data now looks like. Now we just return data. And we're done. Well, there we go. Now we're done. And that's the order we visit things in. So to recap, what we do is recursively, we visit a node, then we visit the entire left side, and then the entire right side. So this order is really significant. And you'll see in the next 2 videos or next 2 solutions for different orders, all we have to do is tweak the order that this happens in. Okay, so that's coming up next. All right, welcome back. Next up, we're going to take a look at post order. So just a slight tweak, a variation on what we wrote in the last video, where we're basically going to change the order of one line that we're going to move, which will make a significant difference to the actual output order. So if you watched the 2 videos ago when I introduced depth first search, I talked about there's 3 main operations or things that we do. For any node, we need to, at some point, visit the node itself, like 10. Then we also need to traverse the entire left half and the entire right side. I shouldn't say half because it's not necessarily half, but the entire left side and the right branch. And then do the same thing on this node. So do we visit it first, then look at the left, then the right? That's what we did in pre-order. If we go back here, we start off by visiting 10, adding it to our list, then looking at the left side. Then once the entire left is done, then we go to the right. So then we get to 6, we visit 6, we look at the left, then the right. There's nothing after, so we just visit 3 and 8. And then we finish out the right side of 10. So that's pre-order. We visit the node first, then left, then right. Post order works differently. You might be able to tell by the name post, after, we visit a node after we have looked at the left and the right. So we explore everything first. We traverse the entire tree or the entire branch from a given node, the left and the right. Then we visit the node. So in post order, we start at 10, but we're not going to visit it. We're going to look at the left and go all the way down to the left, then all the way down to the right, and then we visit a node. So we start at 10, we go all the way to the left, we traverse. So then we get to 6. We're going to go all the way to the left, then the right, and then add 6 in. So that means adding 3 in first. Then we add the right, we visit 8. Now we visit 6 because we've explored the left and the right of 6. Then we don't visit 10 yet. We've only done the left side of 10. Now we do the right side. So we go to the dot right of 15, which is 15. And from there, there's no left. So we explore the right. We get to 20. There's nothing after that. So we add 20 in. We explore or we visit 20. Then we work our way back to 15. Then finally 10. So in this example, in post order, the root is the last thing that's visited. For any node, we explore all children before we actually visit the node. Now, practically what this means is you just need to change the order of your code. So if you wrote the solution or you're looking at my solution from the last video for pre-order, everything's pretty much the same. We're going to write a function, it doesn't take any arguments. We're going to make an array or a list to store the values of the things we visited so that we can return it at the end. We're then going to write a helper function that accepts a node, and recursively, we're going to do these 3 steps. If there's a left property, call the helper function on the left property. If there's a right property, traverse the right property. And then push the value of the node to our variable that stores our visited values, and then invoke the helper function with the current variable. And then finally return the array of values. So this is copy and pasted from the last 2 videos ago. The same pseudocode, except the order is different. Rather than pushing first and then doing the left and the right, we're going to explore the left, explore the right, and then push the value in. So that's post order. Give it a shot. Just, alter the code if you'd like. It's good practice to write it from scratch, but if you're short for time or you're bored, then just copy and paste the line, change the order, and make sure that you get the expected output. So if you use the exact same tree, this is the output you should get for post order compared to this order here for pre-order. So give it a shot and see if you can get it to work. Welcome back. Let's get to work on post order. So we're going to take any node, we're going to explore the entire left side, then the right side, and then finally visit the node itself, add it to our list. Let's hop over to my code, and I'm just going to define depth first search, post order, just like this. We'll make our data array to store our data, and at the end, we'll return data. Then I'm going to define my function traverse, the helper function that takes a node, but rather than pushing in the data first and then looking at the left and looking at the right, we're going to do if node.left traverse node.left, if node.right traverse node.right, and then afterwards data.push node.value. And then we need to invoke traverse at the end, traverse with the root, this dot root. And that's it. So it's the exact same code, except we move this line where we actually visit the node by adding it to the array. We moved it after we explore the left and the right. So we do left, then right, then we push it in. And if we just verify that it works first, let's do both a tree.dfs preorder, tree.dfs post. Nope, that's pre again. And let's make sure it works. So I'll execute my code, and it should have known better. It's only giving me the last return value. Okay, here we go. So this was what we just did. This is from the last video. So you can see this is working. We're getting the expected order. So if this is our tree here, it's the same that I had in the slides. The order would be 3, and then 8, then 6, not 10. We still have to go down the right side. So that means 20, 15, and then finally we get back to 10. until this worked correctly. Compare that with pre-order, where we visit and then look at the left and then the right. So we visit 10, then we go down to the left, we visit 6, then we go down to the left, we visit 3, then we go to the right, we visit 8, then we're back at 10, we visit the right side, 15 and 20. And that's all there is to changing the order, to doing a post-order depth-first search or depth-first traversal. Welcome back. So we have one more depth-first search order to talk about. It's called in order. So if we go back to those three puzzle pieces, we change the order of them, then it changes the output entirely. So those three things are, at some point, we actually visit the node, then we traverse the entire left, and we traverse the entire right. So within order, we're going to traverse the entire left side, then visit the node, and then traverse the entire right side. So what that means is if we start with 10, we traverse the entire left. So that means going to 6. Okay, so we traverse the entire left of 6, meaning we hit 3. We visit 3 first. There's nothing to traverse. It's a leaf. Then we go to 6, and we visit 6. And then we traverse its right. We get to 8. There's nothing to traverse, so we visit 8, and it's added to the list. We go back to 10. So we did the entire left side of 10, traversed it. Now we visit 10. Now we traverse the right side. And that adds 15, and then we visit 20. So this is the same pseudocode, except that in our helper function, we do the left side. We traverse the left side recursively. Then we push the value of the node to a variable. Then we traverse the right. So the end goal, just like all of our other traversal methods, is to build a list or an array containing the values in the order that they were visited. Or you could just print them out, but I would do this so that you can see exactly what's happening. It's easier to compare if you just build an array or a list. So with this sample tree, our output would be 3, 6, 8, 10, 15, 20. So we do the left side, visit the node, then the right side. Just need to change a single line of code. And contrast that with pre-order. Remember here, we visit the node, then the left, then the right. With post-order, we traverse all the way to the left, all the way to the right, and then we visit a node. Okay, so give this a shot. If you have the code from the last two videos, then just change that one line, and you should be good to go. Welcome back. So we have our final implementation of DFS, depth first search. It's going to be really fast because we just need to change a line from our last solution. So to recap, on every node, we traverse the left, then we visit the node, then we traverse the right. So if we go over here, and I add in a solution, so DFS in order, I'm not even going to bother typing the entire thing again. I'm just going to copy it over and change this so that when we traverse the left, then we visit by pushing the data into, or pushing the node value into our data array, and then we do the right side. So if we start here, we're going to traverse the left, and we get to here, well, we still need to traverse the left, then there's nowhere else to go, so we push node.value 3. Then we're back to this one, which was waiting, and we did the left, so now we visit 6, then we do the right. Then we're back to 10. We did the left side, so now we visit 10, and then we go to the right side, and so on. Okay, so let's see if it works. Tree.dfs in order, we get 3, 6, 8, 10, 15, 20. And that's what we expect, 3, 6, 8, 10, 15, 20. So those are the three orders that we're going to talk about. A small change, if you prefer, you can actually rewrite this code like this. You can do, rather than a conditional, you can do node.left and traverse node, and do the same thing down here, node.right and traverse node. It's just a small change. If you don't want to do the conditional, we're just checking if it's truthy. If it's non-zero, this will do the same thing. I think I actually prefer this slightly more verbose because I like putting that if in there, but I know some students are sticklers for making things as succinct as possible. So you could do this, and this applies to all three the solutions, so it's not just this one. But I'll leave it in here, and I'll leave this one as an if, just so that we have some variety in our solutions. All right, so that's depth first search, 3 different ways, 3 different flavors. In every approach, we're working vertically first, if that makes sense, rather than horizontally going back and forth, breadth first search. What I'd like to do next is add a quick video where I talk about the merits of these approaches and why you would use one over the other. All right, so now that we've implemented a couple of ways of traversing a tree, spent a lot of time on it, let's talk about which one is better. Which one should you use? And spoiler alert, the answer is that it depends, and there's pros and cons to all of them. And it's really just dependent on your situation, which is always an annoying answer, I know. So let's start by just talking about breadth first search in general compared to depth first search in general. So ignoring the order, post order, pre-order, in order, put that aside. Breadth versus depth. Which one would you use in a given scenario? Well, I think it depends on the tree. If you have a tree that is fully fleshed out, like this tree, it's as wide as it can be the entire way down. If we're working with a breadth first search, remember that we have this queue that we're storing all of the nodes we have yet to visit, all of the children. So let's say we're here. We're going to visit this node and then add left and right to a queue, and then go to this node, add left and right. Here, left, right. So our queue grows, and it stores a bunch of pieces of data, a bunch of nodes. So by the time we're down here, or imagine we have something with a height of like 100 levels down, we're going to have to store a ton of data in our queue, just in memory. By the end, that queue will be empty, but I'm talking about space complexity. The time complexity of depth first versus breadth first doesn't matter. They're the same. We're visiting every node one time. So that's irrelevant. But the space that's used up in this scenario could be a lot more if you're talking about breadth first on a wide tree. Versus on depth first, we're not storing all of those nodes across the tree. We only have to keep track of the nodes in a given branch all the way down to the end. And the way that we implemented it earlier in this section was using recursion. So each one of these is a frame in the call stack where we're waiting for something else to happen. So in this sort of tree, where it's a lot wider than it is deep, then depth first search would use less space. So it's, again, not about time. We're visiting every node once. It's the same amount of work. It's just how much space we take up in the process of doing that work. If we contrast that with this somewhat more depressing binary search tree, if we traverse this entire thing breadth first, the space that we take up in memory is basically nothing. Our queue is never going to have more than one item in it. We start here, we visit this, we add its right node to our queue, and then we move to this, and we pop it off the queue, or we actually shift it. And then we take this, and we add its child to the queue. So we have one thing in memory at any given time, really, in our queue. But if we're traversing it depth first, if this tree is really, really long, then that means a ton of levels that we have to go down and keep every other level above it in memory. So that's something to consider. Most of the time, your trees will look something like, well, I shouldn't say most of the time, but most of my experience is with trees that look something like this, rather than a super, super long one-sided tree, which doesn't make much sense to keep as a tree. Okay, so to summarize that, time complexity is the same. We're visiting every node once. It doesn't matter, if we have 100 nodes, we're going to visit every single one, breadth first and depth first, same amount of time. Space, though, it really depends on the structure of the tree. If it's a really wide tree, breadth first could store or take up a lot more space for that queue. If it's a really deep, long tree, then depth first could end up taking up more space. Okay, the last thing I'd like to do is quickly talk about when or potential use cases for the different variants of depth first search. So pre-order, post-order, and in order. They're all depth first variants. Why would you potentially use one over the other? And there's not really a great answer. I'm going to give you a couple of examples. This is actually a question I put to some of my teacher friends to see what their input was, what they tell their classes. And pretty much the only feedback I got back was, I just teach them and tell them they need to know it because it's good for them. And I don't really have any great examples about when you would use one versus the other. Well, I'm just doing a little bit more than that. I have a couple of examples, but this isn't going to be super comprehensive. But here's one example. When you use in order on a binary search tree, like we have here, if we look at the data we get back, it is in order. We get all the nodes in the tree in their underlying order. So it goes from lowest to highest. So if you want to take an entire large binary search tree where everything to the right is greater than a node, its parent node, everything to the left is less than the parent node, if you use a depth first traversal in order, you will end up with the set of all the nodes in their order. Depending on what you're doing, that could be useful if you wanted to, grab them in a list or put them in a database or do something with them in that order. It's kind of a stretch, but that is worth knowing that that's a side effect of how this works on a binary search tree. Now, when we talk about pre-order, just to recap how that one works, we visit a node first and then do the left and then the right. And what we end up with, in this case, is a list that looks like 10, 6, 3, 8, 15, 20. And this could be useful if you're trying to clone or duplicate a tree, or you want to store it. You want to flatten it out so you can store it in a file or in a database or something, and then recreate it from that serialized structure. Basically, you freeze dry it, you suspend it in time, and then when you're ready to rehydrate it, you could go and make this the root and then navigate or iterate through this list, and you make this a child, and you make that a child. And it's given to you in an order where you could reconstruct the tree. Versus if we look at something like this in order, you start off with 3 at the beginning of the list. You don't know what the root of the tree is. Versus here, you immediately know this is the root, this is the left, and so on. So those are just 2 situations where one of those variants might make more sense. But remember, at the end of the day, they're very, very easy to switch between. It's not like you're making some massive decision that you can't undo, right? You just change one line, you move it to the beginning or the end of that function call, and then you have the other order. So really, the bigger concern is breadth first versus depth first. All right, so let's quickly recap trees here. They are a nonlinear data structure. They contain a bunch of nodes. There's a single root, and then usually a bunch of child nodes. Binary trees are a special case where we can have values of any type, but each node can have at most 2 children for a parent. Binary search trees, on the other hand, are a more specific version of a binary tree. So we have trees, and then binary trees, and then binary search trees. And binary search trees have to fulfill a special condition. They are a form of an ordered or a sorted tree. So every node to the left of a parent is less than its value, and every node to the right of a parent is greater. So you can only have a binary search tree with data that is comparable. Pieces of data where you can say this is definitely less than or this is definitely greater than. Okay? And then also, what we just spent a lot of time talking about, we can search or traverse trees using breadth first search and depth first search. And within depth first, there are 3 variants we discussed, 3 orders: in order, post order, and pre-order. Okay, that's a lot about trees. I think I've said this at every section at the very end. I recommend you take a break. Do not try and power through all of this because I'm afraid you're going to lose your mind. Okay. All right, welcome back. A brand new section here and a new data structure to go along with it called the heap. So personally, I really like heaps, and hopefully you will too. You'll see why I like them in just a little bit. But first, back to Wikipedia. I showed this article a couple videos ago somewhere in the trees section, where I was explaining that there are many groups of trees and many types of trees within those groups. We talked about binary trees mainly in the trees section, and more specifically, we talked about binary search trees. But there are many other types, and at one point I mentioned heaps. So heaps are another category of trees. So in this video, in this section, we're learning about heaps, but they are trees. So everything that applies to trees in general applies to heaps, but there are some additional special considerations or rules. There are many types within heaps: Fibonacci heaps, Leonardo heaps, a soft heap, a leftist heap. Sounds like something I might have to step over the morning after a San Francisco party, or maybe like an event at Burning Man. Anyway, there are many types of heaps. The one that we're really going to focus on is a binary heap. And actually within binary heaps, there are 2 different types that we're going to talk about. But first, our objectives. So we want to define what the heck a binary heap is. We want to compare and contrast min and max heaps. So those are the 2 types that I mentioned we're going to focus on. Then we're going to implement one of them at least, a max heap. They're very similar, and if you can implement one, you can implement the other. But we're going to focus on writing code for a max heap and add some basic methods. And then we're going to understand where heaps are used in the real world, and also the data structures they help us implement, or different things that we can use them for in other data structures that we'll learn later on. So that's where we're going. Let's start with what is a binary heap. Okay, so a heap is a tree structure. It's very similar to a binary search tree, but it has different rules. So in a max binary heap, the parent nodes are always larger than the children. It doesn't matter if we're talking about the right child or the left child. It's just that the parent is larger than the children, every level down the tree. Or another way of saying that, all children are smaller than a parent in a max binary heap. The opposite's true in a min binary heap, where the parent node is always smaller than both children. So just like a binary search tree, each node can have at most 2 children. So that's where the binary part comes from. But unlike a binary search tree, there is no order to the left versus the right. So this is a max binary heap. The root is the largest node, the largest number in the tree. And to the left and to the right, again, there's no order. It's just that they are smaller than their parent. So both of these are smaller than the parent, and the same is true for both of these. 18 and 27 are smaller than 39, or 12 is smaller than 33. But there is no relationship like we had in a binary search tree. This is the exact same numbers, actually, just represented in a different way. 41, 39, 33, 18, 27, 12. Same numbers, but in a different order. This here is a binary search tree. So we have 33. To the right, we have larger numbers, 41. To the left, we have smaller numbers, like 18. To the right of 18, we have a larger number. To the left of 18, we have a smaller number. So this is a binary search tree. This is not a heap, because in the rules of a heap, if we're talking about a max binary heap, every number below this number, every child below 33 should be smaller than 33. If we're talking about a min, it's the opposite. So this is the correct structure for a max binary heap using those numbers. We have the largest number, and then to the left and to the right are 2 smaller numbers. And then each one of those has a left and a right that must be smaller than the parent. Okay, so here's a couple of rules written out. Each parent has at most 2 nodes. That's where the binary part comes from. The value of each parent node is always greater in a max binary heap. That's what we're really focusing on here, but the opposite's true in a min binary heap. In a max heap, the parent is always greater than the children, but there are no guarantees between the siblings. And also, a binary heap is as compact as possible. So unlike a binary search tree where you can just keep adding on, I showed you some depressing binary search trees that were basically, they looked like a linked list. They were very one-sided. In a binary heap, it always takes up the least amount of space possible. So every left and right is filled before we move down. And also along those lines, left children are always filled out first. So we'll come back to this. Let's just quickly recap. So this is a max binary heap, largest number up top. To the left and to the right are smaller numbers. But it's important to note, these aren't necessarily the second largest numbers in the entire heap. For example, 25 and 36 are the 2 next largest numbers, but they are not on this same tier. It's just any number smaller on the left, any number smaller on the right. And then the same applies all the way down. So it happens that we have 36 here and 25 and 1. Both of those are smaller than the parent. Even if 25 is larger than 19, it doesn't make its way over here. And we'll talk about how this all works, but just remember, the only rule, well, aside from the fact that each node can have 2 children at most, the only real rule is a max binary heap, a child must be smaller than the parent. So again, no implied ordering between siblings. We can't figure out if, that this by default is smaller than this, or that this is larger than that, like we could in a binary search tree. There is no real relationship here, other than 2 siblings, we know they're smaller than the parent. And then also, here's a min binary heap, same idea, except we're working the opposite direction. The smallest node up top, and then both children, the only rule is that they are larger than the parent. Same thing here. But again, there is no relationship between siblings other than the fact that they are larger than their parent. All right, so lastly, why should you care about heaps? Why do you need to know this? Well, we'll come back to this once we actually learn how to implement them, because we're going to learn to implement something called a priority queue using a heap. Heaps are really commonly used to do this. That's all I'm going to say for now. If you want to research what a priority queue is, you can, but we will be implementing one using a heap in just a bit. But they are very commonly used data structure. Basically, think of a queue where we can add things in and take them out, keep track of things to do in an order, where we can also assign a priority, an importance level to each item. And it will move to the correct spot in the queue depending on its importance level. So we'll come back to that. They are commonly used. And they're also used quite a bit with something called graph traversal. So we saw how to traverse a tree. We're going to learn how to traverse a graph, which is a little more complicated. And heaps are often used to assist with that. But really, this is just a high-level overview. We're going to first learn to implement heaps, and then we'll come back to priority queues. But just know that's really the main motivation. They're used all the time for priority queues. That's why I added this. We'll come back to this. Okay, so next, we're going to learn why I like heaps, why I think they're kind of fun. There's sort of a cute little way that we can store them or represent them using a data structure that already exists. So that's coming up next. All right, welcome back. So I hope everyone made it through the important stuff in the last video. I get it if you skip the introduction, the objectives, all that stuff, but it's really important to understand the difference between a binary heap and a binary search tree. They look similar, but they are different. So here we have a max binary heap. 41 is the root. The 2 children need to be smaller. That's really the only rule. Also notice that we fill in the left first. So I mentioned that in the last video. The left child is added and then a right child. And then if we were to add a right one here, the next child would be added to the left down here. So we'll come back to that when we actually implement this. So suppose we wanted to represent this, we want to basically write code to model this, just like we've done with every other data structure. We could implement a tree class and a node class, and each node has a left and a right. And we could do the same thing we did for a binary search tree, but there's actually an easier way. So we can actually use a built-in data structure, an array or a list, same thing, just different names in different programming languages. We can use that to store a binary heap, and I'll show you how. Okay, so there's a little tiny bit of math involved here, not much, just a little multiplication and addition. But if we look at this binary heap, so this is a max binary heap again. We have 100 up top, the largest value, and then below it, we just have 2 values that are smaller than 100. So again, we don't have the 2 next largest numbers. It's just 2 numbers that are smaller, 19 and 36. And then they both have 2 children. It's kind of hard to see in this diagram, but if we were to actually expand it vertically, we wouldn't have any space left to show this. So this down here is our array or our list where we're storing values. It's indexed. So we would have 0, 1, 2, 3, and so on. So we put 100, we put the root at the first index of 0. Here we go. I added in the indices down here. And then what we can see, let's say we want to find the children of 100. Well, we know where they are. It's the next 2 values. The left child is 19. The right child is 36. So we have index of 0. Its children are index of 1 and index of 2. All right, well, that part's easy because it's sort of a special case at the beginning. But now if we wanted to look at the children for, let's say, 19, well, we have to skip over 36, right? And if we look at this diagram, 19 has 2 children, 17 and 12. So the 17 is the left child, and 12 is the right child. So we have a parent at index 1. Its left child is index 3. Its right child is index 4. Okay, next, let's go to 36. So we had 36. We have to leapfrog over to get to 25, which is its left child, and 5, which is its right child. So index of 2 corresponds to 2 children at index of 5 and 6. Okay, well, I didn't do this for every single value, I promise. We're about to skip ahead. 17, though, its children start at index of 7 for 9 and index of 8 for 15. So can you figure out the little mathematical relationship here? What if you have an index for a parent, where are its 2 children located? Here's one more. 5 is the parent. Its children are located at index of 13 and 14. So index of 6 was the parent index, not indices, and its left child was 13, its right child was 14. So what's the relationship here? So for any index n inside of an array, the left child is stored at 2n plus 1, and the right child is at 2n plus 2. Okay? So if we take index 6, for example, we find its children by multiplying that by 2 and adding 1. So 6 times 2 gives us 12. We add 1, we get 13. So that's the left child. We add 2, or we add 1 more, really, we get 14. So they're side by side. Or let's take this index 4, the value of 12. Its children, we multiply 4 by 2, gives us 8, we add 1. So that's going to give us 9 and 10. We add 1, we add 2. 6 and 11, is that correct? Yes. If you follow this line, it's hard. 12's children are 6 and 11. So that's the formula to actually find a child based off of a parent, we take the number, the index, n, we multiply by 2, and we add 1 to get the left, we add 2 to get the right. And we'll be doing that in our code. Hopefully the relationship there makes sense, and you can see how that works and why it works. If not, just we're going to come back to this, and you can just add this into your code and just assume that it works. But I think if you think about it, there's 2 children per each node, and we need a way to flatten that and store that. I like this diagram. It just shrinks it all and smushes it into this list, and you can see how it works. As you move further and further down, you have a lot more children. Anyway, so the other thing is we can work backwards. If we have a child node and we want to know its parent, so it's the same exact math relationship, you just go the other direction. So if we have a child of 6 at index of 9, its parent is at index of 4. Or if we have index 12 for the child, we can figure out that its parent is at index of 5. And the math for that, so if we have a child at index n, we subtract 1, divide by 2, and then also we floor it, meaning we just chop off the decimal, because we can't have 0.5 decimals in as far as an index. They're whole integers. So if we go back and say we're working with 13 right here, index 13, the value is 1. To find its parent, we subtract 1, which gives us 12. We divide by 2, gives us 6. So at index 6, we have the value 5, and that indeed is the parent of 1. Let's try one more. How about index of 10? So at 10, we have this value 11. To find its parent, we subtract 1, which gives us 9. Then we divide by 2. Remember, it's n minus 1 divided by 2 floored. So we take 10 minus 1, that's 9, divide by 2, 4.5. Well, there's no index 4.5, but if we floor it, we just chop off that decimal, we get 4 right here. So the value of 12. Is that indeed the parent of 11? Yes, it is. There it is. So that's the math. That floor part is important because we can't have, like I said, we can't have 4.5 as an index. Okay. So those 2 things we will return back to, because there will be situations where we have a parent and we need to find its children, in which case we do 2n plus 1, 2n plus 2. Or if we need to find a parent based off of a child, it's n minus 1 divided by 2 floored. All right, welcome back. So here is our base structure for our max binary heap class. It's very simple. We are implementing only a max binary heap, but to change it over to a min binary heap or to make a min heap is very simple. Once you know how to do max. So either one could have worked. So we define the class, max binary heap, and the only property it needs in the constructor is a values property. So values will start as an empty list or an empty array, and that's it. We don't need to make a node class like we did for our other tree. We don't need to make a node class like we did for linked lists. We don't need previous pointers or next or left or right. All that we need is an empty array to start. And in this video, I'm going to walk through how we would add an insert method so that we could say max binary heap.insert 10, max binary heap insert 50, and we'll just be storing things in this values array, just like I showed you here, where we can take, instead of having to create a bunch of nodes and connect them manually, we store them in an array and we use their position to model the actual structure. The position, their index, the individual numbers corresponding to each item's position is what actually gives it the structure of the heap. So we'll move things around and swap them. So to make something else's parent, it just goes to the correct index. So we'll come back to that, but that's all that we need to store is an array of values. Okay, so as far as the process to insert something into a max binary heap, it's a little bit more complicated than a binary search tree, but it's still, I think it's relatively, I won't say straightforward, but it makes sense if you think about it. It's logical. So what we do, we fill it out from left to right. So all that honestly means, if we have an array like we have here, if we're trying to insert something to the tree, the only place for it to go is at the end. So we just push on to our list. We just do a array or list.push the new value, whatever it is. Now, of course, it's most likely not going to be in the right spot right off the bat. Let's say we push in 500. Well, that is the largest value in here. 500 is going to need to work all the way up to the top. So we add it to the end, and then we do something called bubbling up. And what that means is basically we swap it until it finds its final correct resting place. in a max binary heap, the larger values are going to bubble up to their correct spot. So what that looks like, if we were to step through it, if we add 55 to the end of the list to our array, this is what we're actually storing in our class. This is just a nice visualization, but this is what's stored. 55 goes to the end. That's not the right spot, but we just put it there to start. And that means by putting it here, its index means it is a child of 33. So this is index of 2 right here. So its children are at index 5 and 6. 2 times 2 plus 1, 2 times 2 plus 2, right? So this is 0, 1, 2, 3, 4, 5, and 6. Those are the two children. As we can see here, it's all set up correctly. Okay, so next we bubble up. And what that means is we take this node and we compare it to its parent. So we compare 55 to 33, and we swap them because 55 is larger. There's a little swap. It's not quite an animation, but you can see it there. And the change is reflected here. So before we had 55 as the child of 33. That was not the correct place. We just put it in without caring. Then we compared it to the parent, and we swap. Then we compare it to the parent again. How about 41 and 55? Well, we swap them. So now our data structure looks like this, where we have 55 as the root, and its two children are 39 and 41. All is good. Everyone's happy in the world of our max binary heap, because now every node satisfies the property that its two children must be less than the node itself. So again, we insert and then we bubble up by swapping. And this is why it's important when I talked about how you could find a parent based off of a child. So if we had, like we had here, 55, we add it to the end, we need to find its parent at 33 and compare them. Then we swapped them. Then we need to find 55's new parent, 41, and compare them. And we swap them. So here's an animated version on Visual Algo, Visual, whatever it is. They give you numbers here so you can see the actual order in the array, in the list that's underlying it. So if you would read it, left to right. This is the first item, then second, third, and so on. So if we were to insert a value, let's say 26 is not going to be exciting. Let's do, how about 100? To insert that, the very first thing we do is add it to the left. The way we add it, it always goes to fill out the left first and then the right. And that's, we're using an array. And so just by adding it to the end of the array, by pushing onto it, it's going to be added here automatically. Okay, so we start here, and then we're going to compare it to its parent. 144, this is a max binary heap, so we are going to swap them. And now we take 100 and compare it to its new parent, which is 70. Well, 100 is still larger, so we're going to swap them. And now we take 100 and we compare it to 99. It's larger, so we swap them again. And now we're done. And this is our new max binary heap. If we insert another value here, like 15, it's going to go right there, and that's where it stays, at least for now. If we were to insert another one, it goes to the left, and it stays there. Let's do a larger value. Sure, 58. We insert to the right, we swap, now we're done. So again, there is no order between the left and right siblings. There's no shared property other than that they are less than their shared parent in a max binary heap. Okay, so the pseudocode to do this, here's the simple version. You just write a method called insert. It accepts a value. We're not working with nodes or anything. It just accepts a number. Insert 10. You add 10 to the end of the values array. You just push 10 into values. And then you bubble it up to its correct spot. So that's the more complicated part. It's easy to add it to the end of the tree, super easy, or the end of the heap. To get it to go to the right spot, it's a little more work. So here's some more detailed pseudocode. If you would like to do this all in one method called insert, you can do that. You could also write a method called insert, which calls another method called bubble up. Totally up to you. But the way bubble up will work, once you push the value in to the end of the values list or the array, it's at the very end, and it's probably in the wrong spot. It could be in the right spot, but it's most likely in the wrong place. So here are the basic steps. You're going to take the item at the last index, the end of the array, the very last thing you added in, and then you're going to find its parent. Remember the math that I showed you. Index minus 1 divided by 2, and you floor that. So that gives you the index of the parent. and then you just compare the value at that index compared to the value that you just added to the end of the array. And then you see which one is larger. It's a max binary heap. If the one at the end we inserted is larger, we swap the values. If it's not, then stop, you're done. It's in the right spot. And you keep repeating that process as long as the values element at the parent index is less than the values element at the child index. Or the other way around, as long as the child is larger than the parent, keep swapping. So you'll swap, and then you'll reset the index to now be the parent index. So you're moving it, right? So if we went back to this example, at the very beginning, we add 55 to the end, we find its parent. Let's just look down here. So we add 55 to the end, we find its parent based off of the index, we subtract 1, we divide by 2, the index is this item at the value is 33, index is 2. We compare, 55 is larger, so we swap. Now the index that we're looking at is this index here, 2. And so now we find, using that number 2, we find the parent. So 2 minus 1 gives us 1, divided by 2 gives us 0.5, floored gives us 0. So the index now that we're comparing it to is index 0. And we compare these two items, and we end up swapping them. And then we stop because there is no next index to look at. There's no parent of this. So you could add that into your code, make sure that it accounts for that and it doesn't break, or you don't hit it undefined or something. Okay, so those are the basic steps. Again, insert, just push to the very end of the list or the array that you're using to store the values, and then bubble up. And here's a pseudocode for bubble up. So try it on your own. Write 2 methods if you prefer, or do it all in one insert method. In the next video, I'll have an implementation. All right, welcome back. So let's implement insert on our max binary heap class. But first, we need to actually define the class. So I'm going to do that now. Max binary heap. It's super simple, at least the skeleton of it is. We have our constructor, and all we have is the property values, which is an empty array. That's where we're going to store the heap. And down here, I just have in the comments sort of our initial, this is exactly the same representation, or it's the representation of this data here, just so that we can work with it and visualize what's happening. So the pseudocode, we're going to define a method called insert. It takes an element or a value, and the easiest part, we push it on to this dot values, just add it to the end. So for example, if this is what values look like, if we just pushed 55 onto the end, that's the first step. Then we need to do the harder part, which is bubble up. And I'm going to define a separate method just to do that, just to keep this. I just personally like to do it this way. You definitely don't have to. You can do all the logic here. So I'm going to call this dot bubble up, which doesn't exist. So I'm going to define that bubble up, and then in here we'll put the actual logic. So remember, what we need to do is take this item, take the index of this item in order to find the parent, which is going to be, if this is index of 6, we need to take 6 minus 1, which gives us 5, divided by 2, which gives us 2.5, and then round down or floor, which gives us index of 2, which is this. So let's make a variable to store the element and also its index. So we're just going to find the last element. So that's going to be this dot values dot length minus 1 gives us the index. So let's make a variable called index. This will keep track of where the newly inserted item is. It will start as the last index, but if we swap, we're then going to update index to be here, for example. And if we swap again, we'd update it to be wherever we swapped with. I'm using let and const, just it's good to include some ES 2015 syntax. So that's the index. I'm going to make a variable just to store the value of the element itself. So const element, so index is going to be changing, const will just stay as the element. So it's going to be this dot values IDX. This is just an easy way. I mean, we could also make it so that the method bubble up accepts the element, and you wouldn't have to do this. I'm fine with how it is here. So we're grabbing the index 6 in our case. And when I say in our case, actually, right now there is no heap that exists. So I should do that now. Let's do let heap equals new max binary heap. And I'm just going to initialize it. I'm going to cheat and just have it start as this so that we don't have to insert those manually. Then we're going to call heap.insert 55. Okay, so if we've just done that, we've added 55 to the end, we've called bubble up, index is 6, the element is 55. Okay, now what we want to do is loop. So I'm going to start with just a while true and just continue to loop over and over and over, and then break out at an appropriate time. So our process is going to be to take this element and compare it to the parent element. So first we need to find the index of the parent. So to calculate that, I'll make a variable called parent idx. Remember the formula? If you don't, it's over here. We take the floor of the index minus 1 divided by 2. So I'm going to do math.floor, and then we need to add extra parens, subtract 1 first, and then divide by 2. Okay, so let parent index equal math.floor, index minus 1 divided by 2. And actually, let me just get rid of the loop for just a moment. Let's just do a console.log parent index to make sure that's working. Run my code. Oh, 3 B's. That's not correct. Hopefully you saw that before me. Try that again. Okay, so it's giving us 2, printing out 2, which is the parent index. Is that correct? Let's look. 0, 1, 2. That gives us the element 33. That is indeed the parent of 55. And if you wanted to verify that based off of this sort of a visualization, you can see 33 is the parent. Okay, so now what we want to do is compare the item at this index to our element 55. Compare those two things. So we have the index of the element and we have its parent index. So now let's do a comparison. So I'm going to make a separate variable to do this because it's a little bit shorter. So let parent equal this dot values of parent index. Because we have to, we don't have to do a variable, right? We could just compare this, but I like to just label it as parent. Then what do we want to do? Well, if parent, we could do it either direction. If element is greater than parent, that means we want to swap. So I'm just going to do this dot values of parent index equals element. So that's putting 55 here. And then we need to set this dot index, this dot values of index to now be parent. So that should swap the values at least one time. We're not looping still. So, and that's only if the element is greater. So in our case it is when we insert 55. Let's just see if it works. Okay, so let's look at our heap now. And you can see we have 55 where 33 used to be. So that's correct. Now we just need to get it to happen again, or keep happening. While what? Well, I'm going to keep it as while true for now. But I'm going to change my loop a little bit. So we're getting the parent index, we're getting the parent, we're checking if the element needs to be swapped, then we're swapping. But if we leave it at this, we're going to have an infinite loop that goes forever. And also, we're never updating index. Index is always still remaining 6. So every time through, parent index is going to be this. So we're going to be comparing 6 and 2, those indices, over and over and over. So what we want to do is actually update index to be parent index. Because if we swapped 55 and 33, we now need to look at what's at 55 and find its parent. So we need to change index to be this, the old parent index. So we're almost there. But rather than doing it this way, where I'm checking if element is greater than parent, I'm actually going to change my logic entirely. Well, I'm going to flip it on its head and change this conditional to be the opposite. If element is less than or equal to parent, if that's the case, break. And then otherwise do this. So it's just a slightly shorter way of saying that. So while true, forever, find the parent index, find the parent, the value there. If the element is less than or equal to the parent, break, we're done. If that's the case, if, for example, we inserted, 11, we compare 11 to its parent 33, we don't swap, we're done. However, in the case of 55, first time through, this is what we had. Then we swap, so that we end up with 33 here and 55 here. And then index now is this, and parent index is right here. So we're working with 0 and 2, and we compare again, and we swap again. So if we actually look at what we get, it's still not going to be totally correct. But if we look at heap, you can see that 55, okay, you can see what's happening. We got a swap where at index 2, we have 41. That's correct. So we swapped 41 and 55. So we went from, I'll just put them all in a row. From this, where we had 55 at the end, we swapped it to here. Then we went to this, where we swapped 41 and 55. But our code keeps going one more time because it's trying to compare 55, which is index of 0. And then it's trying to find the parent index, which is 0 minus 1, negative 1, divided by 2, rounded down or floored down, index of negative 1, which is going to be undefined. And it's comparing undefined to 55. And so you can see it actually does a swap, and we end up with 55 at index of negative 1. So this is a simple fix. We just want to stop, instead of while true, let's just say while index is greater than 0. Because if index is now 0, we know that the element is the largest element. For example, 55, if we swapped it again, we should stop now. There's nothing we could swap it with. So just stop. Now, let's test it out and see if it works now. Look at our heap. All right, we have 55 there. Now let's insert something that's not as large. Let's insert something that isn't going to be swapped at all. Let's do like 1. Look at our heap. Nope, not hiao. If we look at it, you can see, all right, it stays at the end. Now let's insert something like, I don't know, how about 45? And we look at the heap again. So we made a swap with 18. So it was at the end here, we swapped it. So then 45 is right here. And then we did one more swap between 45 and 39. And so we end up with 45 right here. And that's correct. And then finally, let's just make sure if I try and insert something massive that is larger, 199, it should bubble its, oh my gosh, the same typo again. It should bubble its way all the way up top. Let's just look at the values. And it does. Okay, so that is insert. Again, it's just one way of writing it. There are many possible variations, but they all follow the same idea where you insert it at the end and then you bubble it up to the correct spot. Hey, welcome back. So we've seen how to insert nodes or elements into a heap. Now let's talk about the opposite, removing things. The standard place, the one area we usually remove from, is the root. So in a max binary heap, that means removing, well, it means the root in either case, but it means removing the maximum element, the highest value. And in a min binary heap, it means removing the lowest value, the minimum. So the method we define, we could call it remove. We could also call it extract maximum or extract max. And that's pretty common to see that. So when we go on to implement a priority queue, for example, where each element is assigned a priority level, and we want to remove things based off of their priority level, well, the highest priority in a max binary heap, at least, will always move up to the top. And so that's where we'll remove from in our priority queue. I can't speak. We'll always take that root out. It will be the highest priority item. Anyway, the way it works is similar to insert, where we can't just remove this and, well, we can't just leave it, of course. We have to have a new root. But then we can't just we could swap with any element and just put it there, but it's most likely going to be wrong. It's not going to be, the correct compact heap. So what we do is we remove this element and we swap it, or we put the current last value. This is a standard way of doing it. The last value, 12 in our case, would go here, and then we adjust, which I've always heard as sync or syncing down, but I was looking at Wikipedia. There are many terms for it. The procedure for deleting the root from the heap, effectively extracting the max element in a max heap, or the minimum element in a min heap, and restoring the properties, so making sure everything is all kosher again, is called down heap, aka bubble down, percolate down, sift down, trickle down, heapify down, cascade down, and extract min and max. Nowhere did it actually say sync down, which is what I've always heard. So I was a little bit offended by that. They have so many options, but my life is a lie. There is no sync down. It's the same idea though, right? So we had bubble up, which was when we had an element at the end that is in the incorrect spot. It's the last item, and we bubble it up to the correct spot. Well, in this case, what we're going to do is put an element at the root that is most likely wrong and have it bubble down, sink down, sift down, trickle down, whatever, to the correct location. So for example, if this is what we start with, nothing's been removed yet, but if I want to remove the root, I call extract max is what our element or what our method is. It's going to take 41, remove it from this array or this list, and then take 12 and put it in place. So we end up with this. We remove 41 and 12 goes to the beginning. And so we end up with this structure, which is not a correct heap at all. So the next step is to then call whatever, sink down or sift down, and we compare it to its children. So we take 12 and we look at its two children. We take whichever one's larger, which 39 is, and then we're going to swap, assuming that 12 is indeed less than 39, meaning that 39 deserves or should be the new root more than 12. So if that's the case, which it is, we swap. Okay, so now that 39 is in the correct spot, we go back to 12 and we compare it to its new child, or both new children actually, and we're going to swap it with the larger one, if one of them is larger. If both of them are smaller, then we're in the correct spot and we don't need to swap. But in this case, both are larger. So we're going to swap 12 and 27. And we do just that, and we're done. 12 has now sunk down to its correct location, which is basically at the very end again. It's just that it used to be over here on the left because we had an extra node, but we removed that node, and so it had to sink its way down to the correct spot. But now everything is happy again in our binary heap. So let me show you one more slightly better animated example. On Visual Algo, they call it extract max. It's not called remove. But if I call it, step backwards, it removes that root, which is 70, and it's going to swap. Well, it's not actually a swap. It's going to replace it with the last element, 31. So 31 gets up there, and obviously that's wrong. It's not the largest element. It's not the max. So we compare it to the left and the right. And both of them are larger, but 67 is larger than 65, so we're going to swap there. Now 67 is the new root. It's the new maximum element. It's in its correct spot. It's cemented in. Now we do the same thing. We compare 31 to 45 and to 58. Both of those are larger. We're going to swap it with the larger one, which is 58. There we go. Now there are no children left. We have nothing to swap it with, and so it's in the correct spot. And then we would presumably return 70, which was what we removed, right? That's the whole point. We're removing the max, and we probably want to return it. One more time, just for good measure, we'll go faster. This time, what was the element up top? 67. All right, we remove it. We replace it with 15. And now we compare. All right, 65 is largest, so now we swap there. Now we have 15 and 40 and 53. We swap with 53 because that's a larger one. And now it's at its final resting place. It doesn't go anywhere else. All right, so here's the pseudocode if you want to try and implement it. Write a method on our class, our max binary heap, called, you could call it remove, or I'm going to call it extract max or extract maximum. It doesn't take any arguments. You call it, and what it's going to do is just return the root, the old root, but also it's going to delete that root and update the tree, or technically the heap. So you can follow this pseudocode if you want. You don't have to do this line for line, but basically take the first value and swap it with the last one. Then remove that last one, use pop so that we get the old root. So we're going to have the root, swap it with the last item, and then pop the last item. But effectively, take the first item out and then replace it with the last item. Then you have to get to the sink down portion, this sift down, percolate down. Basically, start at the root index. Start at 0. Start with a little counter or an index variable, and find the index of the left child and the right child for that index. So for 0, it's easy, right? We know that if an element is at location 0, its first child is just location 1, and index 2 is the right child. But basically do this math, 2 times index plus 1, 2 times index plus 2. And take those two values that you find, the two children, then take those children and compare them to the element at the parent, the first element, the new root. And if one of them is larger, you're going to swap. However, take note that if both the left and the right children are larger than the parent, then swap with the largest child, as we saw over here. If I step backwards, when we swapped 15 up top, we compare it to 58 and 65. Both are larger, but you're going to swap with 65. And then after you swap, if you do swap, the child that you just swapped with, that index becomes the new parent index, and then you look for its new children and you repeat the process. You loop and keep swapping, loop and swap until neither child is larger than the element, which means that you've successfully sunk down that element that you put at the root. It needs to sift its way down to the correct spot. And then at the very end, return the old root. That's the whole point. That should be the maximum. So give this one a shot. Again, remember the math here. It's 2 times index plus 1, 2 times index plus 2 to find the left and right children given a parent index. Take that, find those children, compare both children to the element that is now at the root, and then swap if you need to. And then you now kind of shift your window over so that instead of looking at the root, you're looking at the new index and looking at its children, and you keep going until there's nothing to swap. All right. So give it a shot, extract max. I'll have a solution up next. All right, welcome back. So let's go ahead and implement extract max, or remove, whatever you want to call it, to remove the maximum element in our max binary heap. So I'll define our method, extract max, no arguments, and we basically have, going back to our pseudocode, a couple of basic steps. We want to take the first element and remove it and replace it with the last element. So there's a couple orders you could do that in. I think what I'm going to do is first store the value of the max. So I'm going to call it max, just equal to the first value, this dot values 0. So that gives me the first element. Like suppose we had, 55. Yeah, sure. Let's just copy this one. If this is what we have, I'm going to take max and set it equal to 55, but it's still in there. Then I'm going to pop the last item off. So I'll call it end this dot values dot pop. So that gives me end. Then I'm going to take end, which is now not there, it's in a variable, and I'm going to put it here. So I just set this dot values 0 equals end. Okay, so that puts 12 here. Wait, was it 12? Yes, that puts 12 right there and removes it from here. And now 55 is in max. So at the end, we do want to return max, but of course, 12 is not at the correct spot. We now need to start that bubbling down process, or whatever, simmering, percolating down. Yeah. Okay. So there is one edge case here that we'll come back to. Let me make a note of that so I don't forget. Okay. So once we swap after this point, so this is removing the first element, the max, replacing it with the last element, which is almost definitely not the max. Now we need to do the whole bubble down thing, whatever we want to call it. Trickle down. Okay, so I'm going to define a method to do that. I'm going to call it this dot sync down, just like I did with over here bubble up. I'm going to just make a separate method. Okay, so instead of trickle down, I guess I'm going with sync down. So over here, I'm going to define sync down. Again, no arguments. You could write this to accept actually an index. It's possible that you would want to, something in the middle. You swapped it, or you wanted to sync down, or you didn't remove from the beginning. Although that's pretty rare. But I'm just going to make it start at the top element always and sync down from there. The root index of 0. So I'm going to start with an index variable. So index is going to equal, I don't even need anything. It's just going to equal 0. It starts as the very beginning. So if this is what we're working with, and let's say that we just put 33 here, this is what we're working with. It needs to sync down. We're going to start at index of 0 right there. And now we're going to find its children. I'm also going to define a couple other variables here equal to the length of the array. So I'm going to call it length. And just set that to be this dot values dot length. This is just going to help me shorten my code a little bit. And also I'm going to do one more for the element itself. So I can have the value like this, or I could actually just set that to be 0. So rather than, having to write this to check the element, I'm going to do this dot value 0. So it's just going to be equal to 33. at the beginning, and it's going to stay at 33. We might be moving where 33 is, but the element is always 33. That's where we're trying to position that number, 33. Okay, so I'm going to loop while true, and at some point I'm going to break out, but that's going to be a little ways from now because we have to start with our main logic, which is we found the parent index. Let's find the two children, the left and the right children, 2 times index plus 1, 2 times index plus 2. So let's start by computing left child index, let's do IDX, equals 2 times IDX plus 1. And then I'll duplicate that line for right child index, but instead add 2. So the first time through, we're talking about 0. Its children are here and here, but if we're talking about 39's children, we're going to multiply that index 1 by 2, so that gives us 2. And then we add 1, index of 3. So its child is here and here. Okay, so this gives us the 2 child indices. I'm also now going to make variables to store the value at those indices. But I can't just right away say, I couldn't do left child equals this dot values left child index. And the reason for that is that there's no guarantee. I could do the same thing for right. There's no guarantee that I'm going to find an element there. There's the potential that this is out of bounds. For example, 41 right here has 1 child at 12. But if we calculated the index for its right child, it's out of bounds. And so if I tried to access it, I would get an error. So we need to make sure it's valid. And I added this right here. Make sure it's not out of bounds. So I'm going to do that before we actually access the value. I'm going to just, for now, just initialize or declare left and right. But leave them, I'll call them left child and right child, and just leave them empty. Okay, one more variable I'm going to make. And this variable is going to keep track of if we did any swaps in this loop. And at the very end, if there were no swaps, so I'm just going to say if swap is null, we're going to break. So this is our condition at the very end to get out of the loop if we never swapped. So at some point, we're going to set swap equal to true or to something else, but not yet. Okay, now we have those variables out of the way. Let's start with the left side. The first thing I want to do is check, is this index in bounds? So if left child index is in bounds, and that's easy, we can just say if it's less than the length. If it was greater than the length or equal to it, then it's out of bounds. So if it's a valid index, we're then going to set left child, this variable that has no value right now, to equal the value at that index. Okay, so for this case, we start with 33. We calculate left and right child indices. So the left index is the number 1. So we check, is 1 less than the length? That's yes, that is. So we're going to set the variable left child to be this dot values of 1, which is 39. So now we have 39 in a variable. And what we're going to do is compare it to 33, which is our element. And that's easy. We just check if left child is greater than the element, then we're going to set swap equal to left child index. This variable swap is going to keep track of the position that we're going to swap with. So for example, in this situation, 33 is in the incorrect spot. We compare it to 39, and at the beginning, it looks like this is where we're going to swap it to. But then we also compare it to 41, and it turns out, oh wait, 41 is actually the larger number. We're going to swap it with this, with index 2. So we're going to keep track of that index with this variable swap. And we're going to reset it to null every time through, so that if we don't find a number larger, because the only time that we're swapping, we're setting it to anything other than null, is when we find a larger number. If there is no child, left or right, left nor right, I guess, that is larger, then swap will stay null and then we'll break out. Okay, so that's the left side. Now we need to do the right side. Same sort of thing. If right child index, we got to check if it's a valid index before we try and access it. We're going to set right child equal to this dot values right child index. Okay, so that gives us the value like 41. Now we compare 33 and 41. Is the right child greater than element? But there's a little extra logic here because remember, we only want to swap with the value that is largest of the two. So in our case, between these two, the right child is largest. So this would work fine. If right child is greater than the element, it's the last thing. We check the left first and then the right. But imagine that it was the opposite, which, ignoring the fact that this may not be a valid tree, heap, let's say that this is what we had. If we're trying to compare this to 41, okay, so we decide this is larger, we're going to swap to here. But then we look at the right child. All that we're doing is comparing 33 and 39. Well, this is larger than 33, swap here. But remember, we want to swap with the largest of the two. So I'm going to change this a little bit to say, if we haven't already swapped, meaning if the left child was not larger than element, so that would be if swap is equal to null still, and right child is greater than the element. But there's also another scenario that this doesn't cover, which is when the right child and the left child are both larger than the element, but the right child is largest. So to cover that, because that means that swap is set to the left already. So that would be like in this scenario where 39 is larger than 33. So we set swap to be this index of 1. But 41 is actually the largest, the right child. So I'm going to add a second condition in here where we're going to say, or if swap is actually set to something and at the same time, the right child is larger than the left child. And this is kind of a gross little statement here. So we also need parens around this entire thing, or I like parens at least. So I'm going to do it like this and indent so that we can read it a bit better. So these are the two conditions where we end up setting swap equal to right child index, because either the left child never was set, so swap was never set to the left child, none of this was true, so swap is null, but the right child is larger than the element, or swap is not null, meaning that the left side was set to be swapped, but the right child is larger than the left child. Oh boy, it gets tough talking about this stuff sometimes. So if that's the case, we're going to set swap equal to right child index. This whole little conditional here, I shouldn't say little, this long conditional is checking to make sure that the right child is the one we're swapping with, like we have in this case, versus in this case, we're going to swap with the left child. Okay, so at the end of the day, at this point, swap should be set to the left or the right child index or null. And if it's still null at the end, that means we're done. So we have this if swap equals null, break. Otherwise, if this doesn't run, it means that swap is either left or right index. Then we need to actually do the swap. So the swap is going to be this dot values index, which we haven't seen in a while. So remember, it started at 0. So this is the index of the thing we're looking at, 33 to start in our example. Okay, so this dot values index equals this dot values of swap. Now swap is going to be an index. It's either the left child index or the right child index. So it's either this or this. Okay, so that's part of the swap. Then we have to do the other part. This dot values of swap equals element, which we already saved in a variable. So we basically say, all right, the thing that was here is now equal to 41. And now at this index, we're putting 33. So we swap the two. Okay, and the final thing we have to do is update the index. Keep looping and swapping. Oh, this part, the child index you swapped to now becomes the new parent. So here we just set index equals the thing we just swapped to. So that if we started with this and we swapped 41 and 33, now our index that we're starting at is here, and we're looking at the children that correspond to index of 2, rather than 0 where we started. Now index is set to 2, so then we calculate the children, which is going to be 2 times 2 plus 1, so index of 5, 3, 4, 5, and then index of 6, which doesn't exist. So that's why we have this check in here to see if those exist, and we keep going. Okay, let's test this out, see if it works. It's kind of a lot of code. I move this down. or get rid of that. I'll come back to this edge case in just a moment. So we insert, this is what it looks like at the beginning. Let me run the code, see if we need, no typos so far, okay. Now let's try and do a heap.extract max. So we get 55, which is the max. And what does heap.values look like? Okay, so if we look at it, we took 33 and put it here, removed that from the end, and we got rid of 55. And we compared it to its two children. We should have swapped 33 and 41. That's correct. And then we look at 33's children, and there's only one child to compare it to, which is this child, and we don't swap, and so we're done. And that's what we got: 41, 39, 33, 18, 27, and 12. Let's try one more. Let's look at heap.values again. So we took 41 out, and we replaced it with 12 here. And then we repeat the process, which means that we swap 39 and 12. And then we look at 12 and compare it to its children. Well, it has two children, which are 18 and 27, and we swap it with 27, the larger of the two. So 12 ends up back here, 27 ends up right there. And there we go. So this is now what we ended up with: 39, 27, 33, 18, 12. Okay, now the edge case I was talking about. If I keep extracting max, how many are left in there? Okay, here we go. If I try and do it on the last one, it should be empty now. But if we look at it, it still has 12. And I extract it again. I could do it many times, and it still is set to 12. What's happening is just a little bloop up here where if there's only one item left, we are basically popping it off and then reinserting it. Because if this is what our list looks like with the number 12, we're saying, all right, the max is equal to 12. Then the end is also equal to 12. So pop it off and save it in a variable called end. Then we're adding this dot values of 0 equals end. So we're putting it back in there, which we don't want to do. So we only want to do this. We only want to add it back in and sync down if there's anything in there. We should leave it empty otherwise. So let's just add an if and just say if this dot values dot length is equal to, or let's just say is greater than 0. Then we'll run this code. Otherwise, we're not going to, because it's empty and we don't want to mess it up. Okay, let's see if it works now. So we have our heap, and I'm going to do a extract max and keep doing that. Okay, and now we hit heap.values and it should be empty. And it is. And every time I try and call it, we get undefined, and that's good. That's how it should work. If I do an insert, we look at heap.values again. We have 10 in there. Let's do one more. Heap.insert 99. It should be in front. Okay, perfect. It's working great. That's the basic way of writing sync down. You can also do this recursively, which I chose not to do here because I feel like it just confuses a lot of students, but you can find some nice recursive solutions. Share some, if you have something that's more succinct, which is not that hard to do. This is pretty verbose, but I wanted to make it sort of step-by-step easy to look at and understand rather than focusing on just making it super brief. Anyway, that is the process to remove the root, whether it is a max or a min. We would have to change a couple things to make it a min binary heap. As far as the comparisons, because we want to look to see if something is greater rather than smaller or the other way around. But other than that, it's the same general approach. So you take the first item, you take it out, you swap it with the last item, and then you sync it down. Okay, I know it's a lot. All right, welcome back. So early on, I think it was the first video in this section, I talked about why you should know or care about binary heaps. Yeah, they come up in interviews. Yes, they're taught in pretty much every computer science course. But also, they're used really commonly to implement something called a priority queue. And I gave like a 5-second rundown of what a priority queue is. And I said we'd come back to it later. We are now doing just that. We're coming back to it. We're going to explain in more detail what a priority queue is, give some use cases for it, but then also implement one using our binary heap code. So we won't have to write a ton of new code. It's really just modifying what we've already done or duplicating it and changing a few things. So that's what we're going to do here. But first, let's just understand what a priority queue is. So according to Wikipedia, it's just a data structure where each element has a priority associated with it, and elements with higher priorities are served before elements with lower priorities. So we have a collection of data, and each node, each element has a priority associated with it. And we want to basically be served, that's passive voice, I guess. We want to retrieve, we want to take one element at a time out of this list or this structure, whatever we're using to store it. We want one thing at a time that we're going to tackle next. Just like in an emergency room at a hospital, you have a bunch of people waiting. Everybody is assigned, internally at least, some sort of priority level. And then a nurse or a doctor comes out and retrieves one person at a time based off of that priority level. So, somebody who walks in with a gunshot wound is going to be seen before somebody with a scratchy throat, for example. So anytime you need to manage data or information of varying priority and have things, that you're inserting and they may not be the lowest priority. You're not inserting things in order. You might be adding something in. Like in the ER example, someone walks in with a gunshot wound. Well, there could be 100 people who were there first, but they all have the flu. The person with the gunshot wound is going to be seen first. So a priority queue should account for that. It always serves the highest priority element. Here's a more real-world example. On Unix machines, on every machine, there's a bunch of processes happening behind the scenes. Thousands of different things that are running behind all the magic of your computer. And you can view it, or view a lot of them at least, on a Unix machine by typing the ps command. And I've added in some additional options, but what it's showing me here is the process ID. And then here, it's technically not called priority, it's called nice, but it is a priority level. And you can see they're pretty much all the same, but then we have certain things that have a higher level or higher nice value, which actually means a lower priority, I'm pretty sure. So if 0, all of these are going to be basically served in the order that they are added in. But then occasionally there's something, let's see, is there anything else? Come on, there's got to be at least one. There we go. Here we go. This thing has a nice level of 10. It's just a priority, or same thing here. This is another thing for Adobe, apparently. So I am not the person to explain how this all works. I know very little about the underpinnings of your operating system and what's happening behind the scenes. I basically know how to find one of these and stop it if it's broken, and that's about it. But what I'm trying to illustrate is that there's a ton of things happening at any given point on your machine, but at the end of the day, there's an order. They're not just all going at the exact same time. Things are being served or being worked on in an order. And there's a priority that each element gets, which is used to determine that order. Another thing worth knowing is that priority queues are separate from heaps. They are just an abstract concept. You could implement a priority queue with an array or a list, which I'll show you in just a second. It's not a great version, it's slow, but it's possible. It's just like when we say list, the idea of a list. Well, you could have a list as a linked list. You could have a list implemented as an array. There are different ways of implementing them. It's just a generic sort of abstract concept, a priority queue. So you could go about it like this. You could use an array or a list and just store things as they come in. So something's inserted, you put it at the end or at the beginning. And then when you need to remove something, when it's time to serve the next item, you would just iterate over the entire thing and just check what's the highest priority. Keep a variable. We start, okay, priority 3, that's the highest. And then we hit 1. Also, it's worth noting, oftentimes a lower number actually denotes a higher priority. So in this case, if we're working for the lowest number, we would start here. Okay, the lowest number is 3. Then we get to 1. Okay, well, that's lower. So this is our new element that we're going to serve, but let's keep going. Nope. This is still greater. This is greater. This is greater. Then we hit the very end and we realize, all right, this is the highest priority thing we're going to serve. The lowest number, the highest priority. So that's not a great approach because every single time we need to serve something new, we have to go all the way through and compare something to every single item because it could be at the very last node, it could be at the very first item. It's not a nice way of doing it. It's simple, but it's naive. So, as you've already probably surmised, we're going to use a heap. So here's an example of how we could do it. This is using a hospital sort of metaphor, emergency room. People walk in and they have different injuries. So at first, our heap is empty. There's one person who walks in with a low fever. So they're going to be the next person to get help. We always remove from the top or from the root of our heap. Right now, there's only one element. It is the root. So they get help first. But let's say that before they get helped, someone else walks in. they have a concussion. That is a higher priority element or value, right? They need to be seen before someone with a low fever. A high fever, oh, that's up for debate. A low fever, though, I think they can wait. Just take a little Tylenol or Motrin, whatever you take. So the person with a concussion are the next to get help now. They are the root. Someone else walks in and they have a lower priority. Well, we don't put them at the root. It's a heap. So this value is less than this priority. So they're going to be below it. It's a child of this parent. So we're still following the rules. Whether this is a min tree or a min heap or a max heap, it doesn't really matter as long as we're consistent. So what we end up with is the concussion is going to be served. They're the next person to get help. But then someone comes in off the street with an exploded head. It's not good. And they need help immediately. So when we insert something with a higher priority like this, it's going to, remember how this works, we add it to the end and then we bubble up in our heap. So if we added it here, we bubble it up to the top, we end up with exploded head with the red priority is the next thing to get help. Then concussion is its first child, then the drunk person, then the low fever. But really all that matters is what the next thing is. And then someone else comes in, they have the flu. Well, they're not as high a priority as an exploded head. So we're just going to put them here for now. So then let's say the exploded head person gets help. So what happens? Well, we remove this node from our heap. And remember what we do is we swap it with the last node and then we have it sync down to the correct spot. And this is what we end up with. So now our heap is serving somebody with the next highest priority, the person with a concussion. And if we were to remove this one again, we would end up with the new root as the flu. So everybody who has a yellow priority will be served before everyone with a green priority. Anyone with a red priority is served before everyone else. Anyway, it's kind of a convoluted explanation, but that's how a priority queue works when you use a heap. All that we care about is the top level element, the minimum or the maximum thing. And every time we add something in, that could potentially be updated. Every time we remove something, we always remove from the top. And so there's going to be a new element there that wasn't there before. So a heap works really well because insertion and removal they have a time complexity of log n compared to if we just did this naive version. If we had 1,000 elements in here, every time we wanted to remove something, if there was no order to them, we were just comparing every single priority to find the lowest or the highest. We're working with O of n time complexity. So if there's 1,000 elements, we're talking about 1,000 comparisons roughly. So that's not good. That's not a good version. It would work, but if we use a heap, it's much faster. Okay, so that's an explanation into what a priority heap is, or priority queue is using a heap. But again, you can implement them in other ways, but a heap is a classic one. On Wikipedia, it goes as far as to say that many people confuse the two or conflate the ideas because a priority queue is so commonly done with a heap. But again, it is an abstract concept. You can implement it in many ways. All right, so next up, I'm going to give sort of my overview, the pseudocode for how we could implement our own. And then after that, I'll have a solution. All right, so if you want to try and implement the priority queue class, using what we've already learned about binary heaps, it's very, very similar. We just have to change the comparisons a tiny little bit. So make a class called priority queue. Basically, you could just rename your binary heap class, just copy it so you can, if you want to save the original, change it to priority queue. We're still keeping a list of values, and that's all we need structurally aside from all the methods. We just need to store the values. So that's unchanged really aside from the name. What is different though is we're not just storing numbers like we were in the past, where we stored numbers and we just used the values of the numbers and compared. We didn't have a class. We didn't have individual items that we were storing, we had numbers, but we didn't have a secondary class like node, which we are going to with our priority queue, because now each element has a value, or each node has a value and a priority. Oops, did I spell that right? Yeah, I guess that is right. I mistakenly thought I spelled that wrong. Anyway, so we have this node class. And each node will look something like this. We have a value. It could be a string, it could be a number, it could be something else. It doesn't matter because we're not using the value to compare. We're only using the priority. So each node has a priority, and that's the value that we use when we actually construct and rearrange the heap. If something is inserted, we're going to compare its priority to the other element's priorities. Once we remove something from the top, we need to sync down, a new element to the correct spot. We're going to compare using its priority. Also, just for some variety here, we are going to implement a min binary heap rather than a max. We've done everything as a max. Often, as like in the case of a hospital, also with the way that Unix, the nice values work, a lower value is going to be served first. So in this case, priority 1 is the highest priority, 2 is a medium priority, 3 is a low priority. So in a hospital, at least some that I've been to, the most critical emergency things are like level 0, level 1, and the least critical are level 5 or something like that. Okay, so we have 2 classes now, a priority queue class and a node class. Each node has a value, which doesn't matter for what we're doing. We just need to initialize it, and a priority, and that's important. Okay, so here's how it should work. Write a min binary heap. So all that means, to make it a min heap, you're just going to need to change the comparisons a little bit. Where in the past, we were swapping things. If one thing was greater than something, we now swap if one thing is less than, or vice versa. Otherwise, it's the same idea. So each node has a value and a priority. Use the priority to build the heap. As something is inserted, compare the priority. As something is removed, compare the priority. Then 2 methods. Rather than an insert method and an extract max, we're going to reskin them as enqueue and dequeue. Honestly, the naming doesn't really matter, but what you do need to change in your code is that when you insert something, as I already mentioned, you compare the priority level. You don't compare the value of the element itself, you compare the priority. When you remove something, you're going to remove the root of the heap, the top level thing, which is the highest, technically the lowest number, but the highest priority. We remove that, and then we have to have, we swap it with the last element. We have it sink down or percolate down, compare using the priority. So that's our goal. Give it a shot. In the next video, I'm just going to take our code we've already written and alter it. So you won't have to watch me, reconstruct the entire heap over like half an hour of code. We'll just take what we've done and just turn it upside down a tiny bit to make it a priority queue. All right, welcome back. So let's implement our priority queue by copying what we've already done. So here's my max binary heap. I just copied it into a new file. And I'm going to first change the name, priority queue. And we're going to leave it as this.values. Then at the bottom or somewhere else, I'm going to define our class node. And node in the constructor takes in a value. I'll call it val. And we just set this.val equals val. And then we also have, it also takes a priority. Whoops, did not add that in. There we go. Okay, so now we have each node has a value and an associated priority. Now we have 2 things we really need to do. The first is make sure we're comparing based off of priority everywhere rather than value, or well, not even value, rather than just the element itself, because we used to not be using this node class at all. We used to just insert things as is. So when we insert something, we're not just going to insert an element, we're going to insert something, so we're going to take a value and a priority, and then we're going to make a new node. So let's do new node equals new node, val, and priority, and then we're going to pass that in, this.values.push, instead of element, it's new node. So that's going to add it to the very end, and then we need it to bubble up, which is what we have here. So that's all good, but then when we look at bubble up, we have a small problem. It's more than a small problem. Our code isn't going to work at all because we're not using priority. We're just comparing values directly. So index is going to be the same. Element is fine. While index is greater than 0, parent index, this is all fine. But we want to compare if element.priority is less than or equal to parent.priority. We'll break. Otherwise, this.values, okay, and that's all the same. If we are trying to make this a min, so I'm actually going to leave this first as a max binary heap, and we'll come back to that. But just note, this is going to need to change. The other thing I forgot to do is change this to be enqueue, which doesn't really matter. Oh, that's not how you spell it, is it? Is that it? I can never remember. I think that's it, yeah. No. There we go. So enqueue, bubble up. All right, and then instead of extract max, we're going to have dequeue. I think that's right. I hope. And we're going to, let's see, we're going to remove the 0th element. Well, we're going to swap. That's all fine. Then we're going to sink down. So in sync down, we are taking the element, that's all fine. The indices, everything is good here. But now what we need to check is right here. If left child dot priority is greater than element dot priority. If, and then same thing over here, right here, right child dot priority greater than element dot priority. Same thing one more time. Left child dot priority. Okay, so remember right now this is a max binary heap still. First, I might have forgot something. Let's just make sure it works. So we're going to make a new, we'll call it, let's say we're in the hospital. So we'll call it ER equals new priority queue. And then we're going to do ER dot, instead of insert, it's now in queue. And the first thing we'll have is, I don't know, how about just common cold? The priority, if we're doing a max binary heap, how it is right now, this will be a low number, like let's say 1. And then let's do a couple more. Let's also do, how about gunshot wound? It's going to be a priority of like 5. And then we'll also have high fever will be a priority of 2. Okay, so let's try running this. And if we look at our ER, first let's just check out the order. Okay, so you can see gunshot wound. Then its first child is common cold. Its second child is high fever. That part doesn't matter, right? And it's not going to be in order with only 3 elements, most likely. But it will rearrange, hopefully, when we dequeue. So let's check. ER.dequeue, we would expect to get gunshot wound. All right. Next, we expect to get high fever, which we did. And then common cold. And then nothing. Okay, so that's working. We have a max binary heap where we're getting elements, based off of the largest number for the priority. If we wanted to switch it around, it's just a matter of coming up here and changing these less than signs to a greater than sign. Same thing. Where else is the other one? Here. Change that to a less than sign. We're just reversing our logic. And one other change we should make, right here, instead of calling this variable max that we're removing, it's now refers to the min. It doesn't actually make a difference functionally, but it's just nice to call it min instead. Okay, so let's do our same thing, except now I'm going to change these priority numbers because something like gunshot wound will have priority level 1. That's high priority. A cold, maybe we'll have like 5. A high fever, we'll give it priority of 4. Let's do a couple more. Let's do common cold. How about gunshot wound? I don't know, broken arm. So that will be pretty high priority, but not the same as a gunshot. So let's give that priority of 2. And then also, let's do another priority of, let's do 3. So middle priority, not that bad. Let's say like glass in foot. I don't know. Okay. So I don't know if this ordering actually makes sense. So I'm going to run the code. And we're going to do our first dequeue. And what would we expect? Well, we want the value that has the lowest priority, gunshot wound. All right, that worked. Next, we expect the value with the next lowest, which is broken arm. Then glass in foot. Then high fever. Then common cold. So you can see that it doesn't matter what order we inserted them in. It's all about the priority. And it's giving us the highest priority element, or the lowest value priority, but the highest actual priority at any moment. And it's a min binary heap now. It's logically the same thing. We just changed some comparisons and renamed a variable from max to min. Otherwise, it's the same idea. Now, one thing that we should consider is what if something has the same priority? Like if there are 2 elements in here with the same priority? Well, right now our code doesn't guarantee that they actually would be returned based off of insertion order. So if it's a queue, so you would expect it, for example, if someone with a common cold got there first, and then we have another person who has, another common cold, same priority level, you would expect to serve or help this person first. And you can add logic to make that work, but by default with our heap, it's not going to work that way. There's no guaranteed order between siblings, between things that are on the same level of a tree, or of a heap, technically a tree. But in our heap, it's just that a parent has a relationship with its 2 children, but the 2 children aren't necessarily, the siblings aren't in a particular order. So what we could do is add logic basically to add in a time here. So we could do like this dot, I don't know, insert time equals date dot now or something like that. And then when we're comparing, instead of just comparing the priority, we would also say if the priority is identical, which one of these was inserted first. And then we would swap based off of that. But that's not really that important at this point because the actual algorithm for your priority queue, the comparison itself, will likely change if you're ever actually writing one. In the real world, it's usually not just, a priority level. It might be a priority level plus how many resources it takes up or how resource intensive it is, plus how long it's been waiting. These different things that might impact the comparison rather than just a direct priority versus priority. Anyway, here's our priority queue. It's a min binary heap that's powering it, or that we're actually implementing it with. You insert things using enqueue, in whatever order they go in, it doesn't matter. It's based off of their priority level. Pretty nifty, I think. Much, much better than trying to do this with an array or a list and just traversing the entire thing to find the next item with the lowest or highest number. This is much faster. We're going to talk about big O, but it is log n for time complexity for insertion and removal. All right, priority queue done. Welcome back. Let's wrap up with binary heaps by talking about how they perform, their big O notation, mainly for time complexity. So binary heaps, both min and max heaps, are great when we're talking about insertion and deletion. That's really what they excel at. They're very fast. Big O of log n for time complexity. So remember, from a binary search tree, that is very quick when we compare it to all the other sort of standard big O's that we've seen. So all the way down here in this sort of light green, not the dark green, but the light green. So as n grows, the amount of time that it takes to insert or to remove something from a binary heap grows slower. It grows at the rate of log n approximately. So let's talk about why that is. So first, remember when we say log n, it's actually log base 2 of n is what it's really referring to, although that doesn't actually matter because we're just kind of referring to this general trend. But if we think about it that way, when we talk about a binary heap, we're talking about log base 2 of n. Well, each time we go down a step in a binary heap, or just any binary tree structure, we have 2 times the number of nodes. So we have 1 node, then 2, then 4, then 16, and so on. So let's focus on insertion. If we want to insert the number 200 into this heap, worst case, which we know is true actually because it's the largest number, it's going to end up over here. But along the way, we only have to compare it 1 time per row, right? 1 time per level of this heap. So we compare it to the first parent, which is 9, because remember, everything's inserted on the left. So 200 is going to be a child of this 9 element. So we compare it, that's 1 comparison. We compare it to its parent, 2 comparisons. Again, 3 comparisons, and then the 4th comparison. And then at this point, we realize, okay, well, 200 is the largest element. If this is a max binary heap, it needs to be the root. So that's 4 comparisons. So for 16 elements, we're talking about 4 comparisons. So you can think of it as 2 to what power gives us 16. 2 to the 4th power, 2 times 2 times 2 times 2 gives us 16. Or if we were to hop over here, this is a maxed out. Unfortunately, I actually can't insert anything else into this heap. The limit is 31 nodes. But if we were to insert something right here, this is where it would go next to be the 32nd node. We would, if it was, let's say we insert 100, which is larger than the root, to find its way up here, it's 1 comparison, 2 comparisons, 3, 4, and then 5 comparisons. So for 32 nodes, we're talking about 5 comparisons, 5 operations. So as n grows to 32, we think about 2 to what power gives us 32? 2 to the 5th power. 2 times 2 times 2 times 2 times 2. So another way of putting that is every time we double the number of nodes, every new full complete layer, we are only increasing the time that it takes by 1. So when we get to 64 nodes, we're talking about 6 operations. And hopefully you can see why it'd be the same for removal, because we insert at the or we remove from the beginning, we swap something to be the new root, and then we have to compare. And if it has to sift all the way back down, the max number of comparisons is going to be the same as we saw here. It's log n. It's the same idea between insertion and removal. Now you might remember from when we talked about binary search trees, where they also had a log n insertion time. In general, or an average/best case, there is also a worst case scenario. Remember this? The very depressing tree that really doesn't look much like a tree, sort of looks like something else. The big O, time complexity, to insert into this tree or to search is O of n because of the way that it's set up, right? If it's constantly just dot right, it's going to take, however many nodes are in here. That's potentially how long it would take to insert if we were trying to insert 100 or something. This is not a problem when we're talking about heaps. Now, why is that? Well, heaps can never look like this. This is against the rules of a heap. Remember that when we insert into a heap, we always fill out the left side first. So unlike a binary search tree where we might have, an incomplete row, well, I shouldn't call it a row, an incomplete level, instead, everything is always filled out before we move on to the next level. So this entire row, this entire section is done, and then we start inserting here and here, and then we keep going across. So there is no possibility for us to have such a crazy, unbalanced, unhinged, depressing tree. And because of that, worst case is still O of, all the way back here, log n for insertion and removal. Now, binary heaps are not really made to be searchable. Like if you really care about optimizing your search, then you probably want to use a binary search tree or something like that. So time complexity for search is O of n. Remember that when we look at a binary heap like this, there is no guaranteed order or even an implied order between siblings. So if we're searching for the node that contains the value 1, we start at the beginning, well, we can't make a decision. We can't, with a binary search tree, we could say, all right, well, it's less than 86, so it's somewhere over here. That's not the case here. It could be anywhere because 1 is less than 86. It's the only condition that we know for sure is true about all of these nodes is they're less than 86. So then we have to look over here and, well, once again, we can't really make a decision. It's somewhere down here maybe, but it still could be over here. And so we keep going and, we're going to have to search here and here and here and here. And finally, we'd find 1. But it also could be over here. There's no rule that it has to be here. It's just in this given scenario, it is. Now, that is a bit of a worst case. Now, if we were looking for something closer to the top of our heap, like we're looking for the number, let's say 80. Well, we start here, and we know that 80 is definitely less than 86. So we have both of these. Well, over here, we know that 80 is less than 85. So it's going to be over here potentially. Over here, we have 77. Well, 77 is not greater than 80, so we can cross off this side of the tree. There is no number greater than 77 over here. So we can make a decision and eliminate some of it, but there's no guarantee every step of the way that that's the case, and it depends on the value that we're looking for. So technically, if you do look it up, I believe the big O for searching is O of n divided by 2 on average, but remember that when we have a constant like that, n divided by 2, n times 2, n times 100, it doesn't matter. We simplify it to big O of n. So as n grows, in general, the amount of time it takes to search also grows just at the same rate as n. So it's linear, O of n. So these are not optimized for searching. But when we're talking about insertion and removal, that's the name of the game with heaps. All right, we have time for a quick recap. So we've spent a lot of time talking about binary heaps, which are a type of tree. Well, technically, a binary heap is a type of a heap. We could have other types of heaps, just like a binary tree is a type of a tree. So we have binary heap, which is a type of a heap, which is a type of a tree. Okay, so they're useful on their own, but also to implement other data structures like priority queues, like we just saw a couple videos ago. They are either, when we're talking about binary heaps, they're either max binary heaps or min binary heaps. And the way that it works, the one rule that governs it, aside from the structure, meaning that each node can have a maximum of 2 children. The other rule in a max binary heap is that every parent is larger than its 2 children. And a min binary heap, every parent is smaller than its 2 children, or however many children it has. We fill them out from left to right, so we don't end up with these unbalanced, wonky, one-sided trees. A heap is always filled out from left to right. It looks like a heap. It's a pyramid of stuff. It's a heap, a pile. And with just a little bit of math, we can pretty easily represent heaps using arrays. So we don't have to make pointers. We don't have to make nodes that point to next, or left and right, or child, or whatever. We can just store them in an array because the rules that we follow makes it very easy to flatten out or represent just using numerical indices. And so that's a nice, easy way of doing it. You don't have to represent heaps that way. You could do heaps. You could make your own class and make a bunch of nodes like we did for binary search trees. It's just easier to do it this way. All right, so that's binary heaps. Hey, welcome back. So we have a brand new section with a new data structure called the hash table, also known pretty commonly as a hash map. So these are used so frequently, you've probably used them all the time, I certainly have, because they're built in to pretty much every programming language out there, whether we're talking about JavaScript or Python or Ruby or Java, just Scala. Pretty much every language has a variation of a hash table or hash map built in as a default type. So you don't have to do anything. Just like with an array, most languages have a built-in array or list type, and you can just use it out of the box. So we will be implementing our own version. We will make our own, but just like with an array, you're probably in 99.999% of the cases going to want to use the built-in array class or list class or whatever similar structure there is. There's no reason to reinvent the wheel. Same with the hash table. But there's a lot of really cool stuff for us to talk about as to how they work, what hashing is. I should actually just talk about that on this slide. So in this section, we're going to explain what a hash table is. That will be in this video. Then, 2 for 1 there. We'll define what a hashing algorithm is. Define what a hashing algorithm. Oh boy, these slides, that's not ideal. So define what a hashing algorithm is. Discuss what makes a good hashing algorithm. There are certain characteristics we're looking for. Then we'll talk about what happens when collisions occur in a hash table, what that means for there to be a collision, and then 2 strategies for handling them, something called separate chaining and another thing called linear probing. Those sound like 2 different methods of torture. So we'll get there, but let's start by just discussing what a hash table is. So as I already mentioned, these are all over the place. You've probably used them in whatever programming language you prefer. Hash tables are used to store key value pairs. And yes, so are arrays. Arrays associate a key, like 0 or 1 or 2 or 3, to a value, which could be anything else, but those are strictly numeric. Hash tables are not. And on top of that, the keys in a hash table are not ordered. So in an array, of course, the indices start from 0 and they go up to some number, they keep going. There's a specific implicit order. Hash tables, that's not the case. And another cool thing about hash tables is that they are fast for finding values, for adding new values, for removing values. It's all fast. So we'll talk about why that is and how it works. But first, let's go into more detail on just why you should care. So as I mentioned, pretty much every language out there has some sort of hash table structure. Because of their speed, they're used really commonly, and they're also just data itself often lends itself to being stored this way. Yeah, if you have sequential data, great, you could use an array. If everything has an order and there's a number that makes sense to associate it with a position, use an array. But a lot of the time, our data may not fit that pattern, so we could use a hash map or a hash table. So here's just a quick overview from certain languages. These are what their implementations of hash maps or hash tables are known as. So Python has a dictionary or dict. JavaScript has objects and maps. And I did put an asterisk here because in objects, you actually are only allowed to use strings as keys, but it's the same idea. Behind the scenes, it's implemented basically as a hash table. Java, Go, and Scala have something called a map or maps. Ruby, they didn't even bother. It's just called a hash. So these all are key value data stores, and they implement hash tables. So hash tables are sort of a generic idea, and you could implement them in many ways. Dictionaries in Python, maps and objects in JavaScript, maps in Java, Go, blah, blah, blah. Okay, so let's pretend that those disappear. We're not able to use the basic built-in JavaScript objects or Python dictionaries. If we still want a key value data store, we need to implement our own. So that's what we're going to do. Imagine they just mysteriously disappear. How would we write our own version of a key value pair hash table, a data store? So imagine we want to store some colors. We're making a website. We have color codes, hexadecimals, which are really difficult to keep track of or to differentiate between. So we could just store them in a list like this, But this, there's an order here that's implicit, but there's no reason that we'd want to store them in a particular order. It doesn't matter. I don't know which color this is, what color that is. You get the point, hopefully. This is not a great way of storing colors unless we just need a random color at any point. That would work. If we're just picking something random out of here, great. But if we need particular colors at a particular moment, it's not great. It's not readable. What do these colors correspond to? So rather than using indices or numbers to access the colors, it would be much better to use, human readable keys like pink, which this is pink, or a version, one type of pink. Orange, red might be, or it is this color. Cyan, this color. This would be much better if I could just say, give me colors of pink or colors of cyan, which, here we go. Colors of cyan is much better than colors 2. So we're going to try and implement this structure on our own. Even though, of course, in JavaScript and Python, you would just be able to do this out of the box. But if we didn't have access to dictionaries or objects or maps, how would we do this? So that's what this section is focused on. I think it's kind of fun because we get to go into some fun detail onto what hashing is, what hashing functions are. We're going to talk a little bit about some math, get into prime number land, discuss how prime numbers play a role in this. It's all sort of fun stuff. So that's our goal, reinvent this basic mapping, key value pairs. All right, so in the last video, we talked about wanting to store information using a key like cyan or pink or H or any string. And by the way, in a hash table, it doesn't have to be a string, but we're just going to focus on strings just to narrow down some of the complexity. But either way, whatever we use, it's not a number. So let's say we're using a string like cyan rather than a number like 0 or 2 or 1 million. This is a lot clearer. So we want human readability, but of course it needs to also work. It needs to be a real thing on our computer. And unfortunately, computers don't know how to find something or insert something at index pink or index hello world or out damn spot or H. Computers don't know how to do that. Thankfully, we have hash tables to the rescue. Okay, so quickly, just a little preface here. Remember that every language, at least every language I've worked with, has a built-in implementation of a hash table. We are actually reinventing the wheel here, which is usually something I try and avoid in these courses, but it's just to help us understand how this works. It's important to understand what's happening behind the scenes. I like to think of it as, we're building a little model, like a toy model of a car engine on our desk to help us understand how real car engines work. If you actually had to use one, you would probably pick the Ferrari engine that you magically have laying around in your house rather than the toy model you built out of cardboard. But either way, you understand how they work now. I don't know if that's a good analogy, honestly. So that's what we're doing. We're trying to build a model to understand how it works. And to do that, we're going to use an array or a list, a way of storing information where we have to use numbers. So what we do in a hash table is we take an input. Again, we're narrowing it down to say strings like hello or pink. We need a way to take pink and turn it into a number that we can store in the array. So if our array goes from 0 to 99, it has 100 slots, 0 to 99, we need a way to convert pink to a number between 0 and 99, and then we store the data at that number. So there are functions that help us do that, and they're called hash functions or hashing functions. I'll actually have a separate video after this one where I talk about the complications of writing a good hash function, why it's difficult. We'll talk about some examples of existing famous hash functions. They are used all over the place. There are very intense teams of people, like multi-country efforts of people working on hash functions because they have a lot of applications in security and cryptography. But what we're talking about are going to be very simple, limited in scope hash functions. The idea is we pass in a string. If this is our array where we're storing our data, we have 10 slots. We pass in a number to our hash function. There are many, many implementations. Just some mysterious hash function over here. I guess you can't see where I'm pointing. To my right, it's a box. If I pass in the string pink, it needs to give me some number between 0 and 9. And every time I pass in pink, it should give me the same number. So it happened to give me 0, the way this hash function is worked, the way this hash function is built. It gives me 0. So I store pink as the key and then this as the value at index 0. Then I go to the same hash function and I say, hey, here is orange red. What does that convert to? Well, it happens to convert to 7, so I store it at 7. I do the same thing for cyan, and I get 3, so I store it at 3. So that's how we go about storing things. Now, if somebody asks me, hey, what's that index, index cyan? Well, our code still doesn't know what index cyan is, but I can take cyan and pass it to the hash function again and say, hey, what was the number you gave me earlier? And it gives me 3. And then I go to index 3. Same thing for pink. So this is why it's important we always get the same number back. If that doesn't happen, then this whole thing is broken. Because if I ask for what's the index of cyan and it gives me 9, there's nothing here. It always has to be the same thing. Once we've inserted something, we need it to be consistent. So writing a hash function that works, that takes a string or any piece of data, an image, a PDF, a video, and somehow spits out a number, it's not easy. And that's what we'll talk about in the next video. All right, welcome back. Let's talk a bit more about the hash function part of our hash table. So we'll be using hash functions to convert keys, like the string pink or cyan, and turn that into a valid array index, a small number. But hash functions have uses all over the world of the internet and privacy and just computing in general. So on Wikipedia, the first use that is listed is indeed hash tables, what we're talking about. But they're also used to help protect your data, to store your data, to authenticate you when you log in on a website. They're used in cryptocurrencies and cryptography in general. There's many types of hash functions, including a subgroup called cryptographic hash functions, which are crazy, the math and the science behind them. This is the stuff where I said there's like teams of researchers working on them. Cryptographic hash functions are a crazy branch of cryptography, which is already a crazy branch of science. It's fun stuff. I have a course am I allowed to say that? I may or may not have a course on this topic and on cryptocurrencies and how it all fits together. Okay, I hope I don't get in trouble for that. Anyway, what we're talking about are just basic hash functions. And the definition of a basic hash function is just a function that takes data of arbitrary size, whether it's 1,000 characters or 1,000,000 characters, and it's going to spit out data of a fixed size. It's going to map an input to an output of a fixed size. So for us, let me just show you an example. This is in Python, which I know a lot of you probably don't know. This is not a Python specific course. That's not important. Languages like JavaScript actually don't expose a built-in hash function, but Python does and some others do. So I'm just going to use this here to demonstrate. This is one type of hash function. There's many implementations, but this one allows us to pass in some data, like let's say hello with an exclamation point. When I hit enter, I get a number. I'm not going to count the characters or the bits, but of this size. And I can do it again and just change something slightly, like make it capital H. And I get a number of the same size. It's shifted over because this negative sign was there. But if we look at the same number, it is the same number of characters, but it's totally different just from changing that H. But I could do a single character like A, and I still get this really long number. Or I could do a super long string that's much larger than that number, and it's going to be condensed down to this. Now, a couple of things that we should talk about. One, so this is a fixed size. This is similarly sized data no matter what the input is, and that's important. The other thing that I want to talk about is in most cases of a hash function, we can't work backwards. This is actually meaningless on its own. If all we have is the output, this is usually a one-way function, meaning that I can't just take this and figure out exactly what generated this number. So this hash function is generating pretty large, well, relatively small in the grand scheme of things compared to other hash functions, but for us, it's too large. We don't want to store numbers, at this index in an array, because then we're going to have a ton of empty space in our array. We want to, store stuff in an array of like 200 or 20 or even 10 spots, 10 elements. And this is like, what, trillions? I don't even know. More than trillions, probably. So we're not going to use this hash function. We're going to write our own simple one. But let's talk about what makes a good hash function. So first up, it needs to be fast. We don't want to spend forever hashing something because when we insert something into our hash table, it needs to be hashed. But also, when we go and fetch it or update it or remove it, every time we try and access it afterwards, we still have to run that hash function again. Right? I have to say, hey, what's the hash of pink? Then that's going to give me a number, and then I'm going to go to that number in the array. And then if I'm trying to update pink, I'm going to say, here's pink, what's the hash? So we want it to be fast. we want to make sure that it's relatively random, or random's the wrong term. We want to make sure that it distributes things uniformly so that things don't cluster. We don't want a dumb hash function that's always going to just give us the middle of an array or position 0. It's useless if every element is stored at the same spot. Now, we might have collisions, and we'll talk about how to handle that. We might have, if we're only storing things in 100 spots in an array, if we're storing like 500 things, we're going to have to share some cubbyholes, some elements there. And that's okay, but we want it to be pretty evenly spread out. And then lastly, we want it to be deterministic, and this is really important. It means that every time we pass in one input, we always get the same output. It's determined that we're going to get the same output. We don't want to we don't want there to be any uncertainty or multiple answers or outputs per one given input. So we want the same input to always give the same output. So let's just quickly run through those. Here's an example. This is a bad example, which is why I wrote non-example, of a slow hash function. We don't want this. All that it does is at the beginning, it loops 1,000 times, 10,000 times, and just prints something out. And then it does the hashing. All right, that's silly, but we want to try and keep things quick and fast. We don't want to have to loop a ton of times. We want something that is constant time. So we're going to write some of our own hash functions in just a bit, but keep that in mind. We want it to be fast. We want it to distribute values uniformly, so not like this, which just gives 0, as this is a valid hash function. If it meets our definition, it takes an input of any size and it maps it to an output of fixed size. It just maps every input to 0, which is not what we want. And then deterministic. So this also is not a good one because it is non-deterministic. It involves a random number, multiply it by 1,000, and then floor that. That's not good because that's not going to give us the same output every time for the same input. So in the next video, I'm going to show you a simple hash function that we could write that will work with strings only, but it meets some of these criteria, and then we'll try and tweak it and make it better. All right, let's try and write our own basic hash function, for now, just with strings. So the goal is to write a function, let's just say it's called hash, and we pass in a string like, I don't know, pink. But on top of that, we also pass in a length of an array. So if we're trying to store our hash table in an array that is 100 items long, we would pass in 100. So this will map pink to be a number between 0 and 99, a valid index in that array. If we did pink, 9, this is hopefully should give us a number between 0 and 8 so that we can store it in the array in a valid position. So to write this, let's ignore this last thing to start. How would we just convert pink to a number? There's many, many ways, but remember it needs to be reliable, deterministic, meaning that it is reproducible every time we get the same output. So we could just take the length of pink and just call it a day and just use 4. The problem with that is that a lot of strings have the exact same length. So if we're working with, the English dictionary and we're trying to store words, I don't know what the most common length is, but they're definitely small strings, traditional words. They're not very long. So we're going to have very, very clustered data. If we had an array that was 1,000 positions long, they'd all be less than, I don't know what the longest word in English is, but they're all less than 50 characters probably. And most of them are less than 10 characters. So that's not really great. But there's another thing we can do, which is to use the underlying UTF-16 character codes for each character. So every character has a numeric value associated with it. And you can actually access that. Like if we do A, there's a method called char code at or car character code at. And we have to pass in an index like 0. And that corresponds to the 0 index of this string. There's only one character. And it gives us a number. Or if I had hi and I did 0, it's going to give me the number for h. If I did it for 1, it gives me the number for I. So these numbers we could basically add them together for a given string. Also, to make it a little simpler, if you subtract 96, this will give us the alphabetic ranking or position. So for example, A is now 1. If we did D, it should be 4. And if we did Z, that should be 26. Perfect. So that works. It gives us, the position in the alphabet, starting from 1 up to 26. So we can use this, And on top of that, we'll add them together. So we'll continue to do this for every character in a string. So let's say I have a variable called total to store everything in, and then we're working with the string hello. So we would do total plus equals the character at position 0, so car code at 0, and then we'll subtract 96 so that this is just to make it easier for us. You don't have to subtract 96, it's still valid. So that adds 8. Then we're going to do character code 1. So that's for E. We do this in a loop, of course. This is for L. This is for the other L. Then we get to O, right? Is that it? 1, 2, 3, 4, 5. Yes. So that's our total value in there. So we get 52. But then we also need to consider that we talked about calling our hash function like this, where you'd pass in a string and then a length. Let's say 11 is our length of our array. We need an index that is going to be valid, and 52 is not. It's too large. So how do we keep it within these bounds? The simplest way is to use modulo. If you don't know or don't remember modulo, it's the % operator in JavaScript and in pretty much every language, programming language at least. Think of it as, you divide something by a certain number and then you take the remainder. That's what we store. That's what we return. So 13 mod 3, for example, 3 goes into 13 how many times evenly? 4 times, right? 4 times 3 is 12. The remainder is 1. We have 1 left over. So if we take the length of the array that we're trying to store, if I say 11, we take total, which is 52, and I modulo, or mod, 11, we end up with a number that is valid to store our data in, which is 8. So whatever the number was, we could take a giant number like this. If I mod by 11, we're going to get a valid array index now between 0 and 10. Just to prove that one more time, keep adding something. You can see we're getting these numbers that are valid array indices. So I have the function already written in the slide. Here we go. It looks like this. Function hash, it takes a key like pink, an array length like 10, and then we make a total variable. We loop through the characters in the key, P, and then I, then N, then K, and then we add the character code for each character to that total. And actually, the way that I decided to do it here is to use the mod array length as we build the string, as we total up the string. So instead of doing a mod at the very end, we add each thing in, we modulus by the array length, and then we start over. Again, the way the hash function works is not the focus here, but I just wanted to show you this is a basic hash function. It's not perfect, but if we called hash with pink and we want to index less than 10, this one gives us 0. We do it with orange red, we get 7. We do it with cyan, we get 3. So it appears to work. I do have it over here as well. If we run it, let's call hash on pink just to make sure. And we will call 10 so that we get an index between 0 and 9. I always get 0 no matter what. If I quit my browser, I restart it, I'm always going to get 0 when I call pink with 10. Now, if I did, let's do orange. I also get 0, so that's something we have to consider. We'll evaluate whether this is a good or bad one in just a moment. Let's try blue. 0 also, no. How about cyan? Okay, so we get 3. How about purple? We get 8. And maroon? All right, so you see we do get these numbers and they're all less than 10. So that works, and every time I call it, I get the exact same output. According to the rules that I laid out in the last video, there are a couple of problems with this current hash function. First, we're going to ignore this one, but it only hashes strings, right? If you tried to give it a number or a Boolean value or something like an array, it's not going to work because we're using a string method. So that's a problem in general if we're trying to actually implement something legitimate. But we're not going to worry about that because that's beyond the scope of this. We're only caring about strings. But a bigger problem is that it's not constant time. The time that it takes, the number of operations that we do, depends on the length of the string or the size of the data. So if we pass in a larger string, it takes longer to hash it. It scales along with the size of the input. So that's not good. We want to fix that. And also, this one's important. It's not very random. Our data can be clustered relatively easily. And so we're going to talk about in the next video ways of improving number 2 and 3 here. We, of course, we're going to end up with clustered data when we're working with numbers, between 0 and 10. There's only, 10 options for our values. So, of course, we're going to have some duplicates. But still, this is not perfect. There's ways of making it slightly more scattered. And I'll give you a hint. It involves using our friend, the prime numbers. Our friends, the prime numbers. Okay, so in the next video, we'll improve this so that we don't end up with this loop, so that we can have a constant time for our time complexity, and then also add some prime numbers in to make this a little more random or distributed evenly. Welcome back. So let's try and refine or revise our hash function from the last video just a little bit. So it's still not going to be revolutionary. It's not going to, blow the minds of computer scientists around the world. It's going to be pretty bad, but it's at least a little better than what we had in the last video. So we're going to focus on improving its performance a little bit so that it runs closer to constant time. And then also we're going to try and increase the randomness, the distribution of things throughout our buckets in our hash table. So here's the code. This was the original one that we had. And the first thing we'll do to make it a little bit faster, so if our key length if our key approaches like 200 characters or 500 characters, although there is a maximum length to a string, but let's just ignore that and say as our key becomes 1,000,000 characters, we're not going to loop over every single character. All that we'll do is add in a minimum. So we're going to take math.min between the length of the key and 100. So whichever one of those is smaller is what we're going to actually loop. So if our key is 30 characters, then we're going to just loop 30 times. But if our key is 1,000,000 characters, we'll just do the first 100. So this is not a perfect solution, but this will work for us for now, just as a slight improvement. And it's really, honestly, the reason I even put this here, because we're not going to work with any characters or any strings that are greater than 100 characters anyway. I just included this to really hit on the point that you want your hash function to be as fast as possible. But we're going to work with small strings that are like 10 characters anyway, so this doesn't honestly matter. Now, the second thing that we're going to do is add in prime numbers. So I'm not going to go into a ton of math here because, frankly, I don't understand half of it. There's a lot of, I actually asked one of my friends, this is a math PhD, and I talked to him about this, and he wasn't totally clear on exactly how it works either, but hash functions almost always take advantage of prime numbers. And there's a couple reasons, but it comes down to reducing collisions, meaning that we don't want data to be stored in the same buckets if we can avoid it. We want to make sure that we are spreading data out as much as possible so that it's faster to retrieve. So anyway, I'm not going to go into a ton of detail or really any detail because it's complicated, but just know that prime numbers, when you use them, especially at the end, if the length of your table itself, the array that you're storing data in, is a prime number, like 31 items long or 13 items long, generally the larger the better, the less likely it is for you to have collisions. And just to illustrate this point, did a little research. There's this question on Quora that has a really good answer. There's a lot of really bad answers to this question on Stack Overflow. People don't really explain it. But this, apparently it's from some guest lecture at MIT a while back. And this person ran a little experiment where they hashed 10 million pairs of data, key value pairs, using different hash functions in different sizes of the actual list or the table they stored it in. Some of them were prime and some of them were not. And you can see, let's just take a look at these first two hash functions. For 10 million pairs of data, this is it's called the search cost, basically the measurement of how many collisions there were. So if we take a look, between a prime number, 8191, that's a prime number, 1.92 collisions. Now if we look over here, we use an even number now. Look at all these collisions. This is bad. We don't want more collisions. So just using a different table length, just one number smaller to make it prime, led to a huge, multiple orders of magnitude decrease in the number of collisions. So this is much, much better here. Or same thing with this, a different hash function. We have 90 is our measurement of the collisions. I don't really know how it's established what 90 actually means, but we can compare that to 4,196 collisions when we use a non-prime length for our list. So the hash table that we're storing things in, it's always good to make it prime. Even if we don't go into a ton of detail on exactly why, you can see here just from this table, changing a prime number, so it's just one number smaller, but a prime number length of the table versus an even number, huge increase or decrease, depending on how you look at it, in the number of collisions. So we're going to use a prime number for our length. Okay, so here's our new hash function where we have our key and our array length. This time we should use an array length that is prime. So let's try hashing, hello, and using 13, and we get 7. Let's try doing goodbye with 13, we get 9. Let's try hi, 10. Cyan, we get 5. Okay, so we're not really going to be able to see if our distribution's any better. It's such a small data set right now, and the length is only 13. You want to use a larger prime number ideally, but we're also only storing trivial pieces of data because this is just a learning exercise, so it doesn't honestly matter. But the improvements we made, in principle at least, are to speed this up so that we set a maximum. We're only going to loop at most 100 characters. So if you pass in a huge piece of data, we're just going to look at the first 100. And if at that point, if we have two strings or two pieces of data that are identical for the first 100 characters, that's okay. They'll collide. We'll store them in the same place. If you know that all of your data follows that pattern, like you're storing 1,000 character strings and the first 100 is always the same, and it was the last couple that were different, well, then we'd probably tweak our algorithm to start at the end of the string, for example, or we do something. But just for this sort of all-purpose example, we're going to cut it off at 100 characters, really just to show you that you should consider that, even if it's not practical for us. Then also, we're adding in a prime number, and we want our array length to be a prime number as well, just to decrease the number of collisions, to make our data more distributed, more random, even though random's not really the correct term because prime numbers aren't actually truly random in their distribution. Not my wheelhouse at all. But anyway, whether this is a great hash function or not, and it's definitely not, it still works well enough for us to implement a basic hash table. So that's what we're going to work towards next. What we have to talk about first is how we handle collisions, because let's see if I can reproduce one. Let's try doing what does pink give us? Poink. Okay, that gives us 5 as well. So what happens when cyan and pink have the same index? What do? Do we store them both there? Do we make the list longer? How do we handle it? That's what we'll talk about in the next video. There are 2 solutions, and then we'll actually go and implement one of them, create a full hash table. So that's coming up next. This is our basic hash function, only works for strings. We improved it a little bit. It's sort of constant time, and also we added prime numbers in so that it's slightly better distributed. Okay, welcome back. So in this video, let's talk about how we handle collisions. So when we have a hash function, whatever it is, and we have a lot of data, it's pretty likely or very common that we will have some collisions. Even if we're working with huge data sets, we have a great hash function, we'll still have some collisions. But we're doing none of that. We're working with a small hash table and a bad hash function. So we are definitely going to have collisions. So how do we handle them? There are many strategies for this, but I'm going to talk about 2 of them here. Separate chaining and linear probing. So let's start by talking about separate chaining. What happens here is basically we just store the pieces of data at the same spot using another nested data structure. So it could be another array or a linked list or something else, but we just store them in tandem. Or does tandem only apply to 2? We store them all together. We joint store them. So we can store things, multiple key value pairs at the same position. So for example, if this is our hash table, let's say it's empty. We hash dark blue and we get 4. So we're going to put that right here. But then we also hash salmon and we also get 4. And we also put that right there. Notice that it's in a nested data structure where we have the array bracket here, goes all the way down to here. So they are stored together. This is the first item. This is the second item. So if we were trying to, if someone asked me, what's the value for salmon? Well, we would hash salmon. We get 4. So we go to index 4. And then we just loop through. We look for salmon in this list. We know it's here somewhere, but there could be 10 things here. So we find salmon. And once we find it, then we get the corresponding value out and return that. So that's one strategy. We store things together. If we're using an array, it's easy to just use what we'll do, a nested array. The second strategy that we're going to talk about at least is called linear probing. So linear probing is a bit different. We only store one piece of data at each position. That's the rule that we try and live by. And what we do when there is a collision is we look forward ahead for the next empty slot. It is a little more complicated, but it does allow us to not have data stored at the same index. We don't have to store things in a nested structure. So for example, if we have an empty table again, we do dark blue, we get 4, well, we put that at 4. But then we do salmon, we get 4 again. Well, we're going to look at 4, there's something there. So then we just look for the next empty slot, which happens to be 5. So we could store it there. Then we do tomato, we get 4 again. So we look, is there something there? Yes. So we're not going to store it there. Look for the next one. Is that empty? Nope. Look for the next one. Is that empty? Yes. So we store it there. So that's how linear probing works. So just to recap, linear probing involves storing one thing at each position, and it means looking ahead, or you could look backwards as well, but it's easier usually to look ahead to find an empty space to store something. And that's different than how we handled it with separate chaining, where we store things together in a nested data structure. So we're going to implement separate chaining in our hash table. It allows us to have, more data than the length of our table. We can store more than 10 things in this table. When we talk about linear probing, though, this only allows us to store 10 things because we're only storing one thing at each position. Soon we're going to run out of space, and then what do? Do we remove things, or do we combine it in some way with separate chaining once the whole table's filled? Do we grow the table? There's many options, but we're going to go with separate chaining. But I just wanted to show you there's also linear probing. Okay, so 2 strategies for handling collisions. Now that we've got all this basic stuff out of the way, explaining what hash tables are, writing a hash function, we have that done. We've talked about how we're going to implement or how we're going to approach collisions. Let's now implement our class and actually write the code to make this work. All right, so let's get started. Let's actually build out our hash table class. Now remember, it's not going to be revolutionary. We're doing this really to understand how this all works. Okay, so here's the starter code. You can just copy this or type it out. I'll include it as a file. It's also in the slides. We have our basic hash table class. We have our constructor, which accepts a size for how large the hash table should be. And there's a default value of 53 because we want it to be a prime number. So if we don't include a size, it will just be 53. Then what we do is make a new array of that size and store that as key map. This is where we'll store all of the data, this .keymap. Then I just copied over the hash function. I changed it slightly because now we don't have to pass in the size of the hash table because it's in a class, so we can access keymap. And you can see here, we're modulusing modding by this .keymap.length. So here's the hash function. We will be adding methods like set and get, which will then be calling _hash, passing in a key, and getting a value. Okay, so here's where we're going to start. Our first 2 methods are set and get. So set accepts a value and a key. I should say that the other way around. A key and a value, like pink, corresponds to the value, whatever that hexadecimal code was, 00FF something something. Key and a value. And what we're going to need to do is hash the key. That's the first thing. Figure out where to store it. And then the second part, we're doing this with separate chaining. So it's a little more complicated than just storing the data there because we're going to store it in a nested structure. So just to remind you, rewind here, what that really means is when we hash something, if we get 4, we're going to go to index of 4 and check, is there anything here? If not, we're going to store it there, but we store it in an array, so a nested list already, so that next time through we can just push on to this list. If we have something else, it's really easy to add it in. So basically, you're never going to just store the data here alone on its own. If it's a single item, you're still going to put it in a nested structure. So your logic will be slightly different. You need to hash the key and get that number, go to that position, and check if there's already data there. If it is, or if there is, just push this on to the array that's already there. If not, put an array there first, and then put the data inside that array. So that's the pseudocode for set. You accept a key and a value, you hash the key, then you store the key value pair in the hash table via separate chaining, meaning in a nested structure. Okay, now the way that get works is similar. It accepts a key, like salmon, for example. We're going to hash salmon and get that number back using our _hash function that's already defined for you. And once we get that value, we go to the position, that index in our array, the keymap array, and we retrieve the value. But of course, what that actually means, using separate chaining, one more time, rewinding here. For example, with salmon, we hash that, we get 4, we go to 4, there's possibly more than one item there. So we need to check based off of the key, salmon. We're going to loop through these and try and find salmon. And once we do, we return this whole thing. So there's no guaranteed order within. So we don't know if salmon will be the first one, the second one, the fifth one. We're just going to check. Once we get to index of 4 where salmon is, we're just going to look for salmon in that nested list. And then finally, if it's not in our hash table at all, return undefined. Just make sure it works. If someone tries to retrieve a value that's not there, we don't want to break our code. It should return undefined. Okay, so add these set and get to this code, or use your own hash function if you'd like, but just make sure that it meets the important criteria. It's deterministic, always the same output for a given input, and give it a shot. Let's implement this in the next video. Okay, so let's start with set. It's pretty short. Basically, we've already done this part, accept a key and a value. We need to hash the key, and then take the result when we hash the key, store the key value pair in the hash table at that location via separate chaining. So that's the only caveat that makes it a little harder, is we need to store things potentially nested within that index. But let's start with the basic part. So let's hash our key. All we have to do is call this ._hash, and we pass in the key and save that to a variable. So let's just call that index. So that's going to go give us the index. For example, let's just return index. Okay, so let's come down here and let's make a variable called ht, just so that we can test everything out. And let's try to do ht.set. Let's do hello world, and the value will be goodbye. Okay, it doesn't matter. Now if we run that, all right, so we're getting index 40, and the default is 53 is our size. If we change that to be, 17, try again, we now get 11, something within the bounds, and every time we run this code, we should get 11. Okay, so that's giving us the index, but we don't want to just return the index. What we want to do now is insert the value at that index, the key and the value together, but there's a problem, which is that we need to do the whole separate chaining thing, which if this is our key map, if it looks like this, and it's empty everywhere, let's just visualize that with spaces. If this is what it looks like, we need to insert at index, let's say right here, whatever this is, index 2. If there's nothing there, we're going to put an empty array and then add our list, our key, comma, value, like this. If there's already something there, we're going to need to do a check either way. Is there something here? If there is, then we just add in our next set of key and value, and we nest them. So I'm just going to do a little check. After we have the index, I'm going to do if there is not this dot key map of our index, meaning take the index we got back, like 11, and check this dot key map at index of 11. Is there anything there? But not. Is there nothing there? If that's the case, that means that we set it to an empty array. So that's the first thing we need to do. This dot key map of index equals empty array. And then either way, we're going to do a this dot key map of that index dot push a new array with key and value. And that's it. Okay, so there's two scenarios. If we insert something, we do a set with a key and a value that gives us an index that is currently unused. There's nothing there, it's unoccupied. We're first going to check if it's unoccupied and then set the index of that array, of our key map, to be an empty array. And then we do a dot push with our key and value pair. However, if there's already something in there, like if we had already run this and then we ran something else that gave us 11 again, then this part is not true, it doesn't run. So we just push key and value, a new array, into the parent array of that index. So let's just test that it works. And how could I best test this? Let's make our size pretty small, like 4. And then I'm going to do a couple of sets. I'll fast forward. Okay, I added a couple of things in, just random strings. And if I execute this now, remember I changed the size, the default, to be 4. So it's going to be tiny. And when I run it, if we look at our hash table, what do we have? Okay, so our key map has an array So there's something at index 0, 1, and 3. There's nothing at index 2. And there's 4 things I inserted, and we can see that they are sharing index of 1. So index of 1 contains an array with cats are fine and I love pizza. Well, keys and values. So there's a key value pair and another key value pair, both which were hashed to index of 1. Up here, we have a single entry. Same thing down here, index of 3 is single entry. So if I were to add something else in, let's do ht.set. I don't know, I'm just going to do hi, bye. Where did it go? Let's look. Looks like it was also inserted there. So we pushed it into this existing array inside of index of 1. Let's try it again, something else. Where does it go this time? Okay, so I did French, fries, and that was inserted at index 2. There was nothing there before. If we go back up here, we only had index 0, 1, and 3. There was nothing at index 2. Now there is, and our logic works. We're adding the array, the empty array first, and then pushing in our data. Okay, so that is set. And what we need to do next is get. This video is getting a bit long, so I'll do get in a separate video after this one. All right, in the last video, we implemented set. Now let's work on get. So get needs to accept a key like pink and then go and look in our hash table. Well, it needs to hash that key, right? And we need to get an index. Then we look to see if there's something in the hash table at that index. And if not, then we return undefined or false or something. Otherwise, we need to return the value itself, which depending on how many things are in there, because with the way we're doing this with separate chaining, there could be 5 or 10 values or more, doesn't really matter, inside of this one index. So we need to find the correct key and value inside of that index in a nested list. So retrieve the key value pair and then return it and return undefined if you can't find it. Okay, so I've updated my example stuff. That's not a good way of putting it. I've updated our demo hash table here with some real colors and color codes. These are all HTML or CSS built-in named colors. Medium violet red, and this is the hexadecimal color code. Okay, I've also updated the size up here to be 17. Although honestly, I probably should have just specified it here and then put this back at, what was it at? 53, was it? Doesn't matter that much. Okay, so we have get written here, the skeleton takes a key in. The first thing we need to do is hash that key. So I'm just gonna copy this here. Get an index. Let index equals this dot underscore hash of our key. So whatever's passed in. Okay, then we need to first check, is there something at that index? So let's just do a if this dot key map of that index like that. So if there's nothing there at that index, then we know for sure we can return undefined, right? So if we do find an index, or if we find something at the index, like let's say that we get index of 8. Well, there is something there, but what do we need to do? Well, we can't just return the first thing. We can't return the entire context of that index. If we did that, let's just do return this dot key map of index. First of all, let's run our code again. Let's do ht.get. What color do I have in there? Yellow. What does it give me? Well, it gives me the entire element in our hash table at that index, which happens to contain 2 items. What we want is to return this sub array, the child. So we need to loop over, potentially, any values in there, and then find what we're looking for and return that entire sub array. So rather than that, we're going to do, let's do a for loop. Start at 0, just loop over an array. So while I is less than this dot key map index dot length I plus plus. So this occurs once we've found the correct spot. Like if I look at the hash table, suppose we hash the key yellow, it comes back as the index 8. So we found the data at 8. So now we need to loop over this, which is an array of 2 items. But we could have 10 things here, and we might be looking for the last thing, or the middle thing, or the first thing. But we're going to start a variable at 0, just a standard loop, while it's less than the length of the item at this index, which in our case is a subarray of 2 items. we are going to add one to I, and then we're just going to check if this dot key map, and what we're actually looking for is to see if the key that was passed in equals the first item in this array and the first item in this array until we find what we're looking for. So if this dot key map index of I, that's going to give us this subarray here, or this subarray here. Then we want the 0 item where we're storing the key, because we're storing our key first and then the value. If that equals the key that we're looking for, then we're going to, I'm going to do it on a separate line because it's kind of a long statement, but return this dot key map, and we want to return index of I, the entire subarray. So let's test it out. I'm going to run this. We got our hash table, and let's do a dot get first of something that is in there, like yellow. Okay, so we get the correct array. Yellow is our key, and our value is that color code. If we try and do something that's not in there, we get undefined. Let's just double check. Let's try doing plum. What else was stored alongside? Let's see. In index 8, we had maroon. So let's just check if it works when we try and get maroon, because that's really the harder case. Yep, looks like it's working. If I try and get plum, I already did plum, didn't I? How about salmon? All right, well, it looks good to me, except for the fact that when we do a get, like if I do olive, we get the entire array. We just want the value. So if we come back to get right here, don't return the entire array, return the value, which is the second item, index of 1, 0, 1. All right, try it again. Let's do ht.getOlive. All right, it's working. Right, we get the corresponding value, not the entire thing. And if we try and add something new, let's set are we done to be yes. If we do ht.get are we done, we get yes. All right, so that's working, and that is the basics of get. So we hash the key that's provided to get an index. Then we check if the key map even contains anything at that index. If not, we just return undefined, right? If I try and do this, we get undefined. Otherwise, we're going to check over every single item that is contained at that index. There might be 1, there might be 50. We loop over and we check for each one. Are you the thing we're looking for? Is your key, index of 0, equal to my key that I'm looking for? If it is, return the value. So this key map index I of 1. Not the most intuitive looking code, not that beautiful, but the shortest way of doing it, or at least one of the shorter ways. All right, so that's get. All right, welcome back. Next up, we have 2 more methods to add to our hash table. They're very similar, just do them in one video, extremely similar. There's one method called keys, which returns an array, a list of all the keys in our table. So you need to collect all of the keys, and then another one called values that does the same thing, but for values. So it collects all the values in a single array and returns that array. So if you've done much programming before, in pretty much any language, there's a way to iterate over a hash table, a dictionary, a JavaScript object, and it often involves looking at the keys or looking at the values as an array or some sort of iterable list and then looping over that. So we're just going to implement similar functionality using our 2 methods, keys and values. One thing that I didn't write here, but I would pay attention to, is how you handle duplicate data. For example, values, it's very likely that we might have multiple values that are exactly the same. For example, if we're keeping track of grades inside of our, like if I'm a teacher and I'm going to map, Colt's got a C, Dave got an A, Lizette got a C, that sort of thing. Well, there were 2 C's as the values. Do we return both of them or do we return one? And most of the time, it's just the unique values that you return and the unique keys that you return. And keys are supposed to be unique anyway, but values aren't. So feel free to implement it either way. I will show both so you can see how it works. But implement 2 methods, keys and values. They're very, very similar. You can copy and paste the code from one to the other and just slightly tweak it. We'll have a solution up next. All right, so let's implement our methods, keys and values. I'm going to start with values actually, because that's the one where we really have to worry about duplicate data. So let's start there. And all we need to do really is make an array to store all of our data. So I'll call it values R, ARR, like that. And then we need to loop over the entire key map, this.keymap. So let's just write a for loop for let I equal 0. Oh, I hate typing these when I'm not using my usual editor. This.keymap, and we want to go .length, and then I++. So this is just going to loop over the entire key map. Like, have I executed this? Oh, I haven't run it yet. If we look at HT here, we're going to loop over all 17 items here. And the first thing we'll check is there anything there? So if this.keymap of I, if that's the case, then let's just start by console.logging this.keymap of I. And if I run this, and then I do ht.values, it's printing out all the arrays that have stuff. It's skipping over all of the empty ones because we're working with something that has 17 slots and we're only using, 6 of them? 6 different slots. So there are 11 empty things we're not printing out. So that's good. So what we want to do instead is loop over this.keymap of I, because we now need to loop through that and collect all the values and push them into our values array. So we need to go over each one of these and find this item, the second piece. So this is index 0, this is index of 1. Okay, so let's do another for loop. This time let's call it j, for let j equal 0. J is less than this.keymap of I dot length. So this.keymap of I is referring to each sub array at that index, j++. Okay, so for each item in there, now what all we need to do is values array dot push, and we only want to push the value, so that is this.keymap of I of j. That gives us the entire thing. So if I did this and I run this ht.values, oh, well, we're not returning anything, so that's useless. Well, that was a very dumb example. Let me add the return at the very end. Let's come down. Where's our correct bracket? Let's do return values array. Okay, rerun the code, ht.values. If we look at it, we are still returning an array that contains both the key and the value. So we only want index of 1 for each one of those items. And if I run it again, we do ht.values, we're now getting all of the values. So we could call it a day here, but then there's also this problem of duplicate data. And like I said, the way a lot of languages handle it is when you do .values or whatever the equivalent is, you only get the unique values. You often don't get all of the duplicates because there's usually no order that's guaranteed, and it could be confusing if you have duplicate data. Usually it's just the uniques. So how would we implement that? Well, the simplest way is before we push it into the values array, we just check, does this key map already, or does the values array already include this item? First, let's get some duplicate data in there. So I'm going to add a purple with this DDA0DD, and let's also add in something else called violet, like this. And so if I rerun this and we look at our values, you can see that we have, what was that? DDA0DD is in there 1 time, 2 times, 3 times. So to prevent that, we'll come over here, and before we push, let's add a conditional. We'll say if the values array dot includes, and we'll use the built-in includes method, this.keymap I j 1. This is the value itself. So each time through, we'll check, does it include DDA0DD? These color codes are not the most intuitive thing for me to be talking about. But if it includes this, we don't want to push. So let's do the opposite. Let's say if not. If it does not include, then we'll push this in. Like that. And let's just test it out now. So I'm using the built-in includes method. So if we try ht.values now, we only get one of these, DDA0DD. All right, so that's one way of handling duplicate values so that we only end up with unique values in our data set that we're returning. Then we return it at the end. We just check each time through for each value. Does it already include that value? If it doesn't, push it in. So we could just duplicate the exact same thing and do keys. So change the name of this to be keys, and we'll call this keys array, even though it doesn't actually make a difference functionally. This will be the same. This is the same. This here is also the same, but then this changes. So this is going to be keys value, or keys array, includes this.keymap ij of 0, because our key, each key is stored at index 0 rather than 1. Okay, and then this also needs to be a 0, and this needs to be keys array dot push, and then we return keys array. So if we test it out now, let's do ht.keys. We get however many values, or however many keys that is. And if we do the same thing for values, there we go. We get fewer, of course, because we had duplicate values. Now, we didn't address what to do with duplicate keys. If somebody inserts something right now, if I actually go and insert plum again, which is already in there, so ht.set plum, which is going to be double, like that. If we look at our hash table, you can see that they're both stored, nested next to each other inside of index 0. So plum was hashed to the exact same thing, 0 each time. That's how it should work. But we end up with 2 children there. And so when I do an ht.get plum, our logic right now is just going to give me whatever was inserted first. And it should always stay that way based off of how it's set up right now. Now, it's probably a better solution to alert your user to that. So here, we could add some logic to check if it's already in there. When we're setting something, we would check if it's empty. Okay, it's not empty. Then you could iterate over the entire thing and check to see if it already contains that key. But we're just going to go with this simple implementation for now. Right now, it allows you to insert many things with the same key, and you're only going to get the first one that was inserted. And that's fine for now. It's not supposed to be very usable anyway. But just keep that in mind that most languages, if you tried to, insert something multiple times, it would overwrite what you already had. So if we did .set plum to be double, that's what plum would be from now on. But either way, we've implemented keys and values. There really aren't supposed to be duplicate keys, but this code here ensures that we're not getting duplicates. Same thing down here with values. So that's keys and values. Now we could call, dot keys or dot values and iterate over the entire hash table if that's what we wanted to. So to print out every single color that we have, we could do something like ht.keys and do a dot for each maybe, and call each, let's go with key, and then just do console.log ht.get key. And if we try running it, we get every single value printed out. And we do have duplicates there because we're using the keys and just getting the value based off of that. And it looks good. So we're officially getting the keys and the values with our separate methods, and we can iterate over them now. All right. So that is the basics of hash tables. Again, not sophisticated, not something you should really use in this implementation, but hopefully it makes sense how it works. All right, so we've implemented the basics of a hash table. We have a way of inserting, we have a way of retrieving a value. We also did the keys and values methods, which aren't as important, to be honest. Now let's talk about the big O, the time complexity in particular, of these basic operations. So insertion, deletion, and accessing data on average, and also best case, are O of 1. Constant time, which is fantastic, that's great. And this really comes down to how good your hash function is. 1, how fast the hash function itself is, and 2, how evenly it distributes things. Minimize the number of collisions. Now remember that big O is a simplification of things. We remove constants, we simplify whenever possible. So saying that our time complexity is O of 1 for insertion doesn't mean that there's only one operation that it takes to insert. It just means the general trend. So it is possible to write a good hash function that is constant time, and pretty much every programming language that has an implementation of a hash table has a constant time hash function. Now that's different than a cryptographic hash function, which does need to actually run for every single bit of data as an input grows. Let's say a file grows from 1 megabyte to 200 megabytes. The hash function needs to actually traverse or parse every piece of that data if it's a cryptographically secure hash function. But when we're talking about hash tables, it's okay if we only look at part of the data, only part of the string in our case, which is what we did. So it's possible to write, in general, a constant time hash function. So insertion, deletion, and access, in general, average case, best case, are constant. So if we had a good hash function, and this is our data set visualized where this is showing, one piece of data stored here. This is talking about separate chaining. So we have, certain indices have two pieces. Even if it takes us one operation to hash our data, let's say we're accessing something like we're accessing this value here. So I have to first hash the key. Then it tells me index 9. I go to index 9. Well, there's two pieces here, so I have to go look at the first one and then the second one. And overall, we would still say that it is constant time because it's 3 operations every time or 5 operations every time. But if we grew this to be 10,000 items or 20,000 elements in our hash table, we would expect it to, with a good hash function, be evenly distributed. It is possible that we could have a really bad hash function that distributes everything really unevenly, everything into one index, which would be pretty useless. But if this was the case, if I wanted to retrieve, or if I wanted to insert, if I wanted to delete something from the end, it's going to be O of n time, because even if my hash function itself is constant time, if it's distributing everything into one spot, then it's basically just a list. And to insert at the end of a list is O of n. It's linear time. So it really comes down to how good your hash function is, how fast it is itself, but also how evenly it distributes things. And this is why I don't recommend writing your own hash functions. Use ones that are known, that are implemented by other languages. There's lots of libraries online. So if you do have to do that, I recommend using something that someone else has already done. So in general, when we talk about hash tables, they're very, very fast. O of 1, constant time for insertion, deletion, and accessing. And when I say access, that means using a given key, finding the corresponding value. When we talk about searching, well, for searching for a key, it can still be very fast. It can be constant time. But if we are searching for a value, then we need to go through every single thing, every item, and check. So that would be O of n. All right. So that's a big O in general, time complexity for hash tables. Now let's do a quick recap. So hash tables are collections of key value pairs. Cool. They exist in many languages. They're already implemented. Dictionaries in Python. They're similar to objects, or actually closer to maps in JavaScript. Pretty much every language has an implementation. So hash tables can find values very quickly using a key. They can add key value pairs very quickly as well. And the way that we implemented our hash table was using an array, where we hash the keys to get an array index, and then we store the data at that position. So our hash function is really important. So a good hash function, also a lot of people just say a good hash, should be fast, ideally constant time. And this is talking about hash table, hash map hash functions, not cryptographically secure hash functions. Those have some different rules. But they should be fast. They should distribute keys relatively uniformly. We don't want any sort of conflicts if possible. We want things to be stored as spread out as possible. And we want it to be deterministic. We need to get the exact same output every time with the same input. And then there's 2 strategies for when we have 2 keys with the same index. When we hash something, we get the same index in our array. There's at least 2 that we talked about: separate chaining and linear probing. Separate chaining involves storing them together in a nested structure in the same array index. Linear probing involves looking forward for the next empty slot. And we focused on separate chaining. All right, so that was hash tables. Again, our hash function was very simple. It was not written with the intent to be very useful, really more as a educational demo. But overall, hash tables, hash maps are super, super useful. We use them all the time. Pretty much anytime you need to store key value data, it makes sense to use a hash table. All right. Hey, welcome back. It's a new section here. It's a brand new morning, at least for me recording this, and most importantly, a brand new data structure, the graph. So I love graphs personally. They're fun to teach, they're fun to implement, but most importantly, they're really, really useful in today's world. Graphs are used in basically any social network. Anytime we're modeling users and recommendation engines, for example, when Netflix recommends another movie or something to you, or advertisers target you based off of something, graphs are usually in play. And when I say graph, we're not talking about a chart which in English, often we also call a graph. I'm not talking about this sort of two-dimensional looking chart. It's a data structure. It's very different than this. So what it is, we'll get to in just a moment. But first, our objectives. So explain what a graph is. Obviously, got to start there. Compare and contrast different types of graphs. And also, we'll compare and contrast graphs to other structures we've seen, like trees, which, hint, hint, are actually a sort of a special type of a graph. And then also talk about their utility, their applications in the real world. Then we'll implement a graph using something called an adjacency list. So there are multiple ways to implement graphs. I'm just going to show you one, the adjacency list, and we'll talk about why. Then we'll traverse through a graph using our good old BFS and DFS, breadth first and depth first search. Compare and contrast graph traversal algorithms. We'll talk about Big O along the way, talk about some fun algorithms. But let's get started by just talking about what a graph is. Take it away, Wikipedia. A graph data structure consists of a finite and possibly mutable set of vertices or nodes or points together with a set of unordered pairs of these vertices for an undirected graph or a set of ordered pairs for a directed graph. Okay, did you get that? Yeah, that doesn't really make much sense, or probably doesn't make a lot of sense. It's kind of clunky. Really what it comes down to is a graph is a collection of nodes and connections between those nodes. So if we go back and read that definition again, let's just sort of skim through it. A finite set of vertices or nodes. So let's just say a set of nodes together with a set of pairs of these vertices. So those are the connections. So we have a bunch of dots, a bunch of nodes, and then connections between them. So this is a valid graph. These are the nodes and these are the connections. Here's another valid graph. The same nodes, just different connections. So the placement of them in this diagram doesn't matter. We could have this same structure. It's just the connections that are important. But, if this B was way over here or this F was way over here, it doesn't matter as long as we have the same lines going, the same connections. It's really just about those lines. Okay, so this is a valid graph. Here's another one. We have some nodes with connections between them. Do I have one more? Here we go. A very different looking one. The same number of nodes, the same letters for each one, but different connections, different lines. So if we go back to something like a linked list, when we talked about linked lists, we had nodes that are connected in a linear fashion. When we had, trees, we had nodes that there was one parent, one topmost node, and then from there were a bunch of children that descended from that one node, and each parent could have its own children and so on. So a tree is a type of a graph, but in these graphs that we're looking at here, there is no parent node, there is no starting place, there is no, entry point. These are all just nodes. They're treated equally, and they're connected in different ways, and those connections can mean different things. Let's actually talk about a few examples, first of all, of where you would use this. So now I want to talk about some real-world applications. Where does this stuff come up? A bunch of nodes connected by lines. Well, all over the place. Social networking, we'll also talk about things like mapping, Google Maps, directions, location, pathfinding, routing. When you request a web page, the actual response itself comes back in a bunch of different little packets all over the place across this massive network. Really, they're just used all over the place. But let's start by talking about social networking or just the internet in general. So this is a visualization I found on Flickr. There's many of these out there, but this was one of the only ones I found that had a license that allowed me to use it. And I think this was somebody who, Ken CF, I think was their name, modeled, I don't know if it was Facebook or what social network, their connections between their friends. I think it was Facebook. And so each dot on here, each little node is a person, like Kimra L. And then you can see all the connections that, Kimra has to other friends. And what's interesting here is that we can see there are these clusters. There's some people that this person knows who maybe don't know any of his other friends or her other friends. Like this Susan E. Maybe they met on a cruise somewhere or he was traveling. But then there's this giant cluster and maybe they went to school together, all these people, or maybe they live in the same city and they went to college. There's, different groups here. But this is a way of representing a social network. So Facebook, Instagram, Twitter, all of these, they're storing your friendships, your relationships, and much, much more than just a name like we have here. But that's the bare minimum, really, to represent the structure of a friend network, of an actual real world social network. Or think of storing actors and their relationships in movies. And, the different actors that have been in each movie, you could store it this way. Here is a visualization of part of Wikipedia. These are pages that link to one another. And this is just a small subset of it. There are way more Wikipedia pages than the nodes that you see here. But we can see there are certain clusters, and like for this one here, whatever this is, it links to a ton of different pages that themselves don't really link to other pages. And this is just Wikipedia, but the web itself, the internet in its entirety, we could model as a graph where we have web pages that link to another page. So anytime that one web page links to another, that would be a connection from one node to another. Here's another application. When we talk about mapping, this is a really, really common one. When we think of how Google Maps, for example, or MapQuest, if you were back and you remember that, printing out directions, I used to have to do that for my parents. When you think about how you would store that, a map itself in roads, let's just only talk about roads, not hiking trails, not bike lanes. There's a bunch of nodes, different cities, different locations, waypoints, restaurants, whatever we're talking about, and then roads that connect them. And those roads are basically the connections that we talked about between the nodes. And in this example, this is in Guatemala, to go from this one city, beautiful city, Antigua, to get to Lake Atitlan, which is a beautiful lake. There are many, many options. This is only showing kind of the two fastest. But of course, we could go some ridiculous route, like go through here, and then go over here, then go up this. And there's a bunch of ways to get there. And Google Maps is basically calculating the fastest way to get there along this graph, where there are many different options. And there's many algorithms that talk about finding that shortest path and what's the easiest way to do that. And it's much more complicated than just the length of the road. There's things like the speed limit of the road, for example. You might have a much shorter road, but it's windier, or it's a dirt road. You might have traffic that Google obviously takes that into account. Things might be closed. So it's a lot more complicated than just calculating the shortest path. But my point is more that we can store this data using a graph. It's a bunch of nodes connected by roads. So recommendation engines, that's another one. When we talk about anytime you see something on a website, people also watched, like on Netflix or Hulu. You might also like X when you're listening to something on Spotify, for example. People you might know, Facebook or Instagram or Twitter, they all suggest those. This thing was frequently bought with on Amazon, for example, and many other web pages. Those are all recommendations that are made to you, and often the way that they're made, the way all this data is stored, is in some sort of graph relationship. So here's a super simple example I made with 2 video games. Imagine that we had this for every single video game ever made, and I didn't actually write out all the data points, but here's a graph for the game Halo and for Borderlands. If you're not familiar with the games, it doesn't matter, but what you can see here, the ones in green, I didn't actually write text for all of them, but the things in green, they are nodes that both of these games have in common. So these are like genre elements maybe, space, future, sci-fi, guns, first-person shooters. But now imagine that you have this expanded not only to include every game in Amazon, for example, or in Steam or whatever app you use to buy a game, but also other things besides just genres. How about user reviews and clicks? People who clicked on Borderlands also looked and browsed what else? Or trailer views. There's so many different things that you would take into account. And then to suggest something, let's say I bought Borderlands and I finished it, to have a little box pop up and say people also looked at X, you might just look, you write code to figure out what games have the most in common, which ones share the most nodes. Okay, well in our graph it's only Halo, so we'll suggest Halo. So the data sets get way more complicated, but anytime we're talking about this sort of X also did this, or you might like this, or you should buy this, I guess that's a little more forceful, you should buy, but you might want this. Those are recommendations pretty much always stored with some sort of graph structure. I forgot I had a little diagram there. The things in common in that box. Here's a cool graph structure that models all the different genres, or most of the genres, in music around the world. So if we zoom in, you'll actually see all of these connections appear. It's pretty crazy. So this purple, let's see, which one are you? That purple is Jamaican/reggae. And if we go, and unfortunately the zoom is kind of annoying, but if I zoom in, you can see, all right, so there's dub, And then we hover over dub and you can see all of its connections to other nodes. For example, it connects to old school rap pioneers. Or if we look at deep funk and new funk, it has some connections over to freestyle and breakdance on the right in red, or to early funk and P-funk. And anyway, this is a fun website to check out, but this is a graph structure at its core, modeling the relationships between genres. This one also has an added dimension, though, of time, I believe, as things developed. You can see that, let's see, down here are the more recent trends. Up top are the older types of music. So you can see like classical is over here. And what is this? Folk music is here. Anyway, so graphs are really commonly used. They're sort of exciting, I think, to know about. And the next thing we need to do, now that we've established the base definition, it's a bunch of nodes with connections between them, and there's not a pattern like there is for a tree or for a linked list. There's sort of free form, and it's just nodes with connections. What we need to do next is talk about different types of graphs and also a little terminology so that we understand the type that we are going to implement, which we're going to get to very shortly. That's coming up. Welcome back. So we've talked about what a graph is generally, some nodes with connections between them. Now let's talk about some particular types of graphs. First of all, there's some terminology. These are the basic terms we have to talk about. A vertex and edge. So a vertex is the fancy term for a node. So in a graph, when we say vertex, it's just on our diagram, one of the circles. An edge is the connection between the nodes. Then there are two pieces we'll come back to, weighted/unweighted and directed/undirected. But first, let's look at this graph. On this graph, any of those circles are vertices. This is a vertex, C. This is a vertex, B. So I might use node and vertex interchangeably, but the technical term, like on Wikipedia, you'll see vertex. Although it does say node as well in the introduction, vertex is like the technical term. And then these connections are edges. So this is an edge from A to E. This is an edge from A to B, from B to D, and so on. So from one vertex to another, that's what an edge is. So there are many, many types of graphs, different distinctions and sort of how they're built and rules they follow, just like with trees. And I actually already hinted at this. A tree, if we actually click on the page for a tree, the definition is that it's a graph in which any two vertices are connected by exactly one path. Meaning that to go from 6 to 2, for example, there's only one path to get there. To go from 3 to 5, there's one path. Contrast that with some of our graphs here. To go from E to D, we could go here, here to here, or we could go here to A to B to F to D. And this is not even a great example. Some of the other ones we've seen, there are way more edges, way more connections. So for a tree to be a tree, it's just a bunch of nodes with a bunch of connections, so it's a graph. However, there's only one path from a given node to another. Okay, now let's talk about directed versus undirected graphs. So this has to do with the edges, the connections between the vertices. So in an undirected graph, there is no direction to, or polarity, you could say, to the edges. So they are two-way connections, is another way of thinking about it. A and B are a connection, so is B to A. If we're traversing this, we could go this way, but we could also go this way. There is no direction associated with an edge. And that's useful, oftentimes, depends on what you're modeling. But let's talk about like Facebook, how Facebook models friends. If you don't have a Facebook account, you probably know how it works. You have to request someone, and then they will accept your request or reject it, but hopefully accept it, unless you're a stalker or something. In that case, you are both friends. So you see that friend stuff on your webpage or on your homepage. They see your content. It's not a one-way relationship. So this is an example of what a couple of friends could look like on Facebook, where if Maria and Tim are connected, that means Maria sees Tim's content and Tim sees Maria's content. Now let's contrast that with a directed graph. So a directed graph is often represented with arrows, which indicates the direction, the polarity of that edge. So for example, from B, we can go to C, we could traverse to E, we could traverse to A. From E, we cannot traverse to B, we cannot traverse to D, or to F. So E is sort of like a dead end here. So on a directed graph, there is a direction assigned to the edge, the connection between vertices, two vertices. Yeah. So that's how you would model a social network like Instagram or Twitter, where our friendships or the following relationship is not a two-way thing by default. For example, on this chart, let's say it's Instagram, we have Maria who follows Tim, and Tim also follows Maria, so they see each other's content. But Maria follows Justin Bieber, so she sees his content. Justin Bieber does not follow Maria back, much to her chagrin. That would really make her day if Justin Bieber would follow her, but he doesn't. Same thing with Tim. Tim follows Justin Bieber. Justin Bieber does not follow Tim. But if we look over here, Justin Bieber does follow Kanye, and Kanye follows Justin Bieber. So you can see, this sort of information in a social network like Instagram is important, because if you are a celebrity, you probably don't want to just see every single person's content who follows you. You want to be able to pick and choose what you see. Unlike on Facebook, where we modeled it with an undirected graph, because all connections are two-way. Although that does ignore the whole Facebook celebrity pages where you can create a special marketing account. But if we're just talking about the basic typical user account on Facebook versus Instagram, this is how we'd model Instagram with a directed graph. Facebook is an undirected graph. Okay, so there's one other piece of terminology, which is a weighted graph versus unweighted. So right now, this graph is actually unweighted because each connection between the vertices, the nodes, each edge has no value associated with it. But now, if I hit this, there we go, magically, it is a weighted graph. So when we assign a value to the edges, it becomes a weighted graph. There is information about the connection itself. So unweighted versus weighted. Everything we've seen so far has been an unweighted graph. This is an unweighted directed graph. This is an unweighted undirected graph. And this is a weighted but undirected graph. So for example, if we're talking about maps, here's our same Google Maps example in Guatemala. I'll get rid of the map. Let's say these are all cities or, gas stations or any sort of points of interest. There's connections, there's edges between them, but they are weighted. We need to know these values. So if we're trying to calculate the shortest path, we can add these. It's not to scale, by the way. I just picked random numbers, but we would add up. If we're trying to go from here to here, we could add 40 plus 20 plus 3, or add 13 plus 120, and figure out which is shortest. Now, this currently, the way it's displayed, is an undirected graph. It's two-way connections. But maybe some of these roads are actually one-way roads, in which case, if we were really modeling Google Maps, we would have a directed and weighted graph where, certain roads, like in San Francisco or Manhattan, for example, but really all over the world, are one-way roads. You can't just go any sort of way that you want. You have to follow the rules, and there is an actual value assigned to those edges. So if we go back to something like Instagram, this could easily be represented as a weighted graph, because you might, if you're a marketer, if we're talking about Instagram's advertising team internally, they care about these relationships, not just who follows who, but also what their appetite is for that person's content, if that makes sense. So there would be some sort of value assigned to this relationship, or more than one value, so that Maria's connection to Justin Bieber might be super strong because she loves Justin Bieber, but Jones maybe isn't as strong. And you could easily store that using a graph data structure. Keep track of, how many times this person did X or Y, or assign a value for how much they love a certain person they follow. So just because I'm displaying this part just to explain what a directed graph is, I'm not saying that it couldn't be a weighted graph. All right, so let's wrap up the terminology. Let's go back here. We have undirected graphs. That's what I first showed you in the last video. There is two-way connections, or you could say that there is no direction to the connections, the edges between the vertices. And even before that, we talked about the term edge is the connection between two nodes, which technically each node is called a vertex. So then there's a directed graph where there is a direction assigned to an edge. An edge could be bidirectional, it could point both ways, but it also could point one way. Then we talked about unweighted versus weighted. So an unweighted graph has no value associated, no magnitude with each edge. A weighted graph does have a value associated with an edge. And so when we're traversing or when we're computing the shortest path, for example, we would use these values. All right, I know that was a lot. Next, we're going to talk about different ways, different strategies for actually storing the information in a graph. How do we model it? That's next. Welcome back. Now that we know a little more about graphs, we know the fancy terminology around them, let's dive into the nitty-gritty details of actually implementing graphs, storing them or representing them using code. So going back to this image from Wikipedia, it's a graph of a small subset of Wikipedia pages. We have each vertex here is a page or an article on Wikipedia, and each edge, each connection, represents, I believe, a link or a reference, a cross-reference. So if we have this chart here, and somebody asked you to store it using code, how the heck would you go about doing that? What data structures would you use to help you? Would you create your own classes? What would you do? It's not easy, but if we break it down, what we really need to store a graph, the important information, are the nodes, the actual vertices, and then a way of storing the connections. So with a linked list, for example, we did .next and .previous if it was a doubly linked list. With a binary search tree, we had .left and .right in our classes. That's not going to work for a graph really, because there's any number of nodes, any number of edges, connections between a node. So what do? Well, you could come up with any number of solutions. Just like with a linked list, you could store a linked list using an array. It just doesn't really make sense because why not just use an array? Same thing with graphs. You could come up with sort of heavy-handed approaches, but there are two standard approaches that we're going to talk about that most articles, blog posts, Stack Overflow, they're the two common ideas for how to do this. And they are called the adjacency matrix and the adjacency list. So before we dive into that, this is the graph that we're going to work with here. Try and represent this using code. It's a little slimmed down from this one, but it's the same idea. We have vertices, a vertex, and then edges between A and B or A and F, and we need to store that information. So going to the adjacency matrix, a matrix, if you're not familiar with it, is just a two-dimensional structure usually implemented with nested arrays, but not always. And basically we store information in rows and columns. So we could represent the connections here using a matrix, something like this. So the way you would read this, it's sort of a Boolean matrix, yes or no, 0 or 1. So between any two vertices, any two nodes, let's say A and D. So if we look at A and we go over to D, there is no edge. It's a 0, false. There's nothing there. But if we look at A and B, go to A, we look at B, there is a connection there. If we look at A and F, A over to F, where there's a 1 right there, which is how we store true. So this is a way of representing all the edges. Notice that it works the same way if we start here. So if we're looking at the connection between C and D, for example, we could start at C on this left axis and go over to D, and we see there's a connection. Or we could start on C up here at the top and go down to D. And that's because it's an undirected graph, meaning that it's a two-way connection. But we could also store directed graphs where only one way is stored, if that makes sense. So what we have here is a matrix. You could do nested arrays to store this information. Zeros and ones is probably the most common, but you could do true or false. You could do, if you wanted, you could do yes or no. But all that you're storing are the edges. So every time that we add a new node, a new vertex, we have to add an entire new row down here, an entire new column. And we'll compare and contrast the approaches in just a bit, explain what these are good at, what a matrix works well doing, and what it sucks at. Quickly, here's a Wikipedia page. I just wanted to show some diagrams. Here's a representation of an undirected graph here. This is the graph. Here's a matrix storing it. Here is a directed graph. You can see the arrows, and you can see the matrix that we're doing or that we're using is no longer symmetrical. The other approach we'll discuss is called an adjacency list. So I actually changed these nodes, the vertices, to be numeric, and you'll see why in just a second. It's easier to show how you could store this. So instead of A and B, C, D, so on, we have 0, 1, 2, 3, 4, 5. So the way that this works is we use an array or a list to store the edges. So if we wanted to figure out what edges, what connections there were between 3 and its other nodes, the other vertices, we would go to index 3 of our array, 0, 1, 2, 3 right here, and then there's a list there that contains the connection. So there's a connection between 3 and 2 and 3 and 4. As you can see here, those are the edges. If we wanted to know, is there an edge between 5 and 1? Well, we would either look at index 1 and look for 5, it's not there, or we'd look at index 5 and look for 1. It's also not there. And this is an undirected graph, so we have things stored both ways. For example, 0 has an edge to 1, 1 has an edge to 0. So this is another way of storing it. However, if we're talking about letters, if we're going back to this, where we have A, B, C, D, E, F, and letters is arbitrary, but let's say it's a name, a string, or something else that isn't just a number, right? This one hinges on using the positions of an array. To find the connections, the edges from 0, we go to the 0th item. And that works, but what if our nodes aren't numeric? What if they're not in order like this? What if they're strings? Or what if there's huge gaps between the numbers? So we don't want to just use an array. What else could we do? Well, we could use a hash table, use a key value pair data structure. So a dictionary, a JavaScript object, a map, there's many ways of doing this depending on the language, but here's the exact same information where we store for a given key, instead of a key being a number like 0 in an array, it's now in a hash table or a hash map. To look at the connections, the edges from A, we look up A inside of this structure, and then we look at the list and we see, all right, there's something from A to B and A to F. As you can see here, A to B, A to F. Same thing, let's do E. So we'd ask for E from this hash map, and we get this. So that tells us there's a connection between E and D and E and F. Okay, so this is an adjacency list. Just like an adjacency matrix, there are two different ways of expressing the edges, the relationships between our vertices. Okay, now let's compare them. So here's kind of an intimidating slide that talks about the big O notation between adjacency lists and adjacency matrices for various operations. So first, a couple of things I should explain. V and E. So V is the number of vertices, E is the number of edges. So if we think about the storage, how much space they take up compared to one another, if we look at an adjacency matrix, you can see we're looking at big O of V squared, where V is the number of vertices. And that makes sense because it's a two-dimensional structure. If we add a new vertex, it means not only just adding one slot in, it means actually adding an entire row and an entire column to our matrix. Compare that with an adjacency list, it really only grows at the rate of the number of vertices and edges. So I think that makes sense, right? All we have to store here, really, the size is governed, or if we go back to this example, same thing in adjacency list. The size of it, the amount of storage, is determined by how many edges, how many connections we have. But if we go to our matrix, it doesn't matter how many connections there are, it matters how many vertices. So we could have 100 more vertices, or let's be more conservative, let's say 9 more vertices, and they might not have very many connections. They could only have one each, one edge each. Well, we're still going to have to add 9 rows down here or up here and 9 columns, and that's a lot of space. So if your data is sparse, if you don't have a lot of connections, a lot of edges, maybe don't use a matrix. So you can use this slide as a reference, but here's a breakdown of some of the key points. So an adjacency list, as we've already talked about, can take up less space in sparse graphs where you don't have as many edges, compared to an adjacency matrix, which takes up more space, V squared, where V is the number of vertices. An adjacency list, if all you want is to know the edges, just iterate, for example, search over all of the edges, and you need to access all of them, it's easier to do with an adjacency list. Because I think that makes sense. If we have this structure, we can just start, all right, here's the edge, here's all the edges, all the edges. If we go to a matrix, we're going to have to iterate over a bunch of things that aren't edges. We're going to, there are things that are stored here that don't exist, if that makes sense. We're leaving empty spaces versus in an adjacency list, we're only storing the meat, the actual connections. Okay, so faster to iterate over all edges, slower to iterate over all edges in a matrix. However, with an adjacency list, looking up a specific edge to see if it exists, for example, can be slow. In a matrix, it's very fast. You can see that on our big O here. To query something, O of 1, constant time for an adjacency matrix. So if I wanted to know, we go back here, is there an edge between A and D? All I have to do is go find that slot, A and D, No, there's not. Is there an edge between B and C? Go to B, C, yes, there is. It's constant time. If we compare that to an adjacency list, actually let's go to letters. If I want to know, is there a connection between A and D? Well, I'm going to have to ask for A first. Then I'm going to have to iterate over this. So depending on how many connections there are, how many edges to A, there could be a ton. And I might have to iterate over the entire thing, depending on the number of edges. So I can't know instantly like I did with a matrix. So that's where we get O of V plus E, where V is the number of vertices, E is the number of edges. So the big O itself doesn't matter that much right now. Just know that in general, a matrix takes up more space. When we're talking about sparse data sets, it's not great. It's slower to iterate over every edge, but it is faster to look up a specific edge. Also, some people think the implementation of a matrix can be a little easier. An adjacency list takes up less space, it's faster to iterate over all edges, but it's slower to query for the existence or to check if an edge is in there. So which one are we going to use? Dum, dum, dum. We're going to go with this rainbow, beautiful text, an adjacency list. So excited about it. It's in there 3 times. Why are we going with an adjacency list? Well, mainly because of the space that it takes up and the fact that most of the data in the real world, whether we're talking about social network data, friends, modeling actors who are in movies together, Wikipedia pages, whatever it is, real world data tends to be sparse. So we can have a ton of nodes, lots of vertices, but usually they're not all connected. And that lends itself more to adjacency lists. Remember this chart. Look at any given node on here. It doesn't really have many connections. Like some of them do, definitely, but there's a lot of nodes that only have one edge, one connection. So for each one of these, whatever the number of nodes is here, the number of vertices, it's going to make a massive matrix. Versus if we're only storing the actual connections using a list, it's a lot easier. And it takes up less space. So because most real world data looks something like this, even though there's a ton of data here, it's a large set, there aren't very many connections compared to how many there could be. So in a matrix, it works well if your data is jam-packed. If your matrix could be almost full, then you might want to use a matrix. But otherwise, I prefer to use an adjacency list. So that's where we're going. And finally, in the next video, we will set up our code and get started. Welcome back. Let's get to work implementing our graph class. So I mentioned in the last video, we're going to use an adjacency list to do this. And our basic class for our graph is super basic. That's a bad way of explaining that. It's very simple. Let's put it that way. All we need is a single property called adjacency list or something similar to store the actual edges, the relationships, the connections between our vertexes or vertices. So it will start empty and we'll add things in one at a time. But first, we need a way just to add a vertex. Before we can add edges, before we can draw the connections, we have to just add the dots, the nodes. So that's where we're going to start. I should mention we're going to do an undirected graph for now. It's very simple to change it to be a directed graph where the relationships, like the edges, are one way. There's a direction from A to B. For us, we're going from A to B and at the same time B to A. So when we add an edge in, we'll talk about how we handle that. But let's start with the basics, adding in a vertex. So here's our first method. We'll use this as our skeleton. Add a vertex is basically a one-liner. It takes the name of a vertex, whether it's 10 or pineapple or Hawaii, whatever it is, we add that in to our adjacency list. So write a method called add vertex, which accepts a name of a vertex. It should add a key to the adjacency list with the name of the vertex, and its value should be an empty array. So we add a vertex first before we can add an edge. So there's no connections at this point. We're just adding in a simple vertex. So if we had a graph called G and it was empty and we called add vertex Tokyo, the result is that our adjacency list looks like this. Tokyo is now a key and the value for Tokyo is an empty list, an empty array. And that's it. So it's really, really simple, this one. All that we do, write the method. You need to just make sure that it accepts a vertex. You add that vertex as a key with a corresponding value of an empty array to the adjacency list, and that's all. So give it a shot. In the next video, there'll be like a 10-second solution. All right, so let's give it a shot. I'll head over here, and the first thing we need to do is define our graph class. We need to add our constructor, doesn't take anything, and we set this dot adjacency, that's the hardest part, is spelling adjacency list, is going to equal an object. Okay, then we add our method called add vertex, which accepts a new vertex, a key, and then all we have to do is do this dot adjacency list of vertex, whatever that vertex is, and set it equal to an empty array. Now, I didn't specify how this should handle duplicates, so if there's already a key in there, one thing we're going to do with this graph class is keep it simple. We're not going to, add in a bunch of error handling. So if somebody tries to add a new vertex that's already in there, it's fine if we overwrite it. Obviously, in the real world, you would want to add some sort of protection in there, return or throw an error that says there's already a vertex in there, or ignore it, because our code is just going to overwrite it and set it to be empty. But it'd be super simple to fix that, right? We would just check if this dot adjacency list of that vertex, if that exists, or let's say if it's not there, then let's just do it on one line. Let's see how long that line is. I think that's okay with me. So we'll just do this, just to keep it really simple. If there's nothing there already, then make it an empty array, and that's it. Doesn't even need to return something. Let's run our code. Let's make a new graph. Just call it g equals new graph. Okay, and we do g.add vertex of Tokyo, for example. We look at g, look at the adjacency list. It now has Tokyo set to an empty array. Do one more with, what else should we do? San Francisco. Okay, and basically that's all there is to it. But let's just make sure that little tiny bit of error checking worked. So I'm going to manually change. This is not how you should interact with it, but we don't have any methods to do anything. So I'm just going to change Tokyo from an empty array to just have something in there. So if we look at the adjacency list now, Tokyo is not an empty array. Pretend that that's an actual relationship. That's data we care about. So if I now did g.add vertex of Tokyo again, we don't want it to overwrite it. And if we look, we still have Tokyo set to its initial data. Okay, so this is fine. That's about as much error handling as we need. Looks good. That's add vertex. Really simple. You didn't even need to do this first part. Just set the adjacency list of that key to be an empty array. Next, we'll add relationships between vertices. We'll add edges. Welcome back. Next up, we'll focus on adding edges, on drawing those connections between two vertices. So if we are adding cities in, like Tokyo and Dallas and Los Angeles and Hong Kong and that sort of thing, let's say that we are working for an airline. We're representing like all the flights that an airline has and the connections, at the back of those airline magazines, if you ever read those anymore, there's those maps that have all those lines from cities. We'll do the same thing, sort of. We're going to model that data structure. Okay, so an edge will represent a flight from one city to another that our airline offers. So to actually add an edge, we need to specify the two cities, the two vertices. We'll just call them vertex 1 and 2. So the function called add edge needs to accept two arguments, v1, v2, vertex 1, vertex 2, whatever you want. And it should find in the adjacency list the key of vertex 1, and then push vertex 2 into that array, and then do the same thing for vertex 2. So it should find in that adjacency list the key of vertex 2 and push vertex 1 into that array. And don't worry about handling errors. If somebody enters an invalid vertex, if that edge already exists, don't worry about that for now. Let's just get the basics. This is really more about fundamentally how this all works. So let me just show you roughly how it would work. If this is what we have at the beginning, like we can do this right now. Just add a new vertex, add a new vertex, add a new vertex. Tokyo, Dallas, and Aspen, there's nothing connecting them. There's no edges. Then if we did add edge, Tokyo, and Dallas, remember that this is an undirected graph. So it doesn't matter if we do Tokyo and then Dallas or Dallas then Tokyo. But our end result would look like this. Tokyo, the key of Tokyo now has Dallas in its array, and the key of Dallas now has Tokyo in its array. Or if we did add edge from Dallas to Aspen, which is really the same thing as Aspen to Dallas, we end up with Dallas now has Aspen in there, and Aspen now has Dallas. Okay, so this is pretty short as well. It's really just 2 lines that you need to do if we're not doing any of the error checking. As I mentioned, all that we're doing is accepting. So write a method called add edge. It accepts 2 arguments. You take that first one and you find it in the adjacency list using that as a key, and then you push the second one into that array, and then you do the same thing for vertex 2. You push the first vertex into its array. Okay, let's see how it goes. All right, so let's implement add edge on our graph class. So let's just define add edge, and it takes 2 vertices. I'll just go with v1 and v2. And then in here, we just need to access this dot adjacency list of v1 is now equal, or not equal to, excuse me. We're going to push into that v2, and then do the same thing, this dot adjacency list of v2. We will push in, not push, v1. And that's all, according to the specs that I laid out, that's all you have to do. Now, if you did want to add error handling in to make sure that this is a valid key and this is a valid key, you could do that. Just a couple of conditional statements, but I'm going to leave mine super simple. Let's just make sure it works. So I'm going to define down here, let's do equals new graph. I'll fast forward through this. Okay, so I have 3 vertices in there. They should all be empty at this point. Great. Now let's try doing g.add edge from, let's go from Dallas and Tokyo, which the direction doesn't matter because it's going to go both ways. And if we look at our adjacency list, we now have Tokyo is in the Dallas array and Dallas is in the Tokyo array. So if we wanted to make this a directed graph, we just wouldn't do both of these, right? We would take the first one so that the order would matter. We would go from v1 to v2 and only do this. We wouldn't go from v2 to v1. But we're assuming that our flights go both directions, which I think most airlines do. I mean, I don't know. It's possible that they only have flights in one direction from one city to another and they fly back a different route. We're ignoring that. Okay, so let's just make sure it works again. Just double check. Let's also add one from Dallas to Aspen. And if we look at our adjacency list now, we have Aspen has Dallas and Dallas also has Aspen. Okay, so that's all there is to adding an edge. Welcome back. Next up, we'll add 2 different methods to remove vertices and edges. So first, let's remove an edge. So we'll need to provide 2 different arguments. What's the actual edge we're trying to remove from Dallas to Tokyo? Okay. And then what that actually means is removing 2 different pieces of data because our connection is stored in 2 places. So write a method called remove edge that accepts two vertices, the names of 2 vertices, 2 keys in our list. Then it should reassign the key of vertex 1 to be an array that contains everything that was there before minus vertex 2. And do the same thing for vertex 2. Reassign the key of vertex 2 to be an array that does not contain vertex 1. And don't worry about handling errors and invalid vertices, things that aren't there. Just assume that we're calling these methods with valid names, valid vertices. So here's an example. If this is the state of our current adjacency list, if we called remove edge Tokyo and Dallas, we're going to need to remove Dallas from the Tokyo list and remove Tokyo from the Dallas list. But that doesn't mean just setting it to be empty, of course. We can't delete the entire thing. We need to maintain Aspen in there. So really, it just means reassigning this list, Dallas, to be equal to this whole thing minus Tokyo. There's many ways of doing it, but give it a shot. Here's what our end result would look like. Tokyo is empty. Dallas still contains Aspen, but that connection has been severed. Dallas and Tokyo no longer are an edge. All right, so give it a shot. All right, let's get to work on removing an edge. So let's define our method over here. Call it, shocker, remove edge, and it accepts 2 vertices. And then all that we need to do is, let's start with the first one. We're going to need to reassign this .adjacency list v1 to be everything it already is minus v2. So I'm just going to use the built-in filter in JavaScript adjacency list of v1.filter, and then I'll just call this v, doesn't matter, and we'll filter where v is not equal to v2, which now I'm looking at v, v1, v2. Maybe to make it clearer, I'll call this vertex 1 and vertex 2. just a moment to update this. Okay. So we're just saying, take the current adjacency list of vertex 1, filter it, keep everything where it is not equal to vertex 2. Okay, and then I'm just going to duplicate this and alter it slightly so it's vertex 2 that we're updating, and we're comparing it to vertex 1. There's other ways of doing this, of course, but let's test this out. So I will quickly update this. Okay, so now I added 2 edges in. Let's just look at the adjacency list. Here's what we have. Aspen connected to Dallas, Dallas connected to Aspen, and then the Tokyo and Dallas connection. Okay, so let's do a g.remove edge from, let's say we're getting rid of the flight from Dallas to Aspen, or from Aspen to Dallas. Let's look at our adjacency list now, and we can see there's no connection now between Aspen, there's nothing in that array, and in Dallas, there's no trace of Aspen. Let's do it one more time for Dallas and Tokyo. And we look at G, everything is empty now. Like most of these methods, we could break it pretty easily. If I tried to do a remove edge from LA to SF, for example, there is no vertex called LA or SF, so we get an error because filter doesn't work on undefined. That's okay. I said, pretty explicitly that we're not going to care about that for these videos. We're just working on the fundamentals of our graph. And that's all there is to removing an edge. Next up, our last sort of basic piece is removing a vertex, and then we'll get to traversal and searching and that sort of thing. Welcome back. So our final basic component around adding edges and vertices and removing them is removing a vertex. So let's say that, we're modeling this airline and we used to fly out of, Hong Kong a lot. But now something happened. I don't know why, it seems like a place you would never pull out of if you're an airline. But let's just say we were removing it from our map. We don't want to fly to Hong Kong anymore. That means removing all edges and also removing the vertex itself. So it's a little bit more complicated. So we'll write a function called remove vertex, and it accepts a single argument, just the name of the vertex we're trying to remove. It should loop as long as there are any other vertices in the adjacency list for that vertex. So meaning if we have Hong Kong in our adjacency list and there are 10 edges in its list, 10 other cities, we need to loop through that and remove each connection. It's not enough just to delete Hong Kong from the list. We also need to remove all of the edges. Otherwise, we're left with these broken edges. So inside the loop, we'll just use our remove edge function we already defined. So we'll call remove edge for each edge in the vertex we're trying to remove. And then lastly, we'll actually delete the key in the adjacency list. So let me show you what that looks like. If this is our initial state, it's a little more complicated. Let's say we're going to delete Hong Kong, the entire vertex. So what that actually means deleting is this entire line, of course. But if we only got rid of this, then we would have Tokyo still as a reference to Hong Kong, even if Hong Kong's gone. And that's broken. That's not good. So we also need to remove that. We need to remove Los Angeles has a connection to Hong Kong, and so does Dallas. So we need to remove all of that. So our logic is really take Hong Kong, if that's what we're removing, loop over its array, and for each one, call remove edge, which we already defined, which will delete Tokyo from Hong Kong and remove Hong Kong from Tokyo. Remove edge on Dallas and Hong Kong, and so on. And then finally, we still need to actually delete Hong Kong, the key, so that there's no reference to Hong Kong in here. And that's something you may not do very often. I don't do it very often. Usually you just leave a key empty or set it to be undefined or something, but let's just remove it entirely from our adjacency list. But in JavaScript, you can do that with just delete and then the thing you're trying to delete. So this is what we would end up with at the end of the day, all trace of Hong Kong gone. All right, so let's get to work on our final method around the very basics at least. After this, we get to go on to traversal and searching and some of the more challenging stuff. And we have to worry about recursion and stuff like that. But for now, removing a vertex. So let's define our method. Come up here, we'll call remove vertex, and it takes in the name of a vertex like Hong Kong. And I've written a couple other method calls to build out a little bit larger graph so that we actually have some data to remove to make sure it all works. So if let's see, remove vertex, what do we need to start with? Well, as always, we're going to need to do this dot adjacency list of that vertex. And that's going to give us, for example, if we go back here, it's going to give us this if we're trying to remove Hong Kong. We need to loop over that. And for each item in there, we're then going to pass it in to remove edge. So let's do a loop right now. We could do while this dot adjacency list vertex, and I'm going to do dot length, which seems weird to do while this dot adjacency list dot length, but I'm going to actually pop off items from this list as we go. So eventually we'll get to 0 and then our loop will stop. You could do a for loop. You don't have to do it this way. So we're going to grab, let's just call it adjacent vertex. You don't even have to make a variable to do this, but to make it a bit easier to read, I'm going to do this here. So we're going to take each item and pop it. So here, if I run this right now, if we look at adjacency list, let's say we're looking at Hong Kong, we're looping over this while this whole thing has a length if we're trying to remove the Hong Kong vertex. First time through, pop this item, Los Angeles, off, and then we're going to call this dot remove edge. And what's the edge we're removing? Well, it's between Los Angeles and Hong Kong, the vertex itself. So the order doesn't matter. We can do vertex and then adjacent vertex, or we could do the other way around because this is an undirected graph. There is no direction. The order doesn't matter. We're removing both parts. Okay, so that will do that, takes care of that. And then if we actually run this now, and we look at G, let's do G dot adjacency list, just check on it one more time. All right, here's Hong Kong. Let's now remove vertex, Hong Kong. And if we look at the adjacency list again, you'll see, what do we have? Well, we got rid of all the references to Hong Kong. If we look up here, this is gone. And for example, there used to be Hong Kong in Dallas and in Los Angeles and Tokyo. And if we look at those, Tokyo, there's no Hong Kong. Los Angeles, no Hong Kong. Dallas, no Hong Kong. However, we still have this empty array. So this is where we need to delete that entire key. So down here, like I said, you may not do this very often. Delete this dot adjacency list of that vertex. So delete Hong Kong entirely. So if I rerun this, we look at the adjacency list again. It's back to Hong Kong. Now let's remove Hong Kong and look at the adjacency list again. There's no trace of it, hopefully. Yes, good, it's gone. Again, I don't know why we'd remove a flight or all flights to Hong Kong. Seems like that wouldn't happen. But you can see it's gone. Let's try removing Aspen now. And if we look at the adjacency list, no trace of Aspen either. Okay, so that's one way of writing remove vertex. There are other ways you could write that would be a little more efficient. Also, you could pretty easily add in some error handling, just add a conditional to make sure that the vertex is valid. But again, I'm keeping this very bare, minimal, just to focus on the logic. So next, now that we have our basic skeleton, we can add and remove vertices, edges. Now we're going to actually build out a little more complex graph and then talk about traversing and recursion and depth first and breadth first, and yeah, get your aspirin or Advil ready or alcohol or whatever you need. It's going to be quite the ride. No, it's fun stuff. Okay, that's next. Hey, welcome back. So at this point, we have the ability to store data in a graph structure. We wrote the graph class, we added in methods to add and remove vertices and edges, so we can store everything, we can represent a graph. Now we get to go to the really, really juicy, meaty, important stuff, which all has to do with traversing our graphs, searching or visiting neighbors from a given node. So we'll get into the real world uses for this. There are many, many of them. Just like 2 slides from now, I'll talk about it. This is also a topic that comes up a lot in computer science textbooks and final exams. It comes up in interviews. which I actually think it's a great interview question because of how many real-world applications there are. So it's not some arbitrary, just test of how much do you remember from college computer science. It's something that actually is relevant in today's world. So we'll talk about why. But when we say traversal, for now at least, I just mean visiting every single node, every vertex in a graph. So there's many ways of doing this. Usually, like when we talk about the real-world applications, you may not be visiting every single node. A lot of what people do has to do with finding nearest neighbors or most similar neighbors or finding the shortest path from one vertex to another in the case of GPS directions. So it's usually more special cases rather than visit every single node in this entire graph just to say that you've done it. But we got to start somewhere. And a lot of the more advanced algorithms are derived from our basic traversal approaches, the procedures we're going to talk about now. So when we say traversal, we mean visiting, updating, checking, searching, printing out, whatever, every vertex in a graph. So we start from one vertex, which if we go back to trees, remember trees are a special subset of a graph where for any given node, there is only one path, one and only path to get to this node. So from 17, the root, to get to 25, this is our only option. To get to 89, there's one option. Now, if we compare that with some other graphs, so the more generic graph, basically this is not a tree. Every tree is a graph, but there are many, many graphs that aren't. So for example, this one. This is a directed graph, which we haven't worked with very much, but it just means that those connections, those edges they have a direction associated with them. They're one way. So let's say I want to go from 0 to 6. And actually, even before that, we have a problem of not knowing where we start from. There is no root. So yeah, maybe as humans, we want to start at 0 because it's the smallest number, but there's no indication that this is the start point. We could start from here or from here. So unlike a tree, when we write the code to traverse a graph, we need to specify our starting point. So let's say I want to go from 0 to 6, for example. There is at least... Well, there's this option, 0 to 1 to 6. We can go 0 to 2 to 3 to 6, 0 to 2 to 3 to 5 to 8 to 6, and I think that's it. If this was a undirected graph, we would have some other options too. We could go from 5, we could go from 7. So my point here is that for any node in a graph, there's no guarantee there's one unique path to get there. Now, that doesn't mean that traversing is harder or more difficult, but it does mean that sometimes, there's certainly multiple orders, but also you may end up having to do some backtracking. You may revisit a node you've already been to. You almost always do. And it's not much code, but we have to write code to pay attention to that. But first, let's go back and talk about why you should care before we get into the specific algorithms. So anytime we have a graph, whether it's a network graph for a torrent website, or we're talking about web crawlers where we have, like Google in the early days, would just follow every link from one page. It still does this, but would go from one web page, follow all links on that web page, and follow them out and out and out. And in reality, it's not a tree structure because you have many web pages that link to one another. So to follow every link, that's a graph structure. So the actual process of traversing, of crawling, is just a graph traversal. Also, when we talk about things like finding the closest matches or recommendations, the shortest path between things, I'm going to show you a couple examples. These all have to do with traversing from one vertex to another. So here's this Wikipedia visualization of a small subset of Wikipedia pages. In order to create this, somebody or some code started from one web page. I don't know which one they started from. And let's say here, and they wrote code to traverse every link in this graph and draw a little dot or something like that, and then follow one of them, followed a link to something over here, and that one linked to many other things, and from there, we went on and on and on and traversed all of these Wikipedia pages. So just to generate this involved some graph traversal. But that is sort of a basic example, just to draw something. If we go back to this example, when we're talking about using a graph structure to help make recommendations, this is an illustration, a poor one, of two video games where I'm trying to show that there's some overlap between Borderlands and Halo. Now, if we had this for 10,000 video games and we had thousands and thousands of data points for each game and things like reviews, scores, genres, how many copies were sold, different elements of the gameplay. So if somebody said that they liked Borderlands and you wanted to figure out a game to recommend to them, or a product to recommend, or on Netflix, a movie to recommend to someone, it involves starting here and trying to find something that's most similar, that you have the most overlap with. So this is a small graph, so we can tell there's only one option, Halo. But if there were millions of other data points, we might need to traverse across them and try and tabulate what's closest, what has the most nodes or the most vertices in common with Borderlands. That involves traversing from one node to a bunch of other nodes. Or here's one more example. If we're talking about friends on something like Facebook, this very simple example, just from this, we could make a recommendation. Let's see, Maria is friends with Nan, Army is friends with Nan, and Tim is friends with Maria and Army. So if we wanted to find a recommendation to Tim, who he might know, like you've probably seen that on Facebook, you might be, I don't know exactly what it says anymore. We recommend this person, or do you know X person, or suggestions for friends. You might recommend Nan based off of the fact that from Tim, we can get to Nan pretty easily. Nan is one jump away. We go to Army, well, 2 jumps, I guess. 1 and then 2. We go to Maria, 1 and then 2. And so we could write some algorithms, traverse outwards, find friends of friends. And whichever friend of friend has the most friend of friend, that's a bad way of putting it. Whoever looks closest, whoever has the most friends of friends with me, recommend them. Okay, so my point is there's lots and lots of applications, even things like artificial intelligence. If we talk about all the different possibilities for a board game, a layout in a game, like tic-tac-toe is a simple example, but let's say something crazy like Scrabble, where there's so many options. You could use a graph to store different game moves and then traverse that graph to find the shortest path to a winning move, the shortest way to win the game, for example. GPS navigation. We have millions or billions of vertices representing a map and intersections and businesses. How do we find the best way to get from one place to another? So that doesn't involve just direct traversal. That involves finding the shortest path, not just blindly traversing the entire graph. But we have to start somewhere before we can talk about shortest path algorithms, before we can talk about making recommendations. We just need to be able to visit every single node. And there are many ways of doing that, just like with trees. So in this section, we're going to talk about depth-first search or depth-first traversal, both recursively and iteratively, and we're going to talk about breadth-first traversal. Now, it's not that different from what we did with trees, but remember the distinction that I showed. There are times where you're going to have to visit a node again or realize you've already visited that vertex and adjust accordingly. But I'm getting ahead of myself. Let's now talk about depth-first search and how it works in the next video. Hey, welcome back. Let's kick things off with depth-first traversal of a graph. So just like with trees, which we spent a good amount of time on, binary search trees or binary trees in general, there are 2 main options for traversing these trees, depth-first and breadth-first traversal. Now within depth-first, we did talk about pre-order, post-order, in-order, but the general idea behind depth and breadth-first is what we care about. So when we say depth-first for this binary search tree, or any tree, it means that we're prioritizing visiting children of a given node before we visit siblings. Or we deepen the traversal before we widen it. So what that really means, whether we're going left or right first, doesn't really matter. But let's say that we go left. So we start at 41, we're going to visit 20. And rather than going to the sibling, we're now going to finish out the children of 20. So that gets us to 11, it's a dead end. Go back to 20, finish out the children, now we hit a dead end. Now we go back and visit 20's sibling. And then we keep doing that. So we prioritize deepening of the traversal rather than broadening, rather than widening. So that's depth first. But in this section, we're talking about graphs that are not trees. And they're not necessarily harder to traverse, but sometimes it can be a little trickier to understand what depth means versus breadth. Because it's easy on a tree where we have a clear direction down, or it depends, how it's drawn. Sometimes you see trees drawn upwards from the root, but however it's drawn, there's a clear path through that tree. There's one root, and then you descend away, or you ascend away, or whatever it is, you're moving away from that root. So depth first means moving away from the root. When we talk about a graph, a more general graph like this, and this is a directed graph. Unfortunately, this website doesn't let me do undirected graphs and traverse them. But anyway, let's say that we pick one of these vertices. There is no root node like there is on a tree. But let's say we're going to start at 0. What does it mean to do depth first traversal from here? Well, really all that it means is finding one neighbor, following one neighbor, let's say 1, but there's actually 3 neighbors. We have 6 and 2. Let's say we follow 1, and then we continue to follow the neighbors of 1 before we visit its siblings. And when we say siblings, it's kind of different than a tree because they're not necessarily on the same level. But let me just put it this way. If we start at 0, let's say that we always choose the lowest number as our next item to visit. So we go to 0 to 1. Now in a breadth first, which we'll come back to, we would then visit the other neighbors of 0, like 2 and 6. But in depth first, we're going to go 0 to 1 to 5, and then come back to 1 and go to 6. And then from 6, we visit its neighbors, like 7, and then 9, and so on. Rather than a breadth first, where we're going to visit 0, 1, 2, 6, all of 0's neighbors first before we visit 1's neighbors and 2's neighbors, and so on. So let me show you a little animated diagram I put together. Here's a simpler graph. There is no, root node that we start from by default, but let's say we're doing a depth first traversal starting from A. We want to explore as far as possible down one branch before we backtrack. Again, we have to decide the order we're going to visit things in. So if we have A, there's 2 neighbors. Which one do we visit first? Well, let's just go with alphabetical order to keep it consistent. These are both neighbors, and we could visit either one first. But let's say we're going to visit alphabetically, so we start from A, and then we visit B. Now, if this were breadth first, we would then go back to A and visit E. But depth first means we're now going to explore B's neighbors. So let's pick a neighbor. Alphabetically first, we have C. We could do D, but let's do C to be consistent. Now from C, we have 2 neighbors. And we've already visited B, so this is an important idea. We have to remember where we've been. Otherwise, we could just go back to B. So we've done B, so that leaves us D. Now from D, we have 2 choices. And if we're going alphabetically, we're going to go to E and then to F. Now that order doesn't really matter as far as depth first. These are both neighbors to D, but it's just helpful for us to kind of have a concrete order if we're just doing alphabetical. Okay, so it's really important that we remember where we've been. Otherwise, we would go from A, let's say we go to B again. Well, B has 2 neighbors, or 3 neighbors, C, D, and A. And if we don't remember we've already been to A, what's stopping us from just going back to A and then going back to B? If we're always picking the earliest alphabetical, the lowest alphabet, A and then B, we'd get stuck. So here's another example. A slightly different graph. I know it's the same nodes, the same vertices, but different edges. If we start from A again, if we're doing lowest alphabetically, we would go to B. And then from B, we only have one choice. We go to D. Now we have 2 choices. Which one do we go to? Well, if we're doing alphabetically first, we go to E. Now we have 2 choices. There are 3 edges, but we know we've already been to D. So do we go to C or F? Well, if we're doing it alphabetically, we go to C. Now, from C, it's a dead end. We visited A, we visited E, so we go back to E. And now we have to finish E, we have F. And then we're done. So here's one more, it's the exact same graph actually, same animation, but down here, I'm displaying our adjacency list. So you can see A is connected to B and C, and that's reflected here. And I do have things listed alphabetically first. So the edge from A to B comes before A to C. Again, it doesn't really matter, but for me to explain, it's easier to do alphabetically first. Okay, so if we look at what happens from A, we start at A, and we visited A, so we're going to cross it off, meaning that anytime we see A as a adjacent node, we're going to ignore it. So we look at A, and we see that there's 2 edges, 2 vertices. So we could go to B or C, and we'll just take the first one. We go to B. So when we visit B, we now cross B off from here and from here to all of its edges. This doesn't mean deleting them. It just means that we're going to remember, I've already been to B, so ignore it next time we see it. So we get to B, which is right here, And we see that it has two edges, A and D, but we've already been to A, we crossed that off. So now we go to D, and we cross D off because we've been there. It has three edges, we cross D everywhere. So now at D, we look, well, there's three choices, but we've already been to B, so we'll go to E next. And we cross off all those E's. Now we go to E. Where should we go from E? Well, let's go to C. Okay, so we go to C. And we cross all those C's off. And now we go back to E where we were last. And we've already visited C, we've already visited D. Now we need to visit F. And we're done. Okay, so that's the basic idea of depth-first traversal. We follow a branch down. It's harder to say we're deepening because it's a little more challenging to visually understand what depth means in a graph. Because when we have a tree, it's easier. We're moving away from the root. In this case, this looks like a loop, basically. So depth is harder to explain. What it really means is just following the neighbors and continuing to follow neighbors before backtracking. So we're going to implement depth-first search both recursively. Oh, I said search. We're actually going to do traversal. It's the same idea, except we're not searching for something. We're just going to visit every node, every vertex. Anyway, we're going to do it recursively and iteratively, just to show you both approaches. It's a good thing to know. So we'll start with the recursive solution. Well, first the pseudocode in the next video, and then an implementation afterwards, and then we'll do it iteratively, and then we'll cover breadth first. Okay, welcome back. So we're going to start off by implementing depth-first traversal of a graph two ways, recursively and iteratively, but first we're doing the recursive version. So I have a more detailed bit of pseudocode after this, but here's sort of the basic explanation. So define your function, your method, DFS, or you might want to call it DFS recursive so that you could do both iterative and recursive. And it takes a vertex to start from. There is no automatic inherent start point like a tree. So let's say you would pass in A. So we need to have a base case when we're doing something recursively. If you haven't seen the recursive section, you definitely want to check that out first. Otherwise, this will make no sense. So our base case is when vertex is empty. So the first time around, that's not going to be the case because we're passing in A or B or some starting point. If that is the case, we return something, return null, just get out of there. Otherwise, we're going to have a list of results. So we're building this array to return at the very end. So we add the vertex to the results list, meaning we've visited it. So we would add A in. And then we mark vertex as visited. So what would we do to actually mark it as visited? I'm just going to do something like this. Have an object, key value pairs, and when we visit F, for example, we add F in here and set it to be true. You don't have to do this. You don't have to set it to be true. You could use just another array and add A in there, but I like this approach. It's more explicit, and it also later on would allow you to mark something unvisited. If for some reason you wanted to, you could set it to be false, but it doesn't really matter. But this is how I'm going to do it. So mark it as visited. Then for each neighbor in that vertex's neighbors, so for all of A's neighbors, if that neighbor is not visited, recursively call DFS on that neighbor. So we would call depth first search on B and on D if those are the two neighbors. And then for each one of those, we do the same thing. We add it to the results list, and then we mark it as visited. We would add it into here so that we don't visit it again. We don't duplicate our work. We don't get stuck in a little loop, which I'll show you that is possible if you don't mark things as visited. And then we visit each of its neighbors. But when we do it recursively, the way that these things are ordered on the call stack, I'll walk through it in the solution video, we end up with a depth-first traversal. So a couple things. Here's the same explanation as before. I'm going to just move through this very quickly. We see that this is the adjacency list representing this graph structure over here. And what we'll do is as we visit A, we're going to start there, I'll add it to my visited object, key value pair. And anytime, let's say we're looking at C later on, we would check, all right, which of its neighbors do we have? So we have C, all right, well, we have A. And we'll look at A. Oh, it's already visited, so we're not going to do that. Anyway, so we start at A, we mark it as visited. So then we go to A's children, and we look at both of them. Has B been visited? Has C been visited? Well, B hasn't, so we're going to recursively call depth first search on B and on C. But because it's recursive, this is going to happen first. And all of B's neighbors will happen before we come back to C. It will be waiting on the call stack. So then we go to B, we visit B, we add it to our list of our object of visited vertices. And we look at B, and it has 2 neighbors. Well, for each one, we're going to check, has it been visited? Has A been visited? Yes, it has. So we're not going to recursively call it. D has not been. So we keep going, and you can step through this on your own, but this is the idea, where we're going to keep track of what's been visited. And each time through, we have this pseudocode for each neighbor in that one vertex's neighbors. Check if it's been visited. If it hasn't been visited yet, recursively call depth first search on it. So remember recursion, call the exact same function again. Now I'll show you the more detailed pseudocode in just a moment, but first I just want to show you this. This is the code with what we've already written that generates this graph structure. So if you do want to follow along so you can test if things are working correctly, it can be a little harder to, if you just make up your own graph, it can be harder to know if it's working because it's less linear than a tree. So it's harder to think through it, at least for me personally. So you could copy this code and have the same structure as me, the same graph, and you should get this same order. So as far as the more explicit pseudocode, the more detailed pseudocode, for the recursive version, write a function that accepts a starting node. And we'll just go with A for now, but don't make it implicit. Don't set a default. We pass in A. Then you're going to create an empty list, an array, to store the end result that will return at the very end. So this will store the order. It should be, A, and then B, and then D, and so on, if we're starting from A. Create an object to store your visited vertices. So that's something like this, but it should start empty. Okay? Then, the slightly trickier part. Inside of, you don't have to do it inside the same function, but I'm going to do it inside of it. Create a helper function which accepts a vertex. So what I'll probably do is name the outer function depth first search recursive. And then the inside I'll just call DFS. And this is the part of our logic that matches the pseudocode I showed you before. So this is the actual recursive function. This function just sets up like the array. It sets up the results that we'll return at the end. It first originally calls our recursive function because I don't know if you remember from the recursive section, we talked about helper method recursion, where sometimes you need some data to persist, so you can't just have one recursive function that calls itself. You might need an outer function. So that's the case here. Okay, so your helper function should return early if the vertex is empty. The helper function accepts a vertex. If it's empty, we're done. The helper function should place the vertex it accepts into the visited object, mark it as visited, and push it into the result the result array, our list that we return at the end. Then for that vertex, loop over all of its children, children's the wrong term, all of its neighbors, and for each one, if they have not been visited, recursively invoke the helper function with that vertex, this helper function. So we don't recursively call the main function, we recursively call the smaller helper function. And then we will, mark each one as visited, add it to the array, check if its children are visited, and keep doing the same thing. Then the important part at the very end, invoke the helper function here. So you define it, then invoke it with a starting vertex. So we set it on its way. And this inner function is going to be updating that results array, and it's going to be updating the visited object. Each time through, it will have access to that. And then at the very, very end, return the result array. This is what will have been constructed by these recursive functions. So we'll end up with A, B, D, blah, 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 if you use the same graph that I used. And again, you can create it easily by just copying this. All right, so give it a shot. Recursion can be hard, but I think I tried to write it out very clearly, step by step. But if you don't want to try it, just watch the next video. As I step through the call stack, we'll see how it works and why it actually is depth first. That's coming up next. All right, let's get started implementing depth first traversal recursively. So first thing we need to do is define a function that accepts a starting node. Okay, so here I have the same graph we've been working with, has an adjacency list, vertex, add edge, remove edge, blah, blah, blah. Down here is the code I showed in the last video. If you want to set up the exact same graph as me, it looks like this, although it's not perfect, this diagram. We already have the nice slides. So what we want to do is come down here and just define. This is going to be very long. You might just want to go with DFS R and DFS I for recursive and iterative. But because this is my solution code, I want people to be able to find it and understand what it is very easily. So I prioritize legibility over length. So depth first recursive, and it takes a vertex, a start point. I actually like calling this start to make that clearer. Okay, so that's the easy part. Now we have a couple things. We need to create a list to store the end result. We need to create an object to store the visited vertices. Okay, so let's do that. I'm gonna come down here and start off by making my, let's go with result first, an empty array. And then we'll also do visited as an empty object. Cool. So next up, we get to the meat of it. Create a helper function which accepts a vertex. And the helper function should return early if the vertex is empty. Let's just start there. So let's define the helper function. I'm just going to call mine DFS. DFS, and it takes a vertex. And then down at the bottom, I'm actually going to immediately invoke it with start, because that's the first time, even though there's no logic yet, the first time through, we want to start it off with start. You could also, you can define it this way, function DFS, blah, 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 and then call DFS manually and pass in start like that. But I prefer to do it this way. So function DFS vertex, and that vertex, we need to check if it's empty. That's our base case. So we'll just do if there's no vertex. And remember, that's when we hit the end of the line, if there's nothing to pass in to DFS. So if there's no vertex, we'll just return, I'll just return null. Okay, is this large enough? Hopefully. Okay, so here's our helper function. This will do the bulk of the work, adding data into result and visited. And then at the very end of this code, we'll return result when we're done. So let's start now with the real meat, which is we need to do this logic. The helper function should place the vertex it accepts into the visited object and push that vertex into the result array. Okay, so in here, we're going to add the vertex into result and add it into visited. And set it equal to true is how I'm going to do it. So we'll do, let's visit it first. Visited of vertex equals true. So that's saying, visited A is true. And then also, we're going to do a result.push vertex. The order doesn't matter. So that's done. What's next? Loop over all of the values in the adjacency list for that vertex. If any of those values have not been visited, recursively invoke the helper function. Okay, well, I'll tell you right now, there's a small problem. We can write this sort of the simple way that you might think it should work. This dot adjacency list, referring to the graph, its adjacency list of vertex. So that should give us, like if we did A, it should give us an array B, comma, C. But let's just print that out. Let's do console.log this dot adjacency list of vertex. Okay, and I'm actually going to execute this code now and call it g.depth first recursive, pass in A. So we should just see that adjacency list, that array printed out, but we don't. We get this error. Cannot read property adjacency list if undefined. It's this lovely problem with this in JavaScript, the keyword this. So what I'm going to do to make this easier is up here, I'm going to define our adjacency list to equal this dot adjacency list, because in here, our context, the meaning of this has changed. So I'm going to preserve it up here and just call it adjacency list. Also, it makes our code shorter. So now if I do adjacency list, it knows when we say that we're referring to this dot adjacency list, where this refers to the actual graph itself. Rerun the code. Now we get B and C. Cool. Okay, so now instead of printing them out, we want to loop over it. So we're going to do a for each neighbor. So I'll call it neighbor. Let's do the little fat arrow. We're going to check if that neighbor has already been visited. So how do we do that? Well, we have this visited object. We just pass in neighbor. So that will be, B and C for the first case if we're starting at A. And we want to do this if it's not been visited. If it has been visited, we can ignore it. But if it's not been visited, what do we want to do? If it hasn't been visited, recursively invoke the helper function with that vertex. Okay, so if it's not been visited, then we want to do return DFS neighbor. Okay, and we're basically done. We're missing one thing at the very end. I'm going to walk through this, of course, but we need to return the actual result array that we're building. Okay, So if this is, first of all, before I actually explain it, let me just make sure I implemented it correctly. It's very easy to have a typo when you're talking. Let's see, moment of truth here. Okay, so g dot adjacent, nope, what am I doing? G dot depth first recursive starting from A. Okay, it's working. A, B, D, E, C, F. I've done this one a couple times, so I know that's the right order. I made the slides with that order. But let's actually walk through what's happening on the call stack. So if you're good just to see that it works and you're done, fair enough. It's a bit difficult to step through. But let's actually open up the debugger, and I'm going to call down here, just copy this line so we see what we're working with, and add a breakpoint. Okay, so if I execute the code, scroll back up to the exciting area, and I step through this. All right, we get our first call of depth first recursive where start is equal to A. And we initialize some of our data. Okay, now, then we get our first call, DFS with start. So vertex is A. So if not vertex, return null. That's not true, right? So we skip that line. We set visited of A to be true. We push A into result. Okay, so result now contains A. So we can scroll down. A has two neighbors, B and C. So we're going with whatever is listed first, which is B. That's the way that I constructed it. I added that connection before A to C. So we go to B first. So let's go to that part. You can see we get this anonymous function for the for each that's been added. And we're going to check, have we visited neighbor? Well, neighbor is B. We have not. So we return DFS of B, and you'll see another DFS in just a moment. Here we go. So we still have a couple calls here on the stack. This is DFS of A, our nested inner function here. This is the for each, which is waiting to also do for each of C. Okay, so now we're at B, and I'll speed this up a bit. We check, is there a vertex? Yes, vertex is B. So that line is not true. We make sure to mark B as visited. We push B into result. So now result has A, comma, B. Now, for each child, shouldn't say child, for each neighbor of B, which means B really only has one, which is D. And I actually misspoke. There are two neighbors. There's A and D, but we've already visited A. So you can see we're checking if we visited neighbor. Well, that's already been marked as visited. So this does not happen. We don't return DFS of A, but we try it again with neighbor set to D now. And this is true. We have not visited D. So we return DFS of D, and you'll see it added to the stack. There it is. This is DFS of D. Vertex is not empty. It's not falsy. So we keep going. We ignore that. Visited vertex is true. So now we visited D. We push D on, and we go to its neighbors. Well, what neighbors does D have? It has B, E, and F. So you'll see first time through, we're looking at B, but we've already visited it. So we ignore. Now we're looking at E, which we haven't visited. So we add DFS of E. Look at this call stack. It's growing quite a bit. DFS of E is up here, and we check if not vertex. All right, there is a vertex, it's E. So we mark it as visited. We push it onto result. Then we go to each of its neighbors. If we look at the adjacency list for E, you can see C, D, and F. All right, so we're going to start with C. It's listed first. And neighbor C, we have not visited C, so we return DFS of C, and it gets added on. Oh boy, I should have made a smaller graph. C, vertex is truthy, so we skip this. We visit it, we set it to be true in visited, results.push C. Now for each of its neighbors. Well, what neighbors does C have? It has A and E. Well, we've already visited A, so we don't do this. We skip. We've already visited E as well, haven't we? Okay. So what happens now? This is the real moment. Finally, we've hit a dead end, right? We go to C, and we've been to A, we've been to E. So now what happens? Well, watch the call stack over here. Something got popped off. There was that for each that was waiting. So that's done. Now we're back here where we have vertex is E, and we're looking at its neighbors, which were C, and now we're looking at its other neighbor, which is D, which we've already visited. And now we're looking at its last neighbor f, which we have not visited. So we're going to add dfs of f to the call stack. There you go. Now we're looking at f, and there is an f. We visit it, we add it to the results. Okay, now we look at each of its neighbors. Is there anything that has not been visited? At this point, we've seen everything. We visited everything on this entire graph. So all of them are marked visited, which means we're not returning anything here. So we keep going. And you'll see things get popped off eventually. And finally, we end up out of our inner helper function, and we're returning result at the very end, which looks like this. And then it should, just a moment, almost there. There we go. A, B, D, E, C, F. Okay. So that was a lot to walk through. I totally understand if you didn't make it through that. I barely survived. So the recursion can be a little difficult to follow, but so just think of it as we visit a node and we visit one neighbor, and then we visit one of its neighbors, and we visit one of its neighbors. Anyway, it's a lot. Totally understand. I hope, though, that it at least makes a little bit of sense how it works, how the recursion works. Remember, I had to do this .adjacency list. This is the one gotcha because the context, the meaning of this changed in our inner function. So I have to preserve it up here. Also, it shortens our code just a tiny bit. I expect there to be a healthy amount of questions on this one. This is a bit tricky, but I think it might also help. In the next video, I'm going to do the same thing iteratively. So actually the order will be slightly different. It will still be depth first. There's not just one depth first order, but the actual result that we get will look a little bit different, and you'll see why in just a bit. Welcome back. All right, so if you made it through the recursive version, or if you just watched the solution, which in itself was a bit of a battle to make it through, we're now going to do the same thing iteratively. And I do recommend doing both of these because I think it helps solidify, for a lot of people, one, graph traversal, but two, recursion and iterative solutions in general, and sort of how they relate and how they're connected. So what we do, instead of using the call stack to help manage our state, to keep track of, where we're going and where we've come from, we're going to just use a stack itself. So in JavaScript, I'm going to just use an array to do that. You could write your own stack class again and take advantage of that, but for us, conceptually, and just to make it short, we'll just use an array. So DFS iterative, here's the basic pseudocode, and then I have the more in-depth version. So we'll make a stack called S, which will be an array, starts empty, and we push the starting node, the vertex will start from A, probably, onto the stack. That's the first thing we want to do. Then we have a loop. While S is not empty, while there's something in the stack, we're going to pop something off of it, call that vertex, and then we're going to check if it's not discovered, meaning if we haven't visited yet, visit it, add it to our list, label it as discovered, and then for each of its neighbors, push them onto the stack. So the first time through with A, well, it hasn't been visited because we just started, so we visit it, and then we mark it as visited. And then we look at A's neighbors, which, if we're using the same graph, are B and D. And once again, I do recommend you set up the exact same graph just to make it easier to follow along. All right, so that's the basics of it. I'll show you the more in-depth version in just a moment. You use a stack. That stack maintains sort of the order of things that you've been to, but also where you need to go back to and visit other neighbors, because the way depth first works, we're going to go all the way down one path, and then we need to go back and visit the other siblings. Not quite siblings, but the other branches. All right, so here's the more detailed pseudocode. Write your function. I'm going to call mine depth first iterative, and it should accept a starting node. I'll just call it start. Then create a stack. An empty array is what I'm going to use, but again, it's up to you how you want to implement that, just to keep track of vertices. Create a list or an array to store the end result. I'll call mine result. It should begin as an empty array. Then create an empty object to store visited vertices. Or you could do it with an array, but we need a way to keep track of what we've already visited so that we don't try and visit them again and get stuck in a loop. And then we need to add the starting vertex to the stack and mark it as visited. So we need to have something in there so that we can add this loop while the stack has something in it. Otherwise, if we tried to just wait to add it inside the loop, it would never run because the stack starts as empty. So we want to put the start at the beginning. We want to put that in the stack. Okay, so as long as the stack is not empty, I would just check as long as it has a length, pop the next vertex from it. If it hasn't been visited yet, mark it as visited, add it to the results list, and push all of its neighbors onto the stack. So I'm just going to use another for each, but rather than recursively calling another function, we're just going to push them onto the stack and use that stack. Rather than the call stack to keep track of where we are, I'm going to use just an array to do it. And then at the very end, we need to return the result array. So a quick note, you'll actually end up with a different order than what we did in the recursive solution. It still will be depth first, but it's a different order, and we'll talk about why that is in just a bit in the solution video. Welcome back. So I'm going to implement the iterative solution now. And the first thing I need to do, of course, is define the function itself. So what did I call this one? Depth first recursive, depth first iterative. You could definitely do something simpler. Okay, so it accepts a starting node, and there's a couple of things we have to get out of the way. We have to make our stack, we have to make our result array, and our visited list, or not a list, object. So visited, we could actually just copy this from up here. Results and visited. But I also need to make my stack, and I said the stack is going to be, I'll just call it stack, an array as well. But we need to put the start in there. Remember this line here, add the starting vertex to the stack and mark it visited. Well, I'm just going to do this rather than pushing it, just have it initialized there. Then after that, we need to mark it as visited. Let's just make sure we did everything else. Made the function, made the stack, created a list, add the, okay, this is all good. We need to add the starting vertex, we did that, mark it as visited, and then we'll add our loop. So I'm going to set visited. I'll make this just a separate line just so we can see these are our variables, our declarations. Visited of start equals true. Again, you could just use an array to manage what's been visited. Let me close this, by the way. But I like doing it this way. With an object, it's just more explicit. Okay, now we need to do our while loop. So while there's something in our stack. So I'm just going to do while stack.length. You could do greater than 0, but stack.length is easy because as soon as we hit 0, we're done. It will be falsy. While the stack has something in it, pop the next vertex from the stack. If that vertex hasn't been visited yet, mark it as visited. So let's start with that. I'm going to make a variable first to store what we're popping off. So I'm just going to call it, I don't know, current vertex equals stack.pop, just like that. Then we need to actually add current vertex to our result array. So result.push current vertex. So that's what we'll return at the very end. And then we're going to go to each of its neighbors. And before I do that, rather than redefining current vertex each time through in this loop, I'm going to come up here and just do let current vertex, and then down here, give it a value. Minor thing, but I just don't like, constantly reinitializing current vertex inside a loop. Now we need to add each of its neighbors to the stack. Well, if they haven't been visited yet. And let's just start by accessing the neighbor. So this dot adjacency list of current vertex. So that's going to give us, if we're talking about A, it will give us an array that contains B and C. Okay, so this dot adjacency list, current vertex dot for each, kind of a long line. I'm going to call it neighbor. You could call it, I don't know, connection, pal. I wouldn't call it pal, probably not. So what do we do? Well, if it has not been visited, so if inside of visited there is nothing for neighbor, if that's the case, we need to make sure that it has been visited. Okay, so we're going to visit the neighbor, and then, well, we'll set it to be visited, then stack.push neighbor, just like that. Okay, and we're basically done. We just have to, at the very end, return our correct result. And as we're going through this, how about right here, we do a console.log of the stack so we can see what we're working with. Okay, so I'm going to execute our code, and I'll call g.depthFirst iterative with A. And what do we get? If I can make this larger. Okay, so first of all, the order we get is different, and we can talk about why in just a bit, but it still is depth first. If you don't remember, let me do the same thing for recursive. We got A, B, D, E, C, F. So the recursive version was A, B, D, E, C, F. which is still depth first. The iterative version, instead of going A and then B, we actually end up going A and then C. But as long as we're following this path down and following one of C's neighbors and its neighbors and its neighbors, it's still depth first. It's just we started with C rather than B because of the way that our code works, and you'll see why. So A, C, well, we go to C's neighbors. We've already been to A, so we go to E. Then from E, we have 3 choices. We've already been to C, so we have D or we have F. And our code goes to F next. And then from F, we could go to E. We've already been there, so we go to D. And then from D, we could go E, F, or B. Well, we've already done this. We've done this, so we go to B. But it still is depth first. We go here, 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 here. So think of it this way. If this is our adjacency list, it's the same for both versions. What we are doing in the recursive version, we started at A, we go to B, alphabetically first, or whatever's first in this adjacency list is visited first. So A to B. Versus in the iterative version, we went to A to C. And then from C, we look at C, we go to E. And from E, we've already been to C, and we go to F. We're taking whatever is at the end, or we're working from this direction, if that makes sense, from the end of the adjacency list rather than from the beginning. So now let's walk through why this works. Let me clear this. And let's do iterative of A. This is what our stack looks like the very first time through. We have A. Okay, so we visit A. We go up through our code a bit more. We're going to visit it, add it to the result. So our result now contains A. Then for each neighbor, well, we have 2, B and C. We add them both in. So we popped A off, it became empty. Then we add B and C. Cool. So then what we're going to do is visit C because we are popping off the end. So we're going to C next. And then we're going to add it to the result. So our result looks like A, C. And then we go to C's neighbors and we push those in. So we end up with B and E because we've already visited A, we don't add it in. So then next, we pop off the stack, we go to E. So we visit E, A, C, E. Okay, so you can see that B is just patiently waiting here. This, if we were doing breadth first, we would go immediately A to C and then back to B. But it's depth first, so poor B is waiting. Or in the recursive version, we go A to B and then C is waiting. Anyway, so we keep going and you can see that we end up with E's children or E's neighbors. F and D are both added in, and D is first and then F, but we pop off the end, so then we visit F next. And then from F, we don't have anything to add because we've already been to E and to D. Well, we haven't been to D, but we've already added it into our stack, and we've already visited it, meaning we've set it to be visited true. Otherwise, D would get pushed in there again. Okay, so then we pop F off. Now we have B and D. We start with D. We pop off the end. And then finally we get to B. It's the last thing added. So we're using a stack, an array, to keep track of sort of where we need to go back to, right? We're going here. We know we need to visit B at some point, but we start with C. And then from C, we go to E. And at E, we're going to go to F, but we also need to remember to go to D. So we add D in as well. But poor B has been waiting this whole time. It's depth first. So I do think for some people I think the iterative version is easier to understand. But I think that the recursive version is important to understand why it works. It's a classic use case for recursion, graph traversal that is. And I think, if you can get one of these, if you can understand, you can walk through it, you're good. So this is the iterative version. We saw the recursive version. They both are depth first. We do get a slightly different order. There's not one exact precise depth first order for any given graph. So there are different orders, but they are depth first. Okay, next up, breadth first. We're only seeing one solution. Welcome back. So we're now moving on to breadth first traversal of a graph. So breadth first prioritizes visiting all of the neighbors at a given depth before moving downwards or visiting neighbors of neighbors. So let's take a look at an example first. With a tree, it's always easier to talk about because we can just say horizontal before vertical, before descending down. With a graph, though, it's a little more complicated, but we can still talk about depth. There are layers, there's levels. It's actually called height. So if we start from 0, there are 3 neighbors of 0. So we could call each one of them 1, 2, and 9, each one of those have a height of 1. So we could put a little 1 next to them. Then if we go from 1, there are 3 neighbors of 1, 11, 3, and 6. Those would have a height of 2. If we look at 9, there's 8 and 4. Those have a height of 2. They are 2 jumps away from 0. 1, 2. Something like 10 would have a height of 3. So when I say height, just imagine a little number here, a 1, and a 1. Then we have a 2, 2, and a 2. And we're going to visit all of the things on the same height, horizontally in this case, or sort of diagonally across, before we visit their neighbors. So here, I'll play it for you. Again, the order we go in this case, is going to be 1, 2, 9. On this website, they use the lowest number first, I believe. But we could also go 9, 2, and then 1. Either way, we're prioritizing visiting neighbors, all neighbors for a given node or vertex before visiting neighbors' neighbors. Okay, here we go. So you can see it actually draws those little numbers. And then from 1, we visit all of its children. I shouldn't say children, all of its neighbors. And we keep going. Now, of course, we have to keep track of what we've already visited because, like here, if I pause, we've already visited 5. So we don't want to continually visit it again. There we go. We're almost there. Okay. So the actual order that we go in doesn't matter that much. Like I said, if we're going to start 9, 2, and then 1, or 2, 1, and then 9, it's just that we're fleshing out all of the neighbors for a given vertex first. So on our more simplified graph, if we start from A, we could go E and then B, or we could go B then E. And that's what I coded in here is A, B, E. Then we go back to B and visit all of its neighbors. So we've already done A. So we have C and D. Then we go back to E and we visit all of its neighbors. But we've already done A, we've already done D. So its only neighbor that's left is F. And then from F, we've already visited everything else. And we're done. So in the next video, I'll have the pseudocode. All right, so here's the pseudocode to implement breadth-first search. It's very similar to what we did for depth-first search, except we actually use a different data structure. Rather than using a stack, we use a queue. But I'm just going to use an array, which we did for the stack, but we just use different methods. Rather than push and pop, we'll use push and then shift, so that we are adding to the end, but removing from the beginning, so that the first thing in is also the first thing out, unlike what we had with the depth-first version, where the first thing in had to wait until the very, very end. Okay, so your function should accept a start. We'll just do A. Create a queue, just use an array, just make a variable called queue, and place the starting vertex in it, so there's something to start. Then, just like before, create our result array, to store, what we return at the end with our order. Make an object to store the visited nodes like we've been doing. Just call it visited. And then mark the starting vertex as visited. Then the bulk of our logic. As long as there's anything in the queue, just a while loop, while there's something in there, we're going to shift the first vertex from the queue and push it onto the array that stores what we visited, that stores our result. So take the first item out and push it to the result, and then for each neighbor in that vertex, all of its neighbors in the adjacency list, if we haven't visited it yet, mark it as visited, and then add it to that queue. Push it into the end. Okay? So we have our queue. It's the exact same process, well, almost the same process as depth-first search or our depth-first traversal, the iterative version, but we're using a queue instead of a stack. So we're still pushing to the end, but we're now shifting from the beginning. Otherwise, it's pretty much the same. I'm going to write the code again in the next video, but you could just take your code if you wrote it, or take my solution and just slightly tweak it. And at the very end, we do need to return the array of all the nodes we visited. Okay? So make this queue to store everything. Put the first node in there where we're starting out. And then while there's something in that queue, we're going to remove the first item. We're going to add it to our result. Then we're going to look at each of its neighbors. And if they're not visited yet, if they're not marked as visited, mark them as visited, and then push them to the queue and keep going. And then return the entire result at the very end. Okay, so let's do that in the next video. All right, welcome back. So I've made a new snippet. Otherwise, basically doing everything the same. I have my same code. You can get that from the slides. A couple videos ago, I talked about this if you want to follow with the same graph. So I'll start by defining breadth first down here, which takes a start vertex. Just call it start. And then we need to define a couple of variables. So I'm going to make my queue as an empty array, and I'm just going to add start in right out of the gate. We need to make our result. We could just copy this from up top, any of these, if you watched the previous videos, and my variable visited to keep track of what we've been to. Then we're going to loop while the queue has a length, and the first thing that we do is remove the first node in the queue from the beginning. So instead of pop, we're going to do shift. So queue.shift and store it in a variable. And we could define the variable here. I'm going to call it current vertex, just like we did in the last video. But I'm actually not going to redefine it in a loop. I'm going to move it up here and then set it here. So initialize it once, set it over and over, update it. Okay. And then we're going to visit that node, which means result.push current vertex. So we take the first item out, and then we push it into our array that we return at the end. Now, the slightly trickier part, we need to go to all of its neighbors. So that's a this.adjacency list of current vertex, and then .for each neighbor. What are we going to do? Well, we're going to check if it's been visited. Or actually, we're going to check if it's not been visited. That's what we care about. Because if it hasn't been visited, then we need to mark it as visited. Just set it to true. And we need to push it onto the queue. And we're actually done. So at the end, we do need to return it. So kind of a lie, we're not quite done. But now we are. So the way that this one works, if we step through it before we even run it, here's our sort of visited result that we're going to have at the very end. And then here's our queue. Let's do it like this. Okay? Perfect. We start by adding A to the queue, and then we remove it first thing and add it to result. And then we go to its neighbors, this.adjacency list of A for each. So there's two things in that list. There's B and there's C. And we're taking the first thing. If we actually looked at the list, B does come before C because I added that connection first. So we're going to add B into our queue, and we're also going to add C into the queue. And then the loop starts over, and we take from the beginning, we shift. So we remove B, and we add it here, if I can type. And then we add its neighbors. So we loop through. Its neighbors are A and D. Well, A has already been visited, so we ignore it. So we add D to the end, right here. And then we remove from the beginning, which gives us C. So we add C into the result, and now we go to its neighbors. Well, we've already been to A, so now we have to go to E. So we add E after D in the queue. Remember, first in is a first out. So we take D out, and we visit D. And we go to D's neighbors. Well, we've already been to B, so we don't add that in. We've already been to E. Well, it's in the queue at least, and that's when we mark it. Remember, we added in after we mark it visited. Okay, so then all we have left is F. So we add F, and now we go to E. We take that from the beginning with shift. We put it here, and then we're going to go to its neighbors. Well, we've been to all of them, so we don't actually add anything in. And we remove F finally, and that's what we visit last. Now, let's see if I'm just making that entire thing up or if this actually works. I'm going to comment that out, run our code, and we have graph.breadth first starting from A. A, B, C. Oh, looks like we have a little issue here. Let's see. Aha, I found the problem. Maybe you saw this before me, but what we're not doing here is marking A as visited at the beginning, which actually is in my pseudocode, and I ignored it. You can see here, mark the starting vertex as visited. So what's happening there, if we just print out, let's do it at the beginning here, console.log the queue, and run my code, g.breadth first from A. Oh, I didn't have to rerun it. Okay, here we go. We start with A in there, but I don't mark it as visited in my visited object. So then we go take it out, we add it to our result, we add the children or the neighbors B and C. Then we take B, but B actually has two neighbors, right? A and D. But we didn't mark A as visited the first time. So we add it back in, and then we add D. And then we keep going from there. But that's not right because we started at A. So if we mark it visited, you'll see at the very end we have A in there twice. That's not good. So we mark it visited right up here. We'll just do visited of start equals true. Perfect. You could also just set that here, visited with a D. And now if we keep that console.log, rerun the code, we end up with A, B, C, D, E, F at the very end because A never gets added back in. And it's all working. All right. So let's get rid of that console.log. Here we go. One more time. G.breadth first search of A, B, C, D, E, F, which means we're going A to B to C to D to E to F. That's breadth first. Okay, so we're going sort of left to right. You can think of it, whatever order they are in, the edges are in the adjacency list. We're going from the beginning of the list to the end. So I added A, B before AC. So we visit B before C, and then D before E, and then F. You could change it if you really wanted to. There's no easy, as far as I know, there's no shortcut to reverse for each. Some languages you can, just specify, I want to loop over this array backwards. But a sort of easy way, just to show you, if we do this, slice.reverse, and I run the code now, you'll see we start from A, but now we go to C, and then B, and then E, and then D, and then F. So rather than A, B, C, like left to right, we're going right to left. Still breadth first. Just like with depth first, we had different orders. Same thing here. And I want to be clear, there's not only two orders. This could be a much larger graph, and we could have, 5 neighbors for A, in which case it's not just B, C, or CB. There would be 3 other neighbors to worry about. Okay, so that's breadth first. Hopefully you can see it's very similar to what we did with the depth first iterative solution. So now that we have all of this out of the way, we're able to visit every single vertex in a graph. We get to go to the fun stuff, which has to do with mainly shortest path algorithms. This is a really important thing to be able to do with graphs, and one of the most commonly done things in all sorts of applications, whether we're talking about Uber, or we're talking about Google Maps, or we're talking about Google search results. It's not just map stuff and GPS. So we'll talk about that in just a bit. Hey everyone, welcome to a new section. This one is a little special. It's a little different because it's not about a new data structure. We're not learning a structure and implementing it. Unlike, I guess, the past 10 plus sections where it was, all right, this is a tree, let's write one. This is a graph, let's write one. Instead, we're learning and implementing a single, very famous algorithm called Dijkstra's. So Dijkstra's algorithm, it's shortened from Dijkstra's shortest path algorithm. Most people, if you just say Dijkstra's, they know what you're talking about. Well, not most people in the real world, but most computer sciencey people. It's very, very famous. It's one of, if not the most famous algorithms out there. We'll talk about why it's named Dijkstra's, who he was, what he did, and most importantly, what the algorithm does in just a bit. But the first thing I want to say is that even though this is not about implementing a new data structure, there are two sort of prerequisite data structures. One is the graph, because Dijkstra's algorithm acts upon a graph. It searches across a graph. So if you didn't watch the graph content, you definitely want to do that. And then the second thing is that it actually uses a priority queue as part of its implementation. So in this section, we're not going to write a priority queue from scratch, because in the binary heap section, we did that. We used a binary heap to implement a priority queue. Now, if you skip that, I understand there's a lot of content in this course, and you don't necessarily have to go, video by video, but I am telling you now, you definitely want to go and just watch the priority queue section or the binary heap section, and in particular, the priority queue videos at the end, because that code will come up here. So I'm just going to copy and paste it over. So just as a warning, those two things, graphs, binary heaps, I would try and familiarize yourself with them first. All right, next, let's talk about our objectives. So first, we're going to understand the importance of Dijkstra's that's happening in this video, the history, that sort of thing. Then as a sidebar, we have to implement a weighted graph because Dijkstra's algorithm works on a weighted graph. And so far, we've only done unweighted graphs. After that, we'll begin sort of digesting and understanding the algorithm. Now, it's not terribly complicated, but it gets long enough that me giving you a single slide of pseudocode probably wouldn't be enough. So I have some animations, some videos, or some slides I made to walk through it, some diagrams. So we're going to just go step by step how it works on a sample graph. Then we'll implement it using a naive priority queue, and then we'll upgrade it a bit using our binary heap priority queue. All right, that's a lot of stuff for a single algorithm. Let's start by talking about what it even is. All right, so if you happen to skip the last video, we're talking about Dijkstra's algorithm here, and the two important things you need to know before you begin this are graphs and priority queues with a binary heap, both of which I have a lot of content on in this course. So what is the algorithm? It's one of the most famous and widely used algorithms around. Pretty much every computer science class around the world learns it at some point. And more than that, it's not just an academic thing. It's not just an interview challenge, although it often is, or it does come up in interviews. Most importantly, it's used all the time. Often, big tech companies will base a lot of their more proprietary, sort of special secret algorithms on top of Dijkstra's, add in some of their own special flavor, I guess. So we'll talk about what that would look like, and a lot of the use cases. But what it does primarily is it finds the shortest path between two vertices on a graph. So if we have a graph with 10,000 different vertices, how do we get from point A to point B? What's the fastest way? There could be a billion options on a really large graph. How do we calculate the shortest one? So that's the problem that Dijkstra's algorithm solves, hence the term or the name Dijkstra's shortest path algorithm. First, let's talk about who Dijkstra was, just a sidebar here. So Edsger Dijkstra, I'm butchering it, I know. He was a Dutch programmer. He actually died relatively recently. Well, not that recently, but 2002 or 2003, I believe. But he was working in the early 20th century when computer science was sort of a new field. And he was a bit of a polymath. I think he started as a physicist, theoretical physicist. He wrote a bunch of essays, not to mention tons and tons of academic papers on programming, mathematics, problem solving. Really smart guy. And more than just smart, very influential. So he helped to advance the field of computer science from, at the time, was more of a burgeoning art to the crazy academic discipline that it is now. He really established a lot of the academic rigor that's present in computer science. He came up with a bunch of papers, most of which are still cited today. I read some fact that out of the 30 most influential papers, he wrote 6 of them, I think. Something like that. I don't know how you determine most influential, but anyway. The other thing is that he actually created new fields within computer science. Single papers that he wrote spawned off these new disciplines. So very, very influential. And unlike some other pioneers whose work sort of at the time was very important and led the way for other breakthroughs, a lot of the stuff that he talked about and wrote about is still in practice today or commonly used, like Dijkstra's algorithm. So here's a little screenshot from Wikipedia. On the right side of his Wikipedia page, like any sort of academic figure or really any person, there's a little bar that says known for. You can see he's known for a lot. Up top, his main achievement that people recognize today, Dijkstra's algorithm, but there are many other algorithms, as you can see, but also things like self-stabilizing distributed systems, shunting yard algorithm, smooth sort, separation of concerns, early software architecture. He did a lot and contributed a lot. So really cool guy and very, very important person. Now the algorithm itself, it is listed up top. It's widely used, widely taught, as I mentioned, and we've kind of explored the main idea behind it, finding the shortest path between one point and another. But the story of how he came up with it and why he even tackled this problem is kind of interesting. I don't know if this is 100% true, but it's on Wikipedia, which doesn't always mean much. But apparently the impetus for him actually doing this, for coming up with his shortest path algorithm, is that he wanted a problem that he could come up with to demonstrate to the general public why computers were awesome, why they were powerful. He wanted to show something that was difficult for humans to do, and how easily computers could do it. So he came up with this travel problem of finding the shortest path along the massive train network in the Netherlands, figuring out the fastest or the shortest way. This is his quote. What is the shortest way to travel from Rotterdam to Groningen? I'm not Dutch, sorry about that. From any given city to given city. It's the algorithm for the shortest path. And then here's his little humble brag, which I designed in about 20 minutes. Apparently he was shopping and then over coffee and he was tired. He designed it at like a little cafe table in 20 minutes. And eventually that algorithm became, to my great amazement, one of the cornerstones of my fame. So it's kind of fascinating. He didn't set out to solve this as his thesis or as his greatest achievement, this problem that haunted him his entire life. It was more of I want to just come up with something that the public will understand, something that will demonstrate the intrinsic value, the worthiness of computers. How about finding the shortest path using the rail network in the Netherlands? And then that is actually what went on to have a lot of implications and use cases to this day. So lastly, let's talk about why that is. Why is it still useful? So the most obvious thing that I've already mentioned this as an example, GPS, or any sort of mapping software, whatever app you use, whether it's Google Maps, Apple Maps, whatever other versions there are out there, or you have one of those old school GPS devices in your car, MapQuest, all of that involves finding the shortest path from one point to another. And all of that data can be represented using a graph. Now, of course, there's a lot of other complications in today's world. And like Google Maps, its algorithm takes not only the distance, but the capacity of a road, the number of lanes, the traffic, accidents, weather, time of day. I'm sure there's many other factors I'm not even thinking about. Holidays. Yeah, there's a lot that goes into it, but it's still based on finding the shortest path. Now, what makes something short might be different because our version we're going to talk about, we're looking at a single criteria, like distance on a map. We're not implementing traffic and all of that stuff. But at its core, we could take Dijkstra's algorithm as we're going to learn it and then tweak it to add in traffic or to account for weather and that sort of thing. Next up, network routing, finding the shortest path for data across a massive network. If you think of computers, they're connected in a graph. Let's just say 1 million computers. How do we break up a large message into a bunch of little pieces, send it across a bunch of computers and end up at another computer? What's the fastest, shortest way to get there? Biology, it's used often to model sort of the spread of infectious diseases across humans, often used in projections. I have no expertise in that. That's just something I read online, but I found fascinating. Airline tickets. If you ever go on those websites and you enter where you're trying to go from one city to another, let's just say one way. Of course, you can optimize for all sorts of different things like duration, price, number of airline miles. But if you're willing, let's say you're trying to come up with the cheapest possible option and you're willing to make like 3 different stops. Well, there's a lot of options and it would be a huge pain to try and manually compute that. But using a shortest path algorithm where it's optimizing for cheapest rather than shortest distance, you might end up flying across the world a couple times, but it might be cheap and you might have long layovers, but the algorithm could do that, could figure that out for you. It looks like I put biology on here twice. Whoops, sorry about that. And many, many other uses, as we'll talk about as we go. But we're going to start with just a bland old graph. Maybe look something like this, where we have numbers representing the distances between cities or junctions in different paths. But before we can even talk about the algorithm, we have one small problem, which is we don't have a way of storing this data right now. If we simplify it, get rid of that map background, we can't do this part right here. We don't have a way of storing the information about a given edge. Our graphs are just vertices and edges. They are undirected, meaning there's no arrows. They are both ways. But they're also unweighted, meaning there's no value associated with them. So the first thing we need to do before we can find a shortest path, we need to just add distances or add a weight to our graph. So it's not hard. It will just take a minute or two in the next video. That's what we do next. So then we can actually implement a shortest path algorithm. So in the next video, I'll be back to write a weighted graph. All right, welcome back. So what we need to do before we can actually find the shortest path in a graph between 2 points, we need to just assign values between those points so we can find any path, short or long. And to do that, It's not that hard. All we do when we add an edge, instead of saying from A to B, we just say from A to B, comma, 90, from B to C, comma, 13. So if we hop over to a quick little snippet, we could just quickly redefine our class. So I'll call it weighted graph, and I'm only going to worry about adding a vertex and adding an edge. We won't worry about removing edges and vertices for now, because let's just focus on the important stuff. So class weighted graph, we'll add our constructor, exact same as our unweighted graph. We have an adjacency list. The main difference, though, is once we're actually adding edges in, what we had before looked something like this, where we had like A, and then it just had an array where we had B and maybe C or something. That's not going to cut it for us, because we now need to store not only the edge itself from A to B, but the value. So it's going to look something more like this, where we have a field, or it's going to be an object, and we'll have two properties. Node, which we'll just say is B, for example, and then weight, which will be 10, a number. And then, of course, we would have the same thing on B, where the node is A and the weight is 10. So instead of just simply the string B, we now need to add in an object. But as far as the vertex, if we had add vertex, it's exactly the same. So add vertex just checks if the vertex is already in the adjacency list, and if it's not, then we add it in and set it to be an empty array. So that's nice and easy. Now we can add in our vertex like A and B and C. Now to add the edge between two vertices, we need to accept two vertices. So let's go with vertex 1 and vertex 2, and then a weight. And if we look at what we did for our for our unweighted graph from earlier in the course, if you look at adding an edge, it's very simple. We just do this.adjacency list of vertex1.push vertex 2, this.adjacency list vertex2.push vertex 1. So we'll have to change a couple things because I used vertex 1 instead of v1, but that's minor. Okay, so vertex 1, vertex 2, vertex 2. But this won't work because we're not using weight. So remember, we need to store an object inside of that adjacency list. So inside this array we're pushing into, we're going to have an object where there's a property called node. It does not have to be called that, but you could call it vertex if you wanted to. But let's go with node and then weight. And rather than doing this, weight, because I want it to be called weight, and also the argument is weight, what we can do is just pass in weight here, and it will do the exact same thing as part of, I believe that was added in ES 2015. It may have been around before and I just didn't know about it. I'll do the same thing here. And that's it. This should be our weighted graph class. Let's see if it works, of course. I just executed the code. So let's make a variable called graph. It's a new weighted graph. And let's do add vertex first. Just say A and B and C. And now let's add an edge from A to B, which is going to be, 9. And then let's do A to C, which will be 5? Sure. And then let's do B to C, which will be 7. Okay, now let's look at the adjacency list rather than just trusting that it works. So we've got A, B, and C. And for each entry in the adjacency list, we have an object with a node and a weight. So for example, from A, we can see there's a connection to B with the weight of 9. And if we look at B, there's a connection to A with weight of 9. From A to C, there's also an edge with weight of 5. If we look at C, where are you? There you are. We have A to C, weight of 5. All right, so this is all working. Like I said, we don't need to worry about removing edges and removing vertices for now because we're focusing on the algorithm, but it's extremely similar to what we saw before, except now you just need to remove an object, but otherwise it's very, very similar. Okay, so now we have all the pieces in place to actually talk about the algorithm. Moving on to Dijkstra's in the next video. So this is our weighted graph class, very, very simple class. Might be confusing if you didn't watch any of the graph section. I should have mentioned that earlier in the video, but I did say that early on in this section. So definitely go rewatch that if you're confused about what I'm talking about here. All we did was add in a weight to each edge. So it's a connection from one vertex to another, now with an associated value. All right, next up, we're going to walk through the basics of the algorithm. Welcome back. Now that we have the weighted graph in place, we can move on to that's not how you spell it. Nope. There we go. It's a dumb joke, but this is actually the 3 attempts it took me to get it right. I'm sorry to tarnish his legacy. I can never remember how to spell his name. But it's the bottom one here, D-I-J. Anyway, what we're going to do now is walk through the steps of how the algorithm works. We're going to visually go through it one step at a time before we translate it to code. And the graph we're going to work with looks like this. So it's a weighted graph. Here's, 6 vertices, and each edge has a number associated with it. Hopefully it's clear what goes with what. And the shortest path that we want to find is from A to E. So there's a couple of options, and this is a very small graph, and most of the ones in the real world are quite large. But even with this small data set, there are many ways to get from A to E. We can go around the edges, we can go through the middle. There's 4+ options. Not to mention, you could take some absurd routes to get there, including loops. And anyway, so that's our goal. So here's the algorithm boiled down or distilled to 4 main steps. Each time through the main loop, we'll do something like this. So we look to visit a new node. That's, the only way that this works is we start at A and we visit nodes. And there has to be some order that we visit them in. How do we decide where to go next? And we start by picking the node with the smallest known distance to visit first. So I'll come back to all of this visually in just a moment. But we always pick the node that has the smallest known distance from A, and we visit that first. Then once we move to that node, we look at each of its neighbors, and then for each one of its neighbors, we sum the distance from A to that neighbor. And if it's smaller than what we currently know about, if it's a smaller distance, then we update our file, essentially. This is a lot to talk about without showing you, so I have a bunch of diagrams like this we'll get to in just a moment. But those are the steps. So every time we visit a new node, every time we're looking sort of to start the loop over, we visit the smallest known distance from A, in our case. We're looking for A to E. So we start with that, we move to that node, and we look at each of its neighbors. And for each neighbor, we already have a distance on file, how far it is from A. And we will update it if the new distance that we've summed together is less than what we currently know about. And I know that sounds crazy, so I'm going to come back to it. But here's our diagram. This is sort of the setup for the next 30-something, maybe 40 slides. I just fade between them, and you'll see stuff come and go. So the same graph is up here. We're going from A to E. It has the same values on there. And down here is sort of the file I was referring to, where we store the shortest distance from A for each vertex. So A is a special case because it's going to be 0. But something like B, well, eventually the shortest distance from A to B is 4, of course. But then like E, which we'll get to, that's our goal, is to figure out what the shortest distance is. And anyway, we'll be updating this as we go. And then previous, I'll explain in just a bit. So let's begin. And the very first thing we do is initialize the shortest distances from A for every vertex. And we don't really know how to do that. That's the whole point. We don't know what the shortest distance is from A to get to F. Imagine there's a million vertices on here. You can't just know from the beginning. So what do? We just put infinity in here. We put a large value, basically an unknown. We don't know any of these values except for one, which is A. We know the shortest distance from A to A is 0. From one vertex to itself, that's going to be 0. So that's what we start with. This is how we always initialize the setup. So we'll make a data structure for this. We won't talk about code just yet, but just imagine you're writing this down on a piece of paper. So A to A is 0. A to B right now is infinity. We don't know. A to E is infinity. So we ignore that. Now remember the steps. The next thing we do, every time we look to visit a new node, we pick the node with the smallest known distance to visit first. Well, we have one choice right now. A, that's the smallest. 0 is clearly smaller than infinity. So we start with A. So we pick the smallest, that's what that's showing here. And I've added it to the visited list here. Now what we need to do is look at each of its neighbors. So from A, we have two choices, A to B, A to C. And I'm always going to go alphabetically, it doesn't really matter. So we're going to start with A to B. So what we do is we go down to B and we check, well, currently the shortest distance from A to B is infinity because we don't know any better. That's just the initial state. So what we found is that the distance from A to B right here is 4. So 4 is definitely less than infinity. So we update this to say, all right, the new shortest distance from A is 4. And you'll see that we update some of these a couple of times. Of course, we can see, looking at the graph, there's nothing shorter between A and B. It's definitely 4. That's the smallest we'll get. Okay, so we update that here. And then over here in this previous structure, we're going to update B and set it to be equal to A. So what that essentially does, and I know I'm missing quotes, it's not valid code, but what this does is it says the way we got to B was through A. And that's obvious in this situation, but later on, something like F, if we update the shortest distance to F, we want to remember, did we get there from D or did we get there from C? There's multiple options. So this structure helps us piece together where we came from, the node that happened or that occurred right before B on our path. So that's a simple one. So we've done everything we need to do for A to B. Now we look at A to C. Okay, so currently from A to C, we have infinity. So we look at that distance, the total is 2. So of course we're going to update this. 2 is definitely shorter. And then we come over here to C, and instead of null, we update it to say, all right, the way we got to C was from A. And that's it for A. We've done both neighbors for node A. So now what we have left to do is we repeat the process. We pick the smallest known value, the shortest distance from A that we haven't visited. So remember, we've been to A, so we're not going to pick A because we just continually do A over and over and over. But now we have two choices. B, the distance is 4, and C, the distance is 2. And when I say distance, it's the distance from node A. Okay, so as you can see, we start with C. That is the smallest known distance. So now we look at C and its neighbors. And there's 3 choices, but we've already done A to C, so we're not going to do that. So now we have C to D and C to F. All right, so let's look at C to D first. So what we do, again, is we look at what the current value is from A to D. It's stored at infinity. So we calculate the new value from A to D through C. And the way we do that is by summing A to C plus C to D. So, for example, we know that C to D is 2. Okay, so we take 2. And then we look at how did we get to C? What was the previous for C? And the previous is A. So then we figure out what is the distance from A to C? 2. So 2 plus 2 gives us 4, of course. And obviously it's easy for us to look at, but you have to think about what your code is going to be doing. So we sum those two together. That gives us 4. And we'll update this right here to say 4. That's definitely smaller than infinity. And then we also need to update over here to say how we got to D. And the way we got there was through C. So that's what we add. Okay, next up, we're going to look at C to F. Same process. So C to F is 4, and then A to C is 2. And the way we know it's definitely this edge is if we look at C, we stored A as the shortest way to get there. So 2 plus 4 gives us 6. So we come down to F, and we check, is 6 less than infinity? Yes. So we update it, so we store 6 here. And then what we need to do is update our previous. How did we get to F? Well, what came right before it was C. So hopefully you can see how this becomes useful. What we're storing here is the shortest path to any given node from A. So the shortest way to get to D is from C. And then the shortest way to get to C from A is directly from A. So we only need to store the previous shortest path. So it's sort of step by step how we get to each node, what's the shortest way to get there, and we combine them all to figure out how to get to E eventually, which isn't done. So we update it to say we came from C. Now we start over. We need to pick the smallest value, shortest distance from A that we haven't visited. So we've done A and C. So we can cross those off. And the shortest thing is either B with 4, D with 4, or F with 6. Well, definitely not 6. And I'm picking B first just because it comes first alphabetically, but either one would work. They're both 4. So now we look at B, and B is easy because we've already visited A to B. so that's not happening. But we have B to E. Okay, so we'll look at that. And that gives us 3 plus what came before B. How did we get to B? We came from A, so that edge is 4. So 3 plus 4 gives us 7 as the new total. And that's definitely less than infinity. So we update this to say, well, the current shortest way that we can get to E is 7 units or whatever this is, 7 miles or something. And then the way we got there, over here, we'll update this to say we came from B, right? So if we stopped right now, it's not the shortest path, but we have a path that we could piece together. So we got to E from B, and we got to B from A. Now, out of the unvisited nodes, where do we go? So we've done A, B, C, and now we have D, E, and F. Well, which one is smallest? D. So we're going to D next. Okay, so here's D, and we have a couple of options. We've already been to C, so we're not going that way. So we either go to E or F. I'm going alphabetically, so E comes first. So we'll look at D to E. So that edge is 3. So now we calculate the total distance from A to E through D. So the total here is 7. And if we look at what we have stored for E right now, it's already at 7. So that doesn't win. It's not less. It's not shorter. So we're not going to update it. You could, if you wanted to, you could write your code so that you added 7 here if they're equal. But there's no reason. We already have a path that is 7 units long. This one. So we ignore it. Now we move on to the next, which is D to F. So our new total here to get to F is 5. And if we look at what we have stored right now, we have 6. Well, 5 is less than 6, so we update it to say 5. And we come over here to F, and we no longer come from C. That's what we had before. This was the shortest way to get to F. But now it's actually shorter if we come from D. So we update it. So this is saying, the fastest way to get to F is from D. The shortest path from A to D is through C. The shortest way from A to C is, through A, because there's a direct line from A to C. Okay, so that finishes up D. We did this edge, we did this edge. So now we cross it off, we visit it. There we go. Now we're going to pick the smallest again. So we have 2 options. We visited all these 4, A, B, C, and D. Now we have E and F. Which one is smallest? Which one has the closest distance or the shortest path to A? Right now, that's F. 5 is smaller than 7. So we'll start here. And we only have one option. We've already done this edge. We've done this edge. So now we look at F to E. So the distance is 1 to go from F to E. And what's the shortest path to get to F? So we add that all together, 4, 5, 6. And if we look at what we currently have stored for E, we have 7. We have 7 from this path on the outside, but we've now found something shorter. So we update this, and we cross those off, and now we add 6. And then, of course, we have to update how we got there, because right now we're storing the old version. If you look at E, we're saying the shortest path from A to E goes through B, but that's not the case. We now just found something shorter where we go through F. So we update this. If we look at E, there we go. We now say the shortest way to get there is through F. And just that one letter difference now makes a huge difference because it's a cascade, it's a chain. Because we look at where F, all right, well, to get to F, we went through D. To get to D, we went through C. To get through C, we went through A. And at this point, we have nowhere left to go aside from E. And that means that we're actually done. We found the shortest path. So to break that down again, I won't go step by step, but every time through, we pick the current smallest distance from A that we haven't visited. We explore each of its neighbors, and we calculate the new shortest distance to each neighbor. And if it's smaller than what we already stored, we update what we stored, and then we reflect the change over here in our previous data structure. And this allows us to piece everything together. So if we look at this, we're done now. All we have to do is work backwards. So to get to E from A, we start at E. And we look at, all right, F. Well, to get to F from A, the shortest possible way, that's what this is all storing, we end up with a list of the shortest way to get to any node from A. The shortest way to get to D from A is through C. And to get to C, we have to go from A. So A, C, D. That's the shortest way to get there. The shortest way to get to E is through F. And from F, first we go through D. From D, we go through C, C to A. So this is our shortest path, A, C, D, F, E. So Dijkstra's algorithm works not only to give you the shortest path between two nodes. At the end, the way we're implementing it, we'll have a data structure that gives us the shortest path from A to all the nodes. And that can be very useful. If you run this once and you don't change your graph, you have this structure that gives you the shortest path to go anywhere. You don't have to rerun it for every, if you're trying to go from A to B and then A to D and A to E, you run it one time and you get all that information. All right. So I know it's a lot. These slides took forever to make, and I hope they were helpful. I definitely recommend stepping through them on your own and just without me kind of explaining what I'm doing in the video, or even on a piece of paper. That's how I learned it originally, literally graph paper, drawing these charts out and keeping track of, all right, we bend to A, cross it off. We bend to B, cross it off, and drawing the graph out. Because from here, the jump to the code isn't that bad. It's just going to be difficult if you're not sure how this actually works. So I really, really, really recommend that you do that. If you're at all confused, if you don't feel like rewatching the video, I don't blame you. It's long. It's not that exciting to go through, but it can be a little more engaging if you do it on your own. And then once you understand it, jumping to the code is a lot easier. All right, so that's what we're going to do next. I'll actually show you sort of real pseudocode, if you will. And then if you want, you can try and implement it. Or, because this is a little complicated, totally understandable if you just code along with me. All right, that's coming up next. All right, so let's give this a shot. But before we even talk about the pseudocode, remember, I don't know if you watched the early videos in this section, but I talked about a priority queue and how that plays a role in the algorithm. Here's where it comes in. When we talk about picking the smallest value here, like if we go back, like here, where we had to pick the next smallest value. So we visited A, C, and B. We need to look at the rest and figure out where we go next. Well, we had 4 for D, 7 for E, and 6 for F. So we chose D. That's 4. This is very easy to do with 3 nodes, but if we have a million that we're keeping track of, finding the next smallest one to visit can take a lot of time if we're doing it naively. So I'm going to do 2 implementations. Here's the first version. So I hit next through all my slides. Here's our simple priority queue. And we're going to start here so that we don't get too distracted. But this is going to give us the next node to visit. And all that it does, it's just an array. And every time you add something to it, you give it a priority. And then we sort based off of that priority, which is what happens here. So every time we insert, we resort. And then we remove from the array. So I've copied it over here just so you can see it. And if we do something like, var queue equals new priority queue, like this, and then I do queue.push, when I push, or actually it's called enqueue. When we enqueue something, let's say just the node A, or let's not do A, let's say B, which has a distance, I'm just going to say of 3. I don't think that's accurate. That's the priority that we add in. And now we'll also enqueue C, which has a distance of 5. Let's do D, which has a distance of 2. And then also, Q, which has a distance of 20. Now, if we look at Q.values, you'll see that it's sorted now based off of that priority. So every time we insert something, it resorts. So if I insert something again, that's really small, like in Q, let's say P has a distance of 1.5, that's going to jump to the very beginning if we look at values again, right? So every time we dequeue, these are the 2 methods we'll be using. Sort is used internally, enqueue and dequeue. When I do a dequeue, it's going to give me whatever has the lowest priority. We want the smallest item. So what we'll do in our pseudocode is just push in these values, like going back here. Let's suppose, ignore the fact that we visited all of these. Let's say all of these were in the queue. When we dequeue, we want whatever has the smallest distance from A. That's what we're prioritizing. So the priority queue is going to help us. And this is not the best implementation. It's simple. But remember, back in the binary heap section, if you watch that, there's a better way, a faster implementation for a priority queue using a heap. This right here, because we're sorting every single time, it's O of n log n, which is not ideal, but it's simple, so we're going with this, and then we'll update our code to use the binary heap in a bit. Okay, so one more time, every time I dequeue, it gives me whatever the current smallest priority is, but if I insert something else, and I dequeue again, if that's smallest, I should get that next. So we'll take advantage of this in our code. Okay, so that's the naive basic priority queue. The goal is just to always get the smallest value out first. No matter what else is in there, just give us the smallest thing first. Okay, so now that we have the basic priority queue, we've talked about how it works, here's the pseudocode. All right, so define your function on the graph, or define it as a method on the weighted graph class. Just call it shortest path or Dijkstra's or whatever works for you. It should accept a starting vertex and an ending vertex. Are we going from A to E, from A to Z? Are we going from SFO to LAX? Whatever the vertex names are, it accepts two, start and end. Whichever one comes first will be start in our case. Then we need to make a couple of data structures, and we'll create our object. We can call it distances. This will act as this table here, where for each vertex, we're going to store the current shortest distance from whatever start point. It doesn't have to be A, of course, but let's say we're working with A to E again. We're going to store in this object the shortest distance from A to B, from A to C, A to D. And at the very beginning, we initialize everything to infinity, if you remember that, because we don't know how far it is from A to C or A to D. The only value we know for sure is A to A, which we start at 0. Then after initializing the values in the distances object, we're also going to make our priority queue. So we make a new priority queue, and it starts out empty, and we add each one of our vertices into that priority queue where we set the priority to be the distance from A. So basically, we add all of the vertices in with a priority of infinity, except for A with a priority of 0. So of course, we get A first. But then later on, we'll have actual values in there that aren't infinity. And every time we dequeue, we get the smallest value back. And that's where we begin. That's what we visit first. Okay, so this just initializes things. And there's actually one more step. We also have to create our previous object, where it's just a simple object where we have a key for every vertex, and we initialize it to a value of null. So that's this data structure here. But everything should start at null, and we will update the value for each key as we go. All right, so it's mainly the setup that takes the most time to explain. Then we just loop as long as there's anything in the priority queue. So as long as there's something to visit, we're going to dequeue a vertex from the priority queue. So that means picking the smallest distance from A. What are we going to start with? Let's say D, because it has a value of 2, and everything else has a value of 4 or 6 or 10 or something. So we start with that, and then the first thing we do is we check, is this the vertex I'm trying to get to? Have I hit the end? And if that's the case, then we're done. Otherwise, we loop through each of its neighbors. So we'd look at all the neighbors for D, and we calculate the distance to that vertex from the starting vertex. And then if that new distance, that sum, is less than what we're currently storing, we update the distances object with a new lower distance. So this is all what we did in the last video, or 2 videos ago, walking through. We update the distance, we update the previous object to now reflect where we came from, and then we enqueue the same vertex with a new total distance from the start node. And that's it, we keep going over and over. So for example, here we'd pick the smallest value using the priority queue. Currently it would have D, E, and F in there because we've done A, C, and B. So we dequeue, which would give us D because it's the smallest with a value of 4. So then we're going to look at D's neighbors. There's 2, E and F. And we start looking at E. Sum that together, it gives us 7. That's actually not less than what we currently have, so we don't do anything. But then we move on to F, the next neighbor of D. So that gives us 5. And if you look at what we stored right now, it's 6. So 5, the new total, is definitely less than 6. So we update it here. Then we come to previous and we say, all right, the new shortest way to get to F is not from C anymore. It's actually to go through D. So we just put D right there. And then after that, we want to enqueue F with the new value of 5 so that it's, updated in our priority queue, and we know next time we're going to pick 5 first because it's the new smallest value. All right, so let's give this a shot. And if you want to, of course, try and implement it, but definitely not something you have to do. It's a little more complicated. If you want to, though, the pseudocode should get you there. Otherwise, in the next video, I'll go ahead and build it. All right, so let's give it a shot. Let's see how it goes. First couple things, I've added the priority queue in. This is our naive priority queue. We'll need to use that. I have a new snippet. I've added the weighted graph code in. Again, we only have a way to add a vertex and an edge. I didn't bother with removing them for now. And then down here, this is new. I implemented the graph from earlier just by adding the vertices and then the various edges. So we're looking from A to E, what the shortest path is, and the graph should match this graph here. So for example, A to C is 2, D to E is 3. And just to verify, what do we have? A to C is 2, and D to E is 3, and so on. So I tested it out, and it was working earlier as far as the distances. It can be hard to write these down accurately. So I recommend you copy them if you want. It's kind of annoying to type this all yourself. All right, so that's just the setup. Now we need to start by defining our function. And I'm just going to call it Dijkstra just to make it clear. I'll do a capital D, even if it's not super conventional. And we need our two nodes, start and finish. So at the very bottom, I want to be able to call graph.Dijkstra from A to E. And we didn't really discuss what the return value should be, and that's okay. The search is the most important part at this point. But let's say it should return an array containing the nodes in order. So A to C to D to F or whatever it was to E. Okay, so we start like this, and there's a couple things we need to do. We need to make a new priority queue. So I'll use ES 2015 syntax. I'm going to call it nodes equals new priority queue, which again is coming from up here. It starts empty. We needed to make our distances object. So I'll call that distances and just initialize an empty object. We need our previous object, which is just, again, another object representing where we store. For C, the quickest path to C was through A, or for E, the fastest way was through F, and so on. So if you're unfamiliar with what I'm talking about, go back and watch, well, I shouldn't say go back and watch. It's this thing right here. So this is distances and this is previous, and that's really all we need for now. Okay, so now we have the bulk of the logic. We need to build up like our very initial distances. So let's just say build up initial state. And what that involves is looping over the entire adjacency list. So let's just do a loop right now. So I'll do a for in loop. So for let vertex in this dot adjacency list. We have a couple things to do. First, we need to set each key in the distances object to be infinity, except for the starting vertex, which should be 0. So to do that, let's just check if vertex equals start. So for example, if we're looking at A, we're going to set distances of vertex equal to 0. Otherwise, I'll do an else just to make it clearer. We're going to set distances of vertex to equal infinity. So that's just initializing everything. So if we're going from A to E, this will initialize our distances object to contain everything, B through E as infinity, and A should be set to 0. And if we wanted to, we could just quickly console.log distances to verify that that's working how it should. If I run this, it is. A is 0 and everything else is infinity. And of course, that's because we're going from A to E. If we were going from B to E, then B would be 0. Okay, so we don't need to console.log that. Now, that's only part of what we need to do. Along with that, we need to add each node, or add a value for each node to our priority queue so we know what to start with and what to take each time, where to visit next. So add each vertex with a priority of infinity to the priority queue, except the starting vertex, which should have a priority of 0, because that's where we begin. So we made our priority queue. It's called nodes, and I'll just do nodes.enqueue, and we pass in two things, the vertex and then a priority, which will be 0. And then down here, we'll do the same thing. Whoops, I hate that. And Chrome doesn't give me an easy way to, anyway. All right, and down here, we'll add infinity. So for every other node in our queue, we're definitely starting with this one because it's 0 compared to infinity. But then we'll be updating, we'll be enqueuing things later with a new priority that isn't infinity. All right, and then the only other thing we have to do for every single node, we need to set previous of that node, of that vertex, to be null. So instead of doing that in the if and the else and duplicating it, I'll just do it down here. So previous of vertex equals null. So that gives us our initial state. We end up with this structure here. We end up with our priority queue reflecting this as well. Then we end up with previous, where we have A, null, B, null, C, null, and we'll update those as we go. Okay, so next, after we've initialized everything, we now need to basically run some code. I'll add a comment here, as long as there is something to visit. And the way we could write that is just while nodes.values.length. That's one way. Nodes is our priority queue, and inside the priority queue we're storing values, so we can do .length of that. That's fine. While nodes.values.length. And the first thing that we need to do is dequeue our node. So start looping as long as there's anything in the queue, dequeue a vertex. So dequeue should give us the current smallest value in there. So I'm going to make a variable called smallest, but rather than initializing it down here over and over and reinitializing it, I'm going to set it up here. I'm just going to call it smallest and not set it to a value, but define it or declare it, Rather than redeclaring it, I'm going to just set smallest equal to nodes.dequeue. So remember from the priority queue video 2 videos ago, it should give us whatever the current smallest value is in there. Give us the vertex with the lowest priority. And actually, we're almost there, but if we look at what smallest is right here, it's not quite what we want. If I execute my code, smallest is going to be the entire node, or this entire object that has the val and the priority. What we want really is just the val, which is going to give us A or B, just so we know which node we're looking at. We don't care about the priority right now. Anyway, so now that we have that out of the way, we're going to have, A as smallest or B as smallest. What we need to do is check, is that vertex the same as our ending vertex? If that's the case, we're done. So I'm not going to actually fill out all the code, but I'll just do a simple check. If smallest is equal to, what did we call ours? Finish. If that's the case, we'll come back to this, but I'll just say we are done and we need to build path to return. But if that's not the case, what we need to do is loop through each neighbor in the adjacency list for that vertex. So if we're looking at A, we need to look at each of A's neighbors, which includes B and C. So I'm going to loop over those neighbors, and the easiest way to do that, smallest is just a variable that looks like A, and we have this .adjacency list. So this .adjacency list of A would give us a whole bunch of, it would give us an array containing, each edge. So I'm going to put that, instead of A, of course, I'm not going to hard code it. I'm going to put smallest in there, and I'm going to use a loop over this. And I'll do a for in. So I'll just call for, let's call it neighbor in this .adjacency list of smallest. Then we could start by just console.logging neighbor, nice and simple, like that. And if I rerun my code, you see what we're getting here is just a number. And that's how the for in loop works, because what we're doing here is looping over an array. If we actually looked at this .adjacency list, if we did that too, this .adjacency list, hopefully you remember what it looks like. One more time, rerun it. This is what we're looking at. So when we loop over A's neighbors, we're just looping over 0 and 1. What we want to do from there is take that number to figure out the actual edge. So I'm going to make another variable called, let's just call it next node. We could call it neighbor node or something, equals this .adjacency list of smallest of neighbor. And neighbor is just a number. So now if we console.log next node, this will actually give us what we're looking for. This is each neighboring node. So now that we have each neighboring node each time through, we need to go and calculate. So I'll add a comment here that just is basically like find neighboring node. Calculate new distance to neighboring node. So let's say that we're looking at D currently as neighboring node. We need to calculate the distance. How do we get to D? Well, we would consult previous. The shortest path to D is through C. And so we look at what C currently has stored, and then we add 2. So I know it's kind of difficult to explain without just showing you. So what we would do, it's not guaranteed that this is going to be smaller. So I'm going to make a variable called, I don't know, candidate, and we're going to take our distances of smallest. So smallest is whatever the actual node we're visiting is, and then we're going to add next node.weight. Let's say we're just starting out. We picked A, which is our vertex. It's the only thing to start with. It's the minimum item. And we look at its neighbor, B. All right. So what we're going to do is take the weight of B from A to B. That edge gives us 4. So we take 4 and we add it to whatever we have stored for A, which is 0. So that one's easy. And we put that under B. But now let's say we fast forward a bit and we're looking at, let's say, keep going. When we get to, we get to B here. All right, so we start with B. B is our neighbor, and we look at B to E. Well, what do we currently have stored for B is 4. That represents the shortest distance from A to B that we know about, and we add that to the distance from B to E, which is 3, and that gives us 7. So that's what we're going to do. Candidate equals the current distance for our node plus the distance to the neighbor. So this distance's smallest would be like the 4. And then the neighbor value is this edge we're adding in. So this is going to be a hopefully smaller, but definitely not always. This is now what we need to compare. Is this smaller than what we currently have stored for the neighbor? So then that's next. We're going to look at if the candidate, our new sum that we added together, is less than what we have for distances of not smallest, but of next node dot node, which, it's a bit of a mouthful there. But what this is reflecting is the fact that next node looks like this. It's an object. And we need to access next node dot node, which is something like F. So I'll walk through this. It's a lot when you think about it this way. But if we go back to here, what we're doing is basically checking. If I go forward to D as an example. All right, we're looking from D to E, right? So we start by taking a look at what do we currently have stored as the shortest way to get to D, 4. And then we're looking from D to E, that's 3. So that gives us 7 total. But what we want to compare that to is not 4, because of course it's going to be more than whatever is at D, because we're adding D plus something else. What we want to compare it to is what's currently at the neighbor, what's currently at E, which is 7 in this case. And it's the same, so we ignore it. But that's what we're trying to do. We take wherever we are, D, we add the current shortest value from A to D plus this new bit, and we compare that to the current shortest for E. So back here, that's what this is. We're calculating a new number, this new sum. This is to D, this is plus E. Then we compare that to what we currently stored for E. All right, so if that's the case, we're now going to update what we stored for E. So next node, distance is next node dot node. And rather than doing next node dot node, why don't we extract this into a separate variable? Let's just call it next neighbor. Just like that. And now here I can say next neighbor, and same thing down here. It's a small difference, but I don't like having to do, did I spell this wrong? Distance is next neighbor equals our candidate. So this is just the equivalent of updating one of these lines. Distances of E, for example, equals 7. It already is 7, but imagine if something else. We update this value. All right, if you're still with me, hopefully the only way this really works and makes sense is if you are able to walk through the diagrams in a couple videos ago. All right, then what we do is we update previous. So previous is our data structure. It's this thing here. And we're going to say, all right, the way we got to previous of next neighbor was through smallest. So smallest is going to be D, and next neighbor might be E. This is just updating how we got there. So to add a couple comments, this is just updating new smallest distance to neighbor. This is updating previous, basically how we got to next neighbor, or to neighbor. And then the last thing we need to do is in queue, in priority queue with new priority. All right, and that's easy. It's just nodes. That's the name of our priority queue, .enqueue, next neighbor, comma, the value, which candidate is what we called it. This is the new sum. All right, so then that goes through, and that's all we need to do as far as the bulk of the logic. All right, so just so we can see if it's working, we're not returning anything, but let's console.log distances at the end. And let's also console.log previous, like that. And let's see what happens. Oh, next neighbor is not defined. Did I miss? Two B's. All right, one more time. Oh, I knew something was wrong. Oh my gosh. All right, I updated every one of these to be next neighbor with 1B. Okay, so you can see that what we end up with at the end is this set of distances that we've kept track of. For example, the shortest path to get to E takes 6 units. And if we construct it working backwards, from E, we go to F. From F, we go to D. From D, we go to C. From C, we go to A. So we just want to spit out, at the very end, what I want this to return is basically an array that looks like A, comma, and then from A, we went to C. From C, we went to D. From D, we went to F. And then finally, from F, we went to E. So we build it backwards because that's all we have. We have E, so we go to F. We have F, we go to D. D, we go to C. C, we go to A. So I'm just going to add them all to an array and just reverse it at the end. It's just a simple way of doing it. But that's the return value I want. So to make that array, that path at the very end, I'm going to come up here and just make a variable called path and set it to be an empty array. So I'll just say to return at end. Okay. Then down here, when we actually find what we're looking for, when we're done, to build up that path to return at the end, I'm going to start. We need to use previous, right? That's what this structure is. And we basically need to loop. So we need to keep looping from E to look at F, and then from F to look at D. And where do we stop? Well, eventually we get D to C, C to A, and then we look at A, and it's null. So we can do a while loop. And this is sort of like traversing any sort of list, even though it's technically an object, but it's this linear path. So I'm going to do while previous of smallest, and I'm going to update what smallest is as we go. So I'm going to do path.push smallest, and then I'm going to say smallest is now equal to previous of smallest. So at the beginning, smallest will be E. Well, it's at the end of our code running, but at the beginning of this bit. So previous of smallest, E gives us F. So we push E in, and now we say smallest is equal to F. And then it starts over. So is there previous of smallest? F, yes, there is. So we push F right here, and then we set smallest to now be D. And we keep going until we get to A, at which point there is no previous of A because it's null, and we're done. Now what we need to do is I'm going to add a break here so that we don't keep looping. I want to stop this loop because even though we found what we're looking for, this loop keeps going while there are nodes in the priority queue. And of course there are more nodes in there. Well, it's not, of course, it's possible that it's the last thing we look at, but it's likely that there's stuff in there. So we're going to break out. And so that will stop everything. And then at the very, very end, if we come down here, oh boy, I hate doing this. Where do we need to go? Let's see. Our loop stops right here. All right, so after our loop, we're going to do let's do console.log of path and see what we have. And I run it. All right, so we're almost there. The only thing is that we need to also reverse it. So to reverse it, and we want to add in A because A is not in here. So to get A in there, which is our beginning, we want A, C, D, F, E. It's pretty simple to fix. We can just do return path dot. I'm going to concat A in there, which is smallest, dot reverse. And if I run my code now, there we go. A, C, D, F to E. And if we tried changing it, instead of A to E, what's the shortest path to get from A to C? Well, that one's easy. We go from A to C. How about to F? A, C, D, F. How about to, I think they're all pretty simple at this point. They're all along the same lines, A, C, and D. And we are done. Now, this is a lot of stuff, and the code is quite intimidating if you are unable to go through and process the slides and kind of walk through step by step. If you're just trying to learn it by looking at this, it's really difficult. But I think that it makes some sense as you go through and step through and you understand each time through what we're actually doing. If you write it down with pen and paper, if you look at what each of these values actually is, when we pick the smallest node, smallest priority, we add the new total together and we compare it to what we had stored for the neighbor, and then we update potentially if it's smaller. There's a lot going on, but if you're able to do that with pen and paper, then this should be easy enough. Well, not easy enough. It should be doable. Either way, this is Dijkstra's, and this is our unoptimized version where we're using a priority queue, which is not, well, this priority queue is not ideal because it's not implemented with a binary heap. It's a bit slow because we're sorting the entire array every single time. If we use a binary heap, it's faster, remember from that section. So next up, we will fix this up just to make it a little bit quicker. Welcome back. In this video, we're just going to upgrade our code a bit using a binary heap priority queue. So this is the priority queue we wrote earlier in the course. We were doing things like with a hospital priority queue. So I'm going to get rid of that. I copied it over. I'm not just altering the original. And we can actually leave everything the same. So we have NQ and DQ, and it's the same interface. It takes a value and a priority, a value and a priority. So all that we have to do now is just add our code into this file here. There's a node class, but we don't have to interact with that. The priority queue does. If you have never seen this code, definitely recommend you check that out first. It's a lot going on, but it's much faster than doing our naive priority queue here. Then we'll just take everything else like this. Oh no, I just deleted it all. Copy it and move it over here. And I'm going to put it up top, I think, so that we have the weighted graph class first, and then I'll move all of these variables and method calls down to the very bottom. And if we take a look, there's a lot of code going on here, but we have our weighted graph, which interacts with the priority queue, which is a binary heap. This priority queue implementation uses a node class, and then at the bottom, we're creating our graph, we're adding the edges, and then finally, we're testing it out. So, moment of truth, and it still works. If you made it through the binary heap section, you should know that this implementation of a priority queue is much faster than a naive version just using an array. Even though the binary heap itself is stored in an array, the way it works is much more efficient than a traditional just sorting the array over and over and over and picking the minimum value. Alrighty, so that's just upgrading our code a bit.